everyone and welcome to the AI and ML full course. Artificial intelligence and machine learning are transforming the way the world works, from voice assistants to self-driving cars and from medical diagnosis to stock market predictions. In this course, we will take you step by step from the fundamentals of AI to hands-on machine learning and deep learning. You will learn the core concepts, explore the most important algorithms, and work with tools to build and train your own models. Plus, you will gain insights into the future of AI and ML and prepare for interview questions to boost your career. And by the end of this course, you will not only understand how AI and ML work, but also know how to create intelligent systems that can make predictions, recognize patterns, and solve real-world problems. So before we get started, please like, share and subscribe to Edureka's YouTube channel and hit the bell icon to stay updated on the latest tech content from Edureka. Also, check out Edureka's postgraduate program in Generative AI and Machine Learning in collaboration with Illinois Tech. It offers a unique opportunity to explore the cutting-edge world of generative AI and develop advanced AI-powered solutions. This program covers in-demand topics including machine learning, deep learning, natural language processing, prompt engineering, generative AI, LLMs, RAG, agentic AI, and much more. Learn from industry experts through a curriculum built around real-world, hands-on use cases designed to equip you with the practical and job-ready skills. So check out the course link given in the description box below. Now, let's get started with our first topic, that is, what is artificial intelligence?
AI or artificial intelligence is the branch of computer science where focused on creating systems that were performed tasks and that would be normally required by human intelligence. These tasks can range understanding of natural language, secondly, recognizing patterns, then making decisions, and lastly, learning from the experiences. AI is a collaboration of ideas, methods, and knowledge, where from the multiple academic disciplines work on a different problem solving and share their knowledge to a better understanding and come up with a good solution. But it can also be rule-based and operate under a set of rules and conditions only. So, I would like to tell you all guys, a small real-time experience or an experiment done by Alan Turing to propagate and to establish the artificial intelligence. Alan Turing was the first person to conduct the sustained research in the field that he called machine intelligence. The Turing test was conducted to explore whether machines could exhibit human-like intelligence. Proposed by Alan Turing in 1950, it involves a human evaluator communicating with both a human and a machine through a text interface. If an evaluator cannot distinguish between the two based on their responses, the machine is said to have passed the test. It serves as a benchmark of the assessing the progress of AI and discussions of the nature and intelligence and consciousnesses. So this is to evolve and to establish that even machines can work as humans. And that is how it is made to bring up the machine's knowledge and the human's knowledge into machines. There are two types of artificial intelligence. First, let's talk about weak AI. Before getting into what is weak AI, I would like to tell you with an example that is performed in a real world. I know you'll all guys will be knowing about Alexa, Apple Siri, and also self-driving vehicles. So, all of these considered as in weak AI. It is also known as a narrow AI or an AI narrow intelligent that is trained by the AI and focused to perform a specific task. Weak AI drives most of the AI that surrounds by us today. Narrow might be a more apt descriptor for this type of AI as it is anything but weak. Next, let us learn about strong AI. Strong AI is made up of artificial general intelligence or artificial superintelligence. Simply, it could be told as where a machine would have an intelligence equal to humans, where humans will track what AI needs to be done. It would be able to self-aware with the consciousness that would be this ability to solve problems, learn, and also plan for the future. Have you ever thought, what does AI do at its core? I'm here to tell you why. AI is essential. It works by analyzing a lot of data to find patterns and useful information. It even learns from this data to get better at a task over time. With this learning, AI can make decisions, predict future events, and do tasks automatically that would normally need human intelligence. This helps business and other organizations work more efficiently. So, AI is about making computers smarter and more helpful in everyday life. So, let me tell you some use cases that is happening in daily uses or daily real life based. Firstly, I have taken is about cybersecurity, as it is a very important and a vital role for many platforms hereafter. Cybersecurity is a critical concern for individual businesses and also governments, as cyber threats continue to evolve in a complexity and sophistication. It would play a very vital role for augmenting cybersecurity defenses. It is all based on the false positive effects that is made by the false information given by any criteria, leading the alert of fatigue and reduced operational efficiencies. Cyber attacks can exploit vulnerabilities in AI models by invading detection and compromising security defenses. They have some private data where it is trained on the basis of incomplete data sets may produce the outcomes of private data. This will raise an ethical concern and also regulatory compliances issues, having a very complicated problems too. So, the next one will be your entertainment. As people know, entertainment is taking a very huge part in everyone's life. For example, it would be a social media too. So, AI is transforming the entertainment industry by revolutionizing content creation, personalization, and audience engagement. So, this can be such as television, gaming, music, and also digital media platforms. One significant use of AI in entertainment is personalized content recommendation. So, personalized entertainment experiences are enhanced through AI driven. It is recommended through systems. They are even having some platforms like Netflix, Prime Amazon, and also Spotify that is making people engaged in a very hype as of now. These recommendations improve over time. So, I would like to conclude by telling artificial intelligence can do amazing things like analyzing data and making tasks easier. But it also brings up huge question about fairness, jobs, and who controls it. We need to be careful in how we develop and use the AI, making sure it helps everyone and doesn't cause harm at all. So this makes easier for people to get into creativity and make rules and guidelines.
So now let's get started with the first topic, which is history of artificial intelligence. The concept of AI goes back to the classical ages. Under Greek mythology, the concept of machines and mechanical men were well thought of. An example is Talos. Talos was supposedly a giant animated bronze warrior who was programmed to guard the island of Crete. Now let's get back to the 19th century. In 1950, Alan Turing proposed the Turing test. The Turing test basically determines whether or not a computer can intelligently think like a human being. The Turing test was the first serious proposal in the philosophy of artificial intelligence. 1951 marked the era for game artificial intelligence. This period was called game AI because here a lot of computer scientists developed programs for checkers and for chess. However, these programs were later rewritten and redone in a better way. 1956 marked the most important year for artificial intelligence. During this year, John McCarthy first coined the term artificial intelligence. This was followed by the first AI laboratory, which was set up in 1959. MIT AI Lab was the first setup, which was basically dedicated to the research of AI. In 1960, the first robot was introduced to the General Motors assembly line. In 1961, the first AI chatbot called Eliza was introduced. In 1997, IBM's Deep Blue beats the world champion Garry Kasparov in the game of chess. 2005 marks for the year when an autonomous robotic car called Stanley won the DARPA Grand Challenge. In 2011, IBM's question answering machine, Watson, defeated the two greatest Jeopardy champions, Brad Rutter and Ken Jennings. So that was a brief history of AI. Now guys, since the emergence of artificial intelligence in 1950s, we have seen an exponential growth in its potential. AI covers domains such as machine learning, deep learning, neural networks, natural language processing, knowledge base, expert systems, and so on. Now that you know a brief history of artificial intelligence, let's move on and understand what exactly artificial intelligence is. So, the term artificial intelligence was first coined by John McCarthy, like I mentioned earlier. He defined AI as the science and engineering of making intelligent machines. In other words, artificial intelligence can also be defined as the development of computer systems that are capable of performing tasks that require human intelligence, such as decision making, object detection, solving complex problems, and so on. So, like I mentioned, artificial intelligence helps in decision making, solving complex problems, it performs high level computations, and also increases the accuracy of your predictions. Right? These are the main features of AI. So now let's understand the different stages of artificial intelligence. So basically, when I was doing my research, I found a lot of videos and a lot of articles that stated that artificial general intelligence, artificial narrow intelligence, and artificial super intelligence are the different types of AI. If I have to be more precise with you, then artificial intelligence has three different stages, right? The types of AI are completely different from the stages of AI. So, under the stages of artificial intelligence, we have artificial narrow intelligence, artificial general intelligence, and artificial super intelligence. So, what is artificial narrow intelligence? Artificial narrow intelligence, also known as weak AI, is a stage of artificial intelligence that involves machines that can perform only a narrowly defined set of specific tasks. Right? At this stage, the machines don't possess any thinking ability. They just perform a set of predefined functions. Examples of weak AI include Siri, Alexa, AlphaGo, Sophia, the self-driving cars, and so on. Almost all the AI-based systems that are built till this date fall under the category of weak AI or artificial narrow intelligence. Next, we have something known as artificial general intelligence. Artificial general intelligence is also known as strong AI. This stage is the evolution of artificial intelligence, wherein machines will possess the ability to think and make decisions just like human beings. There are currently no existing examples of strong AI, but it's believed that we will soon be able to create machines that are as smart as human beings. Strong AI is actually considered a threat to human existence by many scientists. This includes Stephen Hawking. Stephen Hawking quoted that the development of full artificial intelligence could spell the end of human race. Moving on to our last stage, which is artificial superintelligence. Artificial superintelligence is that stage of AI when the capability of computers will surpass human beings. Artificial superintelligence is currently seen as a hypothetical situation as depicted in movies and science fiction books. You see a lot of movies which show that machines are taking over the world. All of that is artificial superintelligence. Now, I believe that machines are not very far from reaching the stage taking into consideration our current pace. However, such systems don't currently exist, right? We don't have any machine that is capable of thinking better than a human being or reasoning in a better way than a human. Artificial superintelligence, basically any robot that is much smarter than humans. Now, moving on to the different types of artificial intelligence. Based on the functionality of AI based systems, artificial intelligence can be categorized into four types. The first type is reactive machines AI. This type of AI includes machines that operate solely based on the present data and take into consideration only the current situation. Reactive AI machines cannot form inferences from the data to evaluate any future actions. They can perform a narrowed range of predefined tasks. An example of reactive AI is the famous IBM chess program that beat the world champion Garry Kasparov. This is one of the most impressive AI machines built so far. Next, we have limited memory AI. Now, like the name suggests, limited memory AI can make informed and improved decisions by studying the past data from its memory. So, such an AI has a short lived, or you can say a temporary memory that can be used to store past experiences and hence evaluate your future actions. Self driving cars are limited memory AI that use the data collected in the recent past to make immediate decisions. For example, self-driving cars use sensors to identify civilians that are crossing the road. They identify any steep roads or traffic signals, and they use this to make better driving decisions. This also helps in preventing any future accidents. Next, we have something known as theory of mind artificial intelligence. The theory of mind AI is a more advanced type of artificial intelligence. This category is speculated to play a very important role in psychology. This type of AI will mainly focus on emotional intelligence so that human beliefs and thoughts can be better comprehended. The theory of mind AI has not been fully developed yet, but rigorous research is happening in this area. Moving on to our last type of artificial intelligence is the self-aware artificial intelligence. So guys, let's just fold hands and pray that we don't reach the state of AI where machines have their own consciousness and become self-aware. This type of AI is a little far-fetched, but in the future, achieving a stage of super intelligence might be possible. Geniuses like Elon Musk and Stephen Hawking have constantly warned us about evolution of AI. So guys, let me know your thoughts in the comment section. Do you ever think we'll reach the stage of artificial super intelligence? Moving on to the last topic of today's session is the different domains or the different branches of artificial intelligence. So artificial intelligence can be used to solve real-world problems by implementing machine learning, deep learning, natural language processing, robotics, expert systems, and fuzzy logic. Now, guys, these are the different domains, or you can say the different branches that AI uses in order to solve any problem. Recently, AI has also been used as an application in computer vision and image processing. Right, for now, let me tell you briefly about each of these domains. Machine learning is basically the science of getting machines to interpret, process, and analyze data in order to solve real-world problems. Right, under machine learning, there's supervised, unsupervised, and reinforcement learning. If any of you are interested in learning about these technologies, I'll leave a link in the description box. You all can go through that content. Next, we have deep learning or neural networks. So deep learning is the process of implementing neural networks on high dimensional data to gain insights and form solutions. It is basically the logic behind the face verification algorithm on Facebook. It is the logic behind the self-driving cars, virtual assistants like Siri and Alexa. Then we have natural language processing. Natural language processing refers to the science of drawing insights from natural human language in order to communicate with machines and grow businesses. So an example of NLP is Twitter and Amazon. Twitter uses NLP to filter out terroristic language in their tweets. Amazon uses NLP to understand customer reviews and improve user experience. Then we have robotics. Robotics is a branch of artificial intelligence which focuses on the different branches and applications of robots. AI robots are artificial agents which act in the real world environment to produce results by taking some accountable actions. So I'm sure all of you have heard of Sophia. Sophia the humanoid is a very good example of AI in robotics. Then we have fuzzy logic. So fuzzy logic is a computing approach that is based on the principle of degree of truth instead of the usual modern logic that we use, which is basically the Boolean logic. Fuzzy logic is used in medical fields to solve complex problems which involve decision making. It is also used in automating gear systems in your cars and all of that. Then we have expert systems. An expert system is an AI-based computer system that learns and reciprocates the decision-making ability of a human expert. Expert systems use if-then logic notions in order to solve any complex problem. They do not rely on conventional procedural programming. Expert systems are mainly used in information management. They are seen to be used in fraud detection, virus detection, also in managing medical and hospital records, and so on. So guys, to sum it up, these were the different branches of artificial intelligence.
These are the terms which have confused a lot of people, and if you two are one among them, let me resolve it for you. Well, artificial intelligence is a broader umbrella under which machine learning and deep learning come. You can also see in the diagram that even deep learning is a subset of machine learning. So you can say that all three of them, the AI, the machine learning, and deep learning, are just the subset of each other. So let's move on and understand how exactly they differ from each other. So let's start with artificial intelligence. The term artificial intelligence was first coined in the year 1956. The concept is pretty old, but it has gained its popularity recently. But why? Well, the reason is earlier we had very smaller amount of data. The data we had was not enough to predict the accurate result. But now there's a tremendous increase in the amount of data. Statistics suggest that by 2020, the accumulated volume of data will increase from 4.4 zettabytes to roughly around 44 zettabytes or 44 trillion GBs of data. Along with such enormous amount of data, now we have more advanced algorithm and high-end computing power and storage that can deal with such large amount of data. As a result, it is expected that 70% of enterprise will implement AI over the next 12 months, which is up from 40% in 2016 and 51% in 2017. Just for your understanding, what is AI? Well, it's nothing but a technique that enables the machine to act like humans by replicating the behavior and nature. With AI, it is possible for a machine to learn from the experience. The machines adjust their responses based on new input, thereby performing human-like tasks. Artificial intelligence can be trained to accomplish specific tasks by processing large amount of data and recognizing pattern in them. You can consider that building an artificial intelligence is like building a church. The first church took generations to finish, so most of the workers who were working in it never saw the final outcome. Those working on it took pride in their crafts, building bricks and chiseling stone that was going to be placed into the great structure. So as AI researchers, we should think of ourselves as humble brick makers whose job is to study how to build components, example parsers, planners, or learning algorithm, or etc. anything that someday someone and somewhere will integrate into the intelligent systems. Some of the examples of artificial intelligence from our day-to-day life are Apple series, chess playing computer, Tesla's self-driving car, and many more. These examples are based on deep learning and natural language processing. Well, this was about what is AI and how it gains its hype. So moving on ahead, let's discuss about machine learning and see what it is and why it was even introduced. Well, machine learning came into existence in the late 80s and the early 90s. But what were the issues with the people which made the machine learning come into existence? Let us discuss them one by one. In the field of statistics, the problem was how to efficiently train large complex model. In the field of computer science and artificial intelligence, the problem was how to train more robust version of AI system. While in the case of neuroscience, problem faced by the researchers was how to design operational model of the brain. So these were some of the issues which had the largest influence and led to the existence of the machine learning. Now this machine learning shifted its focus from the symbolic approaches it had inherited from the AI and moved towards the methods and model it had borrowed from statistics and probability theory. So let's proceed and see what exactly is machine learning. Well, machine learning is a subset of AI which enables the computer to act and make data-driven decisions to carry out a certain task. These programs or algorithms are designed in a way that they can learn and improve over time when exposed to new data. Let's see an example of machine learning. Let's say you want to create a system which tells the expected weight of a person based on its height. The first thing you do is you collect the data. Let's see, this is how your data looks like. Now each point on the graph represents one data point. To start with, we can draw a simple line to predict the weight based on the height. For example, a simple line W equal H minus 100, where W is weight in kgs and H is height in centimeter. This line can help us to make the prediction. Our main goal is to reduce the difference between the estimated value and the actual value. So in order to achieve it, we try to draw a straight line that fits through all these different points and minimize the error. So our main goal is to minimize the error and make them as small as possible. Decreasing the error or the difference between the actual value and estimated value increases the performance of the model. Further on, the more data points we collect, the better our model will become. We can also improve our model by adding more variables and creating different prediction lines for them. Once the line is created, so from the next time if we feed a new data, for example height of a person to the model, it would easily predict the data for you and it will tell you what his predicted weight could be. I hope you got a clear understanding of machine learning. So moving on ahead, let's learn about deep learning. Now what is deep learning? You can consider deep learning model as a rocket engine and its fuel is its huge amount of data that we feed to these algorithms. The concept of deep learning is not new, but recently its hype has increased and deep learning is getting more attention. This field is a particular kind of machine learning that is inspired by the functionality of our brain cells called neuron, which led to the concept of artificial neural network. It simply takes the data connection between all the artificial neurons and adjusts them according to the data pattern. More neurons are added if the size of the data is large. it automatically features learning at multiple levels of abstraction, thereby allowing a system to learn complex function mapping without depending on any specific algorithm. You know what? No one actually knows what happens inside a neural network and why it works so well. So currently you can call it as a black box. Let us discuss some of the example of deep learning and understand it in a better way. Let me start with a simple example and explain you how things happen at a conceptual level. Let us try and understand how you recognize a square from other shapes. The first thing you do is you check whether there are four lines associated with the figure or not. Simple concept, right? If yes, we further check if they are connected and closed. Again, if yes, we finally check whether it is perpendicular and all its sides are equal. Correct? If everything fulfills, yes, it is a square. Well, it is nothing but a nested hierarchy of concepts. What we did here, we took a complex task of identifying a square in this case and broke it into simpler tasks. Now this deep learning also does the same thing but at a larger scale. Let's take an example of machine which recognizes the animal. The task of the machine is to recognize whether the given image is of a cat or of a dog. What if we were asked to resolve the same issue using the concept of machine learning? What we would do? First, we would define the features such as check whether the animal has whiskers or not, or check if the animal has pointed ears or not, or whether its tail is straight or curved. In short, we will define the facial features and let the system identify which features are more important in classifying a particular animal. Now, when it comes to deep learning, it takes this to one step ahead. Deep learning automatically finds out the feature which are most important for classification, compared to machine learning where we had to manually give out that features. By now, I guess you have understood that AI is the bigger picture and machine learning and deep learning are its subpart. So let's move on and focus our discussion on machine learning and deep learning. The easiest way to understand the difference between the machine learning and deep learning is to know that deep learning is machine learning. More specifically, it is the next evolution of machine learning. Let's take few important parameters and compare machine learning with deep learning. So starting with data dependencies. The most important difference between deep learning and machine learning is its performance as the volume of the data gets increased. From the below graph, you can see that when the size of the data is small, deep learning algorithm doesn't perform that well. But why? Well, this is because deep learning algorithm needs a large amount of data to understand it perfectly. On the other hand, the machine learning algorithm can easily work with smaller dataset. Fine. Next comes the hardware dependencies. Deep learning algorithms are heavily dependent on high-end machines, while the machine learning algorithm can work on low-end machines as well. This is because the requirement of deep learning algorithm include GPUs, which is an integral part of its working. The deep learning algorithm requires GPUs as they do a large amount of matrix multiplication operations, and these operations can only be efficiently optimized using a GPU as it is built for this purpose only. Our third parameter will be feature engineering. Well, feature engineering is a process of putting the domain knowledge to reduce the complexity of the data and make patterns more visible to learning algorithms. This process is difficult and expensive in terms of time and expertise. In case of machine learning, most of the features are needed to be identified by an expert and then hand-coded as per the domain and the data type. For example, the features can be a pixel value, shapes, texture, position, orientation, or anything. Fine. The performance of most of the machine learning algorithm depends on how accurately the features are identified and extracted. Whereas in case of deep learning algorithms, it try to learn high-level features from the data. This is a very distinctive part of deep learning, which makes it way ahead of traditional machine learning. Deep learning reduces the task of developing new feature extractor for every problem. Like in the case of CNN algorithm, it first tries to learn the low-level features of the image, such as edges and lines, and then it proceeds to the parts of faces of people, and then finally to the high-level representation of the face. I hope the things are getting clear to you. So let's move on ahead and see the next parameter. So our next parameter is problem-solving approach. When we are solving a problem using traditional machine learning algorithm, it is generally recommended that we first break down the problem into different subparts, solve them individually, and then finally combine them to get the desired result. So this is how the machine learning algorithm handles the problem. On the other hand, the deep learning algorithm solves the problem from end to end. Let's take an example to understand this. Suppose you have a task of multiple object detection, and your task is to identify what is the object and where it is present in the image. So let's see and compare how will you tackle this issue using the concept of machine learning and deep learning. Starting with machine learning, in a typical machine learning approach, you would first divide the problem into two steps. First, object detection and then object recognition. First of all, you would use a bounding box detection algorithm like GrabCut, for example, to scan through the image and find out all the possible objects. Now, once the objects are recognized, you would use object recognition algorithm like SVM with HOG to recognize relevant objects. Now, finally, when you combine the result, you would be able to identify what is the object and where it is present in the image. On the other hand, in deep learning approach, you would do the process from end to end. For example, in a YOLONet, which is a type of deep learning algorithm, you would pass an image and it would give out the location along with the name of the object. Now let's move on to our fifth comparison parameter. It's execution time. Usually, a deep learning algorithm takes a long time to train. This is because there are so many parameters in a deep learning algorithm that makes the training longer than usual. The training might even last for 2 weeks or more than that if you're training completely from the scratch. Whereas in the case of machine learning, it relatively takes much less time to train, ranging from a few weeks to few hours. Now the execution time is completely reversed when it comes to the testing of data. During testing, the deep learning algorithm takes much less time to run. Whereas if you compare it with the KNN algorithm, which is a type of machine learning algorithm, the test time increases as the size of the data increase. Last but not the least, we have interpretability as a factor for comparison of machine learning and deep learning. This factor is the main reason why deep learning is still thought 10 times before anyone uses it in the industry. Let's take an example. Suppose we use deep learning to give automated scoring to essays. The performance it gives in scoring is quite excellent and is near to the human performance. But there's an issue with it. It does not reveal why it has given that score. Indeed, mathematically it is possible to find out that which node of a deep neural network were activated, but we don't know what the neurons were supposed to model and what these layers of neuron were doing collectively. So we fail to interpret the result. On the other hand, machine learning algorithm like decision tree gives us a crisp rule for why it chose and what it chose. So it is particularly easy to interpret the reasoning behind it. Therefore, the algorithms like decision tree and linear or logistic regression are primarily used in industry for interpretability.
So why exactly are we using Python for artificial intelligence? Why aren't we using any other language? Right? Now, there are a couple of reasons as to why Python is so popular when it comes to AI, machine learning, and deep learning. The first reason is less coding is required. Now, artificial intelligence has a lot of algorithms. If you have to implement AI in any code or in any problem, then there are going to be tons and tons of machine learning algorithms involved, deep learning algorithms involved, right? Now, testing all of these can become a very tiresome task. That's where Python usually comes in handy. Now, the language has something known as check as you code methodology, which eases the process of testing, right? You can check your program as you code it. Basically, as you're typing each sentence, your errors or your any sort of mistakes in your code will be given to you, right? So testing becomes much easier when it comes to Python. The next important reason why we're choosing Python is it has support for pre-built libraries, right? Python is very convenient for AI developers because all of the algorithms, machine learning algorithms and deep learning algorithms are already predefined in libraries, right? So you don't have to actually sit down and code each and every algorithm. That will take a lot of time, right? That's a very time consuming task. And thanks to Python, you don't have to do that because they have libraries and packages that have all the algorithms built in them, right? So if you want to run any algorithm, all you have to do is you have to call the function and load the library. That's all. It's as simple as that. Now, the next reason is ease of learning. So guys, Python is actually the most simplest programming language, right? If you ask me, I think it's the most easiest programming language. It's very similar to English language, right? If you read a couple of lines in Python, you'll understand what exactly the code is doing. It has a very simple syntax, and this simple syntax can be implemented to solve simple problems like addition of two strings, and it can also be used to solve complex problems like building machine learning models and deep learning models. So ease of learning is a major factor when it comes to why Python is chosen for artificial intelligence, right? Next, we have platform independent. So a good thing about Python is that you can get your project running on different operating systems, right? And what happens when you transfer your code from one operating system to another operating system is we find a lot of dependency issues. To solve that, Python has a couple of packages, such as there is a package known as PyInstaller. Right? This PyInstaller will take care of all the dependency issues when you're transferring your code from one platform to the other platform. So all of this support is provided by Python. The last reason is massive community support. This is a very important point because it is important that you have a large community that will help you out with any errors or with any sort of problems in your code. Right? So Python has several communities and several forums and groups on Facebook. So if you have any doubts regarding any error, you can just post those errors in these groups and you'll have like a bunch of people helping you out, right? So guys, these are a couple of reasons as to why Python is chosen for artificial intelligence. It's actually considered the most popular and the most used language for data science, AI, machine learning, and deep learning. To prove that to you, here is a stat from Stack Overflow. Stack Overflow recently stated that Python is the fastest growing programming language. If you look at the graph, you can see that it has taken over JavaScript and Java and C hash, C++, and PHP, right? So Python is actually growing at an exponential rate, especially when it comes to data science and artificial intelligence. A lot of developers are very comfortable with the Python language because, it's a general purpose language, first of all. So most of the developers are already aware of Python. And then using the same language in order to solve complex problems like artificial intelligence, machine learning, and deep learning is something every developer wants, right? They want a simple language in order to code all the complex algorithms or the complex models, right? So that's why Python is the best choice for artificial intelligence. For those of you who are not aware of Python programming and don't know much about Python, I'm going to leave a couple of links in the description box, right? You can go through those links and study a little bit more about how Python works or how the coding part works, right? I'm going to be focusing mainly on artificial intelligence and I'll be showing you a lot of demos. So those of you who are not aware of Python, make sure you check the description box, right? Next, I'm going to discuss the different Python packages for artificial intelligence. Now, these are the packages that are specifically for machine learning, deep learning, natural language processing, and so on. So let's take a look at all these packages. So first, we have TensorFlow. If you are currently working on a machine learning project in Python, then you must have heard of this popular open source library known as TensorFlow. Right, this library was developed by Google in collaboration with Brain Team. TensorFlow is used in almost every Google application for machine learning. Now, let me just discuss a few features of TensorFlow. It has a responsive construct, meaning that with TensorFlow, we can easily visualize each and every part of the graph, which is not an option when you're using other packages such as NumPy or Scikit, right? Another feature is that it's very flexible. Now, one of the most important TensorFlow features is that it is flexible in operability, meaning that it has modularity and the parts of which you want to make standalone, it offers you that option, right? It's very flexible in that way. It'll give you exactly what you want. Now, a good feature about TensorFlow is that you can train it on both CPU and GPU, right? So for distributed computing, you can have both these options. Also, it supports parallel neural network training. So TensorFlow offers pipelining in the sense that you can train multiple neural networks and multiple GPUs, which makes the models very efficient on any large scale system, right? So parallel neural network training is supported by TensorFlow, right? This is one of the most important features of TensorFlow. Apart from this, it has a very large community. And needless to say, if it has been developed by Google, then there's already a large team of software engineers who work on stability improvements and all of that, right? The next library I'm going to talk about is scikit-learn. Now, scikit-learn is a Python library that is associated with NumPy and SciPy, right? That's why it has the name scikit-learn. Now, this is considered to be one of the best libraries for working with complex data. There are a lot of changes that are being made in this library, and one modification is the cross-validation feature, which provides the ability to use more than one metric. Right? Cross-validation is one of the most important and one of the most easiest methods for checking the accuracy of a model, right? So cross-validation is being implemented in scikit-learn. And apart from that, again, there are a large spread of algorithms that you can implement by using scikit-learn, right? These include unsupervised learning algorithms, starting from clustering, factor analysis, principal component analysis, to all the unsupervised neural networks. Scikit-learn is also very essential for feature extracting in images and text. So mainly scikit-learn is used for implementing all the standard machine learning and data mining tasks like reducing dimensionality, classification, regression, clustering, and model selection. Next up, we have NumPy. Now, NumPy is considered as one of the most popular machine learning libraries in Python. Now, let me tell you that TensorFlow and other libraries, they make use of NumPy internally for performing multiple operations on tensors. The most important feature of NumPy is the array interface. It supports multi-dimensional arrays, right? That's one of the most important features of NumPy. Another feature is it makes complex mathematical implementations very simple, right? It's mainly known for computing mathematical data. So NumPy is a package that you should be using for any sort of statistical analysis or data analysis that involves a lot of math. Apart from that, it makes coding very easy, and grasping the concept is extremely easy with NumPy. Now, NumPy is mainly used for expressing images, sound waves, and other mathematical computations. All right. Moving on to our next library, we have Theano. Theano is a computational framework which is used for computing multi-dimensional arrays. Right? Theano actually works very similar to TensorFlow, but the only drawback is that you can't fit Theano into production environments. But apart from that, Theano allows you to define, optimize, and evaluate mathematical expressions that involve multi-dimensional arrays. Right? This is another library that lets you implement multi-dimensional arrays. Features of Theano include tight integration with NumPy. An advantage of Theano is that you can easily implement NumPy arrays in Theano, right? That's why there's a connection between Theano and NumPy, because both of them effectively use multi-dimensional arrays. Transparent use of GPU. Now, performing data-intensive computations are much faster when it comes to Theano because of its use of GPU, right? Theano also lets you detect and diagnose multiple types of errors and any sort of ambiguity in the model. So guys, Theano was actually designed to handle the types of computations required for large neural network algorithms, right? It was mainly built for deep learning and neural networks. It was one of the first libraries of its kind, and it is considered as an industry standard for deep learning research and development. Theano is being used in multiple neural networks projects, and the popularity of Theano is only going to grow with time, right? A lot of people actually haven't heard of Theano, but let me tell you that this is one of the best ways to implement deep learning and neural network models. Moving on, we have Keras. Now, Keras is considered to be the most popular Python package. It provides some of the best functionalities for compiling models, processing your data sets, and visualizing graphs. It is also popular in the implementation of neural networks, right? It is considered to be the simplest package with which you can implement neural networks. In fact, in our today's demo for deep learning, we'll be implementing Keras in order to understand how neural networks work. Few of the features of Keras include that it runs very smoothly on both CPU and GPU. It supports almost all the models of a neural network, right? From fully connected, convolutional, pooling, recurrent, embedding, all of these models are supported by Keras. And not only that, you can combine these models to build more complex models. Keras is completely Python based, which makes it very easy to debug and explore, right? Since Python has a huge community of followers, it's very simple in order to debug any sort of error that you find while implementing Keras. So the libraries that I discussed so far were dedicated to machine learning and deep learning. For natural language processing, we have the most famous library known as the Natural Language Toolkit, which is an open source Python library mainly used for natural language processing, text analysis, and text mining. The main features include that it studies and analyzes natural language text in order to draw useful information from all this natural language text. It performs text analysis and sentimental analysis by performing tasks such as stemming, lemmatization, tokenization, and so on. Now, don't worry if you don't know what any of those terms mean. I'll be discussing all of those terms with you by the end of today's session. So guys, these were a couple of Python based libraries which are very essential for implementing machine learning and deep learning and artificial intelligence when you're using Python, right? These libraries are perfect for implementing AI. So guys, if any of you have any doubts regarding the libraries, or if you want to learn more about the libraries, I will leave a couple of links in the description box. You can go through those videos as well. So now let's move on to the main topic of discussion, which is artificial intelligence. Now, before we get started with the demand of artificial intelligence, let me tell you that AI was invented long ago. AI goes back to the 19th century. It was not something that was recently invented, even though AI has recently gained a lot of popularity. We can say that in the past decade, AI has gained the maximum popularity. But it was actually invented in the 19th century. Now, especially in the year 1950, there was somebody known as Alan Turing. I'm sure a lot of you have heard about the Turing test. The Turing test is basically used to determine whether or not a machine is artificially intelligent, meaning that whether a machine can think intelligently like a human being, right? This was the first proposition, and this was one of the most important breakthroughs in artificial intelligence, right? Somebody known as Alan Turing, he published a landmark paper in which he speculated about the possibility of creating machines that think, right? So the Turing test was the first serious proposal in the philosophy of artificial intelligence. This was done in 1950, right? After this, we had eras of AI. We had the game AI, which was in 1951. Now, since the emergence of AI in 1950s, we have seen an exponential growth in its potential, right? AI covers domains like machine learning, deep learning, neural networks, natural language processing, knowledge base, and so on. It's also made its way into computer vision and image processing. But the question is, if AI has been here for over half a century, why has it suddenly gained so much importance, right? Why are we talking about artificial intelligence now? The main reasons for the vast popularity of AI are the following, right? The first reason is more computational power. Now, AI requires a lot of computing power. Recently, many advances have been made and complex deep learning models can be deployed. And one of the greatest technology that made this possible are GPUs. Since the invention of GPUs, we can compute much more with our computers. Initially, we could barely process 1 GB of data, right? We only had hard disks to store additional memory and all of that. Now our computers can process tons and tons of data. So now we have more computational power, which is one of the main reasons behind why AI became so popular. So by having more computational power, it becomes much easier to implement artificial intelligence. Next reason is more data. Now, big data is one of the most important reasons behind the development of artificial intelligence. Now, AI and data science and machine learning, deep learning, all of these processes are here only because we have a lot of data at present. And the main idea behind all these technologies is to draw useful insights from data. Now, since we start generating a lot of data, we need to find a method that can process this much data and draw useful insights from data such that it benefits an organization or it grows a business. That's why artificial intelligence and machine learning comes into the picture, right? So more data led to the demand of artificial intelligence. Apart from this, we also have better algorithms now, right? We have state-of-the-art algorithms. Most of them are based on the idea of neural networks, and these are constantly getting better. Neural networks are actually one of the most significant discoveries in artificial intelligence because with neural networks, you can take in 1,000 layers of input data, right? You can take in a lot of input data to perform computations. So through neural networks, we're actually able to solve a lot of problems, including healthcare problems, fraud detection problems, and so on. Another reason is broad investment. So our universities and governments and startups and any tech giants like Google, Amazon, and Facebook, they are all investing heavily in artificial intelligence, which also led to the demand of AI. So AI is rapidly growing both as a field of study and also as an economy, right? It's adding a lot to the economy. And I think this is the perfect time for you to get into the field of artificial intelligence because right now AI is in a really high demand. AI, machine learning, data science, all of this are of really high demand at present. Right, so this is the perfect time for you to get started with artificial intelligence. Now, let me tell you that the term artificial intelligence was first coined in the year 1956 by a scientist known as John McCarthy. Now, John McCarthy defined artificial intelligence as the science and engineering of making intelligent machines. Now, let me give you a descriptive definition of artificial intelligence. Artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. In a sense, artificial intelligence is a technique of getting machines to work and behave like humans. In the recent past, AI has actually been able to accomplish this by creating machines and robots that have been used in a wide range of fields, including healthcare, robotics, marketing, business analytics, and many more. Right? So AI is actually a very vast field. It covers a lot of domains, including machine learning, natural language processing, knowledge base, deep learning, computer vision, and expert systems. So these are a few domains that AI covers. Now let's move on and discuss the different types of artificial intelligence. Now guys, AI is structured along three evolutionary stages. You can say that AI is developed along three evolutionary stages. We have something known as artificial narrow intelligence, followed by artificial general intelligence, and finally we have artificial super intelligence. Artificial narrow intelligence, which is also known as weak AI, it involves applying AI only to specific tasks. Many of the currently existing systems that claim to use artificial intelligence are actually operating as weak AI, which is focused on a narrowly defined specific problem. Now, take Alexa. Alexa is actually a good example of artificial narrow intelligence. It operates within a limited predefined range of functions, right? There is no genuine intelligence or no self-awareness despite being a sophisticated example of weak AI. Google search engine, Sophia, and self-driving cars, and even the famous AlphaGo fall under the weak AI category. Then we have something known as artificial general intelligence. This is also known as strong AI, and it involves machines that possess the ability to perform any intellectual task that a human being can. Now, guys, machines don't possess human-like abilities. They have a very strong processing unit that can perform high-level computations, but they're not yet capable of thinking and reasoning like a human. And there are also many who question whether it would be desirable. For example, Stephen Hawking warned that strong AI would take off on its own and redesign itself at an ever increasing rate. Humans who are limited by slow biological evolution couldn't compete and would be superseded. Right, so we have a lot of tech giants and a lot of geniuses who are actually worried if strong AI is ever implemented, it might take over the world. Right, so guys, let me tell you that strong AI is something that has not been implemented yet. We are only at the first stage of artificial intelligence, which is artificial narrow intelligence, also known as weak AI. Right, we haven't yet reached strong AI or artificial super intelligence. So, artificial superintelligence is a term that refers to the time when the capabilities of a computer will surpass humans. Right? ASI is currently seen as a hypothetical situation as depicted in movies and science fiction books where machines have taken over the world. Right? So, artificial superintelligence is something that is very far off, but tech masterminds like Elon Musk believe that artificial superintelligence will take over the world by the year 2040. Right, there are a lot of people who are against the development of artificial general intelligence and artificial super intelligence. A lot of us believe that we should stick to weak AI and not move any further and risk the existence of human civilization. So guys, let me know your thoughts about artificial intelligence in the comment section. I'd love to know what you guys think about AI and whether you all believe AI will take over the world or not. So now let's move on and talk about how artificial intelligence is different from machine learning and deep learning. A lot of people tend to assume that artificial intelligence, machine learning, and deep learning are the same because they have common applications, right? For example, Siri is an application of AI, machine learning, and deep learning. So how are these technologies related, right? Or how are they different from each other? Now, artificial intelligence is the science of getting machines to mimic the behavior of human beings. Machine learning is the subset of artificial intelligence that focuses on getting machines to make decisions by feeding them data. Deep learning, on the other hand, is a subset of machine learning that uses the concept of neural networks to solve complex problems. So, to sum it up to you, artificial intelligence, machine learning, and deep learning are heavily interconnected fields. Right? Machine learning and deep learning aids artificial intelligence by providing a set of algorithms and neural networks to solve data-driven problems. However, AI is not restricted to only machine learning and deep learning. Right? It covers a vast domain of fields which include natural language processing, object detection, computer vision, robotics, expert systems, and so on. Right? So AI is a very vast field. Guys, I hope I cleared the difference between AI, machine learning, and deep learning. Also, a lot of you might be confused about data science. Data science is now an umbrella term, right? Data science basically means to derive useful insights from data. So data science actually uses AI, machine learning, and deep learning, right? So it implements all of these three technologies in order to derive useful insights from data, right? Now let's move on to the most interesting topic in artificial intelligence, which is machine learning. Now, guys, the term machine learning was first coined by a scientist known as Arthur Samuel in the year 1959. Looking back, that year was probably the most significant in terms of technological advancements. In order to define machine learning, if you browse the internet for what is machine learning, you'll get at least 100 different definitions. In simple terms, machine learning is a subset of artificial intelligence which provides machines the ability to learn automatically and improve from experience without being explicitly programmed to do so. In a sense, it is the practice of getting machines to solve problems by gaining the ability to think. Now, the question here is, can a machine think or can a machine make decisions? Well, if you feed a machine a good amount of data, it will learn how to interpret, process, and analyze this data by using something known as machine learning algorithms. To give you a basic idea of how the machine learning process works, look at the figure on this slide. A machine learning process always begins by feeding the machine lots and lots of data. Now, by using this data, the machine is trained to detect any hidden insights and trends in the data. These insights are then used to build a machine learning model by using a machine learning algorithm in order to solve a problem. The basic aim of machine learning is to solve a problem or find a solution by using data. Now, moving ahead, I'll be discussing the machine learning process in depth, right? So don't worry if you haven't got the exact idea of what machine learning is. Now, the machine learning process involves building a predictive model that can be used to find a solution for a particular problem. A well-defined machine learning process will have around 7 steps. It always begins with defining the objective, followed by data gathering or data collection. Then we have something known as preparing data, which is also called data pre-processing. Then we have data exploration or exploratory data analysis. This is followed by building a machine learning model. Then we have model evaluation and finally predictions. This is how the process of machine learning works. To understand the machine learning process, let's assume that you've been given a problem that needs to be solved by using machine learning. Let's say that the problem is to predict the occurrence of rain in your local area by using machine learning. Now, the first step is to define the objective of the problem. Right? At this step, we must understand what exactly needs to be predicted. In our case, the objective is to predict the possibility of rain by studying the weather conditions. So at this stage, it is essential to take mental notes on what kind of data can be used to solve this problem or the type of approach that you must follow to get to the solution. The questions you should be asking yourself is, what are we trying to predict? Right? Here we're trying to predict whether it'll rain or not. Right? You need to understand what are the target features. Target features are basically the variable that you need to predict. Here we need to predict a variable that will show us whether it's going to rain tomorrow or not. Then you must also understand what kind of data you will need to solve this problem. Apart from that, you need to know what kind of problem you're facing. Is it a binary classification problem or is it a clustering problem? Now, if you don't know what classification and clustering is, don't worry, I'll be talking about all of these things in the upcoming slides. So your first step is to define the objective of your problem. You need to understand what exactly needs to be done here, right? How can you solve this problem? Moving on, your next step is to gather the data that you need. At this stage, you must be asking questions such as what kind of data is needed to solve this problem? Is the data available to me? And if it's not available, how can I get the data? Right? Once you know the type of data that is required, you must understand how you can derive this data. Data collection can be either done manually or it can be done by web scraping. But don't worry if you're a beginner and you're just looking to learn machine learning, you don't have to worry about getting the data. There are thousands of data resources on the web. You can just download the data set and you can get going. Coming back to the problem at hand, the data needed for weather forecasting includes measures such as humidity level, your temperature, the pressure, the locality, whether or not you live in a hill station, and so on. Such data must be collected and it has to be stored for analysis. This is where you collect all the data. Now, moving on to step number 3 is data preparation. The data that you collected is almost never in the right format. All right, even if you collect it from an internet resource, if you download it from some website, even then your data is not going to be clean, right? It's not going to be in the correct format. There's always going to be some sort of inconsistencies in your data. Inconsistencies include any missing values or any redundant variables, duplicate values. All of these are inconsistencies. Removing all of this is very essential because they might lead to any wrongful computation. Therefore, at this stage, you can scan the entire data set for any missing values and you have to fix them here itself. Now, actually, this is one of the most time-consuming steps in a machine learning process. If you ask a data scientist which step he hates the most or which step is, the most time-consuming, they're probably going to tell you data processing and data cleaning, right? It's one of the most tiresome tasks because you need to look at all the values that are there. You need to find any missing values, any data that is not relevant to you, right? All of this has to be removed such that you can analyze the data in a better way. Now, step number 4 is exploratory data analysis. So guys, this stage is all about getting deep into your data and finding all the hidden data mysteries. EDA or exploratory data analysis is like the brainstorming stage of machine learning. Data exploration involves understanding the patterns and the trends in your data. So at this stage, all the useful insights are drawn and any correlations between the variables are understood. For example, in the case of predicting rainfall, we know that there is a strong possibility of rain if the temperature has fallen low. Such correlations have to be understood and mapped at this stage. EDA is actually the most important step in a machine learning process because here is where you understand your data. You understand how your data is going to help you predict the outcome. Moving on to step number 5, we have building a machine learning model. So all the insights and all the patterns that you got from your data exploration stage, those insights are used to build the machine learning model. So this stage always begins by splitting the data set into 2 parts, that is training and testing data. Now remember that the training data will be used to build and analyze the model. The model is basically the machine learning algorithm that predicts the output by using the data that you feed to it. An example of machine learning algorithm is logistic regression and linear regression. All of these are machine learning algorithms. Now, don't worry about choosing the right algorithm, right? First, we'll focus on what the machine learning process is. But anyway, choosing the right algorithm will depend on several factors, right? It depends on the type of problem you're trying to solve, the data set, and the level of complexity of the problem. In the upcoming sections, we'll discuss all the different types of problems that can be solved by using machine learning. Moving on to step number 6, we have model evaluation and optimization. Now, after you build a model by using the training dataset, it is finally time to put the model to a test. The testing dataset is used to check the efficiency of the model and how accurately it can predict the outcome. Now, once the accuracy is calculated and any further improvements in the model, they have to be implemented at this stage. Methods like parameter tuning and cross-validation can be used to improve the performance of the model. Before I move any further, I don't know if all of you know what training and testing dataset means. In machine learning, the input data is always divided into 2 sets. We have something known as the training dataset and we have something known as the testing dataset. So in machine learning, you always split the data into 2 parts. right? This process is known as data splicing. Now, the training data set will be used to build the machine learning model, and the testing data set will be used to test the efficiency of the model that you built. This is what training and testing data set is. They're not a categorical variable. Categorical variable is anything that has some categorical value. For example, gender is a categorical variable. Gender has either male, female, or other. It has a defined set of values. That is a categorical variable. So guys, that was the entire machine learning process. Now, as we continue with this tutorial, in the upcoming sections, I will be running a demo in Python in which we will be performing weather forecasting. So make sure you remember all these steps that I spoke about, because I'll be going through all these steps by using Python. We'll be coding all of this that we just spoke about. Now, the next topic we're going to discuss is the types of machine learning. A machine can learn to solve a problem by following any one of the three approaches. You can say that there are three ways in which a machine learns. The three ways are supervised learning, unsupervised learning, and reinforcement learning. These are the three methods in which you can train a machine to learn. So first, let's discuss supervised learning. So what is supervised learning? Supervised learning is a technique in which we teach or train the machine by using data which is labeled. To understand this better, let's consider an analogy. As kids, we all needed guidance to solve math problems. At least I had a really tough time solving math problems. Yeah, so our teachers always helped us understand what addition is and how it is done. Similarly, you can think of supervised learning as a type of machine learning that involves a guide. The label dataset is a teacher that will train the machine to understand the patterns in the data. The label dataset is nothing but the training dataset. So to better understand this, consider the figure. Right here, we are feeding the machine images of Tom and Jerry, and the goal is for the machine to identify and classify the images into two separate groups. Basically, one group will contain Tom images and the other group will contain images of Jerry. Now pay attention to the training dataset. The training dataset that is fed to a model is labeled, as in we're telling the machine, listen, this is how Tom looks and this is how Jerry looks. We're basically labeling each data point that we're feeding to the machine, right? If the image is of Tom's, we've labeled it as Tom, and if the image is a Jerry image, then we're going to label it as Jerry. By doing this, you're training the machine by using labeled data. So to sum it up, in supervised learning, there is a well-defined training phase done with the help of labeled data. Right? The rest of the process is the same. After you feed the machine labeled data, you're going to perform data cleaning, then exploratory data analysis, followed by building the machine learning model, and then model evaluation, and finally your predictions. Also, one more point to remember is that the output that you're going to get in a supervised learning algorithm is a labeled output. This Jerry will be labeled as Jerry and this Tom will be labeled as Tom. Basically, you'll get a labeled output. Now let's understand what is unsupervised learning. Unsupervised learning involves training by using unlabeled data and allowing the model to act on that information without any guidance. So think of unsupervised learning as a smart kid that learns without any guidance. In this type of machine learning, the model is not fed with any labeled data. As in, the model has no clue that this image is Tom and this image is Jerry. It figures out patterns and the differences between Tom and Jerry on its own by taking in tons of data. For example, it identifies prominent features of Tom such as pointy ears, bigger in size and so on to understand that this image is of type 1. Similarly, it finds such features in Jerry and knows that this is another type of image, maybe type 2. Right? Therefore, it classifies the images into two different clusters without knowing who is Tom and who is Jerry. Now, the main idea behind unsupervised learning is to understand the patterns in your data set and form clusters based on feature similarity. Basically, it'll feature similar images or similar data points into one cluster, and it'll form another cluster which is totally different from the first cluster. So look at the output over here. The unlabeled output is basically clusters or groups of two different data. Next, we have something known as reinforcement learning. Now, reinforcement learning is comparatively different, right? It's pretty different from supervised and unsupervised. It is basically a part of machine learning where you put an agent in an environment, and this agent learns to behave in the environment by performing certain actions and observing the rewards which it gets from these actions. To understand reinforcement learning, imagine that you were dropped off at an isolated island. What would you do? Initially, we'd all panic, right? But as time passes by, you will learn how to live on the island. You will explore the environment. You will understand the climate conditions. You'll understand the type of food that grows there. You'll know what is dangerous to you and what is not. You'll understand which food is good for you and which is not. This is exactly how reinforcement learning works. It involves an agent, which is basically you stuck on the island, that is put in an unknown environment, which is the island, where the agent must learn by observing and performing actions that result in rewards. Reinforcement learning is mainly used in advanced machine learning areas such as self-driving cars, AlphaGo, and so on. So guys, that sums up the types of machine learning. Before we go any further, I'd like to discuss the difference between supervised, unsupervised, and reinforcement learning. Now, first of all, we have the definition. Supervised learning is all about teaching a machine by using labeled data. Unsupervised learning, like the name suggests, there is no supervision over here. The machine is trained on unlabeled data without any guidance. Reinforcement learning is totally different. Here you have an agent who interacts with the environment by producing actions and discovers some errors and rewards. Now, the type of problem that is solved using supervised learning is regression and classification problems. We'll discuss what regression, classification, and clustering is in the upcoming slide, right? So don't worry if you don't know what it is. Unsupervised learning is mainly to solve association and clustering problems. Reinforcement learning is for reward-based problems. Now, what is the type of data in supervised learning? It is labeled data. That is the main difference between supervised and any other type of machine learning. In supervised, you have labeled data. In unsupervised, we have unlabeled data. Whereas in reinforcement learning, we have no predefined data at all. The machine has to perform everything from scratch. It has to collect data, analyze, do everything on its own. Now, the training in supervised learning is external supervision, meaning that we have external supervision in the form of the labeled training data set. In unsupervised, there is obviously no supervision. There is an unlabeled data set, therefore there's no supervision. In reinforcement learning, there is no supervision at all. Now, the approach to solving supervised learning problem is basically you're going to map your labeled input to your known output. In unsupervised learning, the machine is going to understand the patterns and discover the output on its own. Reinforcement learning, here the agent will follow something known as a trial and error method, right? It's totally based on the concept of trial and error. Popular algorithms under supervised learning are linear regression, logistic regression, support vector machines, and so on. Under unsupervised learning, we have the famous K-means clustering algorithm. Under reinforcement learning, we have the Q-learning algorithm, which is one of the most important algorithms. It is basically the logic behind the famous AlphaGo game. I'm sure all of you have heard of that. So guys, these were the differences between supervised, unsupervised, and reinforcement learning. Now let's move on and discuss the type of problems that you can solve by using machine learning. Now there are three types of problems in machine learning. Now any problem that needs to be solved in machine learning can fall into one of these three categories. Now what is regression? In this type of problem, the output is a continuous quantity. For example, if you want to predict the speed of a car given the distance, that means it is a regression problem. First of all, what is a continuous quantity? A continuous quantity is any variable that can hold a continuous value. A continuous variable is any variable that can have infinite number of values. For example, the height of a person or the weight of a person is a continuous quantity, right? I can have a weight of 50.1 kgs or 50.12 or 50.112 kgs. This is a continuous quantity. Regression problems can be solved by using supervised learning algorithms. Another type of problem is the classification problem. Here the output is always a categorical value. Classifying emails into two classes, for example, classifying your email as spam and non-spam, is a classification problem. Here again, you'll be using supervised learning classification algorithms such as support vector machines, naive Bayes, logistic regression, and so on. Then we have clustering problem. Right? This type of problem involves assigning the input into two or more clusters based on feature similarity. For example, clustering the viewers into similar groups based on their interest or based on their age or geography can be done by using unsupervised learning algorithms like k-means clustering. One thing you need to understand is under supervised learning, you can solve regression and classification problems. Under unsupervised learning, you can solve clustering problems. Reinforcement learning is something else altogether, right? You can solve reward-based problems and more complex and deep problems. So now let's move on and understand the different machine learning algorithms. Now, I will not be going into depth for machine learning algorithms because there are a lot of algorithms to cover, but we have content around almost every machine learning algorithm out there. So I'll be leaving a couple of links in the description box, right? You can check out all these links and understand how each of these machine learning algorithms work in depth. So I'm just going to show you a hierarchical diagram of how the algorithms are structured. So under machine learning, we have three types of learning. We have supervised, unsupervised, and reinforcement. Under supervised learning, we have regression and classification problems. And under unsupervised learning, we have clustering problems. Reinforcement learning is completely different. I'll be leaving a link in the description specifically for reinforcement learning. You can check out the entire content of reinforcement learning there. Now, regression problems can be solved by using linear regression. Algorithms such as linear regression, decision trees, and random forests can also be used in regression problems. But usually decision trees and random forests, all of these are used to solve classification problems. Famous classification algorithms include k-nearest neighbor, which is basically KNN, decision trees and random forests, logistic regression, naive bayes, support vector machines. All of these are classification algorithms. Coming to unsupervised learning, we have clustering and association analysis. Right? Clustering problems can be solved by using k-means, and association analysis can be solved by using Apriori algorithm. Apriori algorithm is mainly used in market basket analysis. Right? For this algorithm as well, I'll be leaving a link in the description. We've performed a very excellent demo wherein we've showed how market basket analysis can be done by using Apriori algorithm. Markov model is also explained in one of the videos. I'll be leaving that link in the description box. Now, to sum up machine learning to you, I'll be running a small demonstration in Python. Right? Like I promised earlier, I will be using Python to understand the whole machine learning process. All right, so let's get started with that demo. So guys, for those of you who don't know Python, I will leave a couple of links in the description box so that you understand Python. But apart from that, Python is pretty understandable. If you just look at the code, you'll know what exactly I'm talking about. Right? So don't worry. And also I'll be explaining everything in the code. So I'm using PyCharm in order to run the demo. Right? So guys, like I said, if you don't know Python, I'll leave a couple of links in the description box. You can go through those videos as well. The main aim of our demo is to build a machine learning model that will predict whether or not it will rain tomorrow by studying the past dataset. Now, this dataset contains around 145,000 observations on the daily weather conditions as observed in Australia. Right? The dataset has around 24 features, and we will be using 23 features out of that to predict the target variable, which is rain tomorrow. So this dataset I collected from Kaggle. Right? For those of you who don't know, Kaggle is an online platform where you can find hundreds of data sets, and there are a lot of competitions held by machine learning engineers and all of that. It's an interesting website. Now, the problem statement itself is to build a machine learning model that will predict whether or not it will rain tomorrow. This is clearly a classification problem. The machine learning model has to classify the output into two classes, that is either yes or no. Yes will stand for it will rain tomorrow, and no will basically denote that it will not rain tomorrow. Right? This is a classification problem. So I hope the objective is clear. Right, so we'll begin the demonstration by importing the required libraries. So first of all, for mathematical computations, we'll be importing the NumPy library. We'll also be importing the pandas library for data processing. Next, we will load the CSV file. Basically, my data is stored in a CSV format in this file. Weather.os.csv is my data set. So basically, I've saved this file in this path. Right, so that's what I'm doing here. I'm loading my data set. and I'm storing it in a variable known as df. Next, what we'll do is we'll see the size of our data frame. Let's print the size of the data frame. We'll also display the first 5 observations in our data frame. So let's look at the output. Basically around 145,000 observations and 24 features. Now 24 features are basically the variables that are there in my data set. For example, date is a variable, location is a variable, minimum temperature, till rain tomorrow, all of these are variables. So I have around 24 features in my data set, right? Now the variable that I have to predict is rain tomorrow, okay? If the value of rain tomorrow is no, it denotes that it will not rain tomorrow. But if the value is yes, then it will denote that it will rain tomorrow. So rain tomorrow is basically my target variable, right? I'll be finding out whether it's going to rain tomorrow or not. So this is my target variable, also known as your output variable. My input variables will be the other 23 variables: date, location, minimum temperature, rain today, risk. All of this will be my input variables. Now these variables are also known as predictor variables. Basically, they're used to predict your outcome. So these are also known as predictor variables. Now the next step is checking for null values. This is basically data pre-processing. Let me just comment it for you. This is data preparation or data. Right, so this stage is data pre-processing, right? Here we start checking for any null values or any missing values. That's exactly what I'm doing over here. I am checking for any missing or null values in my data set. If you notice the output, it shows that the first 4 columns have more than 40% null values, right? So it's always best for us to remove features or such variables because they will not help us in our prediction. Now, during data pre-processing, it is always necessary to remove the variables that are not significant. Unnecessary data will just increase our computations. That's why it's always best if we remove the unwanted or unnecessary variables. Now, apart from removing these 4 variables, we'll also remove the location variable and we will remove the date variable, right? I'll come to this variable in a minute. We'll also be removing location and date variable because both of these variables are not needed in order to predict whether it'll rain tomorrow, right? We do not need to know the location and the date. Now, we'll also be removing this risk variable. Risk variable basically tells us the amount of rain that might occur the next day. Right now, this is a very informative variable and it might actually leak some information to our model. By using this variable, we'll easily be able to predict and there's no point of doing that. This variable will give us too much information. Right? So that's why we're going to remove this variable as well. It'll leak a lot of information. So after that, if you print the shape of your data frame, we have only 17 variables and so many observations. Now after this, we'll just look at any null values and we'll remove them. This drop.any function will just remove all the null values, right? Then if you print the shape of your data frame, we'll have around 112,000 rows with 17 variables. This is the shape of the data set after removing all the null values and all the redundant or unnecessary variables. Now it's time to remove the outliers in the data. So after you remove any null values, we should also check our data set for any outliers. An outlier is a data point that is very different from your other observations. Outliers usually occur because of miscalculations while collecting the data. These are some sort of errors in your data set. So in this whole code snippet, we're just getting rid of outliers. This is the output that we get, all our outliers. Next, what we'll be doing is we will be assigning zeros and ones in the place of yes and no. The only thing is we're going to change the categorical variables from yes and no to 0 and 1. Right? That's exactly what we're doing over here. Now, if there are any unique values such as any character values which are not supposed to be there, we'll be changing them into integer values. That's all we're doing over here. After this, we'll be normalizing our data set. This is a very important step because in order to avoid any biasness in your output, you have to normalize your input variables. Right? To do this, we can make use of the min-max scalar function, which Python provides in a package known as sklearn. You can use that package in order to normalize your data set. So after normalizing our data set, this is what our data set looks like. This is before normalization. You can see that these are in 2 digits, whereas these values are in single digits, right? This causes a lot of biasness. But once we normalize the values, we know that all of the values are in a similar range. We have everything in decimals, right? So normalization is something that has to be performed, because if you have a data set like this, your output is not going to be correct. And that's why we perform normalization. So now that we are done with pre-processing, what we're going to do is it's time for exploratory data analysis. Let me just comment it for you. This is exploratory data analysis. So basically here what we're going to do is we're going to analyze and identify the significant variables that will help us predict the outcome. To do this, we'll be using the select k-best function, which is present in the sklearn library. There's a predefined function in Python called select k-best, which will basically select the most significant predictor variables in our data set. When we run that line of code, we get these 3 variables to be the most significant variables in our data set. Right? The main aim of this demo is to make you understand how machine learning works. That's why, to simplify the computation, we'll assign only one of these significant variables as the input. Instead of taking all 3 variables as input, we'll select one variable and we'll take that as the input, and the output is the rain tomorrow variable. So basically, we are creating a data frame of all the significant variables. Basically, we're choosing this variable in order to predict our outcome. Obviously, our outcome is rain tomorrow variable. So our input is humidity level and our output is to detect whether it'll rain tomorrow. The next step is data modeling. All of you are aware of what data modeling is. To solve this, we'll be using classification algorithms over here. We'll use logistic regression. We will use random forest classifier, which is another machine learning algorithm. We'll also use the decision tree classifier and support vector machine. Right? We'll be using all of these algorithms in order to predict the outcome. We'll also check which algorithm gives us the best accuracy. So guys, we're just using multiple algorithms or multiple classification algorithms on the same data set. We're not doing anything very complex over here. So we start by importing all the necessary libraries for the logistic regression algorithm. We're also going to import time because we'll be calculating the accuracy and the time taken by the algorithm to get the output. So the first step is data splicing. I've already mentioned data splicing is splitting your data set into your testing data set and into your training data set. That's exactly what we're doing over here. So 25% of your data is assigned for the testing data and the remaining 75% is your training data. Here you're creating the instance of the logistic regression algorithm. This is an instance that you created. Then you'll fit the model by using your training data set. So basically, to build your machine learning algorithm, you'll be fitting your training data set. So xtrain and ytrain variables have your training data set. After that, you will be evaluating the model by using your testing data set. Then you'll calculate the accuracy score, right? I'll also be printing the accuracy using logistic regression and the time taken using logistic regression. Let's look at the accuracy. Don't worry about these warnings, they are not important. So accuracy using logistic regression is around 0.83%, which is 83% accuracy, approximately 84%. And this is the time taken. So the accuracy is actually pretty good, right? 84% is a good number. Then we have random forest classifier. Here again, we'll import the libraries that are needed to run random forest classifier. Then we're again calculating the accuracy and the time taken by the classifier. Data splicing, like I mentioned, splitting the data into testing and training data set. Then you're just building the model by using the training data set. After that, you'll evaluate the model by using the testing data set, and you'll finally calculate the accuracy. The accuracy using random forest is again approximately 84%, which is a really good number. Then we have decision tree classifier. Here again, we'll be importing the libraries needed for this classifier. We'll be calculating the accuracy and the time taken by this classifier. Data splicing, followed by building the model by using the training data set, evaluating the model by using the testing data set, and finally calculating the accuracy and printing the accuracy. So let's see the accuracy using decision tree classifier. Again, we have an accuracy of around 83 to 84%. This is a pretty good number. And last, we're going to do this by using another classification algorithm known as support vector machine. Here again, we are importing the needed libraries. Then we're calculating the accuracy and the time, performing data splicing. Then we're building the model by using the training data set, testing the model using the testing data set, and finally printing the accuracy. So guys, all the classification models gave us an accuracy score of approximately 84% to 83%. So this is exactly how a machine learning process works, right? You begin by importing all your data, then you perform data pre-processing or data cleaning. After that, you perform exploratory data analysis, where you understand the important patterns or the important variables in your data set. After that, you build a model, then you will evaluate the model by using the testing data set, and finally calculate the accuracy. I showed you all the steps in the machine learning process by using a practical demonstration in Python. So guys, give yourself a pat on the back because we just understood the whole machine learning process with a small implementation in Python. Now let's move on to our next topic, which is limitations of machine learning. Before we understand what deep learning is, it's important to know the limitations of machine learning and why these limitations gave rise to the concept of deep learning. One major problem in machine learning is machine learning algorithms and models are not capable of handling high dimensional data. Right? We can take in data with 20 to 30 feature variables, but when it comes to data sets which have thousands of variables, machine learning does not work. Machine learning is not capable enough to process that much data. So high dimensional data cannot be analyzed, processed, and modeled by using machine learning. Another limitation is that it cannot be used in image recognition and object detection because these applications require the implementation of high dimensional data. Another major challenge in machine learning is to tell the machine what are the important features it should look for in order to precisely predict the outcome. So basically, you're selecting the important features for the machine learning model and you're telling them, like, these are the important features, and this is what you should use in order to build the model. This process is known as feature extraction. Now, in machine learning, this is a manual process. You're going to manually input as a programmer. You're going to tell that these are the important predictor variables. But what happens when your data set has hundreds of variables? How are you going to sit and choose every variable and perform analysis on each variable to understand which is a really significant variable? That's going to become a very tedious task, right? It's not possible for you to manually sit down with 100 variables, check the correlation with each variable, and understand which variable is significant in predicting the output. So performing feature extraction manually is very tedious, and that is one of the major limitations of machine learning. Now, deep learning comes to the rescue to all of these problems. So let's understand what deep learning is and why we have deep learning in the first place. So deep learning is actually one of the only methods by which we can overcome the challenge of feature extraction. This is because deep learning models are capable of learning to focus on the right features by themselves, requiring minimal human intervention, meaning that feature extraction will be performed by the deep learning model itself. You don't have to manually tell that this feature is important, that feature is important, choose this feature for predicting the output. All of this is not needed in deep learning. The model itself will learn which features are most significant in predicting the output. Also, deep learning is mainly used to deal with high dimensional data, right? It is based on the concept of neural networks and is often used in object detection and image processing. This is exactly why we need deep learning. It solves the problem of processing high dimensional data and manual feature extraction. Now, how exactly does deep learning work? Now, deep learning mimics the basic component of the human brain called the brain cell. The brain cell is also known as a neuron. So, inspired from a neuron, an artificial neuron was developed. Deep learning is based on the functionality of a biological neuron. So, let's understand how we mimic this functionality in an artificial neuron. Now, guys, an artificial neuron is also known as a perceptron. Let's understand what this biological neuron does and how deep learning is based on this concept. In a biological neuron, you can see these dendrites, right? In this image, you see something known as dendrites. These dendrites are used to receive any input. These inputs are summed in the cell body, and through the axon, it is passed on to the next neuron. So similar to the biological neuron, a perceptron or an artificial neuron receives multiple inputs applies various transformations and functions, and provides an output. Right? So that's how artificial neural networks, or that's how deep learning works. Now, guys, the human brain consists of multiple connected neurons called a neural network. Similarly, by combining multiple perceptrons, we've developed what is known as deep neural networks. The main idea behind deep learning is neural networks, and that's what we're going to learn about. So now let's understand what exactly deep learning is. Deep learning is a collection of statistical machine learning techniques used to learn feature hierarchies based on the concept of artificial neural networks. So the main idea behind deep learning is to use the concept of neural networks. A deep neural network will have three layers. Okay, there's something known as the input layer, followed by the hidden layers, and then we have the output layer. The input layer is basically the first layer, and it receives all the inputs. So all the inputs are fed into this input layer. The last layer is obviously the output layer. This layer will provide your desired output. Now, all the layers between the input and your output layer are known as the hidden layers. Now, the number of hidden layers in a deep learning network will depend on the type of problem you're trying to solve and the data that you have. We'll get into depth of what exactly a hidden layer does, but for now, this is how a neural network is structured in deep learning. So guys, deep learning is used in highly computational use cases such as face verification, self-driving cars, and so on. Right? So let's understand the importance of deep learning by looking at a real-world use case. So I'm sure all of you have heard of the company PayPal. Now, PayPal makes use of deep learning to identify any possible fraudulent activities. So the company makes use of deep learning for fraud detection. Now, PayPal recently processed over $235 billion in payments from 4 billion transactions by its more than 170 million customers. So basically, it processed this much data by using deep learning. PayPal uses machine learning and deep learning algorithms to mine data from the customer's purchasing history, in addition to reviewing patterns of any sort of fraud stored in the database, and it will do this to predict whether a particular transaction is fraudulent or not. Now, the company has been relying on deep learning and machine learning technology for around 10 years. Initially, the fraud monitoring team used simple linear models, right? They use machine learning. But over the years, the company switched to more advanced machine learning technology called deep learning. This shows how deep learning is used in more advanced and more complicated use cases. The fraud risk manager and the data scientist at PayPal, he quoted that what we enjoy from more modern, advanced machine learning is its ability to consume a lot more data, handle layers and layers of abstraction, and be able to see things that a simpler technology would not be able to see, even human beings might not be able to see. This is exactly what he quoted. He said that a simple linear model is capable of consuming around 20 variables. But with deep learning technology, you can run thousands of data points. He also quoted that there is a magnitude of difference. You will be able to analyze a lot more information and identify patterns that are a lot more sophisticated. So by implementing deep learning technology, PayPal can finally analyze millions of transactions to identify any fraudulent activity. This is how PayPal makes use of deep learning. Not only PayPal, we also have Facebook, right? Facebook makes use of deep learning technology for face verification. You've all seen the tagging feature at Facebook, where we tag our friends in photos. All of that is based on deep learning and machine learning. So guys, that was a real world use case to make you understand how important deep learning is. Now let's move on and look at what exactly a perceptron is, right? We'll be going in depth about deep learning. A perceptron is basically a single layer neural network that is used to classify linear data. It is the most basic component of a neural network. Now, a perceptron has four important components. It has something known as inputs, weights and bias, summation functions, activation and transformation functions. These are four important parts of a perceptron. Now, before I discuss this diagram with you, let me tell you the basic logic behind a perceptron. There is something known as inputs, right? The input x, here you can see x1, x2 till xn. So let me explain the structure of a perceptron. What you're going to do is you're going to input variables into the perceptron, right? This x1, x2 till xn basically stands for input. W1, W2 till Wn stands for the weight assigned to each of these inputs, right? There is a specific weight that will be randomly initialized in the beginning for each of your input. Next, you have something known as the summation element. Here what you do is you multiply the respective input with the respective weight and you add all these products, right? That is basically your summation function. After this is what is your transfer function, also known as activation function, right? The activation function will basically map your input to your desired output. So your input will go through these processes. It will go through summation and activation function in order to get to the output. So guys, remember that the neural networks work the same way as the perceptron. So if you want to understand how deep neural networks work, you need to understand what a perceptron does. A deep neural network is nothing but multiple perceptrons. So let me tell you how the entire thing works once again. So basically all your inputs are multiplied with their respective weights. Now you add all the multiplied values and you call them as a weighted sum. You use the summation function to add all of this. After that, you apply the weighted sum to the correct activation function or the transfer function. Activation function is very similar to a function in our brain. The neurons become active in our brain after a certain potential is reached. That threshold is known as the activation potential. So mathematically, there are a few functions which represent the activation function. Basically, the signum, the sigmoid, the tanh, all of these are activation functions. You can think of activation function as a function that maps the input to the respective output. Then I spoke about something known as weights and biases. All right, now you must be wondering, why do we have to assign weights to each of our input? Weights basically show the strength of a particular input or how important a particular input is for predicting the output. In simple words, the weightage denotes the importance of an input. Bias is basically a value which allows you to shift the activation function curve in order to get a precise output, right? So that's exactly what weights are. I hope all of you are clear with inputs, weights, summation, and activation function. Also, one important thing I forgot to mention in a perceptron is a single layer perceptron will have no hidden layers, right? There'll only be an input layer, an output layer, and a couple of transformation functions in between. That's all will be there in a perceptron. Now, a perceptron, like I mentioned, is used to solve only linear problems. If you look at this data distribution, how do you think we can solve this? This data is not linearly separable. So you cannot use a single layer perceptron to separate this data. Right? That's why we need something known as a multi-layer perceptron with back propagation. I'll be explaining this in the next slide. So complex problems that involve a lot of parameters and high dimensional data can be solved by using multiple layer perceptron. Now a multi-layer perceptron is the same as a single layer perceptron. The only difference is that a multi-layer perceptron will have hidden layers. So the number of hidden layers in a model depends upon various factors. I told you it depends on the complexity of the problem you're trying to solve. It depends on the number of inputs in your data and so on. So it works in the same way. All your inputs are multiplied with your weights and then you do the summation and then there is a transformation function or a activation function. While designing a neural network, in the beginning itself I told you we initialize weights with some random values. We do not have some specific value for each weightage. Initially we've selected random values. It is always important that whatever weight values we have selected will be correct. Now, whatever weight values we've assigned to each input, it denotes the importance of that input variable. So we need to assign the weights in such a way, or we need to update the weights in such a way that it denotes the significance of that particular input. So initially we are selecting some random value for weight. And let's say that we use this weight value to get our output. Now, what happens is the output is actually way different or it is not precise when compared to our actual output. Basically, the error value is very huge. So how will you reduce the error? The main thing in a neural network is the weightage that you give to an input variable, right? Depending on the weightage that you give to an input variable, you're telling the neural network how important that variable is. Now, what if you randomly give some weightage and your output is wrong? The first thing that comes into your mind is that you need to change the weight, because the weight signifies the importance of a variable. So basically what we need to do is we need to somehow explain to the model to change the weight in such a way that the error becomes minimum. Let's put it in another way. So basically we need to train our model. One way to train our model is called as backpropagation. So in backpropagation, what happens is once you've initialized a weight to each of the input, you calculate the output, right? You get an output, and let's say you have a very high error value in that output. What you'll do is you'll backpropagate, as in you'll go back to the weight and you'll keep updating the weight in such a way that your error becomes minimum. This is exactly what backpropagation is. You'll be going back to the first layer, you'll be updating each of the weights in such a way that your output is more precise. So guys, basically the weight and the error in a neural network is highly related. By updating the weight in a particular way, your error will decrease. So you need to figure out how you need to update the weight. Do you have to increase the weight or decrease the weight? Once you figure out whether you have to increase or decrease the weight, you have to just follow that direction in such a way that your error is minimized. That's exactly what backpropagation is. So the final output of backpropagation is you're going to select the weight that minimizes the error function. And then you're going to use that weight to solve the whole problem. Right? This is what backpropagation is about. Now, in order to make you understand deep neural networks, let's look at a practical implementation. So again, guys, I'll be using Python to run the demo. If you don't have a good idea about Python, check the description. I'll leave a couple of links about Python programming. Now, in this demo, I'll be walking you through one of the most important applications of deep learning. I will demonstrate how you can construct a high-performance model to detect credit card fraud. Right? We'll be using deep learning models to do this. Now, before that, let me just tell you something about our data set. Right? The data set contains transactions made by credit cards in the year September 2013 by European cardholders. This data set presents transactions that occurred in 2 days, where we have 492 frauds out of 285,000 transactions, approximately 285,000 transactions. Out of these transactions, 492 were frauds, and the data set is quite unbalanced, right? The positive class accounts for 0.172%. So the positive class, basically the fraudulent class. So again, we're going to start by importing the required packages. We're going to import Keras, Matplot library, Seaborn library, and sklearn for pre-processing. Right? Again, min-max scalar, which is for normalization. We're going to import our data set and store it in this variable. Right? This is the path to my data set. My data set is in the CSV format, or also known as comma separated version. Now we're going to print out the first 5 rows of our data set. Right? Let's take a look at the output. So here is the time of the transaction, V1, V2, V3, etc. These are all the features of our data set. I'm not going to go into depth of what these features stand for, because this demo is all about understanding deep learning. Now these V1, V2, V3, these are all predictor variables which will help us predict our class. So guys, don't worry about what these features are. These features are just information and details about your transaction, such as the amount you spend or the time of transaction and so on. So here we have the amount variable, which denotes the amount spent. After that, we have the class variable. Now this class variable is your output variable or your target variable. So your class is basically your output variable. Value 0 denotes that there has been no fraudulent activity. But if you get a class of 1, it means that this transaction is a fraudulent transaction. For example, this transaction is not fraudulent. That's why we have a value of 0 over here. All right, so this is our data set. Next, what we're doing is we're counting the number of samples for each class, right? We have class 0 and class 1, where in class 0 denotes the normal transaction, which is non-fraudulent transaction, and class 1 will denote the fraudulent transactions, right? So we have around 492 fraudulent transactions and around 284,315 non-fraudulent transactions. So when you see this, you know that our data set is highly unbalanced. Highly unbalanced means that one class has a really small number when compared to the other class, right? There's no balance between the two classes. So here what we're doing is we are sorting the data set by class for stratified sampling. Stratified sampling is a statistical technique for sampling your data set. Now this type of sampling is always good if you have an unbalanced data set. Next, what we're going to do is we're going to perform data pre-processing. Data pre-processing in deep learning mainly has a method known as dropout method. Next, what we're going to do is we're going to drop out the entire time column. We do not need the time of the transaction in order to understand if the transaction was fraudulent or not. Right? So that's why we're getting rid of unnecessary variables. Right? So we're dropping out that variable. So after dropping out the time variable, we are going to assign the first 3000 samples to our new data frame. Right? This DF sample will have our first 3000 samples, and we're going to use those 3000 samples. So here we're just counting the number of class for each of these samples. After that, we're just counting the number of samples for each of the class. Right? We're doing the same thing again, and here we get class 0 has 2508 samples and class 1 has 492 samples. Now this makes the data set quite balanced, right? It's very balanced when compared to our old data set. Next, we'll just randomly shuffle our data set, right, in order to remove any sort of biasness in the data. After that, we'll split our data set into two parts. One is for training and your other data set is for testing, right? This is also known as data splicing. Then we'll be splitting each data frame into feature and label, meaning that your input and your output. You'll be doing this for your training data and for your testing data, right? All you're doing is you're separating your input from your output. Next, we're looking at our training data set, right? We're printing the shape of our training data set. The training data set has around 2400 observations and 29 variables or 29 features. Similarly, we'll be printing out the size of our test data frame, right? That's exactly what we're doing over here. After that, we'll perform normalization. Right, for this, we'll be using the min-max scaler. So in normalization, we'll basically be scaling all our predictor variables around the same range so that there is no biasness in our prediction. After this, we'll be plotting a function for each of the learning curves. For your training phase and for your testing phase, you'll be plotting a learning curve. Now I'll show you the output of this in a couple of minutes. For now, let's move on to the main part, which is model creation. Right, in this demo, we'll use 3 fully connected layers. We'll also use dropout technique. Now, dropout is a type of regularization technique that is used to avoid any sort of overfitting in a neural network. It is a technique where you select neurons and you drop them during the training phase. We'll be using the ReLU as the activation function, which is a type of activation function just like sigmoid and tanh. So the type of model that we'll be using is the sequential model. Right, sequential is the easiest way to build a model in Keras. Right, we're using the Keras library over here. If you remember, I imported that in the beginning. Right, it allows you to build a model layer by layer. So each layer has weights that correspond to the layer that follows it. After this, you'll use the add function to add the dense layers. Basically, your hidden layers you're going to add over here. So in our model, we'll be adding 2 dense layers or hidden layers, you can say. So here what we're doing is we're adding the first dense layer. Now guys, a dense layer is standard layer type that works for most cases. Right? In a dense layer, all the nodes in the previous layer connect to the nodes in the current layer. So guys, don't get too involved into what exactly is happening here. All I'm doing is I'm creating a sequential model. And what is happening is I'm just assigning the number of inputs for each of the dense layer or for each of the hidden layer. I'm also assigning dropout value. Dropout is basically to prevent overfitting. Overfitting might occur when your model memorizes the training data set. Overfitting basically reduces the accuracy of a model. That's why we're using the dropout method to prevent overfitting. So in the first hidden layer, we have around 200 units, right? We have the activation function ReLU. Then we're adding the second dense layer with again 200 neurons and the ReLU activation function. Kernel initializer is uniform, meaning that it's just sequential and normal. Then we're again adding a dropout layer of 0.5. The dropout value of a network has to be chosen very wisely. Okay, a value that is too low will result in a minimal effect, and a value that is too high will result in underlearning by the network. So 0.5 is a standard dropout value. Now this last layer is our output layer. In the output layer, we'll obviously have only one neuron. We'll have one neuron that will show us the output class, either 0 or 1. 0 will show us non-fraudulent transactions and 1 will denote fraudulent transaction. Right? That's why we have only one neuron over here, and the activation function here is sigmoid, right? Since the number of neurons is only 1. After that, we're printing the model summary. Now, I'll show you the summary and everything. Before that, let's just understand what exactly optimization functions are. We'll understand what this optimization function does. Now, an optimizer takes care of the necessary computations that are used to change the network's weights and bias. So basically, your optimizers will take care of all your computations, such as changing the weight or updating the weight. If you'll remember, I spoke about backpropagation, right, where you'll update the weight and all of that. That is done by using optimizers. Here we're selecting an optimizer known as the ADAM optimizer. So ADAM optimizer is one of the current default optimizers in deep learning. Right? It stands for adaptive moment estimation. We don't have to get into the depth of all of this. Right? All of these are predefined optimizers in our Keras package itself. After this, we're going to fit our model by using the training features. We're also setting 200 epochs, and also there's something known as epochs and batch size. Right? We're setting epochs as 200 and batch size as 500. I'll tell you what exactly this means. Now, batch sizes are basically used so that we don't overfit our model, right? We're going to basically split our data set into 500 batches. So our input will be going in the form of batches, right? And our batch size is 500 inputs per batch, and we'll be going through 200 epochs, meaning that our training will iterate 200 times. This is basically the number of times we're training our model. All right, that's what epoch and batch size is. After that, we're just showing our training history, and we're just printing the accuracy curve for our training phase. We're also going to print our loss curves for our training phase, basically the error curves. And then finally, we have the evaluation. Here we'll be testing our model by using our testing dataset. Then we're finally printing the accuracy on our testing dataset. After that, we're just going to plot a heat map, which I'll be showing y'all. Let me just show you the output. So guys, in this entire line of code, all we're doing is we're printing an accuracy plot, right? Basically, we're printing a heat map. I'll show you what the heat map looks like. This is just to check the accuracy. We're comparing all the correctly predicted values to our incorrectly predicted values. So this is our training history. Here, blue stands for our training phase, and this is our validation or our prediction stage. That was our training curve, and this is our loss curve. Now, when you compare it to the actual validation stage, it's quite similar, right? Meaning that our model is doing pretty well. So guys, this is the heat map that I was talking about. This is basically going to give us the class for each of our predictions, right? It basically plots the classes that we correctly predicted, right? Basically, for each data point, it's just going to tell us whether we predicted it correctly or not. It's sort of a confusion matrix in the form of a heat map. So guys, these are all our epochs, basically the 200 iterations that we went through, right? This is the 50th iteration, is showing us our loss, it's showing us our accuracy as well. Right here we have 88%, 90%, 92%. Now, if you carefully look at the epoch accuracy values, you see that as we train our model even more, our accuracy keeps increasing. Initially, our accuracy was around 83, right? At epoch number 15, our accuracy was around 83%. But as we kept training our model a little bit more, our accuracy kept increasing. We have 90, we have 91, 94, 95, 96, and so on. Right? So basically, the more you train your model, the better it's going to be. So guys, this was our entire demo. Now, in the end, I'm printing out the false positive rate and the false negative rate. Right? All of this basically denotes how many of the data points was I correctly able to predict as fraudulent and how many did I predict wrongly. That's all the false negative and the false positive rate denotes. So guys, this was the entire demo on deep learning. Now, if you have any doubts regarding the deep learning demo, please mention them in the comment section and I will solve your queries. Right, now let's look at our last topic for the day, which is natural language processing. Now, before we understand what is natural language processing, let's understand the need for natural language processing and a process known as text mining. Text mining and natural language processing are heavily correlated, right? I'll talk about both of these in the upcoming slides. For now, let me tell you why we need natural language processing or text mining. So guys, the amount of data that we're generating these days is unbelievable. It is a known fact that we are creating 2.5 quintillion bytes of data every day, and this number is only going to grow. With the evolution of communication through social media, we generate tons and tons of data, right? The numbers are on your screen. So basically, we post around 1.7 million pictures on Instagram per minute, right? I'm talking about posts per minute. All of these numbers are per minute values. These are the amount of tweets, 347,000 tweets per minute, right? This is a lot of data. We're generating data while we're watching YouTube videos, when we're sending emails, when we are chatting, and all of that, right? Even the IoT devices at our house, right? We have Alexa. All of this is generating a lot of data. A single click on your phone is generating a lot of data. Now, not only that, out of all the data that we generate, only 21% of the data is structured and well formatted, right? The remaining of the data is unstructured. And the major sources of unstructured data include text messages from WhatsApp, Facebook likes, comments on Instagram, the bulk emails, and all of this, right? All of this accounts for the unstructured data that we have today. Now, the data we generate is used to grow a business. So by analyzing and mining the data, we can add more value to a business. This is exactly what natural language processing and text mining is all about. Text mining and NLP is a subset of artificial intelligence wherein we try and understand the natural language text that we get from text messages and so on in order to derive useful insights and grow businesses by using these insights. So what exactly is text mining? Text mining is a process of deriving meaningful insights or information from natural language text. So all the data that we generate through text messages, emails, and documents are written in natural language text, right? And we're going to use text mining and natural language processing to draw useful insights or patterns from such data in order to grow a business. Now let's understand where exactly do we make use of natural language processing and text mining. Now, have you ever noticed that if you start typing a word on Google, you immediately get suggestions, right? This feature is known as autocomplete. It will basically suggest the rest of the word to you. We also have something known as spam detection, right? Here's an example of how Google recognizes this misspelling Netflix and shows results for the keyword that matches your misspelling. Let me show you a couple of more examples. We also have predictive typing and spell checkers and features like autocorrect, email classification. So predictive typing and spell checkers, all of these are applications of natural language processing. All of this basically involves processing the natural language that we use and deriving some useful information from it, right? Or running businesses from it. Netflix uses natural language processing in a really good fashioned way, right? It basically studies the reviews that customer gives for a particular movie and it tries to figure out if that movie is good or bad depending on the review. So Netflix actually uses NLP in a very interesting manner. It tries to understand the type of movies that a person likes by the way a person has rated the movie or by the way the person has reviewed a movie. So by understanding what type of review a person is giving to a movie, Netflix will recommend more movies that you like. That's how important NLP has become. Now let's look at what exactly NLP is. NLP, which also stands for Natural Language Processing, is a part of computer science and artificial intelligence, which deals with human language. Right? It's basically the process of processing natural language in order to derive some useful information from it. For those of you who have studied natural language processing or have heard of natural language processing, there is a huge confusion between text mining and natural language processing. So text mining is the process of deriving high quality information from text. But the overall goal is to turn the text into data for analysis by using natural language processing. So basically, text mining is implemented by using natural language processing techniques. Right? There are various techniques in natural language processing that can help us perform text mining. That's how text mining and natural language processing are related. Natural language processing is the techniques that are used to solve the problem of text mining, text analysis, and all of that. Let's look at a couple more applications. Sentimental analysis is one of the major applications of natural language processing. You see, Twitter performs sentimental analysis, Facebook, Google, all of these perform sentimental analysis. Sentimental analysis is mainly used to analyze social media content that can help us determine the public opinion on a certain topic. And then we have chatbots. Now, chatbots use natural language processing to convert human language into desirable actions. We also have machine translation. NLP is used in machine translation by studying the morphological analysis of each word and translating it to another language. Advertisement matching is also done using NLP in order to recommend ads based on your history, right? These are few of the applications of NLP. Now, let me tell you the basic terminologies under natural language processing. So, tokenization is the most basic step in natural language processing. Tokenization means breaking down the data into smaller chunks or tokens so that they can be easily analyzed. So the first step is you'll break a complex sentence into words. Then you'll understand the importance of each of the word with respect to that sentence in order to produce a structural description on an input sentence. So for example, take this sentence. How would I perform tokenizations on this sentence? Let's say that tokens are simple is a sentence and I want to perform tokenization on this sentence. This is what I'm going to do. I'm going to split the sentence into different words. I'm going to understand each word with respect to that sentence, right? This is done to simplify operations in natural language processing, right? It's always simpler to analyze a single token instead of analyzing an entire sentence. Then we have something known as stemming. Now look at this example. Right here we have words such as detection, detecting, detected, and detections. We all know that the root word for all of these words is detect. So stemming algorithm basically does that. It works by cutting off the end or the beginning of the word and taking into account a list of common prefixes and suffixes that can be found in an inflected word. Stemming basically helps us in analyzing a lot of words. We know that detections, detected, and detection basically mean the same thing. So all we're doing is we're going to ease our analysis by removing prefixes and suffixes which do not make sense, right? We just need to understand the morphological analysis of the word, right? So that's why we're randomly cutting the prefixes and suffixes in such a way that we only get the important part of the word. This is called stemming. Now, this cutting of words can be successful in some occasions, but not always. That is why we say that stemming approach has a few limitations. In order to get over these limitations, we have a process known as lemmatization, right? Lemmatization, on the other hand, takes into consideration the morphological analysis of the words. It does not randomly cut the word in the beginning and the ending. It understands what the word means and only then it cuts the word. For example, let's consider the word recap. If we perform stemming on the word recap, we'll get cap, right? The output will be cap. But cap and recap do not have the same meaning, do they? They have absolutely different meanings. That's why stemming is sometimes not considered to be the right thing to do. But when it comes to lemmatization, it's going to understand the meaning of recap. Only then will it perform any sort of change in the word or it'll cut down the word. So basically, it groups together different inflected forms of a word called lemma. Lemmatization is similar to stemming because it maps several words into one common root, but the output of a lemmatization process is always a proper word. An example of lemmatization is to map gone, going, and went into go. Gone, going, went, all of them mean go. So basically, by lemmatization, you can just output the words as go. That is what lemmatization is. Next, we have something known as stop words, right? Stop words are basically a set of commonly used words in any language, right? Not just English, any language. The reason why stop words are critical to many applications is that if we remove the words that are very commonly used in a given language, we can finally focus on the important words. For example, in the context of, let's say you open up Google and you look for strawberry milkshake recipe. Instead of typing strawberry milkshake recipe, let's say you type how to make strawberry milkshake. Now here what Google will do is it will find results for how to and make. Instead, if you just type strawberry milkshake recipe, you will get the most desired output. That's why it's always considered a good practice in natural language processing to get rid of stop words, right? Stop words will just increase our computation and it'll just add additional work to us. They are not very helpful when we are analyzing important documents, right? We need to focus on the important keywords in the documents instead of all of these commonly used words. Example of stop words include the, how, when, why, not, yes, no. All of these are stop words, right? So in order to better analyze our data, we need to get rid of stop words. Now, the last terminology I'm going to discuss is document term matrix. Now, it is important to create something known as the document term matrix in natural language processing. A DTM or a document term matrix is basically a matrix that shows the frequency of words in a particular document. Let's say that we're trying to understand if the sentence "this is fun" is available in one of my documents. So if it is there in my document 1, I'm going to put a 1 corresponding to each of the words that is available in my document. For example, in document 2, I have "this is," but I do not have the word "fun." Similarly, in document 4, I have the word "this," but I do not have the word "is" and "fun." So basically, a document term matrix is like the frequency matrix of a document. So during text analysis, you always begin by building a document term matrix. Right here, you try to understand which words frequently occur and which words are important and not important in the document. So guys, these were a couple of terminologies in natural language processing.
So guys, let's see what we are going to explore today. So today we are going to explore real-world examples of machine learning, starting your journey, how you can start your journey to machine learning, and key concepts and impacts of machine learning in your day-to-day life. So guys, to help you navigate through this video, here is a quick rundown for you guys. Table of contents. What is machine learning? How does machine learning works? 5 features of machine learning, types of machine learning, what skills one should have to learn machine learning applications, and last but not the least guys, that is future of machine learning. So guys, I'm going to amaze you with this best example of Google Translator, an AI which converts from one language to the another. I have chosen one language for you guys since many of you watch animes and all. So I'm going to convert from Japanese language to the English language. Buckle up, let's get started. So guys, I'm going to write a word in Japanese, that is Ohayo gozaimasu. If you know what Ohayo gozaimasu means, then please comment down below. So I'm going to convert Ohayo gozaimasu from Japanese to English. So let's copy this and paste this in here. So Ohayo gozaimasu in Japanese, but in English it means good morning. A Google translator works on a neural network, and a neural network is a machine learning algorithm which learns from Japanese language, keeps on improving itself, and gives you the optimal output, that is good morning in English. This is how a language translator works. Let's see one more example. If I write here one more thing, that is Hajime Mashite. Hajime Mashite in Japanese, if you know, then please comment down below. Let me see what does it mean. So Hajime Mashite in Japanese, but in English it means nice to meet you. Here also the same. The neural network is learning from Japanese language and showing you what does it mean in English language. So let me properly explain you what it actually does. So guys, a translator is nothing but it's an AI machine that converts from one language to the another using a machine learning algorithm called neural network. Now what neural network does is it learns from one language, makes some mistake or errors, then keeps on improving itself so that it can convert to another language, such as from Japanese to English or from English to Japanese. So guys, the translator which you are using works on neural networks, and this is how a translation works. So guys, you must be thinking, then what is machine learning? So moving on to what is machine learning, we have a machine learning is nothing but a training from historical data or experiences, or in layman terms you can say learning from data to predict future or required output is called machine learning. Guys, a simple machine learning algorithm works in a way that you have a data of any kind and you give it to a machine. Now what does machine does is it learns from it in different ways using some different algorithms and gives you the required amount of future or predicts the required amount of output you wanted. Now guys, you must have understood what is machine learning. Let's deep dive a bit. Let's see what are the features of machine learning. We have 5 features of machine learning, that is predictive modeling, automation, scalability, generalization and adaptiveness. These are the 5 main features of any machine learning. So guys, tighten your seatbelts. Let's move to these one by one. Predictive model. In the predictive model, what it does, it uses some mathematical functions and statistical techniques on the historical data and gives you the future predictions. The best example I can give you guys is the stock market prediction app, where it uses some graphs, straight line graphs and charts to show you the prediction based on the historical data using some statistical and mathematical functions. This is how a predictive model works. Moving on to our next topic, that is automation. Automation is one of the best features to save money. You know why? Because the companies which are having the less domains and cannot hire the employees, they can automate different machines to do the same work as the employee does. Such as if you want a developer but you don't have the cost to pay, then you can automate a machine that can develop for you. This is the best example I can give you for the automation feature. So guys, moving on to our next feature, that is scalability. Scalability has its own importance because a machine learning algorithm, if it is not scalable, then it cannot handle larger amount of data sets or bigger data sets. I can give you the best example, that is Amazon. So guys, here I am at the Amazon website and you can see a lot of product, and not only you can see but whole world can see who are using Amazon app. Now this system is a scalable system. No matter how many customers are here and they are buying, the system will never crash. It can handle that amount of larger data sets. So this is the best example of a scalable system. So guys, moving on to our next feature, that is generalization. In generalization, what it does is it's the ability of the model to generalize things, to forecast new data. Suppose your model is trained on a data set and you are going to test it on some another data set which is not there in the training, but still your model is giving 95% of accuracy. Means your model is generalizing, your model is summarizing and giving you the best and optimal result. Now guys, moving on to our last feature, that is adaptiveness. You can take it as a survival of the fittest thing, because if your model is not surviving the real-time environments or the new problems, then your model is not adaptive or good. It will going to extend. Suppose there is a model which is built on traditional model and still giving you best and advanced solutions on the real-time problems, then your model is adaptive and is the optimal model you can have. So guys, clear your mind because we are going to go in the types of machine learning. There are 4 different types of machine learning. First we have is supervised or guided machine learning. In the supervised or guided machine learning, what it does is if there is a data set and having some values and you are labeling it as a specifying the value to the machine, then it will recognize those data through the labels and giving you the optimal classification. For example, if you have the pictures of cats and dogs, and you have to classify it, then you will label it as cats and dogs, then your machine will recognize those labels and classify and give you the optimal result. So in supervised learning, what we have is a supervised algorithm. We have some labels and we are putting those labels to a data set, and after this the machine easily recognizes and giving you the optimal results. So guys, moving on to our next type, that is unsupervised or unguided learning. In unsupervised or unguided learning, what machine does is you are giving the data which is not labeled, and after few trainings and making some errors, the machine easily recognizes it. So what we have is an unsupervised algorithm. We have some unlabeled data, and in those unlabeled data, your machine is trying to find patterns. After few errors, it will give you the optimal results. Moving on to our next type, that is semi-supervised learning. In semi-supervised learning, the algorithm uses both unsupervised and supervised in combined form, giving you the optimal result. For example, we have a semi-supervised algorithm and we are trying to find out patterns from the data sets which are both labeled and unlabeled. So this is how a semi-supervised learning works. Moving on to our last type, that is reinforcement learning. The reinforcement learning you can understand in a way like when you are playing a game, you make some mistake, then learn from them, then again make some mistake in a level, learn from them and reach your goal. This is how reinforcement learning works in a software. The software is being trained multiple times, making some errors and learning from them and giving you the optimal results. This is the best example I can give you for the reinforcement learning, that is the gaming system. So guys, what we have is a reinforcement algorithm and an environment. We are taking some actions in that environment, making some errors and getting some results, then again making some errors and getting some results. This is how a reinforcement model works in a machine learning. So guys, moving on to the examples of machine learning, we have a voice recognition system and an image recognition system. These both you are using in your phone, in your laptop every day, and machine learning is being used. Now guys, you have learned so much. Now you must be thinking that how should I start my journey? What skills I should have? So these are the skills required to learn machine learning, that is SQL, structured query language, JavaScript, C++ are programming for those who are moving with machine learning to the data scientist, and Python, one of the best programming language for the machine learning. And last but not the least, if you are moving a bit deep down in the machine learning towards the deep learning, then you need NLP or natural language processing. These skills are required for the one who want to learn machine learning. So guys, moving on to the real life examples of machine learning I have, that is Google searches. Google searches uses your history, track it down, then giving you the prediction based on your histories. For example, let me show you. So guys, I came here at Google. Now I'm going to type Amazon and it's giving me that results which are already there in my history. I must have searched before a month ago, 2 months ago, then 4 months ago, and all that history combined form is being predicted in here. Now Amazon Prime is there, Amazon videos are there. So this is how a predictive model is working behind this Google searches. Moving on to our next real life example guys, that is Instagram. You swipe Instagram every day, every night. So all that is based on your past data only. If you are seeing some videos of cats, then further swipes will be the cats only. So this is how your history is being tracked down and watched by the Instagram machine learning algorithms and giving you the results of the same. So this is how a real feeder in Instagram works. Moving on to our next example, that is movie recommendation system on any movie watching website such as Netflix or anime websites such as Watch Anime, Anycon, etc. So guys, if I take you to AnyWatch and show you the anime recommendation, trending ones are based on the people's choices they are watching more based on your histories only. If I watch any of these animes and I watch them regularly, then the recommendations will show me the same. So this is how a recommendation system works in AnyWatch, or you can say in Netflix, based on your choices in past datas. So guys, moving on to the future of machine learning, it will be using everywhere. The advanced techniques in medical field, architecture field, electrical field, and yes, in the computer science field. Machine learning will be everywhere. It will be revolutionizing the world.
Now let's explore different types of ML models. So not all data is structured the same way, and different problems require different approaches. So for example, predicting stock prices requires the models that learn from historical trends. And then identifying objects in images needs models that recognize patterns in visual data. Next, the chatbots and voice assistants rely on the models trained to understand and generate human language. So to tackle these challenges, as I discussed previously, that ML is divided into different learning models, such as supervised, unsupervised, and reinforcement learning. And each has its own strengths and it is used depending on the problem at hand. Since we know why different ML models are needed, let's see how they play a crucial role in generative AI. Well, generative AI is one of the most exciting applications of machine learning. And unlike traditional ML models that make predictions or classifications, generative models create entirely new content. And here's how ML enables AI to generate. So first here we have text. Language models like GPT generate human-like text for chatbots, content writing, and coding. Next is the image. So AI-powered tools like DALL-E can create realistic images from textual descriptions. Next is videos. So advanced ML models synthesize lifelike video content, transforming media, marketing, and even filmmaking. So these advancements in generative AI are reshaping creativity and automation, proving that machine learning is not just about making decisions, it's about creating new possibilities. So now that we have seen how ML models enable AI to create new content, so now let us briefly understand the different types of machine learning models. So here, the first type of machine learning model is supervised learning. Supervised learning trains a model using labeled data, where each input has a corresponding correct output. And this makes it ideal for tasks where historical data can be used to predict future outcomes. For example, let's say spam detection. Email services like Gmail uses supervised learning to classify emails as spam or not spam by learning from past labeled examples. The next example is the price predictions. So real estate platforms use regression models to predict house prices based on the features like location, size, and amenities. Now, let us see some of the popular algorithms. So first, let's discuss on decision trees. These models break down the data into a tree-like structure, where each node represents a decision based on a feature. So they are easy to interpret and work well for both classification. For example, deciding if an email is a spam or not, and regression example predicting house price. However, they can become overly complex. Next is the support vector machines. So SVMs are powerful for classification tasks as they find the optimal boundary, also called a hyperplane, and that best separates different classes in the data. They work well for high-dimensional spaces and cases where the distinction between categories is clear, such as handwriting, facial recognition, or medical diagnosis. So now that we have seen how labeled data is used, so now let's explore how unsupervised learning finds patterns without labels. Well, unsupervised learning works with unlabeled data, identifying hidden patterns and relationships without predefined categories. So here we have some of the popular algorithms. So first is the K-means clustering. This algorithm partitions data into a predefined number of clusters by grouping similar data points based on their attributes. It works well for tasks like customer segmentation, where businesses can group customers based on purchasing behavior. However, it assumes clusters are spherical and may struggle with irregular shaped data. Next, we have autoencoders. So these are specialized neural networks designed to learn efficient data representations by encoding and reconstructing input data. Let us see some of the examples. So first example here we have is customer segmentation, where e-commerce platforms group customers based on their shopping behavior to offer personalized recommendations. The next example is market analysis. Businesses analyze purchasing trends to find association, such as which products are frequently brought together. Now we have covered both labeled and unlabeled learning. So let's see how semi-supervised learning combines the best of both worlds. So, semi-supervised learning bridges the gap between the supervised and unsupervised learning by using a small amount of labeled data along with large amount of unlabeled data. So for example, let's say AI assistant medical diagnosis. Labeled medical images such as X-rays with diagnosis are scarce, but large amounts of unlabeled images exist. Semi-supervised learning helps AI learn patterns from both labeled and unlabeled data, improving accuracy in disease detection. Alright, now let's explore the reinforcement learning, where AI learns through trial and error. Well, reinforcement learning is inspired by the concept of learning through trial and error. So models interact with an environment, receive rewards or penalties for actions, and refine their strengths over time. For example, let's say gaming. Mario AI, developed using reinforcement learning, learns to navigate levels by optimizing actions through trial and error. The next example is robotics, where robots learn to walk, balance, or perform tasks through reinforcement learning by maximizing positive outcomes. Also, reinforcement learning uses agents, actions, and rewards to improve decision making, making it ideal for tasks requiring continuous learning and adaptation. So now that we have covered all the types of machine learning models, so let's go over some of the key tips to help you choose the right one for your needs. So here are the tips. When it comes to supervised learning, classifying emails as spam or not, and diagnosing diseases from patient data. Next is the unsupervised learning, So unsupervised learning is best when you're grouping shoppers by behavior and detecting fraud in banking. Next, we have semi-supervised learning. And this is best when you're improving speech recognition with limited labeled data and identifying fake news. And finally, the reinforcement learning. This will be best when you're training self-driving cars to navigate, optimizing AI in video games like Mario. So whether it's supervised, unsupervised, semi-supervised, or reinforcement learning, each model plays a crucial role in shaping AI's future. So as generative AI continues to evolve, these models are driving innovation in text, images, and video generation. So which machine learning model do you find the most fascinating? Let me know in the comments below.
Let me connect you to the real life and tell you what all are the things which you can easily do using the concepts of machine learning. So you can easily get answer to the questions like which types of house lies in this segment, or what is the market value of this house, or is this a mail, a spam, or not a spam? Is there any fraud? Well, these were some of the questions you could ask to the machine. But for getting an answer to these, you need some algorithm. The machine need to train on the basis of some algorithm. Okay, but how will you decide which algorithm to choose and when? Okay, so the best option for us is to explore them one by one. So the first is classification algorithm, where the category is predicted using the data. If you have some question like, is this person a male or a female? Or is this male a spam or not a spam? Then these category of question would fall under the classification algorithm. Classification is a supervised learning approach in which the computer program learns from the input given to it and then uses this learning to classify new observation. Some examples of classification problems are speech recognition, handwriting recognition, biometric identification, document classification, etc. Shall we move ahead? Okay. So next is the anomaly detection algorithm, where you identify the unusual data point. So what is anomaly detection? Well, it's a technique that is used to identify unusual patterns that do not conform to expected behavior, or you can say the outliers. It has many applications in business, like intrusion detection, like identifying strange patterns in the network traffic that could signal a hack, or system health monitoring, that is spotting a deadly tumor in the MRI scan. Or you can even use it for fraud detection, credit card transaction, or to deal with fault detection in operating environment. So next comes the clustering algorithm. You can use this clustering algorithm to group the data based on some similar condition. Now you can get answer to which type of houses lies in this segment or what type of customer buys this product. The clustering is the task of dividing the population or data points into a number of groups such that the data point in the same groups are more similar to other data points in the same group than those in the other groups. In simple words, the aim is to segregate groups with similar trait and assign them into cluster. Now this clustering is a task of dividing the population or data points into a number of groups such that the data points in the X group is more similar to the other data points in the same group rather than those in the other group. In other words, the aim is to segregate the groups with similar traits and assign them into different clusters. Let's understand this with an example. Suppose you're the head of a rental store and you wish to understand the preference of your customer to scale up your business. So is it possible for you to look at the detail of each customer and design a unique business strategy for each of them? Definitely not, right? But what you can do is to cluster all your customer, say into 10 different groups based on their purchasing habit, and you can use a separate strategy for customers in each of these 10 different groups. And this is what we call clustering. Next, we have regression algorithm, where the data itself is predicted. Question you may ask to this type of model is like, what is the market value of this house? Or is it going to rain tomorrow or not? So regression is one of the most important and broadly used machine learning and statistics tool. It allows you to make prediction from data by learning the relationship between the features of your data and some observed continuous valued response. Regression is used in a massive number of applications. You know what? Stock prices prediction can be done using regression. Now you know about different machine learning algorithm. How will you decide which algorithm to choose and when? So let's cover this part using a demo. So in this demo part, what we'll do, we'll create 6 different machine learning model and pick the best model and build the confidence such that it has the most reliable accuracy. So for our demo part, we'll be using the IRIS dataset. This dataset is quite very famous and is considered one of the best small project to start with. You can consider this as a hello world dataset for machine learning. So this data set consists of 150 observation of iris flower. There are 4 columns of measurement of flowers in centimeters, the 5th column being the species of the flower observed. All the observed flowers belong to one of the 3 species of Iris setosa, Iris virginica, and Iris versicolor. Well, this is a good project because it is so well to understand. The attributes are numeric, so you have to figure out how to load and handle the data. It is a classification problem, thereby allowing you to practice with perhaps an easier type of supervised learning algorithm. It has only 4 attributes and 150 rows, meaning it is very small and can easily fit into the memory. And even all of the numeric attributes are in the same unit and the same scale. It means you do not require any special scaling or transformation to get started with. So let's start coding, and as I told earlier, for the demo part, I'll be using Anaconda with Python 3.0 installed on it. So when you install Anaconda, how your navigator would look like. So this is my homepage of my Anaconda navigator. On this, I'll be using the Jupyter Notebook, which is a web-based interactive computing notebook environment, which will help me to write and execute my Python codes on it. So let's hit the launch button and execute our Jupyter Notebook. So as you can see that my Jupyter Notebook is starting on localhost 8890. Okay, so this is my Jupyter Notebook. What I'll do here, I'll select new notebook Python 3. This is my environment where I can write and execute all my Python codes on it. So let's start by checking the version of the libraries. In order to make this video short and more interactive and more informative, I've already written the set of code. So let me just copy and paste it down. I'll explain you then one by one. So let's start by checking the version of the Python libraries. Okay, so there's the code. Let's just copy it, and let's paste it. Okay, first let me summarize things for you. What we are doing here, we are just checking the version of the different libraries. Starting with Python, we'll first check what version of Python we are working on. Then we'll check what are the version of SciPy we are using. Then NumPy, Matplotlib, then Panda, then scikit-learn. Okay, so let's execute the run button and see what are the various versions of the libraries which we are using. Hit the run. So we are working on Python 3.6.4, SciPy 1.0, NumPy 1.14, Matplotlib 2.12, Pandas 0.22, and scikit-learn of version 0.19. Okay, so these are the version which I'm using. Ideally, your version should be more recent or it should match. But don't worry if you lag few versions behind, as the APIs do not change so quickly. Everything in this tutorial will very likely still work for you. Okay, but in case you are getting an error, stop and try to fix that error. In case you are unable to find the solution for the error, feel free to reach out Edureka even after this class. Let me tell you this, if you're not able to run the script properly, you will not be able to complete this tutorial. Okay, so whenever you get a doubt, reach out to Edureka and just resolve it. Now if everything is working smoothly, then now it's the time to load the dataset. So as I said, I'll be using the iris flower dataset for this tutorial. But before loading the dataset, let's import all the modules, function, and the object which we are going to use in this tutorial. Same, I've already written the set of code, so let's just copy and paste them. Let's load all the libraries. So these are the various libraries which we'll be using in our tutorial. So everything should work fine without an error. If you get an error, just stop. You need to work on your SciPy environment before you continue any further. So I guess everything should work fine. Let's hit the run button and see. Okay, it worked. So let's now move ahead and load the data. We can load the data direct from the UCI machine learning repository. First of all, let me tell you, we are using Panda to load the data. Okay, so let's say my URL is this. So this is my URL for the UCI machine learning repository from where I'll be downloading the data set. Okay. Now what I'll do, I'll specify the name of each column when loading the data. This will help me later to explore the data. Okay. So I'll just copy and paste it down. Okay. So I'm defining a variable names which consist of various parameters including sepal length, sepal width, petal width, and class. So these are just the name of column from the data set. Okay. Now let's define the data set. So dataset equals panda.read_csv. Inside that, we are defining URL and the names that is equal to name. As I already said, we'll be using Panda to load the data. All right. So we are using panda.read_csv. So we are reading the CSV file, and inside that, from where that CSV is coming, from the URL. Which URL? So this is my URL. Okay. Our names equal names. It's just specifying the names of that various columns in that particular CSV file. Okay. So let's move forward and execute it. So even our data set is loaded. In case you have some network issues, just go ahead and download the iris data file into your working directory and load it using the same method. But yeah, make sure that you change the URL to the local name or else you might get an error. Okay. Yeah, our data set is loaded. So let's move ahead and check our data set. Let's see how many columns or rows we have in our data set. Okay, so let's print the number of rows and columns in our data set. So our data set is dataset.shape. What this will do, it will just give you the numbers of total number of rows and total number of column, or you can say the total number of instances or attributes in your data set. Fine. So print dataset.shape. What you are getting? 150 and 5. So 150 is the total number of rows in your data set and 5 is the total number of columns. Fine. So moving on ahead, what if I want to see the sample data set? Okay, so let me just print the first 30 instances of the data set. Okay, so print dataset.head. What I want is the first 30 instances. Fine. This will give me the first 30 result of my data set. Okay, so when I hit the run button, what I'm getting is the first 30 result. Okay, 0 to 29. So this is how my sample data set looks like. Sepal length, sepal width, petal length, petal width, and the class. Okay, so this is how our data set looks like. Now let's move on and look at the summary of each attribute. What if I want to find out the count, mean, the minimum and the maximum values and some other percentiles as well? So what should I do then? For that, print dataset.describe. What it will give, let's see. So you can see that all the numbers are the same scales of similar range between 0 to 8 centimeters, right? The mean value, the standard deviation, the minimum value, the 25 percentile, 50 percentile, 75 percentile, the maximum value, all these values lies in the range between 0 to 8 centimeter. Okay. So what we just did is we just took a summary of each attribute. Now let's look at the number of instances that belong to each class. So for that, what we'll do, print dataset first of all. So let's print dataset and I want to group it, group by using class, and I want the size of it, size of each class. Fine. And let's hit the run. Okay, so what I want to do, I want to print what? Data set. How I want to get it? I want it by class. So group by class. Okay, now I want the size of each class. Find the size of each class. So group by class dot size. Execute the run. So you can see that I have 50 instances of Iris setosa, 50 instances of Iris versicolor, and 50 instances of Iris virginica. Okay, all are of data type integer of base 64. Fine. So now we have a basic idea of our data. Now let's move ahead and create some visualization for it. So for this, we are going to create two different types of plot. First would be the univariate plot and the next would be the multivariate plot. So we'll be creating univariate plots to better understand about each attribute. And the next we'll be creating the multivariate plot to better understand the relationship between different attributes. Okay, so we start with some univariate plot. That is plot of each individual variable. So given that the input variables are numeric, we can create box and whiskers plot for it. Okay, so let's move ahead and create a box and whiskers plot. So dataset.plot, what kind I want? It's a box. Okay, and do I need a subplot? Yeah, I need subplots for that. So subplots equal true. What type of layout do I want? So my layout structure is 2 cross 2. Next, do I want to share my coordinates, x and y coordinates? No, I don't want to share it. So share x equal false. And even share y, that too equals false. Okay, so we have here dataset.plot kind equal box. My subplots is true, layout 2 cross 2. And then what I want to do it, I want to see it. So plot dot show, whatever I created, show it. Okay, execute it. Now this gives us a much clearer idea about the distribution of the input attribute. Now what if I had given the layout to 2 cross 2? Instead of that, I would have given it 4 cross 4. So what it will result? Just see. Fine. Everything would be printed in just one single row. Hold on guys, Arya has a doubt. He's asking that why we are using the share x and share y values. What are these? Why we have assigned false values to it? Okay Arya, so in order to resolve this query, I need to show you what will happen if I give true values to them. Okay, so be with me. So share x equal true and share y that equals true. So let's see what result we'll get. You're getting it. The x and y coordinates are just shared among all the 4 visualization, right? So Arya, you can see that the sepal length and sepal width has y values ranging from 0.0 to 7.5, which are being shared among both the visualization. So is with the petal length, it has a shared value between 0.0 to 7.5. Okay, so that is why I don't want to share the value of x and y. So it's just giving us a cluttered visualization. So Arya, why I'm doing this? I'm just doing it because I don't want my x and y coordinates to be shared among any visualization. Okay, that is why my share x and share y value are false. Okay, let's execute it. So this is a pretty much clear visualization which gives a clear idea about the distribution of the input attributes. Now if you want, you can also create a histogram of each input variable to get a clear idea of the distribution. So let's create a histogram for it. So dataset.hist. Okay, I would need to see it. So plot.show. Let's see. So there's my histogram, and it seems that we have two input variables that have a Gaussian distribution. So this is useful to note as we can use the algorithms that can exploit this assumption. Okay, so next comes the multivariate plot. Now that we have created the univariate plot to understand about each attribute, let's move on and look at the multivariate plot and see the interaction between the different variables. So first, let's look at the scatter plot of all the attribute. This can be helpful to spot structured relationship between input variables. Okay, so let's create a scatter matrix. So for creating a scatter plot, we need scatter matrix, and we need to pass our data set into it. Okay, and then what I want to see it. So plot.show. So this is how my scatter matrix looks like. It's like that the diagonal grouping of some pair, right? So this suggests a high correlation and a predictable relationship. All right, this was our multivariate plot. Now let's move on and evaluate some algorithm. Now it's time to create some model of the data and estimate their accuracy on the basis of unseen data. Okay, so now we know all about our data set, right? We know how many instances and attributes are there in our data set. We know the summary of each attribute. Now I guess we have seen much about our data set. Now let's move on and create some algorithm and estimate their accuracy based on the unseen data. Okay, now what we'll do, we'll create some model of the data and estimate their accuracy based on some unseen data. Okay, so for that, first of all, let's create a validation data set. What is a validation data set? Validation data set is your training data set that will be using it to train our model. Fine. All right. So how we'll create a validation data set? For creating a validation data set, what we are going to do is we are going to split our data set into two parts. Okay. So the very first thing we'll do is to create a validation data set. So why do we even need a validation data set? So we need a validation data set to know that the model we created is any good. Later, what we'll do, we'll use the statistical method to estimate the accuracy of the model that we create on the unseen data. We also want a more concrete estimate of the accuracy of the best model on unseen data by evaluating it on the actual unseen data. Okay, confused? Let me simplify this for you. What we'll do, we'll split the loaded data into two parts. The first 80% of the data, we'll use it to train our model, and the rest 20% will hold back as the validation data set that will use it to verify our trained model. Okay, fine. So let's define an array. This is my array. What it will consist of? It will consist of all the values from the dataset. So dataset dot values. Okay. Next, I'll define a variable x, which will consist of all the column from the array from 0 to 4, starting from 0 to 4. And the next variable y, which would consist of the array starting from this. So first of all, we'll define a variable x that will consist of the values in the array starting from the beginning 0 till 4. Okay, so these are the column which will be included in the x variable. And for a y variable, I'll define it as a class or the output. So what I just need the fourth column, that is my class column. So I'll start it from the beginning and I just want the fourth column. Okay, now I'll define my validation size, validation underscore size. I'll define it as 0.20 and I'll use a seed. I'll define seed equals 6. So this method seed sets the integer starting value used in generating random number. Okay, I'll define the value of seed equals 6. I'll tell you what is the importance of it later on. Okay, so let me define first few variables such as x underscore train test, y underscore train, and y underscore test. Okay, so what we want to do is select some model. Okay, so model underscore selection. But before doing that, what we have to do is split our training data set into two halves. Okay, so dot train underscore test underscore split. What we want to split is the value of x and y. Okay, and my test size is equals to validation size, which is a 0.20. Correct. And my random state is equal to seed. So what the seed is doing here, it's helping me to keep the same randomness in the training and testing data set. Fine. So let's execute it and see what is our result. It's executed. Next, we'll create a test harness. For this, we'll use 10-fold cross-validation to estimate the accuracy. So what it will do, it will split our data set into 10 parts. Train on the 9 part and test on the 1 part. And this will repeat for all combination of train and test splits. Okay. So for that, Let's define again. My seed that was 6 already defined, and scoring equals accuracy. Fine. So we are using the metric of accuracy to evaluate the model. So what is this? This is a ratio of number of correctly predicted instances divided by the total number of instances in the data set multiplied by 100, giving a percentage. Example, it's 98% accurate or 99% accurate, things like that. Okay. So we'll be using this scoring variable when we run the build and evaluate each model in the next step. So our next part is building model. Till now, we don't know which algorithm would be good for this problem or what configuration to use. So let's begin with 6 different algorithms. I'll be using logistic regression, linear discriminant analysis, k nearest neighbor, classification and regression trees, naive Bayes, and code vector machine. Well, these algorithms which I'm using is a good mixture of simple linear or non-linear algorithms. In simple linears, which included the logistic regression and the linear discriminant analysis, or the non-linear part, which included the KNN algorithm, the CART algorithm, the naive Bayes, and the support vector machines. Okay, so we reset the random number seed before each run to ensure that evaluation of each algorithm is performed using exactly the same data splits. It ensures the results are directly comparable. Okay, so let me just copy and paste it. Okay. So what we are doing here, we are building 5 different types of model. We are building logistic regression, linear discriminant analysis, k nearest neighbor, decision tree, Gaussian naive Bayes, and the support vector machine. Okay. Next, what we'll do, we'll evaluate model in each turn. Okay. So what is this? So we have 6 different model and accuracy estimation for each one of them. Now we need to compare the model to each other and select the most accurate of them all. So running this script, we saw the following result. So we can see some of the result on the screen. What is this? It is just the accuracy score using different set of algorithms. Okay, when we are using logistic regression, what is the accuracy rate? When we are using linear discriminant algorithm, what is the accuracy, and so and so. Okay, so from the output, it seems that LDA algorithm was the most accurate model that we tested. Now we want to get an idea of the accuracy of the model on our validation set or the testing data set. So this will give us an independent final check on the accuracy of the best model. It is always valuable to keep a testing data set for just in case you made a overfitting to the testing data set or you made a data leak. Both will result in an overly optimistic result. Okay. You can run the LDA model directly on the validation set and summarize the result as a final score, a confusion matrix, and a classification report.
Let us understand what regression in machine learning is. So what exactly is regression? The main goal of regression is the construction of an efficient model to predict the dependent attributes from a bunch of attribute variables. A regression problem is where the output variable is either real or a continuous value like salary, weight, area, etc. We can also define regression as a statistical means that is used in applications like housing, investing, etc. to predict the relationship between a dependent variable and a bunch of independent variables. For example, let's say in the finance application or investing, we can actually predict the values of certain stock prices or those values depending on the independent variables like how many years it takes for a stock to actually mature, or how many days will it take to grow, or those variables that you have in investing. And depending upon that, we can make a possible outcome or a possible prediction of how our stock is going to be invested in a profit state or a loss state, or all those things. Or we can take another example like housing. We can take different parameters like number of years it's been there, how many people have used it, or what is the area of the house. Depending on all these factors, or how many rooms does a house have, we can predict the price of a house. So this is basically what regression really is. So let us take a look at the various types of regression techniques that we have. We have simple linear regression, then we have polynomial regression, support vector regression, decision tree regression. We have random forest regression, and we have logistic regression as well. That is also a type of regression that we have. But for now, we'll be focusing on simple linear regression. So let's talk about how or what exactly is simple linear regression first. So one of the most interesting and common regression technique is simple linear regression. In this, we predict the outcome of a dependent variable y based on the independent variables x. So the relationship between the variables is linear, hence the word linear regression. Then comes the polynomial regression. So in this regression technique, we transform the original features into a polynomial feature of a given degree and then perform regression on it. So this is basically polynomial regression. After this, we have support vector machine regression, or we can also call it SVR. We identify a hyperplane with maximum margin such that the maximum number of data points are within those margins. It is also quite similar to the support vector machine classification algorithm. Then we have decision tree regression. A decision tree can be used for both regression and classification, but in this case of regression, we use the ID3 algorithm, which is iterative dichotomizer 3, to identify the splitting node by reducing the standard deviation. After this, we have a random forest regression, which is basically an ensemble of predictions of several decision tree regressions. So this is all about the types of regressions. For now, we are going to focus on simple linear regression. So let's take a look at what exactly is a simple linear regression. Simple linear regression is a regression technique in which the independent variable has a linear relationship with the dependent variable. The straight line in the diagram is the best fit line, and the main goal of the simple linear regression is to consider the given data points and plot the best fit line to fit the model in the best way possible. So if we talk about a real life analogy to explain linear regression, we can take an example of a car resale value. So we have different parameters, when we are talking about a resale value of a car, like how many years the car has been there in the market and how many kilometers it has been ridden, the kind of mileage the car gives, and then we have different parameters we can focus upon, and all these independent variables somehow are linearly connected or interconnected to the price of the car. So that is one example to understand linear regression. We'll be doing that in the use case. I'll be telling you about how you can predict the price of car. Now, talking about linear regression terminologies, there are a few terminologies you have to be thorough with to begin with linear regression. So first of all, we have to talk about cost function. So the best fit line can be based on the linear equation that is given here. So in this, the dependent variable that is to be predicted is denoted by y. A line that touches the y-axis is denoted by the intercept b0. The b1 is the slope of the line, and x represents the independent variables that determine the prediction of y. The error in the resultant prediction is denoted by e. Now talking about cost function, the cost function provides the best possible values for b0 and b1 to make the best fit line for the data points. We do this by converting this problem into a minimization problem to get the best values for b0 and b1. So with this, the error is minimized in this problem between the actual value and the predicted value, and we choose the function above to minimize. Now we square the error difference and sum the error over all the data points. The division between the total number of data points and the produced value provides the average square error for all the data points. It is also known as mean squared error, and we can change the values of b0 and b1 so that the MSE or the mean squared error value is settled at the minimum. So this is one terminology, that is cost function, that we use in linear regression. Then we have the gradient descent. So the next important terminology to understand linear regression is gradient descent, of course, and it is a method of updating b0 and b1 value to reduce the MSE, which is the mean squared error. The idea behind this is to keep iterating the b0 and b1 values until we reduce the MSE to the minimum. Now to update b0 and b1, we take the gradients from the cost function, and to find these gradients, we take partial derivatives with respect to b0 and b1. And these partial derivatives are the gradients and are used to update the values of b0 and b1. I'm sure guys this might be a little confusing for you guys if you are new to this, like gradient descent and cost function, but you don't have to worry about this, because in Python when we're using a linear regression, we're going to be using the sklearn or the scikit-learn library, so you don't have to worry about this. You just have to integrate your model with the linear regression module that we have already over there, and you will be done with it. And when I'm implementing the linear regression model, you'll see how easy it is to actually implement linear regression in Python. So after this, let's talk about a few advantages and disadvantages of linear regression. So talking about the advantages first, linear regression performs exceptionally well for linearly separable data. And it is actually very easy to implement, interpret, and very efficient to train as well. And even though the linear regression is prone to overfitting, it handles it pretty well using dimensional reduction techniques, regularization, and cross-validation. And one more advantage is that the extrapolation beyond a specific data set. So these are all the advantages that we have with linear regression. Let's talk about a few disadvantages as well. So one of the most common disadvantage with linear regression is that it takes the assumption of linearity between dependent and independent variables. The next disadvantage is it is often very prone to noise and overfitting as well, which is not a very good sign for any model if you are doing regression or classification in machine learning. The next disadvantage is it is very quite sensitive to outliers as well. And the last one is that it is very prone to multicollinearity. So these are all the advantages and disadvantages of linear regression.
So let's understand the what and why of logistic regression. Now this algorithm is most widely used when the dependent variable, or you can say the output, is in the binary format. So here you need to predict the outcome of a categorical dependent variable. So the outcome should be always discrete or categorical in nature. Now by discrete, I mean the value should be binary, or you can say you just have two values. It can either be 0 or 1. It can either be yes or a no, either be true or false, or high or low. So only these can be the outcomes. So the value which you need to predict should be discrete, or you can say categorical in nature. Whereas in linear regression, we have the value of y, or you can say the value you need to predict is in a range. So that is how there is a difference between linear regression and logistic regression. Now you must be having a question, why not linear regression? Now guys, in linear regression, the value of y, or the value which you need to predict, is in a range. But in our case, as in the logistic regression, we just have two values. It can be either 0 or it can be 1. It should not entertain the values which is below 0 or above 1. But in linear regression, we have the value of y in the range. So here, in order to implement logistic regression, we need to clip this part. So we don't need the value that is below 0, or we don't need the value which is above 1. So since our value of y will be between only 0 and 1, that is the main rule of logistic regression, the linear line has to be clipped at 0 and 1. Now once we clip this graph, it would look somewhat like this. So here you are getting a curve which is nothing but three different straight lines. So here we need to make a new way to solve this problem. So this has to be formulated into an equation, and hence we come up with logistic regression. So here the outcome is either 0 or 1, which is the main rule of logistic regression. So with this, our resulting curve cannot be formulated. So hence our main aim to bring the values to 0 and 1 is fulfilled. So that is how we came up with logistic regression. Now here, once it gets formulated into an equation, it looks somewhat like this. So guys, this is nothing but a S curve, or you can say the sigmoid curve or sigmoid function curve. So this sigmoid function basically converts any value from minus infinity to infinity to your discrete values, which a logistic regression wants, or you can say the values which are in binary format, either 0 or 1. So if you see here, the values are either 0 or 1, and this is nothing but just the transition of it. But guys, there's a catch over here. So let's say I have a data point that is 0.8. Now how can you decide whether your value is 0 or 1? Now here you have the concept of threshold, which basically divides your line. So here threshold value basically indicates the probability of either winning or losing. So here by winning I mean the value is equals to 1, and by losing I mean the value is equals to 0. But how does it do that? Let's say I have a data point which is over here. Let's say my cursor is at 0.8. So here I'll check whether this value is less than my threshold value or not. Let's say if it is more than my threshold value, it should give me the result as 1. If it is less than that, then it should give me the result as 0. So here my threshold value is 0.5. Now I need to define that if my value, let's say 0.8, it is more than 0.5, then the value shall be rounded off to 1. And let's say if it is less than 0.5, let's say I have a value 0.2, then should reduce it to 0. So here you can use the concept of threshold value to find your output. So here it should be discrete, it should be either 0 or it should be 1. So I hope you caught this curve of logistic regression. So guys, this is the sigmoid S curve. So to make this curve, we need to make an equation. So let me address that part as well. So let's see how an equation is formed to imitate this functionality. So over here we have an equation of a straight line, which is y is equals to mx plus c. So in this case, I just have only one independent variable. But let's say if we have many independent variables, then the equation becomes m1x1 plus m2x2 plus m3x3 and so on till mn(xn). Now let us put in b and x. So here the equation becomes y is equals to b1x1 plus b2x2 plus b3x3 and so on till bn(xn) plus c. So guys, your equation of the straight line has a range from minus infinity to infinity. But in our case, or you can say in logistic equation, the value which we need to predict, or you can say the y value, it can have the range only from 0 to 1. So in that case, we need to transform this equation. So to do that, what we had done, we have just divided the equation by 1 minus y. So now if y is equals to 0, so 0 over 1 minus 0 which is equals to 1. So 0 over 1 is again 0. And if we take y is equals to 1, then 1 over 1 minus 1 which is 0. So 1 over 0 is infinity. So here my range is now between 0 to infinity. But again we want the range from minus infinity to infinity. So for that what we'll do, we'll have the log of this equation. So let's go ahead and have the logarithmic of this equation. So here we have just transform it further to get the range between minus infinity to infinity. So over here we have log of y over 1 minus 1, and this is your final logistic regression equation. So guys, don't worry, you don't have to write this formula or memorize this formula. In Python, you just need to call this function, which is logistic regression, and everything will be automatically for you. So I don't want to scare you with the maths and the formulas behind it, but it's always good to know how this formula was generated. Moving ahead, let us see the various use cases wherein logistic regression is implemented in real life. So the very first is weather prediction. Now, logistic regression helps you to predict your weather. For example, it is used to predict whether it is raining or not, whether it is sunny, is it cloudy or not. So all these things can be predicted using logistic regression. Whereas you need to keep in mind that both linear regression and logistic regression can be used in predicting the weather. So in that case, linear regression helps you to predict what will be the temperature tomorrow, whereas logistic regression will only tell you whether it's going to rain or not, or whether it's cloudy or not, whether it's going to snow or not. So these values are discrete. Whereas if you apply linear regression, you'll be predicting things like what is the temperature tomorrow, or what is the temperature day after tomorrow, and all those things. So these are the slight differences between linear regression and logistic regression. Now moving ahead, we have classification problem. So Python performs multi-class classification. So here it can help you tell whether it's a bird or it's not a bird. Then you can classify different kind of mammals. Let's say whether it's a dog or it's not a dog. Similarly, you can check it for reptile, whether it's a reptile or not a reptile. So in logistic regression, it can perform multi-class classification. So this point I have already discussed that it is used in classification problems. Next, it also helps you to determine the illness as well. So let me take an example. Let's say a patient goes for a routine checkup in a hospital. So what doctor will do, it will perform various tests on the patient and will check whether the patient is actually ill or not. So what will be the features? So doctor can check the sugar level, the blood pressure, then what is the age of the patient? Is it very small or is it an old person? Then what is the previous medical history of that patient? And all of these features will be recorded by the doctor. And finally, doctor checks the patient data and determines the outcome of its illness and the severity of illness. So using all the data, a doctor can identify whether a patient is ill or not. So these are the various use cases in which you can use logistic regression. Now I guess enough of theory part. So let's move ahead and see some of the practical implementation of logistic regression. So over here I'll be implementing two projects wherein I have the data set of a Titanic. So over here we'll predict what factors made people more likely to survive the sinking of the Titanic ship. And in my second project, we'll see the data analysis on the SUV cars. So over here we have the data of the SUV cars, who can purchase it, and what factors made people more interested in buying SUV. So these will be the major questions as to why you should implement logistic regression and what output will you get by it. So let's start by the very first project, that is Titanic data analysis. So some of you might know that there was a ship called as Titanic which basically hit an iceberg and it sunk to the bottom of the ocean. And it was a big disaster at that time because it was the first voyage of the ship and it was supposed to be really strongly built and one of the best ships of that time. So it was a big disaster of that time, and of course there's a movie about this as well. So many of you might have watched it. So what we have data of the passengers, those who survived and those who did not survive in this particular tragedy. So what you have to do, you have to look at this data and analyze which factors would have been contributed the most to the chances of a person's survival on the ship or not. So using the logistic regression, we can predict whether the person survived or the person died. Now, apart from this, we'll also have a look with the various features along with that. So first, let us explore the data set. So over here, we have the index value. Then the first column is passenger ID. Then my next column is survived. So over here, we have two values, a 0 and a 1. So 0 stands for did not survive and 1 stands for survived. So this column is categorical where the values are discrete. Next, we have passenger class. So over here, we have three values, 1, 2, and 3. So this basically tells you that whether a passenger is traveling in the first class, second class, or third class. Then we have the name of the passenger, we have the sex or you can say the gender of the passenger, whether passenger is a male or female. Then we have the age, we have the SIB SP. So this basically means the number of siblings or the spouses aboard the Titanic. So over here we have values such as 1, 0 and so on. Then we have patch. So patch is basically the number of parents or children aboard the Titanic. So over here we also have some values. Then we have the ticket number, we have the fare, we have the cabin number, and we have the embarked column. So in my embarked column, we have three values. We have S, C, and Q. So S basically stands for Southampton, C stands for Cherbourg, and Q stands for Queenstown. So these are the features that we'll be applying our model on. So here we'll perform various steps and then we'll be implementing logistic regression. So now these are the various steps which are required to implement any algorithm. So now in our case we are implementing logistic regression. So our very first step is to collect your data or to import the libraries that are used for collecting your data and then taking it forward. Then my second step is to analyze your data. So over here I can go through the various fields and then I can analyze the data. I can check, did the females or children survive better than the males, or did the rich passenger survive more than the poor passenger, or did the money matter, as in who paid more to get into the ship, were they evacuated first, and what about the workers, does the worker survived, or what is the survival rate if you were the worker in the ship and not just a traveling passenger. So all of these are very interesting questions and you would be going through all of them one by one. So in this stage you need to analyze your data and explore your data as much as you can. Then my third step is to wrangle your data. Now data wrangling basically means cleaning your data. So over here you can simply remove the unnecessary items, or if you have a null values in the data set, you can just clear that data and then you can take it forward. So in this step you can build your model using the trained data set and then you can test it using the test. So over here you will be performing a split which basically split your data set into training and testing data set. And finally you will check the accuracy so as to ensure how much accurate your values are. So I hope you guys got these 5 steps that we're going to implement in logistic regression. So now let's go into all these steps in detail. So number one, we have to collect your data, or you can say import the libraries. So let me just show you the implementation part as well. So I'll just open my Jupyter notebook and I'll just implement all of these steps side by side. So guys, this is my Jupyter notebook. So first let me just rename the Jupyter notebook to, let's say, Titanic data analysis. Now our first step was to import all the libraries and collect the data. So let me just import all the libraries first. So first of all, I'll import pandas. So pandas is used for data analysis. So I'll say import pandas as PD. Then I'll be importing numpy. So I'll say import numpy as NP. So numpy is a library in Python which basically stands for numerical Python, and it is widely used to perform any scientific computation. Next, we'll be importing Seaborn. So Seaborn is a library for statistical plotting. So I'll say import Seaborn as SNS. I'll also import matplotlib. So matplotlib library is again for plotting. So I'll say import matplotlib.pyplot as PLT. Now to run this library in Jupyter Notebook, all I have to write in is percentage matplotlib inline. Next, I'll be importing one module as well so as to calculate the basic mathematical functions. So I'll say import maths. So these are the libraries that I'll be needing in this Titanic data analysis. So now let me just import my data set. So I'll take a variable, let's say Titanic data, and using the pandas, I will just read my CSV, or you can say the data set. I'll write the name of my data set, that is titanic.csv. Now I have already showed you the data set. So over here, let me just print the top 10 rows. So for that, I'll just say, I'll take the variable Titanic data dot head and I'll say the top 10 rows. So now I'll just run this. So to run this, I just have to press Shift plus Enter, or else you can just directly click on the cell. So over here, I have the index, we have the passenger ID, which is nothing but again the index which is starting from 1. Then we have the survived column, which has the categorical values, or you can say the discrete values, which is in the form of 0 or 1. Then we have the passenger class, we have the name of the passenger, sex, age, and so on. So this is the dataset that I'll be going forward with. Next, let us print the number of passengers which are there in this original dataset. So for that, I'll just simply type in print. I'll say number of passengers. And using the length function, I can calculate the total length. So I'll say length, and inside this, I'll be passing this variable, which is Titanic data. So I'll just copy it from here. I'll just paste it dot index. And next, so let me just print this one. So here the number of passengers which are there in the original data set we have is 891. So around this number were traveling in the Titanic ship. So over here my first step is done, where you have just collected data, imported all the libraries, and find out the total number of passengers which are traveling in Titanic. So now let me just go back to presentation and let's see what is my next step. So we're done with the collecting data. Next step is to analyze your data. So over here we'll be creating different plots to check the relationship between variables, as in how one variable is affecting the other. So you can simply explore your dataset by making use of various columns and then you can plot a graph between them. So you can either plot a correlation graph, you can plot a distribution graph. It's up to you guys. So let me just go back to my Jupyter notebook and let me analyze some of the data. Over here, my second part is to analyze data. So I just put this in header 2. Now to put this in header 2, I just have to go on code, click on markdown, and I just run this. So first let us plot a count plot where you compare between the passengers who survived and who did not survive. So for that I'll be using the Seaborn library. So over here I have imported Seaborn as SNS. So I don't have to write the whole name. I'll simply say sns.countplot. I'll say X is who survived, and the data that I'll be using is the Titanic data. Or you can say the name of variable in which you have stored your data set. So now let me just run this. So over here, as you can see, I have survived column on my x-axis, and on the y-axis, I have the count. So 0 basically stands for did not survive, and 1 stands for the passengers who did survive. So over here, you can see that around 550 of the passengers who did not survive, and there were around 350 passengers who only survived. So here you can basically conclude that there are very less survivors than non-survivors. So this was the very first plot. Now let us plot another plot to compare the sex as to whether out of all the passengers who survived and who did not survive, how many were men and how many were female. So to do that, I'll simply say sns.countplot. I'll add the hue as sex. So I want to know how many females and how many males survived. Then I'll be specifying the data. So I'm using Titanic data set. And let me just run this. Okay, I've done a mistake over here. So over here you can see I have survived column on the x-axis and I have the count on the y. Now, so here your blue color stands for your male passengers and orange stands for your female. So as you can see here, the passengers who did not survive, that has a value 0. So we can see that majority of males did not survive. And if we see the people who survived, here we can see the majority of females survived. So this basically concludes the gender of the survival rate. So it appears on average women were more than 3 times more likely to survive than men. Next, let us plot another plot where we have the hue as the passenger class. So over here we can see which class that the passenger was traveling in, whether it was traveling in class 1, 2 or 3. So for that, I'll just write the same command. I'll say sns.countplot. I'll keep my x-axis as subject only. I'll change my hue to passenger class. So my variable is named as P class. And the data set that I'll be using is Titanic data. So this is my result. So over here you can see I have blue for first class, orange for second class and green for the third class. So here the passengers who did not survive were majorly of the third class, or you can say the lowest class or the cheapest class to get into the Titanic. And the people who did survive majorly belong to the higher classes. So here 1 and 2 has more rise than the passenger who were traveling in the third class. So here we have concluded that the passengers who did not survive were majorly of third class, or you can say the lowest class. And the passengers who were traveling in first and second class would tend to survive more. Next, let us plot a graph for the age distribution. Over here, I can simply use my data. So I'll be using pandas library for this. I'll declare an array and I'll pass in the column that is age. So I plot and I want a histogram. So I'll say plot.hist. So you can notice over here that we have more of young passengers, or you can say the children between the ages 0 to 10. And then we have the average age people. And if you go ahead, lesser would be the population. So this is the analysis on the age column. So we saw that we have more young passengers and more mediocre age passengers which are traveling in the Titanic. So next, let me plot a graph of fare as well. So I'll say Titanic data. I'll say fare. And again, I'll plot a histogram. So I'll say hist. So here you can see the fare size is between 0 to 100. Now let me add the bin size so as to make it more clear. So over here, I'll say bin is equals to, let's say 20. And I'll increase the figure size as well. So I'll say fig size. Let's say I'll give the dimensions as 10 by 5. Okay, so it is bins. So this is more clear now. Next, let us analyze the other columns as well. So I'll just type in Titanic data. And I want the information as to what all columns are left. So here we have passenger ID, which I guess it's of no use. Then we have to see how many passengers survived and how many did not. We also see the analysis on the gender basis. We saw whether female tend to survive more or the men tend to survive more. Then we saw the passenger class, whether passenger is traveling in the first class, second class or third class. Then we have the name. So in name we cannot do any analysis. We saw the sex. We saw the age as well. Then we have SIB SP. So this stands for the number of siblings or the spouses which are aboard the Titanic. So let us do this as well. So I'll say sns.countplot. I'll mention x as sib sp, and I'll be using the Titanic data. So you can see the plot over here. So over here you can conclude that it has the maximum value on 0. So you can conclude that neither a children nor a spouse was on board the Titanic. Now second most highest value is 1. And then we have very less values for 2, 3, 4 and so on. Next, if I go above, we saw this column as well. Similarly, you can do for Parj. So next we have Parj, or you can say the number of parents or children which were aboard the Titanic. So similarly, you can do this as well. Then we have the ticket number. So I don't think so any analysis is required for ticket. Then we have fare. So fare we have already discussed. As in the people who tend to travel in the first class usually pay the highest fare. Then we have the cabin number and we have embarked. So these are the columns that we'll be doing data wrangling on. So we have analyzed the data and we have seen quite a few graphs in which we can conclude which variable is better than the another or what is the relationship they hold. So third step is my data wrangling. So data wrangling basically means cleaning your data. So if you have a large data set, you might be having some null values or you can say NaN values. So it's very important that you remove all the unnecessary items that are present in your data set. So removing this directly affects your accuracy. So I'll just go ahead and clean my data by removing all the NaN values and unnecessary columns which has a null value in the data set. So next I'll be performing data wrangling. So first of all, I'll check whether my data set is null or not. So I'll say Titanic data, which is the name of my data set, and I'll say is null. So this will basically tell me what all values are null and it will return me a Boolean result. So this basically checks the missing data and your result will be in Boolean format, as in the result will be true or false. So false means if it is not null and true means if it is null. So let me just run this. So over here you can see the values as false or true. So false is where the value is not null and true is where the value is null. So over here you can see in the cabin column we have the very first value which is null. So we have to do something on this. So you can see that we have a large data set, so the counting does not stop, and we can actually see the sum of it. We can actually print the number of passengers who have the NaN value in each column. So I'll say Titanic underscore data is null and I want the sum of it. So I'll say dot sum. So this will basically print the number of passengers who have the NaN values in each column. So we can see that we have missing values in each column, that is 177. Then we have the maximum value in the cabin column and we have very less in the embarked column, that is 2. So here if you don't want to see these numbers, you can also plot a heat map and then you can visually analyze it. So let me just do that as well. So I'll say sns.heatmap. I'll say y tick labels to false. So I'll just run this. So as we have already seen that there were 3 columns in which missing data value was present. So this might be age. So over here almost 20% of age column has a missing value. Then we have the cabin columns. So this is quite a large value. And then we have 2 values for embarked column as well. Add a CMAP for color coding. So I'll say CMAP. So if I do this, so the graph becomes more attractive. So over here your yellow stands for true, or you can say the values are null. So here we have concluded that we have the missing value of age, we have a lot of missing values in the cabin column, and we have very less value which is not even visible in the embarked column as well. So to remove these missing values, you can either replace the values and you can put in some dummy values to it, or you can simply drop the column. So here let us first pick the age column. So first let me just plot a box plot and they will analyze with having a column as age. So I'll say sns.boxplot. I'll say X is equals to passenger class. So it's P class. I'll say Y is equals to age. And the data set that I'll be using is Titanic set. So I'll say data is equals to Titanic data. You can see the age in first class and second class tends to be more older rather than we have it in the third class. Well, that depends on the experience, how much you earn, or might be there n number of reasons. So here we concluded that passengers who were traveling in class 1 and class 2 tend to be older than what we have in the class 3. So we have found that we have some missing values in M. Now one way is to either just drop the column or you can just simply fill in some values to that. So this method is called as imputation. Now to perform data wrangling or cleaning, let us first print the head of the data set. So I'll say Titanic.head, sorry, it's Titanic underscore data. Let's say I just want the 5 rows. So here we have survive, which is again categorical. So in this particular column, I can apply logistic regression. So this can be my Y value or the value that I need to predict. Then we have the passenger class, we have the name, then we have ticket number, fare, cabin. So over here we have seen that in cabin we have a lot of null values, or you can say the NaN values, which is quite visible as well. So first of all, we'll just drop this column. So for dropping it, I'll just say Titanic underscore data, and I'll simply type in drop and the column which I need to drop. So I have to drop the cabin column. I'll mention the axis equals to 1, and I'll say in place also to true. So now again, I'll just print the head and let us see whether this column has been removed from the data set or not. So I'll say Titanic.head. So as you can see here, we don't have cabin column anymore. Now you can also drop the NA values. So I'll say Titanic data dot drop all the NA values, or you can say NaN, which is not a number. And I'll say in place is equals to true. It's Titanic. So over here, let me again plot the heat map, and let's say what the values which were before showing a lot of null values, has it been removed or not. So I'll say sns.heatmap, I'll pass in the data set. I'll check it is null. I'll say y tick labels is equals to false. And I don't want color coding, so again I'll say false. So this will basically help me to check whether my values has been removed from the data set or not. So as you can see here, I don't have any null values. So it's entirely black. Now you can actually know the sum as well. So I'll just go above. So I'll just copy this part and I'll just use the sum function to calculate the sum. So here that tells me that data set is clean, as in the data set does not contain any null value or any NaN value. So now we have wrangled our data, or you can say clean our data. So here we have done just one step in data wrangling, that is just removing one column out of it. Now you can do a lot of things. You can actually fill in the values with some other values, or you can just calculate the mean and then you can just fit in the null values. But now if I see my data set, so I'll say Titanic data.head. But now if I see over here, I have a lot of string values. So this has to be converted to categorical variables in order to implement logistic regression. So what we will do, we will convert this to categorical variable into some dummy variables. And this can be done using pandas, because logistic regression just take two values. So whenever you apply machine learning, you need to make sure that there are no string values present, because it won't be taking these as your input variables. So using string, you don't have to predict anything. But in my case, I have the survived column. So I need to predict how many people tend to survive and how many did not. So 0 stands for did not survive and 1 stands for survive. So now let me just convert these variables into dummy variables. So I'll just use pandas and I'll say pd.getDummies. You can simply press tab to autocomplete. I'll say Titanic data and I'll pass the sex. So you can just simply click on shift plus tab to get more information on this. So here we have the type data frame and we have the passenger ID, survived, and the passenger class. So if you run this, you'll see that 0 basically stands for not a female and 1 stands for it is a female. Similarly for male, 0 stands for it's not male and 1 stands for male. Now we don't require both these columns, because one column itself is enough to tell us whether it's male or you can say female or not. So let's say if I want to keep only male, now I'll say if the value of male is 1, so it is definitely a male and it is not a female. So that is how you don't need both of these values. So for that, I'll just remove the first column, let's say female. So I'll say drop first and true. So over here it has given me just one column which is male and has the value 0 and 1. Now let me just set this as a variable, let's say sex. So over here I can say sex.head and I just want to see the first 5 rows. Sorry, it's dot. So this is how my data looks like. Now here we have done it for sex. Then we have the numerical values in age, we have the numerical values in spouses, then we have the ticket number, we have the fare, and we have embarked as well. So in embarked, the values are in S, C, and Q. So here also we can apply this get dummy function. So let's say I'll take a variable, let's say embark. I'll use the pandas library. I'll enter the column name, that is embarked. So let me just print the head of it. So I'll say embark.head. So over here we have C, Q, and S. Now here also we can drop the first column because these two values are enough whether the passenger is either traveling for Q, that is Queenstown, S for Southampton, and if both the values are 0 then definitely the passenger is from Cherbourg, that is the third value. So you can again drop the first value. So I'll say drop and true. Let me just run this. So this is how my output looks like. Now similarly you can do it for passenger class as well. So here also we have three classes, 1, 2 and 3. So I'll just copy the whole statement. So let's say I want the variable name, let's say PCL. I'll pass in the column name, that is P class, and I'll just drop the first column. So here also the values would be 1, 2 or 3, and I'll just remove the first column. So here we just left with 2 and 3. So if both the values are 0, then definitely the passenger is traveling in the first class. Now we have made the values as categorical. Now my next step would be to concatenate all these new rows into a data set, or you can say Titanic data. Using the pandas, we'll just concatenate all these columns. So I'll say p.concat, and I'll say we have to concatenate sex, we have to concatenate embark and PCL. And then I'll mention the access to 1. I'll just run this. Okay, I need to print the head. So over here you can see that these columns have been added over here. So we have the male column which basically tells whether a person is male or it's a female. Then we have the embarked which is basically Q and S. So if it's traveling from Queenstown, the value would be 1, else it would be 0. And if both of these values are 0, it is definitely traveling from Cherbourg. Then we have the passenger class as 2 and 3. So if the value of both these is 0, then the passenger is traveling in class 1. So I hope you got this till now. Now these are the irrelevant columns that we have it over here. So we can just drop these columns. We'll dropping P class, the embarked column, and the sex column. So I'll just type in Titanic data dot drop, and I'll mention the columns that I want to drop. So I'll say I'll even delete the passenger ID because it's nothing but just the index value which is starting from 1. So I'll drop this as well. Then I don't want name as well, so I'll delete name as well. Then what else we can drop? We can drop the ticket as well. And then I'll just mention the access, and I'll say in place is equals to true. Okay, so my column name starts from uppercase. So these has been dropped. Now let me just print my data set again. So this is my final data set, guys. We have the survived column which has the value 0 and 1. Then we have the passenger class. Oh, we forgot to drop this as well. So no worries, I'll drop this again. So now let me just run this. So over here we have the survived, we have the age, we have the SIB SP, we have the parch, we have fair, male, and these we have just converted. So here we have just performed data wrangling, or you can say clean the data, and then we have just converted the values of gender to male, then embark to QNS, and the passenger class to 2 and 3. So this was all about my data wrangling or just cleaning the data. Then my next step is training and testing your data. So here we will split the dataset into train subset and test subset. And then what we'll do, we'll build a model on the train data and then predict the output on your test dataset. So let me just go back to Jupyter and let us implement this as well. Over here, I need to train my dataset. So I'll just put this in heading 3. So over here, you need to define your dependent variable and independent variable. So here, my y is the output, or you can say the value that I need to predict. So over here, I'll write Titanic data. I'll take the column which is survived. So basically, I have to predict this column whether the passenger survived or not. And as you can see, we have the discrete outcome, which is in the form of 0 and 1. And rest all the things, we can take it as a features, or you can say independent variable. So I'll say Titanic data dot drop. So we'll just simply drop this survived, and all the other columns will be my independent variable. So everything else are the features which leads to the survival rate. So once we have defined the independent variable and the dependent variable, next step is to split your data into training and testing subset. So for that, we'll be using sklearn. I'll just type in from sklearn.cross validation, import train test split. Now here, if you just click on shift and tab, you can go to the documentation and you can just see the examples over here. I'll click on plus to open it. And then I just go to examples and see how you can split your data. So over here you have xtrain, xtest, ytrain, ytest. And then using this train test split, you can just pass in your independent variable and dependent variable and just define a size and a random state to it. So let me just copy this and I'll just paste it over here. Over here we'll train, test, then we have the dependent variable train and test, and using the split function we'll pass in the independent and dependent variable, and then we'll set a split size. So let's say I'll put it at 0.3. So this basically means that your data set is divided in 0.3, that is in 70-30 ratio, and then I can add any random state to it. So let's say I'm applying 1. This is not necessary. If you want the same result as that of mine, you can add the random state. So this will basically take exactly the same sample every time. Next, I have to train and predict by creating a model. So here logistic regression will grab from the linear regression. So next I'll just type in from sklearn.linear model import logistic regression. Next I'll just create the instance of this logistic regression model. So I'll say log model is equals to logistic regression. Now I just need to fit my model, so I'll say log model dot fit, and I'll just pass in my x train and y train. Alright, so here it gives me all the details of logistic regression. So here it gives me the class weight, dual, fit, intercept, and all those things. Then what I need to do, I need to make prediction. So I'll take a variable, let's say predictions, and I'll pass on the model to it. So I'll say log model dot predict, and I'll pass in the value that is x test. So here we have just created a model, fit that model, and then we had made predictions. So now to evaluate how my model has been performing, so you can simply calculate the accuracy, or you can also calculate a classification report. So don't worry guys, I'll be showing both of these methods. So I'll say from sklearn.metrics import classification report. So over here I'll use classification report, and inside this I'll be passing in y test and the predictions. So guys, this is my classification report. So over here I have the precision, I have the recall, we have the F1 score, and then we have support. So here we have the value of precision as 75, 72, and 73, which is not that bad. Now, in order to calculate the accuracy as well, you can also use the concept of confusion matrix. So if you want to print the confusion matrix, I'll simply say from sklearn.metrics import confusion matrix first of all, and then we'll just print this. So here my function has been imported successfully. So I'll say confusion matrix, and I'll again pass in the same variables, which is y test and predictions. So I hope you guys already know the concept of confusion matrix. So can you guys give me a quick confirmation as to whether you guys remember this confusion matrix concept or not? So if not, I can just quickly summarize this as well. Okay, Jagriti says a yes. Okay, Swati is not clear with this. So I'll just tell you in a brief what confusion matrix is all about. So confusion matrix is nothing but a 2 by 2 matrix which has a 4 outcomes. This basically tells us that how accurate your values are. So here we have the column as predicted no, predicted y, and we have actual no and an actual yes. So this is the concept of confusion matrix. So here let me just feed in these values which we have just calculated. So here we have 105, 105, 21, 25, and 63. So as you can see here, we have got 4 outcomes. Now 105 is the value where our model has predicted no, and in reality it was also a no. So here we have predicted no and an actual no. Similarly, we have 63 as a predicted yes. So here the model predicted yes, and actually also it was a yes. So in order to calculate the accuracy, you just need to add the sum of these two values and just divide the whole by the sum. So here these two values tells me where the model has actually predicted the correct output. So this value is also called as true negative. This is called as false positive. This is called as true positive, and this is called as false negative. Now in order to calculate the accuracy, you don't have to do it manually. So in Python, you can just import accuracy score function and you can get the results from that. So I'll just do that as well. So I'll say from sklearn.metrics import accuracy score, and I'll simply print the accuracy. And I'll pass in the same variables, that is y test and predictions. So over here it tells me the accuracy as 78, which is quite good. So over here if you want to do it manually, you have to plus these two numbers, which is 105 plus 63. So this comes out to almost 168, and then you have to divide it by the sum of all the four numbers. So 105 plus 63 plus 21 plus 25. So this gives me a result of 214. So now if you divide these two numbers, you'll get the same accuracy, that is 78%, or you can say 0.78. So that is how you can calculate the accuracy. So now let me just go back to my presentation and let's see what all we have covered till now. So here we have first split our data into train and test subset. Then we have built our model on the train data and then predicted the output on the test data set. And then my fifth step is to check the accuracy. So here we have calculated accuracy to almost 78%, which is quite good. You cannot say that accuracy is bad. So here it tells me how accurate your results are. So here my accuracy score defines that, and hence we got a good accuracy. So now moving ahead, let us see the second project, that is SUV data analysis. So in this, a car company has released new SUV in the market. And using the previous data about the sales of their SUV, they want to predict the category of people who might be interested in buying this. So using the logistic regression, you need to find what factors made people more interested in buying this SUV. So for this, let us see a data set where I have user ID, I have gender as male and female, then we have the age, we have the estimated salary, and then we have the purchased column. So this is my discrete column, or you can say the categorical column. So here we just have the value, that is 0 and 1. And this column we need to predict whether a person can actually purchase a SUV or not. So based on these factors, we will be deciding whether a person can actually purchase a SUV or not. So we know the salary of a person, we know the age. And using these, we can predict whether a person can actually purchase a SUV or not. So let me just go to my Jupyter notebook and let us implement logistic regression. So guys, I will not be going through all the details of data cleaning and analyzing the part. So that part, I'll just leave it on you. So just go ahead and practice as much as you can. Alright. So my second project is SUV predictions. Alright. So first of all, I have to import all the libraries. So I say import numpy as np. And similarly, I'll do the rest of it. Alright. So now let me just print the head of this data set. So this we've already seen that we have columns as user ID, we have gender, we have the age, we have the salary, and then we have to calculate whether the person can actually purchase a SUV or not. So now let us just simply go on to the algorithm part. So we'll directly start off with the logistic regression, or how you can train a model. So for doing all those things, we first need to define an independent variable and a dependent variable. So in this case, I want my x, that is an independent variable. I say dataset.ilog. So here I'll be specifying all the rows. So colon basically stands for that. And in the columns, I want only 2 and 3 dot values. So here it should fetch me all the rows and only the second and third column, which is age and estimated salary. So these are the factors which will be used to predict the dependent variable, that is purchase. So here my dependent variable is purchase. And the dependent variable is of age and salary. So I'll say dataset.ilog. I'll have all the rows and I just want fourth column, that is my purchased column dot values. Alright, so I've just forgot one square bracket over here. Alright. So over here I have defined my independent variable and dependent variable. So here my independent variable is age and salary and dependent variable is the column purchase. Now you must be wondering, what is this ilog function? So ilog function is basically an indexer for pandas data frame, and it is used for integer based indexing, or you can also say selection by index. Now let me just print these independent variables and dependent variable. So if I print the independent variable, I have the age as well as the salary. Next, let me print the dependent variable as well. So over here you can see I just have the values in 0 and 1. So 0 stands for did not purchase. Next, let me just divide my dataset into training and test subset. So I'll simply write in from sklearn.crosssplit.crossvalidation import train test. Next, I'll just press shift and tab, and over here I'll go to the examples and just copy the same line. So I'll just copy this. I'll remove the points. Now I want the text size to be, let's say, 25. So I have divided the train and test split in 75-25 ratio. Now let's say I'll take the random state as 0. So random state basically ensures the same result, or you can say the same samples taken whenever you run the code. So let me just run this. Now you can also scale your input values for better performing, and this can be done using standard scaler. So let me do that as well. So I'll say from sklearn.preprocessing import standard scaler. Now why do we scale it? Now if you see our data set, we are dealing with large numbers. Well, although we are using a very small data set, so whenever you're working in a prod environment, you'll be working with large data set where you'll be using thousands and hundred thousands of tuples. So their scaling down will definitely affect the performance by a large extent. So here let me just show you how you can scale down these input values. And then the pre-processing contains all your methods and functionality which is required to transform your data. So now let us scale down for test as well as a training data set. So I'll first make an instance of it. So I'll say standard scaler. Then I'll have xtrain. I'll say sc.fit, fit underscore transform. And I'll pass in my xtrain variable. And similarly, I can do it for test, wherein I'll pass the xtest. Alright. Now my next step is to import logistic regression. So I'll simply apply logistic regression by first importing it. So I'll say from sklearn.linear model import logistic regression. Now over here I'll be using classifier. So I'll say classifier dot is equals to logistic regression. So over here I'll just make an instance of it. So I'll say logistic regression. And over here I'll just pass in the random state which is 0. And now I'll simply fit the model. And I'll simply pass in xtrain and ytrain. So here it tells me all the details of logistic regression. Then I have to predict the value. So I'll say ypred is equals to classifier, then predict function, and then I'll just pass in xtest. So now we have created the model, we have scaled down our input values, then we have applied logistic regression, we have predicted the values, and now we want to know the accuracy. So to know the accuracy, first we need to import accuracy score. So I'll say from sklearn.metrics import accuracy score, and using this function we can calculate the accuracy, or you can manually do that by creating a confusion matrix. So I'll just pass in my y test and my y predicted. Alright, so over here I get the accuracy as 89%. So if we want to know the accuracy in percentage, so I just have to multiply it by 100, and if I run this, so it gives me 89%. So I hope you guys are clear with whatever I have taught you today. So here I have taken my independent variables as age and salary, and then we have calculated that how many people can purchase the SUV, and then we have calculated our model by checking the accuracy. So over here we get the accuracy as 89, which is great.
Let's compare the two models. So first of all, let's look at the definition of linear regression and logistic regression. So the main aim of linear regression is to predict a continuous dependent variable based on the values of the independent variables. But when it comes to logistic regression, the aim is to predict a categorical dependent variable based on the values of independent variables. These are the main aim of each of these models. Now let's look at the variable type. Now in linear regression, the dependent variable is always continuous. Alright, this is very important to remember because this is the main objective of linear regression. Okay, it makes use of continuous dependent variables to predict continuous values. Similarly, when it comes to logistic regression, you're going to use categorical dependent variable to predict a categorical value. Alright, now let's look at the estimation method. So guys, linear regression is based on the least square estimation, which basically says that the regression coefficient should be chosen in such a way that it minimizes the sum of the square distance of each observed response. Okay, now this is in depth about linear regression, so that's why I'm going to leave a link in the description. Now logistic regression on the other hand is based on maximum likelihood estimation. Okay, this basically says that the coefficients should be chosen in such a way that it maximizes the probability of y given some value of x. Next is the equation. Earlier we discussed this equation where for linear regression we have y is equal to b naught plus b1 into x plus e. Okay, similarly this is the equation for logistic regression. So the next difference is the best fit line. So guys, linear regression aims at finding the best fitting straight line, which is also called the regression line. Alright, but when it comes to logistic regression, if you try and map the relationship between the dependent and independent variable, you're going to get a curve, which is also known. Linear regression, there has to be a linear relationship between the two. So when I say linear, I mean that the variables have to vary linearly. Okay, that's how the straight line is formed in the first place. All right. When it comes to logistic regression, it's not necessary to have a linear relationship, predicted integer value, or basically a continuous value. So when it comes to logistic regression, the output has to be a binary value. Okay, so it should either be class A or class B, or it should be 0 or 1, something like that. Finally, we have applications. Now, linear regression is mainly used to predict outcomes like the expected number of sales, and it's always used to predict some continuous value. All right, but when it comes to logistic regression, it's mainly used in classification. So when you want to classify a data set into two different classes, then you use logistic regression. You can find a lot of applications of linear regression in the business domain. And logistic regression is mainly used in the cybersecurity, image processing, and classification domain.
What is classification? And if I have to tell you about classification, uh, like for example, what happens is like we have two type of, when we talk about machine learning is nothing but like a series of instructions you give it to the computer so that it can learn the patterns from your data set, right? To give you an example, imagine that there is a trending topic. For example, you want to find it out whether Prime Minister Modi will be the second prime minister, once again the prime minister for the country or not. Okay, so now what you will do is you will collect the data set from multiple different sources, and you will actually build it like a algorithm where you will get a label as yes or no. Yes, he will continue as the next prime minister, or no, he will not continue as a next prime minister. So you will collect the data set and you will feed this data set to the computer, and this process is called as a machine learning, right? So now in this case, what happens is so this is about the classification, right? So now machine learning is basically of two types. One is called as a supervised machine learning, another is called as a unsupervised machine learning, and the third one is a reinforcement machine learning. So when we speak about supervised machine learning, as the name suggests, it provides some supervision, right? For example, the teacher teaching the kid, it's a supervised machine learning, right? So we will give the trained examples, we will give the trained data set with the pure label on top of that. This is called as a supervised machine learning. So if I draw in front of you, this type of machine learning look like this, supervised machine learning, where what happens is like you would have the data set, which is a structured data set, and you would have one column which is called as a label, what you want to predict. Okay, and you would have a various predictors by which you want to predict. To give you an example, imagine that you want to predict a pricing of a community. Okay, you want to predict what would be the pricing of apartment in a particular community, right? Now these can be the variable, like you can see that what would be the number of how many floors it has. You can have a variable like what is a pollution level, how many educational institutions are nearby, right? So based upon that, the pricing will change. But this type of supervised machine learning, why it is called supervised machine learning? Because we provide the independent variable, or we provide the predictors, also we provide the label data set. Okay, now this supervised machine learning is basically of two type. So this supervised machine learning, one first is called as the regression based supervised machine learning. Okay, and the second one is called as a classification based supervised machine learning. Now, what is the difference between regression based and a classification based supervised machine learning? Regression based supervised machine learning is that machine learning where what you want to predict is continuous in nature. Okay, imagine you want to predict the community prices, right, which is a continuous value. If it is a continuous value, then we will go ahead with regression based supervised machine learning. Okay, whereas if you want to predict something which is the discrete outcome, to give you an example, you want to predict that whether I will win the match or not. Okay, I want to predict whether the particular employee will churn out from the company or not. You want to predict like whether the person will have a cancer or not. You're getting my point, right? So if you have the output which you want to predict is in the form of yes or no, or true or false, right? This is called as the supervised machine learning, but a classification based supervised machine learning. Okay, so classifications based supervised machine learning is the process of dividing the data set into different categories or group by adding a label. Okay, so always remember that whenever you guys want to predict the classes in the data set, whenever you want to predict, like whether this will happen or not, whether a person will do a credit card fraud or not. You're getting my point, right? Whether the employee will churn out from the company or not, right? Whether the particular person will have a diabetes as a disease or not. All these questions, wherever you want to find it out, yes or no, or true or false, or you want to predict classes in the data set, this is called as a classification based supervised machine learning. Okay, so this is what is called as a classification based supervised machine learning. And today I will teach you, I will tell you about various form of classification based supervised machine learning, although we will do a deep dive into decision tree. Right now you will be able to understand that decision tree, how decision tree is connected to the network, what we are learning today with classification based supervised machine learning. Okay, so now we have various algorithms. Algorithm is nothing but a set of mathematical equations for classification based supervised machine learning. We first of all, we have something called as decision tree, then we would have something called as random forest, then knife base, and then KNN, which is called as a k nearest neighbors. Okay, so let me give you few statements about this algorithm, and we have many others, but today we will focus on one of them, which is decision tree. So now first let's start with decision tree. Now what is a decision tree? What I was telling you is, believe me or not, decision tree is something you use every day in your daily life. For example, you take decisions, and today also you took a decision to attend this webinar, right? But how do you decide a decision? Based on various further decisions, right? For example, for today joining the webinar, you have seen that, okay, when this webinar is about, okay, so you said it is weekday or weekend, then you might have said check it out, right? What is the time of the webinar? Then you might have checked it out, what is the topic of the webinar, right? So, and who is conducting this webinar? So based upon this, you took a decision, shall I go ahead or not go ahead? You're getting my point, right? So this is what is called as a decision tree. We call it as decision tree because it is a graphical representation of all the possible solution to a decision. It's like a tree. Like decision tree is like a tree. Why? Because a tree also start with a root and then it emerge into various branches. Similarly, you have a decision tree, which I'm showing to you here as a simplest algorithm, which is being used for machine learning purposes. Now it is something like this. Imagine that you want to find it out that, like, do you want to go to a restaurant or do you want to buy an hamburger? Okay, so you have two choices. Either you can go for a restaurant or either you can buy a hamburger. Now how would you decide which one you would follow? So you will start with what is called as a root node. You will start with the root node that whether I am hungry or not, right? If I am hungry, right, then only I will go for all these activity. If I am not hungry at all, then simply go and sleep. You got my point, right? So this is how you will start with the first node, which is to find it out whether I'm feeling hungry or not. If I'm feeling hungry, then I will decide that, well, I have money which is around $25 worth. If I have money, then I will go for a restaurant. If I don't have a money, then I will buy an hamburger. You understood this? This is simplest representation of decision tree. Basically, you decide something on the basis of the previous outcomes. And you can imagine any sort of example here. Imagine that you want to find it out whether the person will do a credit card fraud or not. Again, it will depend upon the previous circumstances that, for example, it will depend upon how much is the salary of the person. It will depend upon what is the job profile of the person. It will depend upon the fact that, like, for example, how many fraud or how many cards this person have, right? So on basis of, you will decide that whether this will do a credit card fraud or not. So this is the simplest form of classification based algorithm. Then we have the next algorithm, which is called as a random forest. Now, what is a random forest? As the name suggests, you built one decision tree in the last example, right? But one decision tree can sometimes be overfitting as a case, right? So people said that, like, why should I only trust one decision tree? For example, whenever you take a bold decision in your life, you don't trust only a single voice, right? You want to hear it from multiple different people to make your decision more stronger, right? go to a doctor. If the doctor says to you that you have this type of a disease, you don't believe in that. What you do is you also talk to second doctor, third doctor, fourth doctor to confirm that this is true or not. Okay, so this is what is called as a random forest. As the name suggests, why it is called random forest? It is called random forest because now you're building the various number of decision trees here. It's like a forest of all the trees, right? It is no longer a single tree, it is a forest of complete trees. So for example, you can imagine that if it is my training data set, I will split my training data set into multiple examples, multiple decision trees will be built, and then based upon the majority, I will decide whether should I do this or not. Okay, so it is also called as a bagging sort of methodology where we bring the outcome of various models, or we bring the outcome of various trees all together to make the to make our powerful decision. Okay, so this is another example. This is another algorithm which is called as a random forest. Then after random forest, we have something called as naive Bayes. Okay, now what is a naive Bayes algorithm? Naive Bayes is also a simplest algorithm, but naive Bayes is basically based on the Bayes theorem. Okay, so this algorithm is basically based on the Bayes theorem, and Bayes theorem is based on the conditional probability, right? So it is based on the conditional probability, which is your naive Bayes. Now in naive Bayes, what happens is like we decide that whether something will happen or not on the basis of probability. So let me illustrate you with this example. Imagine that you want to find it out whether I would have a disease or not. Okay, so first of all, the probability of having a disease is 0.10 and the probability of not having a disease is 0.90. Okay, so if there is a probability of having a disease is 0.10, you will further find it out that what is the probability that my test will be positive given I am diseased. What is the probability that my test to diagnose the disease is negative given I have a disease? Right? Similarly, if you go into this direction, if there is a probability of not having a disease is 0.90, you will find it out that what is the probability of having a disease, test being positive with no disease, and what is the probability of no disease given I don't have the disease, which is 0.90. So basically here you check the outcomes. Here you check the outcome of all the possible combinations. This is what is called as the naive Bayes algorithm or Bayes theorem, or conditional probability based theorem. Okay, then we also have something which is called as a key nearest neighbor, which is the one of the finest algorithm, which also helps you in deciding the classification. Right now, what is k nearest neighbor? K nearest neighbor, as the name suggests, what happens in this case is we try to build, basically it's like a neighbor. So it's something like this. Like if I give you the data set, say I give you the customer data set, okay, and it is a transaction data set. So customer number one has bought a product number one, right, from a particular vendor at a particular rate, and this is a profit this customer has given to us, and this is the revenues. Okay, this is my customer number one. Similarly, you would have customer number two, customer number three, customer number four. Right now, if I ask you that which customer profiling is nearby same, right? So what you can do is you can group your customers, or you will get to know that which customer behave in the similar way. So you can say that customer one, customer three, and customer four, they behave in a similar way because they are giving us the high profit and high revenue margins. You understood? So this is what happens in the case of k nearest neighbor. So k nearest neighbor, what you generally do is you find it out that what I would be able to, find it out who is my nearest neighbor, like what are the similarities in the patterns we have, right? This is what we use for k nearest neighbors. And this you can see that, for example, the algorithm based on the distance based mechanism find it out that how many people or what type of audience is similar to the outcomes, right? So then moving further here, with the second topic, let's go into detail about what is decision tree all about, right? So far I have touched base on classification based algorithm, right? And I was teaching you different type of classification based algorithm, but since the focus of today's class is decision tree, let's take a deep dive into the decision tree. Okay, so let's get started with decision tree. A decision tree is a graphical representation of all possible solutions to a decision based on a certain condition. What does it mean? It means that it is as simple as that. Imagine that this is a tree, right? So it is like a tree where you have a problem statement that should I accept a job offer or not? Imagine that you want to find it out that should I accept a job offer or not? This is a problem statement which is there in your mind. Now, how would you solve this problem statement with the help of a decision tree? First of all, you will start with what we call as a root node. We will start with a root node, starting with, to find it out, what is a salary? Okay, what is a salary I'm getting? So if my salary is equal to or greater than equal to 50,000, I'll go here. If my salary is not greater than equal to 50,000, I will say I will not accept this offer. Okay, now imagine that you say that your salary is greater than 50,000, then you will check another variable here. You will check it out whether I have to commute more than 1 hour. If I have to commute more than 1 hour, I will decline the offer. You're getting my point, right? Then you will, if you don't have to commute more than 1 hour, then you will still consider this option, and then you will check it out. For example, in this case, we are checking it out whether you are getting the free offers also, like coffee or some snacks or other things like that. If yes, then you will accept finally the offer. Otherwise, you will decline the offer. You got my point? This is how our decision tree works. Basically, decision tree will keep on splitting unless and until you are able to find it out your decision. Okay, so here the decision was, shall I accept this or not? Right? So it will keep on splitting unless and until you get your decision whether you do this or not. Like this example which I have explained you. Okay. Now, with this, what happens is, like, let me, if I go further and explain you further on this decision tree, let's understand this more importantly, right? Let's understand this one by one. So imagine that this is my data set. Okay. Now, in my data set, you can see that I have various colors given to you. It's like a green color, yellow color, red color, and a yellow color. I am saying if there is a green color fruit with a diameter of 3, right? And I can say it is a mango. Whereas I'm saying if it is a yellow color and a diameter 3, still will be called as a mango. If it is a red color with 1 diameter, then it is a grape. And it can be a red color with a diameter of 1, still can be a grape, but even a yellow with a diameter of 3 can be lemon. Now, what is happening in this case is, if you have this type of a data set where you want to predict the label of the fruit, right? You want to predict whether a fruit will be mango, whether a fruit will be lemon, right? Or whether a fruit in this case is mango and lemon or grape. I have to build a classifier, which is a decision tree classifier on the basis of this data set. Imagine this is a problem statement given to you. Now, first of all, what you will do here is you will take this data set, right? You will take this data set and you will start with a root node. Root node, imagine here is like, is my diameter of the fruit greater than equal to 3 or not? Okay, is my diameter of the fruit greater than equal to 3 or not? If it is greater than equal to 3, right? Now, if it is greater than equal to 3, you can see that you have 3 fruits here, 3 rows of the data set here. One is green with 3 mango, yellow with 3 lemon, yellow with 3 mango. And wherever it fails in the condition, you are left with where the diameter is not greater than equal to 3, it is less than equal to 3. Then which are the data set we have? Red 1 grape and red 1 grape. Okay, so I hope you are understanding this, right? How we have starting with the decision tree with the based on one condition here, right? Which is diameter. Now, based upon this, what I will do is I have to split it further. Here in this case, I don't have to split it because I already got the result. So if my diameter is greater than equal to 3, in my data set, if the diameter is not equal to greater than equal to 3, I know it is a grape. right? Whereas if the diameter is greater than equal to 3, then it can be a mango or it can be a lemon. I'm not sure on my decision. So what I will do here is I will split it further. So I have to split this further. Here the splitting is not required, but if I split this further, I may check it out now. Is the color equal to yellow or not? Now, if the color is equal to yellow, then I have two fruit, which is your this row, which is, your mango or lemon. And if the color is not equal to yellow, then you will have the another row of the data set, which is, which you are left with, right? So this is how you have done this work in the case of your decision tree. Okay, and how you will find it out at which type of the criteria or which type of the algorithm I should, or which type of criteria or variable I should choose here to split the tree is on the basis of Gini index and the information gain, which I will illustrate and show you in the few slides from now. Okay, so I hope with this you understand the how your decision tree works, basically on the basis of the condition. And if you get a pure subset, then no need to split it further. If there is no pure subset, you will keep on splitting unless and until you get a pure subset. Okay. So in this case, what has happened is you got 100% mango. Here you got 50% mango and 50% lemon. Okay. So now this is what I have told you in the previous slide, like how does it work, right? Now this all depend upon the Gini index basis, right? Now in the next subsequent slide, let me tell you and explain you about Gini index and information gain. How does it work, right? How does that something works on the basis of your Gini index? So imagine that, imagine that I have a feature here, is the color green or not, right? Basis of whether the feature, whether you have a color green or not, what would happen here is if the color is green, you will get this row here. If it is not, you will get these two rows here, right? In the next, it may decide on the other basis, right? It can be, is the diameter which is greater than equal to 3 or not, and many other things. Okay. Now let's go ahead, the example and the questions which is coming to your mind, which is related to, decision tree terminologies. I'm pretty sure you would have these questions in your mind and you would be thinking that how should I decide that which feature I should use and which feature shouldn't I be using? This is the question which you had. And this is an excellent question for understanding the decision tree. But before I go on to that, I have to tell you about some of the terminologies which we commonly use while we build the decision tree. So first of all, decision tree looks like this type of a tree based structure. Okay, so every decision tree will have its root node. So root node is where the decision tree will start. So it represents the entire population or sample, and it is further get divided or into two or more homogeneous sets. So as you know that this will be the first feature on the basis of your tree will start. Like tree start with a root, your in this case your decision tree will also start with a root node. Okay, now once you have the root, after that in a tree what happens is you will start getting the branches, right? I hope you understand what is branches. In this case we will keep on splitting unless and until we get a decision whether this will happen or not. So it's like a branches. Okay, then we would also have a parent or a child node. So child node is nothing but when you have a branches, then the branches can also have the outcomes. So in the previous example, like for example, we have whether the diameter is greater than equal to 3 or not. You remember whether the diameter is greater than equal to 3 or not. If it is true, what is happening? If it is a false, what is happening? So this is a child or child node. Basically, this is an intermediate node. This is not the final decision which is being made. So this is called as a parent or the child node. Then we also have other terminology here, which is splitting, which you know that we will keep on splitting unless and until you get a desired node. And finally, the tree end with the leaf node. So always remember one thing, you will start your tree with a root node. Root node is a node with which we will start the decision tree, and you will end your decision as decision tree at a leaf node where you will get a decision that you should do this or not. Okay, and now pruning is the activity where you will cut down the decision tree if it is pruned lot amount of times. I will even explain you this. it is a case of overfitting. You shouldn't build shouldn't build 1,000 branches of the tree when it is not even required. So I'll explain you this point. Now let's move further here and let's see this with the help of an example, which was your Gini index and your information gain, right? So this is where you were asking me that which question to ask and when, right? How would you decide that which feature has to be taken first, right? Let's take up an example here, and I would encourage every one of you to hear me really fine here, because this is on the basis how would you decide, or how the algorithm decide to break this further. And I'm explaining you with the help of one simplest example, and we will do some maths over it. So imagine that there is a data set where I want to find it out whether I will play the match or not. Okay, there is a cricket match or there is a football match or whatever it is. I want to find it out whether I will play the match or not. Okay, now how do the decision tree look like? Decision tree look like this. If the outlook, if the outlook is humid, if the outlook is humid, and if the outlook is humid and humidity is very high, then I will not play the match. On the other hand, if the outlook is humid and humidity is normal, I may play the match. Okay. If the outlook is absolutely clear, then I will always play. On the other hand, if outlook is windy and the winds are very strong, I may not play the match. On the other hand, if the outlook is windy and the wind are weak, I may play the match. So now what is happening again is that you are not sure how you decided with outlook, how you decided with these nodes here, how you decided with these features here. Let me try to show you this entire data set. So this entire data set look like this. Okay, so this is basically your 14 days data set, and this exactly happens in the case of your classification based algorithm. You will get a data set like this. So you can imagine that you want to find it out, I would like whether I will play or not, right? This is what you want to essentially find it out, whether I would play or not. On basis of what? On basis of 4 different variables you have. 4 different variables or features in the data set is outlook, temperature, humidity, and wind, right? So now it can be like if the outlook is sunny, temperature is hot, humidity is high, wind is not there, I will not play the match. This is how you will read this one data point, right? Similarly, I have multiple data point. Now I have to decide how can I build a decision tree, and out of these 4 features, which feature should I use first as my root node, right? So this is what I have to decide, and let's do it accordingly, right? So now what I'll do from here is I will illustrate you what is Gini index, what is information gain, and how does this happens, right? And this is basically used to build your decision tree. So before I make you understand about Gini index or information gain, one thing which you should always remember is to understand the concept of impurity. What is impurity? Impurity is nothing but, you can see there is a basket where you have apples, right? Now, if you have a basket which is of apple and another tray, it is written the label as apple. Now, in this case, you will never make a mistake. You will never make a mistake because here you have an apple, here you have only one label. So everything will be perfect. It will be 100%. Basically, there is no impurity, there is no problem in your data set, right? On the other hand, let me flip the story. In this case, imagine that I have different fruits in the basket, which is like apple, you have a banana, you have a grapes, you have a cherries and many other things, right? And you have many apples, many labels here. In this case, try imagining you have to match each fruit with its label, right? Now, in this case, the impurity cannot be equal to 0. The impurity will not be equal to 0 in this case, because what would happen here is that you have a chances of misclassification, right? This is a very important concept, right? When you have perfect thing, the misclassification will not happen. But whereas if you have a multiple labels with multiple fruit, misclassification or impurities will not be equal to 0, right? So this is associated with a term called as entropy. Maybe in your childhood days, you have learned about entropy in your chemistry class. In a simple sense, what is entropy? Entropy is a randomness of the space, sample space. Whenever you are not sure on your decision, then entropy will be more. Imagine that I'm giving you the data set where it is like 51% of doing this thing, 49% of not doing this thing. 51% chance that the employee may leave the organization, 49% chance that employee may not leave the organization. So basically, you are not sure on your decision. If you are not sure on your decision, then the entropy will be very high. On the other hand, if you are very sure on your decision, then the entropy will be very low. So basically, we need that feature which can provide us lowest entropy rather than the highest entropy to select as that as a good feature. So we generally find it out entropy by the help of this formula. What we simply do is don't get scared with this formula because everything happens automatically in R or Python, right? Imagine, just look at this formula. What is this formula? This formula says that what is the probability that something will happen, multiply by log base 2 probability that something will happen, subtract this with probability that something will not happen, into log base 2 probability that something will not happen. Okay, let's take up an example. Don't worry about it. Let's take up an example that probability that I will win the match, you will apply here, and probability that I will not play the match or win the match, you will apply here, and then you will calculate the entropy. Let's take an example how you can do this in our case. So in our case, let me show you. Yeah, how we will build the decision tree in our case. In our case, you just see here what is happening is that we have 14 instances or 14 rows of the data set where 9 times if you see it, I will play the match and 5 times I will not play the match. Okay, so if you see carefully, there are 9 labels where I'm playing the match and there are 5 labels where I'm not playing the match, right? So first of all, I have to find it out the total entropy. How I will find the total entropy? This is being determined by probability that I will play the match, multiply this with log base power 2 probability that I will play the match. What are the chances that I will play the match? 9 out of 14. All of you will be with me, right? This is 9 out of 14. Multiply with log base 2, 9 out of 14. Subtract this with what is the probability that I will not play the match? 5 out of 14. Multiply this with log base 2, 5 out of 14. So once you calculate this, you will find it out the entropy of this entire system. Entropy of this entire system is 0.94. Okay, so this is the entropy of your entire sample space. This is the first thing. Now, how this entropy will help you in selecting which features you will take or not. So let's go further. So now we will take each feature one by one, whether I should take outlook, whether I should take temperature, whether I should pick up humidity, or whether should I pick up windy, right? Let's go one by one. Now, first I'm plotting for outlook. Imagine for outlook, how many times, so what are the distinct value of outlook? Outlook can be sunny, outlook can be overcast, or outlook can be rainy, right? These are the 3 different combinations you can have for outlook. Now if the outlook is sunny, 2 times I'm playing, 3 times I'm not playing the match. If the outlook is overcast, I'm always playing the match. If the outlook is rainy, 3 times I'm playing, 2 times I'm not playing the match, right? This is how I have bifurcated it. What I will do in the next iteration is, let me find it out the entropy of outlook. Okay, so if we start with outlook, remember this formula, which is, probability that I will play, multiply with the probability that I will play, right? And subtract with probability which I will not play, and log base 2 of not playing. So 2 by 5 is the chances that I will play, into log base 2, 2 by 5. This is a subtraction here, right? With I will play and log 3 by 5 I will play, right? So you will calculate this entropy when outlook is sunny. Yeah, so you got this entropy when the outlook is sunny is 0.971. Accordingly, you will proceed with calculating the entropy when the outlook is overcast. Outlook is overcast, always you are playing, right? If the outlook is overcast every time you are playing, so it means that you will get a probability of 0. If you apply in that formula, you will get 0. And third, what would happen if the outlook is sunny? In that case, you will again multiply and you will put the formula and you will get it out 0.971, right? So you will find it out entropy for each and every distinct combination of your feature. You got my point, right? Outlook being sunny, outlook being overcast, outlook being sunny, overcast, sunny, and rainy. This should be replaced here, right? And then what you will do is you will finally calculate the information gain. Information gain is nothing but what you will do is you will pick it up the chances, you will pick it up the entire chances when you are playing, right? Which is 5 out of 14. You remember 5 out of 14 were the total chances that I will play into if it is sunny, plus 4 out of 14 if it is overcast, 5 out of 14 if it is rainy, right? And you will calculate the information from this outlook. And once you calculate the information, you will subtract this information from your total entropy, which I found it out in the last slide, which was 0.94. You will subtract this and you will get the information gain, or this is also called as a information gain from a particular feature. So basically, these type of a calculation, first of all, don't get scared away that you have to do this calculation. But what I'm trying to explain you is this is how your algorithm will work. For each and every feature, it will calculate the information gain from your feature, right? If you have the more information gain, it means that this variable is of very important in predicting that something will happen or not. Okay, so for outlook, I got the information gain as 0.247 with all the calculation. Remember, then we will proceed with wind, if the wind is there or not, right? And then I will proceed with wind and I will calculate the information gain and say information gain I found it out is 0.048, right? Similarly, we will calculate for all the 4 of them. Let me put it together for all of you. So this is what happens here. Now, if I put in front of all of you, these were the 4 different variable I have: outlook, temperature, humidity, and wind, right? I am calculating the information gain for each one of them, and the information gain I got for outlook is 0.247. So if the information gain is highest in a particular feature, that feature will become your root node. You got my point. So therefore, we will pick it up outlook as our root node. Similarly, for when the tree gets started later on as a branch node also, your information gain will be calculated, and whichever feature is giving you more information gain, that will be picked up later in the your tree also. So this is how you will build your decision tree, and you will finally get a decision tree like this. Okay. So now what I will do is, like I will quickly show you how do we do the decision tree in your Python. Okay. So I'll show you how do you do this in Python, and then I will summarize for all of you that why decision trees or tree-based algorithms are better than your other algorithm. Okay. So how do you choose? Basically, that which algorithm you will select and when. Okay, so I'll describe you this, but before, let's jump on to Python and go there. So what I have done here is, like, I had built the decision tree in front, already. So quickly I will walk you through the commands. Okay, so what happens here is that in Python, as you would be well versed with this, that we generally import packages in Python. So I'm importing NumPy, I'm importing matplotlib for plotting the chart. I'm importing various packages from your sklearn, which is for machine learning purposes, right? So I am importing your label encoder, your decision tree classifier, classification report, and I'm importing your tree, right? So we have all this which I am importing, right? After I import, what I will do is I'm reading my data set. So I'm showing you this with the help of our iris data set, which is one of the very popular data set for building the a decision tree, right? For any particular source. So imagine that this is my data set, and I'm just showing you 6 rows of the data set where, I want to find it out whether a particular flower species will be Setosa, versicolor, or virginica. I have 3 different flowers which I want to predict, and on the basis of sepal length, sepal width, and petal width. So basically, I have different dimensions of flowers length and width, and based on that, I want to find it out whether the particular species will be Setosa, versicolor, or virginica. You got my point, right? So this is a data set. So what I will do is, as you know, with every machine learning data set, we play with the data set. So I'm checking the information here, what type of the data type it is. So sepal length, it is a float, petal length, it is a float, and species is a object. Why object? Because this is a categorical column. So after this, I'm also checking whether there is any null value present in the data set or not, because if there is any null value, then we have to get rid of that null value, or we have to replace that null value with some imputed value, right? This is what I'm checking here. Once I do that, I'm also plotting this because we usually do visualization, right, to understand the data set better. So what I'm doing here with the help of SNS, which is your SNS.pair plot, I'm plotting all the possible plots. So basically sepal length with sepal width, what type of the combination look like. So Setosa, versicolor, and virginica, there are 3 different species you can see in the data set. And this is what I'm getting a trend between your sepal length and sepal width. Similarly, this is basically from sepal width to petal length, right? So this is how I'm understanding the patterns, or I'm understanding the relationship between the variables in the data set. So this is what I'm understanding here. I'm also checking whether there's a correlation or not. Higher the shade, it means there will be a strong correlation. So all of these things is being done as a part of exploratory data analysis before even you start your machine learning model, right? Once you do this, after that, what I have to do is, after that, what I'm trying to do is, I am taking your species column, what I want to predict, as my target variable, which is your dependent variable. And so this is the dependent variable, and with the help of what I want to predict will be my independent variable. So I'm calling X all my independent variable, and I'm calling target as my dependent variable. Once I do this, then you will also think about it that the variable which I want to predict is the flower species, right? But I want to convert this into 0 and 1 class, 0, 1, 2 class, because your computer cannot understand text, right? Computer can only understand the numbers. So what I'm doing here is I'm changing it to the class, right? So what I'm trying to do here is I'm saying wherever it is Setosa, it will become 0. Wherever it is Virginica, it will become 1. And it is versicolor as a third category, it will become to the training data set, and remaining 20% I'm taking as a test data set. Okay. Now I will call decision tree classifier. Like I want to make a decision tree, and I want to fit this on my training data set and the test data set. And I will start building the decision tree, and with the help of so here is when I have created the decision tree, and here is when I'm checking the prediction, how accurate my decision tree is. So I got my precision, which is good. I got my recall, I got my F1 score, and I also get the support, right? So all these matrices are being used to calculate your how accurate your predictions are. So higher the precision, better the results would be, right? And finally, I'm showing to you that how does the tree look like. So I had tried to plot this decision tree in front of you. So basically it starts with petal length, and you can see the Gini index coming up here, or the information gain, which is information gain and Gini index are reciprocal to each other. If you want to use information gain, you will get that score. If you don't want to use information gain, you will get Gini index. So they are both reciprocal of each other. It is one and the same thing. You use Gini index or you use information gain. They are the two different metrics to build your decision tree. So you can see that based on a petal length, the tree gets splitted like this. Then based on the petal length of different dimensions, your tree further split, then it further split, then it further split, and finally you get to know that whether the particular species will be versicolor or virginica. Okay, so this is how your entire decision tree is built in Python. Okay, so this is how it's so simple. I know it takes time to build this thing, but once you are a good data scientist and you understand all these things, It is very simple to build all these things very easily in Python or R, right? So now, finally, going back, how would you decide? How would you decide that which algorithm, which algorithm will be taken when? So what happens is this is on the basis of scikit-learn. So it starts something like this. Okay, so it is on the basis of like this, that first of all you see here that um, whether how many samples you have, how many data points you have in the data set, right? If you have more than 50 samples, then you will go here. If you have less than 50 data point, then you will go here. So you will get more data set, right? So if you have more data, if you have greater than 50 data point, then you will go further, you split of your data set. If it is not, then you just the kind advise it, get more data set. Okay, so then you will decide at what you want to predict. If you have a labeled data set, then you will go here, right, and do clustering. If you don't have the labeled data set, then you will see whether you want to predict a quantity. If yes, you will go in regression. If you want to predict, if you just want to do exploratory analysis, you can do dimensional reduction. If you have a labeled data set, for classification, you can do all this classification. So basically, this is a cheat sheet which we generally use to decide that what we have to do with the data set and when.
Let's understand what is a random forest. So random forest is constructed by using multiple decision trees, and the final decision is obtained by majority votes of these decision trees. So let me make things very simple for you by taking an example. Now suppose we have got 3 independent decision trees. Yeah, we are just taking 3 decision trees. And I've got an unknown fruit, and I want that these trees would give me a result of what exactly this fruit is. So I pass this fruit to the first decision tree, the second decision tree, and the third decision tree. Now a random forest is nothing but a combination of these decision trees. So the results are being fed into the random forest algorithm. So what it sees is that, okay, the first decision tree classifies it as peach. The second decision tree says that it is an apple. And the third one says that it is a peach. So random forest classifier says that, okay, I've got the result as 2 peach and 1 for an apple. So I would say that the unknown fruit is an peach. All right. So this is based on the majority voting of the decision trees. And that is how a random forest classifier comes to a decision of predicting the unknown value. Okay, so this was a classification problem, so it took the majority vote. Now suppose if it was a regression problem, it would have taken mean of it. Okay, so now let's move on further to understanding what is a decision tree. But before that, we should understand that random forest, the building blocks are decision trees. And that's why studying decision tree becomes important, because if we understand one decision tree, we can apply the same concept to random forest. Okay. So now let's move on forward and understand the important terms in random forest. And this will also help us consolidate whatever we have learned so far. So we've taken the same small decision tree of the previous example, and let's understand these are also the important terms which will be relevant to random forest also. So the first is the root node. Now here what happens is that the entire training data is being fed to the root node. And then we've got here that each node will ask either true or false question with respect to one of the feature. And then in response to that question, it will partition the data set into different subsets. That's what it is doing here based on the condition that if the body mass is greater than or equal to 3500, it asks a question either yes or no. And based on that, again, further partition is done. And if not, then it just classifies the species. And then again, what happens is that the splitting. Now, this is very important here. The splitting takes place either with the help of a Gini or entropy methods, and these helps to decide the optimal split. And we will be discussing about splitting methods very soon, right? Okay. And then we've got the decision nodes, which provide the link to the leaf nodes. And these are really important because then only the leaf nodes would tell us what actually the real predictions or to which class does this species belong. So now coming to the leaf node, and these are the endpoints where no further division will take place and we will obtain our predictions. Okay. So now coming up to another important thing here is working of random forest. So now for working of random forest, we will have to understand a few important concepts like random sampling with replacement, feature selection, and also the ensemble technique, which is used in random forest, and that is bootstrap aggregation, which is also known as bagging. So we will understand this with the help of an example, which will be very simple. And then we will go on understanding how feature selection is done in both the classification and the regression problem. Actually, how random forest select features for the construction of decision trees. Well, in random forest, the best split is chosen based on Gini impurity or information gain methods. So this also we will understand. Now let us first understand random sampling with replacement. Now what happens here is that we've got a small subset of the same penguin dataset, wherein we've got some 6 rows and 4 features, that means 4 columns. And the arrows that you can see is that now we will be creating 3 subsets from this small subset, right? And these 3 subsets will become our decision trees. And then we'll be constructing decision trees from these subsets. So let us create our first subset. And you can see here that the subset is randomly being created. And for convenience sake, let me just also show you the different subsets here. Okay, so now for better understanding, let us understand this, that in the first subset, if we focus, we've got certain random rows here, and we've got certain feature, but we do not know how this feature has been selected. We got island and we got body mass, but in the second subset, we got island and flipper length, and in the third subset, we got body mass and flipper length, right? Now let's look at the rows. Now, when I am talking about these features, I will say this is feature selection, and remember this term. Now coming to the second concept, that is random sampling. Now random sampling is nothing but selecting randomly from your subset. So I'm selecting randomly certain rows from my subset and creating further subset. Okay, so what is replacement here? Replacement can be seen here and can be understood with this second subset. We see here that the Gento species, this row is being repeated again. And this is replacement. That means that when we are working with repeated rows and this row can be repeated again in the second or the third subset, then this is random sampling with replacement. That means my random forest can use a row multiple times in multiple decision trees, right? So this is the basic concept of random sampling with replacement and feature selection in random forest. Another important term which I would like to bring into the notice is that when we are working with these type of small subsets, these are also known as a bootstrap data sets. And when we aggregate the results of all these data sets, it becomes bootstrap aggregation. So just filling in the gaps so that later on the concepts become more clear. So now let's move on to drawing decision trees of these subsets. Okay. So let's draw the decision tree of the first subset. Again, we are taking body mass as the first root node, and then based on a decision like if the mass is greater than or equal to 3500, then take a decision either yes or no. If it is no, then the species is chin strip, and if it is yes, then again you partition based on island, and if it is Togresen, then it is Adelie, and if it is Bisco, then it is Gento species. Okay. So this is how we will construct 2 more decision trees of the remaining subsets. So in the second subset, let us just again create decision tree. And here now we are taking flipper length, and then based on a condition that if the flipper length is greater than or equal to 190, then make a split. If it is yes, then the species become Gento. And if it is no, that means again make a decision based on island. And if it is Togresen, it is Adelie. And if the island is Dream Island, then it is a chin strip species. So this is how the decision tree of the second subset has been created. And this is how it will take decisions, right? Based on the tree length, depth, and also the features it is selecting. Okay. So now let's create the third decision tree of the third subset. And we get a decision tree something like this, wherein body mass, if it is greater than 4000, and if it is yes, then clearly it is a Gento species. And if it is no, then again make a partition with respect to flipper length, another feature here. And then if it is again greater than or equal to 190, then the species would be Adelie, else it would be chin strip. So this is how decision tree 3 will make a decision. Now let's just keep these decision trees with us, okay? and we will make sense of these trees just in a while. Okay? But before that, let us understand how feature selection is done in a random forest. How am I selecting the columns? So for classification, by default, the feature selection is taken as the square root of total number of all the features. Now suppose I've got here 4 features. So it is a classification problem. I will take the square root of these 4 features, which becomes 2. So decision tree would be constructed based on 2 features each. If suppose I had 16 features, then it would be square root of 16. That would be 4. So 4 features would be taken in each decision tree. All right. And suppose if this would have been a regression problem, then by default, what would happen? The features would be selected by taking the total number of features and dividing them by 3. Okay. So this is how by default the feature selection is being done by a random forest. Okay. Now let us move on forward to consolidating our learning. So now we are coming to ensemble techniques, that is also known as bootstrap aggregation. Random forest uses ensemble techniques. And what is ensembling? It just means that you are aggregating the result of the decision trees and taking the majority vote in case of classification and the mean in case of regression problems and giving the output. Okay. So now we have again plotted all our decision trees here. And below we can see that there's an unknown data and I want to predict the species of this data. So what will happen is that again, let us just feed this problem to each of the decision tree and let's see what each decision tree makes the prediction. So I just feed this unknown data to decision tree 1 and it says that, okay, the species seems to be chinstrape. Okay. And then decision tree 2 says that based on the data, it has been found that the species is Edureka. And then decision tree 3 says that, no, I with my decision tree, this species is chinstrap. Okay. Now, all these data is being fed to random forest classifier. And it says that, okay, for chinstrap, I've got 2 votes. For Edureka, it's got 1 vote. So the new species would be chinstrap, right? So this is how the bootstrap aggregation is done based on the majority voting and the decisions taken by different decision trees. They have been combined together, aggregated, and we get an ensembled result in the random forest. Okay, so this was very simple concept of ensemble techniques which has been used in random forest. Okay, so now let's move on forward to splitting methods. So what are the splitting methods that we use in random forest? So splitting methods are many, like Gini impurity, information gain, or chi-square. So let's discuss about Gini impurity. So Gini impurity is nothing but it is used to predict the likelihood that a randomly selected example would be incorrectly classified by a specific node. And it is called impurity metric because it shows how the model differs from a pure division, right? And another interesting fact about Gini impurity is that the impurity ranges from 0 to 1, with 0 indicating that all of the elements belong to a single class and 1 indicates that only one class exists. Now value, which is like 0.5, this indicates that the elements, they are uniformly distributed across some classes, right? Now moving on forward to information gain. Now this is another splitting method which random forest can use, and information gain utilizes entropy. So entropy is nothing but it is a measure of uncertainty. So information gain, let's talk about that first. So the features they are selected that provide most of the information about a class, right? And this utilizes the entropy concept. So let's see what is entropy. This is a measure of randomness or uncertainty in the data, right? So we will understand this entropy with the help of a small example. So don't worry about it. So let's understand this entropy. Now suppose there's a fruit tray with 4 different fruits, right? And what do you feel about the entropy here? That means the randomness of the data. Is it really easy to classify these fruits into the respective class? So this becomes really uncertain and the data looks messy here. But what if we just split here these into 2 trays, wherein the first tray would have peaches and oranges, and in the second tray will have apples and lemons. So now this becomes a little more certain. We get low randomness here, and this is called as low entropy. So when we move down from tree, that means from root node to the leaf nodes, the entropy reduces. And we can also calculate information gain from this entropy. That is the difference in entropy before and after the split that is known as information gain. Okay, so once we move down the tree and start reducing the randomness from the data, the entropy becomes lower, and that is what we want in our data. If there's low entropy, that means we are likely that the predictions would be more accurate, and we can make predictions very easily as compared to very messy data which has high entropy. Okay, so that was about entropy. And now let us just move on to the practical demonstration or a hands-on on random forest. Okay, so now it's time for a hands-on on random forest. So let us just import a few basic libraries of Python in our Jupyter notebook, and we will run this. We will import pandas as PD, numpy as np, and seaborn as sns. Now seaborn is needed here because we want to load a data set, that is a penguins data set, with the help of seaborn. And this is already been preloaded in seaborn. This is already loaded data set, and seaborn has got multiple data sets, for practice for beginners. So it is a good way to practice for data sets. Now we can see this asterisk sign, that means it is telling us to wait. So let us just let it get loaded. So we got our data in an object called df, and we can see the first 5 entries here. And this data frame is shown in the form of a table, rows and columns. And we see here some species, island, bill length, bill depth, flipper length, body mass, and the sex of the penguin. So our task is to specify or to classify these species of penguins into the respective correct species, right? So we see the shape of our data, and we see that it is like 344 rows and 7 columns. And we will see the info. So we see df.info, and this gives us, along with the non-null count, we also get the data type of the values. So we have got species island as the object data type, whereas the bill length, bill depth, triple length, and body mass are in floating point, or you can say floating data type, and the sex is in object data type, right? So now moving on forward to calculating how many null values are there with the help of df.isNull.sum. So we get certain some around 2 null values in all these columns, as you can say the features like bill length, bill depth, flipper length, and body mass, whereas there are 11 null values in sex feature, right? So what we do is, since they are very small null values, we can just drop it, or you can also ignore them. So here in this data frame, what I'm doing is I'm just dropping these null values, and let us just check whether they have been dropped or not with the help of, again, the same function .isNull.sum, and then we see that yes, they have been dropped from our data frame. Now let us do some feature engineering with our data. Now we have seen that we have got some object data type in our data frame, and before feeding it into algorithm, that is random forest, we have to transform the categorical data or the object data type into the numeric. So we are using here one-hot encoding to convert the categorical data into numeric. Now there are various ways in Python which we can do that, like one-hot encoding, or you can also use the mapping function in Python, but here we are using one-hot encoding. So let us just do that. And we find here, first of all, let us apply it on the sex column. And here we see that we have got 2 unique values in sex, that is male and female. And we use pandas here to get dummies. That is how we will apply this one-hot encoding, because this is how get dummies work. So what happens is here is that the new unique values are converted into the respective columns in the data frame. So we see here we have got 2 unique values, males and female, and they are being converted into the columns. Okay, so one thing to note here is that we also get a problem of dummy trap, because here we see only 2 unique values. Now suppose if I had 6 or 7 unique values and I do this one-hot encoding, I would have lots of features in my data frame, and that would lead to several complexities. So what I do is, to keep things simple, I can use one-hot encoding when my data frame or my unique counts are low, when my unique values are less. So since I had just 2 or 3, I can use it. So I'm using here. So what I do is, again, now one row, one column, as we can see here, that it is redundant, giving me extra information. So I will just drop it. So I drop this first column, and what I get in this data frame is only male. So let us just infer whether I can also infer females from this or not. So if the value is 1, that means the penguin is a male. And if the value is 0, that means the penguin is a female. Okay, so only one column is needed for this data frame. So I just kept one and dropped the another one. Okay, now apply again one-hot encoding to the island feature. So in island, if we check the unique values, we've got 3 unique values here. Togresen, Bisco, and Dream Island. And the object is the data type, right? So again, we will use pandas, pd.getDummies, and we will apply it on the feature island, and let's get the head of it. So we get here, again, the unique values were converted into columns, and we get here respective 3 columns. And then again, we will just drop the first column to get the remaining 2 columns. So here also we can infer that if the island is Togresen, if it is 1, then it is not Dream, neither Bisco, right? So this is how we can read it from the data frame and understand that. Now remember this thing that these 2, island and here sex, these are 2 independent data frames. These are not yet included in the main data frame. So what we will do now is we will concatenate the above 2 data frames into the original data frame. So what we do, we again create a new data frame, that is new data, and let us just concat with the help of pd.concat function, and we will concat what? Df, island, and sex. And access is 1, that means in the column. Okay. So when we will run this, let's see the head of it. So everything gets concatenated in a single data frame, which is good for the feeding this data into or splitting the data into test and train data. So now we have this new data frame, and we've got some repeated columns here which needs to be deleted. So what we do is we will delete sex and island here, which are just repeating, because we've got here male, and we have also got here Dream and Togresen. So we do not require this island column, neither this sex. So we just drop it with the help of new data.drop and the column names x is 1 in place equals to true, right? And let's see the head of this data frame. Head of the data frame gives me 5 unique values, right? And now it is time to create a separate target variable. And what we'll do is we will store in a variable called y only species. So what we do is from this new data.species, we will just store the species in this y. And we see this y.head, that is the first 5 species. And we got the values here. That means another target variable is being created now. So, and you can also see the y.unique values as Edureka, Chinstrap, and Gentoo. So now we see here 3 unique values of the penguin, that is Chinstrap, Edureka, and Gentoo, and the data type is object here. So again, we need to convert this object into the numeric data type. So now what we are doing is we are using the map function in Python, and what we do is we map Edureka to 0, Chinstrap to 1, and Gentoo to 2. So this is how we see then all the values are being mapped to numeric. This is another way to convert a categorical value into a numeric value in Python. Now what we do is let us just drop the target value species from our main data frame. So we just drop it, and let's see our new data frame. So we see that we don't have any target species here, right? Okay. So in X, let's store this new data and perform the splitting of the data. So what we do is from sklearn.model selection, we will import our train test split, and we will split our training data into 70% and 30%. So test data becomes 30% and training data is some 70%. And this random state is 0, which means that I'm not fixing any random state. And this is also used for the code reproducibility. Now suppose if I again run this code, I will get the same result. It will not change. You can set this random state to any of the random number as per your choice, and the result would differ. Okay. So now let us print the shape of xtrain, bytrain, xtest, and ytest. So we see here that it has been split into 70 and 30%, and we get xtrain as 233 values here and 7 features, and xtest has 100 values and 7 features. Similarly, ytrain, you can see 233 values and ytest has 100 values. That means the species. Okay. So that has been perfectly splitted into 70 and 30%. Now what we do is we will train the random forest classifier on the training set. How do we do it? We will import the random forest classifier from sklearn.ensemble. So we've already dealt with what is ensemble. And then in classifier, we will store this random forest, and this n estimator is nothing but decision trees. So we are creating some 5 decision trees here, and the criteria is entropy. And again, random state is set to 0. So let's see. And then we will fit this X train and Y train. So this has been fitted, and the criteria is entropy here. All right. So now let's make some predictions, and let's create a variable called yPredict, and we will just predict it on xtest. And we have also printed this y prediction. And now let's print the confusion matrix to check the accuracy of random forest algorithm. And what we do is from matrices, sklearn matrices, we will import classification report and confusion matrix, and also the accuracy score. So we will just import them, and then in CM variable, we will print the confusion matrix of Y test and Y predictions. So we will print it, and we see here the accuracy score also, which is 98%. So our random forest classifier is giving us a very good accuracy of 98%. And you can see a confusion matrix that only 2 cases have been misclassified. Rest all the cases have been correctly classified by random forest classifier. Okay, so now let's move on to printing the classification report of Y test and Y prediction. Let's see. And we get the precision as 96%. That means the true predictions by the algorithm is 96%. The recall or the true prediction rate is 100%, which is very nice. And F1 score is also good, which is 98%. So this is giving us a good result. But what if we change the criteria from entropy to Gini? So let's just experiment with that too. So let's try this with the different number of trees and change the criteria to Gini coefficient. So now again from sklearn.ensemble, we will import random forest classifier and fit it. Okay. And here what we are doing is just we are using 7 trees. Previously we used 5. And now in the criteria, we will use Gini coefficient and random state is 0. So let's run this and see whether there is a change in accuracy or not. And let's predict this. And let's check the accuracy score. What is the accuracy score for this random forest classifier with 7 trees? So we get 99% accuracy with changing the criteria and changing the number of trees. So you can just experiment with different number of trees and different number of decision trees. Let's just experiment with 12 decision trees and see what happens. So you can see the accuracy reduced to 98%. Okay. With 7, we were getting 99. So let's just keep 7 because it is giving us really good accuracy. So this is about random forest classifier and how it works with several trees and different criteria to give us very good accuracy on our training and test data.
The case that we are discussing is basically the KNN algorithm, which is an algorithm which we used for mostly supervised machine learning, which is where you have labeled data. Okay, so what is KNN algorithm? So as we said, KNN algorithm is K nearest neighbors algorithm, and it is an example of supervised learning algorithm where basically you try to classify a new data point based on the neighbors of that data point, which is basically which data points are closer to it. For example, here, as you can see, you have on one side couple of cats, and on the other side you have on one side you have dogs, and on the other side you have cats, right? Now, if a new data point is given to us, there is a picture of a new animal, and if it is lying somewhere here, right, then we know that it is nearer to the cats, right, and therefore we will classify it as cat. Whereas if it is sort of nearer to the dogs, then we classify it as dog, right? So that's the neighborhood for the dog, and therefore we sort of classify it, that new animal or the new picture, as being or that of a dog. And this is quite this is something which is we even see in our regular day-to-day life, right? We have had examples where our parents keep telling us, okay, don't play with those kinds of children or something because they are not good in their studies, or probably they are not so good in their behavior, because you would become like them, right? So it's again an example from real life of classifying a particular person based on the company that they keep, right, or from the with the kind of people that they are. So that's sort of the example. And now let me actually go back. Okay, what are the features of K nearest neighbors algorithm? Okay, so let's talk about the features of KNN. So as I said, KNN is a supervised learning algorithm. Typically, it is used for supervised learning kind of problems. It's very simple, as we mentioned. Intuitively, you can it's about what kind of neighbors do you have. So your class is predicted based on your nearest neighbors, as the name suggests. And then it's a non-parametric technique. So I would like to spend a couple of minutes here to discuss about what we mean by by non-parametric. So typically, the supervised machine learning algorithms are of two kinds, right? One is the parametric types, and the second one is the non-parametric type. When we say parametric, what we mean is basically that the machine or the algorithm assumes that there is an underlying function or a distribution that is known of the particular data set. Like, for example, the linear regression would assume that the relationship between two things x and y is linear in nature, right? And similarly, for a distribution, a Gaussian distribution, it would assume a normal distribution of the data points, and so on. So a lot of the supervised machine learning algorithms, they assume some kind of function association between the predictor, which is basically the root causes which help you in predicting, and the variable that you are trying to predict. Whereas there are certain algorithms like the KNN or the Parson window or the linear discriminant analysis, which is of the kind which is called non-parametric, because it does not assume any particular kind of distribution or any particular kind of functional relationship of the data that you are trying to predict, or you're trying to learn the pattern of. So KNN is one of the kind. As I said, Parson window is another one, which is basically where you in Parson window, essentially, the volume of the data set or the area that the data set covers is known, whereas you're trying to find the k there, which is the number of data points within that area or the volume, right? Whereas in case of non-parametric technique like KNN, it's the opposite, where the k is known, which is basically you would like to associate the class of the data point that you are trying to predict based on the k number of neighbors around it. Now k can be 3, 4, 5, whatever, right? 10, 20, and so on. Essentially, the difference between Parson window and KNN is that in KNN, you already know the k, and then from the k you try to find out the volume, and therefore then you try to find the probability or the density underlying distribution. And then there is the discriminant analysis, which is of, again, two kinds: linear discriminant and multiple discriminant analysis, where basically what you do is you transform the underlying data, the features, into a higher dimension, and in such a way that in the new feature space, after you have transformed the data, you now try to apply a parametric approach. Like, for example, you will try to project the features onto a line, or if it is on a subspace which is higher dimension than a line, then essentially it becomes multiple discriminant analysis. So basically, those are the three kinds of non-parametric techniques. So even if you were not able to sort of get the full hang of what these three types are, what you need to keep in mind is that non-parametric technique does not assume any kind of distribution or any kind of functional relationship of the underlying data, and therefore it gives us a lot of flexibility. Whereas the parametric techniques, they basically assume some kind of functional relationship between the data points, or they assume some kind of distribution. So where would you use a non-parametric versus a parametric technique, right? So basically you would use non-parametric technique, where you do not know about the functional relationship. That is one. Second is that, there is maybe, let's say, large amount of data, and so on. And thirdly, non-parametric technique like KNN does not work in a very high dimensional data. So you would also use parametric techniques in that case. Whereas if you have, smaller data sets, you would use, typically non-parametric techniques. And then also, if you understand that the relationship between the data points might be, for example, linear or something like that, you would use a parametric technique. So you're assuming that there is some kind of relationship, like a linear relationship or something like that between the data point. So that's where you will use the parametric technique. So again, just to summarize, basically non-parametric is an approach where you do not assume any kind of distribution or functional relationship, whereas parametric assumes a functional relationship or basically a distribution between the data points. The other feature of KNN is that it is a lazy algorithm. So what do we mean by lazy algorithm? Actually, in most of the supervised learning algorithms, you basically train your model on the training data set, then you have your model, and then you apply this particular model to the test data set to then classify or predict. For example, whether a new image is that of a cat or a dog, right? So this can be, some kind of algorithm like support vector machine or regression or logistic regression or whatever, right? So you run this logistic regression or you run this regression or support vector machine on the training data set, and it learns the features or it learns the parameters of the model from that data set, and then applies this learnt model on the test data set. Whereas in case of KNN, actually there is no training step at all. That's why it's called a lazy algorithm, because what it does is, at the time that you are actually now want to predict, at that point in time, actually it will go and it will do all the calculations of the distance of the new data point, like for example the new image of the cat or dog, from all the other data points that you have. So it will calculate all the distances, and then we'll check for those data points which are, or the k data points which are nearest to this. So that's why it's called lazy algorithm, because nothing happens till the point, or no calculations happen till the point you are actually trying to predict something. So there is no training step involved. Okay, and then it's used for both classification and regression, as we just mentioned. So it can be used to predict the values as well as be able to classify something like, okay, whether it is a cat or dog, or if you're trying to, let's say, predict some value, some forecast or something, that for that also you can use it. And then it is based on feature similarity, which is basically, what do we mean by feature similarity? So feature can be things like, if for example, you are looking at classifying cats versus dog, right? So is the eyes like a dog? That can be one of the features. How do the ears look? That can be one of the features. What about the tongue, the face, and so on? So there can be multiple such features, and how similar these features are between two data points, which is used basically by the KNN algorithm. And then, as I said, there is no training step involved. So these are the features of KNN algorithm. And therefore, now let's look at actually just some simple examples of how it works. So as you can see here in this slide, we have two classes of data. So one is all these blue data points, and there is another one which is the orange data points. Now, if you have a new data point, which is this pink one here, which class should it belong to? Should it belong to class A or should it belong to class B? So what you would do is, you would actually start calculating the distance of this pink data point from every square or blue triangle data point. And then you will decide, you will have to assume a particular K. Let's say K is 3, right? Which is, I'm looking at the nearest 3 data points. And in that case, basically, as you can see, if we draw this circle, right, then we see that 2 of the nearest data points within that circle is of the square orange kind. So basically, we will predict that this particular new data point belongs to class A. Whereas K value was 7, right, as in this particular example now. You would see that 4 out of the 7 is actually of the blue triangle kind, and therefore we will now classify it as belonging to class B. So essentially this prediction changes, as you can see here, depending on what is the K value. So therefore the question is, what should be the value of K, right? And typically what happens is, you run a trial and error, and basically you come up with, okay, what is the best K value? But essentially what one needs to understand is that as the value of K increases, basically the partition line starts moving towards becoming more and more linear. So it starts becoming less flexible, and it starts assuming some kind of a linear dividing line or something like that. So what happens is that in that, as you increase the K, your bias basically increases, but your variation reduces. So we know that in classification problems or in machine learning problems, bias and variance are two things that we are trying to manage, right? Bias is basically how close you are to the actual class or to the actual value, whereas variation is how much variability is there in your prediction. So as the k increases, the bias sort of increases, but the variance reduces. And then it is vice versa. So if your k decreases, let's say at k is equal to 1, where you are only looking at just one nearest neighbor and then predicting based on that, actually the bias is the least, which means it is the most flexible. K is equal to 1 is the will give you the most flexible demarcating line or function, whereas the variability will be the maximum. So that's the sort of the trade-off, and that's how we actually determine k. So we have to get a k value in such a way based on trial and error that sort of maximizes our or reduces the bias as well as the variance, and that's the kind of optimization we are trying to do. Okay, so how do we calculate the distance itself, right? And distance typically can be of many kinds. So the example here is of the Euclidean distance, but you can have other kinds of distances like Manhattan distance or Mahalanobis distance, and you can look up references for other kinds of distances. Now Euclidean distance is calculated for the point P1 and P2 as given here. Essentially Euclidean distance is nothing but the square root of sum of the x coordinates of these 2 points P1 and P2, and then y coordinate square of these 2 points P1 and P2. And this is just an example of one kind of distance, and other kinds of distances like Manhattan or Mahalanobis are also there. And then this calculating this distance becomes quite challenging, especially in cases where you are trying to, for example, calculate, let's say, how close two LinkedIn profiles are, right? Or trying to classify the category of electrocardiogram and so on and so forth. So there we have to bring in more creativity to just decide what kind of distance to use. Okay, now let's move ahead. We will now talk of some use cases where KNN can be used, and this is an example of how KNN can be used for book recommendation. So if you have purchased books on Amazon or wherever, right, some of these recommendations are based on KNN algorithm. And then as we said, KNN is like based on features, right? So maybe let's say what will be the nearest neighbors of a particular book. It can be based on who is the author, what is the topic, and so on and so forth. And then there are other use cases like I mentioned, so for classifying satellite images, for classifying handwritten digits on image analytics, or for classifying electrocardiograms, etc. Typically KNN can be used. Okay, so now actually we will get into some hands-on. Okay, so to start the hands-on session, I'll go to this Jupyter notebook that I already have installed on my system, and I have a certain code written which we will take two examples. Both the examples are based on data sets which are available in the open source, so you can easily get access to that data. So what we do is we start by importing the necessary libraries. So we import pandas, Seaborn, NumPy, and Matplotlib. Basically, pandas and NumPy are there for doing the data manipulation and also for storing data as matrices or as arrays, and be able to perform some mathematical procedures on them. And then Seaborn is basically used for plotting, and Matplotlib for plotting as well. And this line here, get IPython, just helps us to run the images that we'll be creating in line with Jupyter Notebook instead of opening up a new window. So let's run this, and what it will do is it will import all these packages for us which we are going to use. And then we will first import the breast cancer data that is available in your scikit-learn datasets. So we import that, and then let's just initialize that data into a variable here called cancer. So cancer here represents all the breast cancer data. And now let's actually look at what this data is. It's a bunch of attributes in this dictionary here. So you have data, the target, which is basically nothing but whether it is a cancer or not. So whether it is malignant or benign. Malignant means it's a bad cancer, and benign means, well, it's just a tumor, it's not cancerous. Target's name, description, feature names, which is basically the features that will tell us whether a particular case belongs to cancerous or non-cancer, or malignant or benign. And then actually let's just print the description of this particular data here. So as you can see, we can use this command to print the description here. And then we see that there are 569 data points with about 30 attributes. And these attributes are radius, texture, parameter, etc. And the max and min values of those are given here. And then now let's look at some of the feature names. So these are the feature names, radius, texture, and so on. And now let's actually set up a data frame of this particular data here using pandas, this function here. So there are 569 data points, and all these are basically your features as we talked about. And let's look at the target variable, which is nothing but whether it is telling us whether a particular data point belongs to malignant or benign. So 0 is cancerous and 1 is non-cancerous. And then we convert the target into a data frame as well. And then let's look at the couple of examples of how the data points look like. This is one row of the data points with all the several feature values that we have. So basically we use this package called standard scalar from scikit-learn for pre-processing and for standardizing the variables. And we initialize this standard scalar into a variable called scalar. So standardizing is nothing but basically bringing all the samples to essentially the same range, right? Because what might happen is some of the data point, like for example temperature might be from 0 to 100, and some price might be from, let's say, 1000 to 100,000 or whatever, right? So the absolute values can lead to some issues with respect to the prediction. Therefore we have to standardize it or bring it between, let's say, -1 and 1, so, and then a mean of 0, right? So we have to bring everything to the same scale to be able to compare the samples. So we first of all we fit this standardization or normalization on the data set we have, and that is we calculate the variance and the means, and then we actually apply it on the data set to transform it to the actual values. And then if we look at the scaled values now, so let's look at the scaled values, and this will give an example of the top 5 rows here. So we can see now the values are between -1 and 1, or rather it is standardized essentially with a normal distribution. And then we divide this data into test and train. So basically we will train the model and then we will test it on a separate data set. If you use the same random state, you should be able to get the same result. Otherwise, you may get a different result here. And essentially, we are keeping the testing size to 30, which means that we are dividing the entire data set into 2 parts. The train part, which is having 70% of the data, and the test part, which is having 30% of the data. And again, we are using this package called train test split from the scikit-learn package. So we get the X and the Y's, which are basically nothing but your train, and the X's are your predictors and Y is your predicted variable, whether it is cancerous or not. And then now let's import the K nearest neighbors classifier. This is the actual algorithm, which we are importing from scikit-learn package. And now we initialize this particular algorithm, and then we fit it on the data. And some of the parameters, as you can see, is basically what is the leaf size and so on and so forth. The nearest n neighbors we are taking. So we are taking k is equal to 1 here, basically, as of now. We will see the results based on that, and then we will change it and see how the results vary. And we now run it on we now try to predict it. And then we will now try to evaluate what the results look like. So we have imported the classification report and confusion matrix, which is basically trying to see whether we were able to correctly classify the cancerous and non-cancerous as non-cancerous as or not. So we can see that this is the actual and this is the predicted. So basically some data points here 5 and 4 are classified wrongly, otherwise all the others are classified well. So if we look at the accuracy, calculated accuracy actually, so we see that the precision, which is true alarm, right, which is basically from the cancerous samples, how many were you able to actually predict as cancerous? If you see, the accuracy is quite high, almost 94-95%. And then the recall, which is from all of the cancerous samples, how many were you able to actually predict accurately, is about again 94-95%. And F1 score is nothing but a combination of both precision as well as recall, and that's quite good as well. So with k is equal to 1, we are able to get already some good results. Now let's try to see how to choose the k value, right? So this is basically nothing but a bunch of code that actually runs the k value from 1 to 40 and then tries to check the accuracy. And this is just like doing a trial and error to see where we get the best results so that we can then use the best k value. So if you can see this particular plot here, after we plot the result from the running the trial and error from 1 to 40, we see that the error actually starts decreasing, and somewhere around this k is equal to 21 we get the minimum value of error. So for us the best k value is 21. So now if we compare the results between k is equal to 1 and k is equal to 21, we should be able to see the prediction result. So as you can say, this was the result with k is equal to 1, which is we get about 94-95% accuracy. And then with k is equal to 21, we will see whether the accuracy improves, right? So we see that yes, the accuracy has now gone up to almost 99%, which is, we earlier had 9 misclassified data points out of all of the points, and then here we have just 2 data points which are misclassified from the test data set. So now this was one example of applying KNN on the cancer data set, which is available freely. And now let's look at another example, which is the iris data set, and again available freely as well. So iris is a type of flower, and we will see what flower is it. So just give me a moment here. So we again start by importing the necessary libraries, and then we'll look at what this iris dataset is. So the iris dataset comprises of 50 samples of 3 species of iris flower, which is iris setosa, iris virginica, and iris versicolor. These are the 3 types of iris flowers. And if you run this, basically we will find that, okay, sorry, we did not copy the code here, so it was giving an issue. Let's just run it again. Okay, so we see that it is this particular flower, which is iris setosa. So the iris setosa you can see. And now let's look at the other 2 kinds of flowers here. So which is iris versicolor. So this is iris versicolor. And then you have the iris virginica. So we see that this one is iris virginica. So essentially we now will import the sort of data set. We have already done that, and we will now use the Seaborn package to actually plot some of this data and see how it looks like, which is basically do some kind of exploratory data analysis. So if we look at the data itself, so this is the top 5 rows from the data, right? So essentially the data consists of basically what is the sepal length, sepal width, petal length, and petal width. And this is nothing but basically your petal is your this colored part of the flower, and the sepal is basically your green part here, right? So it is talking about what is the sepal length, sepal width, and petal width of each of the species, whether it is setosa, virginica, or versicolor. And we will see whether we can use KNN to actually classify these flowers into the data points into these categories of flowers. So let's do some quick, see that this pair plot actually just plots the sepal length, sepal width, and the petal length, petal width of each of the samples of Setosa, versicolor, and virginica. And we see that the green dots, which are the Setosa flower, is actually quite separable from the others. It's when you plot, let's say, for example, sepal length and petal length, right? We see that this is quite separate from the other data points. So let's see whether we can actually be able to classify it using KNN or not. And here we are running a kernel density estimation function on the Setosa flower to check what kind of distribution it has. So this is the kernel density estimation plot using the SNS package. So only for the Setosa flower. So if we plot the sepal length and sepal width, we get something distribution like this. So essentially we see that the maximum centered around here, and then there is a distribution, as you can see here. So there's some kind of a linear relationship here. Okay, so now we will again do the same standardization of the variables that we had done in the cancer dataset case. So we are importing the standard scalar function from the scikit-learn pre-processing. So we will initialize that. So we are again basically doing the standardization or normalization of the data. And we will do the standardization on everything except the species, which is a categorical value, right? So it's categorical whether it is which kind of flower it is. So we have removed that, and then we have done the standardization or normalization on rest of the data. So we now convert this into a data frame, a pandas data frame. And if we look at the top 5 rows, now it's all converted or transformed. So the values are now normally distributed basically. Okay, so now we divide the data again into train and test. And we again have a training of about 70% and test data set of about 30%. So we are dividing that entire data set into these 2 buckets. And we will now use KNN to see if we can use KNN to classify them. Again, the same n k is equal to 1. And we will check the results, and then we will do a trial and error to check what is the best value of k. So here k is equal to 1. And now we are going to predict on the test data set and look at the results. So we are now importing the classification report and the confusion matrix. So if we look at the confusion matrix, we see that kind of already we are getting quite good prediction. So just 2 misclassified points. And if we look at the accuracy, we see that the accuracy is quite high, around 96% already. Now we have to see what is the best value of k. So essentially we will again run k is equal to 1 to 40 and check which is the best value. So let's plot the errors when we vary the k from 1 to 40. And we see that actually the error decreases and then increases. So basically the error is minimum with k is equal to, let's say, 3 or even 5 or maybe 11. So let's choose one of these values. So let's say k is equal to 3. And let's see how the results look like. Does it improve the accuracy or not? So we now see that even the 2 data points which are misclassified earlier is now classified properly. So the accuracy improves to 100%. So that's the example of how you can choose k.
What is naive Bayes? Let us understand naive Bayes with an example. Here, I just cannot seem to figure out which are the best days to play football with my friend. Can you please help us out? All possible conditions are given to us. There is summer, monsoon, and winter, which is nothing but the outlook. Am I correct in saying that? Summer, monsoon, and winter is nothing but the outlook. Then we have sunny or not sunny. So that basically is the humidity, right? And then we have windy or no windy. That speaks about the winds. How are the winds, right? So if you look at these combinations, Okay, we will look at this using navy bars on how do we decide whether we can play or not. So if I have noted down all the days it was good, bad to play football and the combination of weather matrices on that day, that will be perfect, right? That is perfect, and we will be able to do navy Bayes classifiers using that. Now, navy Bayes classifier comes from the navy Bayes theorem, and navy Bayes theorem is purely and purely based on the assumption of independence. So what does it mean? When I say independence, what it means is that this variable has no relationship, no association with this variable. Now, when I talk about this in a linear context, obviously in summer, you will see that we have more sunny days. Yes. So if you look at it from the correlation area, from the linear algebra concepts, linearly, these two are correlated to each other. Am I correct in saying that? Obviously, in monsoon, we have less sunny days. In winter, we further have less sunny days. Yeah. So, although there is a relation, Navy Bayes' theorem says that all these variables are independent of each other. What does that mean? If this is causing any kind of an effect, if this is causing any kind of an impact, this should not matter. Okay, there is going to be no relationship. Summer, monsoon, winter, it has its own weightage. Okay, and it has nothing to do with the other conditions. Every condition is equally significant. All right. So what happens in navy Bayes is we estimate the posterior probability of every event happening. Here we calculate the posterior probability of an event happening. Okay. So here if you see, if you look at the sunny conditions, what we have done, sunny conditions, we have this distribution that there is no play happening in summer, there is play happening in monsoon, there is play happening in winter, right? So based of the season, we are figuring that out. Similarly, for windy conditions, we are doing that, right? Again, then we do it for a combination, right? Whether when windy conditions are yes and no, what happens to play? Okay. So here, what at the end of the day, what gets selected is the one which has a posterior probability of greater than 5. Now, when I talk about posterior probability, what do I mean by posterior probability? Let me have a blank slide. Here you go. Actually, it's given, so I need not show you that. What is the simplistic probabilistic classifier here? What is the probability of an event A happening given B? So if you look at our problem context, what is it that we are trying to figure out? We are trying to figure out what is the probability of play happening given the outlook is sunny, comma, the winds are normal and there is no rain. On any given day, when there is no rain, there is no wind, and the outlook is sunny, whether play will happen or not. So what we end up doing is we calculate the posterior probability of play happening given these conditions. We also calculate the posterior probability of play not happening given these conditions, and then we normalize these probabilities. Mathematically, we do all of these calculations to figure out navy Bayes. Okay. Now here, see, here we are talking about one event. Here we have three events. We have outlook, we have winds, and we have rains. So what this becomes is probability of three independent events. So what we will do, we figure out what is the probability of play happening given outlook is sunny, we also figure out what is the probability of play happening, multiply this with the probability of wind as no, given no, then probability of play happening given rain is no. We figure out all the three independent probabilities, multiply it. All right, this is what we do mathematically. This is what is done mathematically in Navy Bayes theorem. Ultimately, the posterior probability probability of an event A happening given B conditions is calculated by first calculating the class probability. What is the class probability here? Probability of it raining given play was happening in that day. This is multiplied by the total probability of play happening and divided by the total probability of sunny conditions. Here, as you see, this is the posterior probability. This is the class probability. Here is the predictor's probability. This is the outlook. X is the outlook. C is what we are trying to predict, right? And here is the likelihood. So how is this formulated into our table? Now, if you correlate this to our graph, what will be the likelihood? What will be the likelihood of sunny conditions given play happens? Sunny conditions, play happens. 2 divided by 3 out of, sorry, how many sunny conditions do we have? 6 conditions. In 6 conditions, how many days does play happen? 2 days. 2 by 6, 1 by 3. What is the class probability? So of all the events that are given to us, how many days does play happen? Okay, this is how this is calculated. So here you see what we have done is, let me go back to the previous slide. Here you go. Okay, here what we have done is we have calculated this table. Now it speaks about a data set. Where can you get this data set? You can look for golf play days data set online. You can look for golf play days data set. Okay, in this data set you will find all the data which is required for this particular example to be done. So what I will be doing is I will be doing this example, this Navy Bayes classification with you in Python. All right, so whatever calculations are being done here, okay, I will do the same activity in Python with pen and paper, and instead of doing this in a numeric way where I'm doing a lot of probabilistic calculations, I will achieve this simply in very limited lines of code, with Python. Once I have done that, I will come and explain this probability table to all of us. I'm going to use some basic libraries. All right, so here what I will be doing is using some very basic libraries for this activity. All right, done. Now let me quickly go and read the data set. So for that, what I will do is quickly change my working directory. And now let me quickly go and read my data. So my data frame is pd dot. Here you go. This is my data set, right? So if you look at this data set, in this data set, you have 14 days. In these 14 days, you have the outlook, overcast, rainy and sunny. You have temperature. Temperature is hot, cool and mild. You have humidity. You have wind and you have play, right? So I will not be using, okay, let us use all four. In this example, they are using only 3 variables, but in our hands-on, okay, in this hands-on, what I will be doing is I will be using all 4 variables. Let us do that. Okay, so before I do that, let me convert everything into a category. If you look at your data frame right now, it's not, everything is not into a categorical variable. Here you go, see. Okay, so let me quickly go and convert everything into a category. And once I have done this, let me create a new data frame in which I have everything as a category code, so that I have numbers. I'll show you what do I mean by this. So let me execute this. Here you go. See, now I have 2 data frames. In the first data frame, I have all these values. These are now categorical variables. But in the second data frame, I have all ones and zeros. So wherever you see there is sunny conditions, now I have a code 2. Rainy conditions, code 1. Similarly, when play happens, I have a 1. When play does not happen, I have a 0. This is what I have done. This data frame is available online. Okay, you can get this data frame online. All right, now my data frame is ready. So now what I'm going to do is I'm going to divide my data frame into training and testing. I have 14 records. So let's take 10 records for training. I will give 10 records as an input, and I will give 4 records, last 4 records, as my test data frame. All right. So now I will need to create my X and my Y. So how I will do that is I'll say Y underscore train is equal to, from train, I don't want the play variable. That play variable should be my Y. As simple as that. And I will say X underscore train is equal to train. Okay, and I will do the same thing for my test data frame also. Now, those who are new to Python will find this a little bit strange. Please bear with me. But these are the only calculations, only steps which need to be performed every time you are trying to achieve Navy bias algorithm or any kind of an algorithm. Right? So here, now you see, this is my training data frame in which play variable is not there. Play variable is not there. This is my Y, in which only play variable is there. This is my training data set. So both of them have 10 records with the matching index. Similarly, test data frame, 4 records with the matching index, right? So that we know which data frame is where. Now, multinomial Navy bias. Very simple, 3 lines of code and my model will be done. Okay, first I initialize my model. Here you go, I have initialized my model. In this model, I fit my data. In this model, I will fit my data. So to do that, what I say is fit x underscore train comma y underscore train. Done. Your model object is now ready. And now you can simply get the classification outcomes. So we have in our test data frame, if you look at our test data frame, this is our test data frame. We have four conditions. All four are sunny, high temperature, low humidity, and windy, right? And if you look at their outcomes, these are their outcomes. On the first 2 days, play is not happening. On the next 2 days, play is happening. Let us look at what is the prediction of our model for this. So to do that, what I simply do is x out is equal to model.predict. To this, I give my x underscore test. Here you go. Okay. Now you have your y out variable. So this is the prediction for all the four inputs that you give, and this is the prediction. First day, we say play does not happen. Let us match it. Let us try to match it with our here. See, out of 4 records, 3 records we are predicting correctly. 3 records we are predicting correctly. If you want to check the accuracy, what is the accuracy of your model? What you can simply do is print. Let us print the accuracy on both training and testing. Training accuracy. How do I get the training accuracy? Very simple. Model.score, and here I give my x underscore train comma y underscore train, and then we do the testing accuracy also. To calculate the probabilistic scores. So what is the probability of summer given it is playing conditions? Total, how many playing conditions are there? Total, there are 9 playing conditions. 9 days play happened. That becomes our denominator. Out of those days, how many days was summer is our numerator. That is how for this we get a probability of 0.33. Then we calculate the class probability where we look at how many days was it summer. Out of total 14 days, 5 days was summer, so that's the probability, and the class probability is 0.64. Put everything into our equation, and this is what we get. Okay, so we do this for each and every condition. So here we calculated for winter. All right, once we have done it for all 3 days, winter, sunny and windy days, we substitute those here, and that gives us the probability which is more than 0.5. Thus now we can say that if it is winter, sunny, and conditions are sunny and there are winds, conditions are not sunny and there are winds, play can happen. Look at another example. If a single card is drawn from a standard deck of playing cards, the probability that card is a king is 4/52, since there are 4 kings in a standard deck. King is the event. This card is a king. This is the event. The prior probability of this is 1/13. If evidence is provided, for instance, someone looks at the card, that the single card is a face card, then the posterior probability can be calculated using bias theory. Okay, since every king is also a face card, the probability of face happening given you getting a face card given it's a king is 1. Since there are 3 face cards in each suit, all right, it's actually 4. Ace is also a face card, so it's jack, queen, queen, and ace. The probability of the face card is 4/13. Okay, so if you combine these 3 likelihoods, what you get is 13/4. So using bias theorem, this is the probability that you get.
What is support vector machine? support vector machine comes under supervised machine learning, and we use it specifically for performing the task of classification. So support vector machine is a discriminative classifier that is formally designed by a separate hyperplane. Okay, it is a representation of examples as points in a space that are mapped so that the points of different categories are separated by a gap as wide as possible. So in this case of this support vector machine, let's say I have some data points. So there are some data points of X and there are data points of circle. Now this support vector machine is a type of machine learning algorithm where if I have the collection of points, so here in this data points, I have two classes. One is X and the another one is circle. Now, given this kind of data points, okay, given this kind of binary classification problem, so the expectation is, in case of support vector machine, I'm going to draw a hyperplane which separates as much as possible. Okay, so I'm going to draw a hyperplane which separates these two classes as much as possible. So it says that I'm going to draw a hyperplane and it will be separated by a gap as wide as possible. So that is the intuition behind support vector machine. Okay, now that you have an intuition behind what is support vector machine, let's understand as how does this SVM, that is support vector machine, would work. So in case of support vector machine, so here there is one more example. I have the set of points which is green color, and I have another set of points which are in red color. So these two points are belonging to the different classes. Now what I'm going to do is I'm going to draw a hyperplane which separates these two classes data points as much as possible. And when I'm drawing the hyperplane, I'll make sure that this hyperplane is equidistant from my support vectors. Now the support vectors is nothing but the point which is closer to my hyperplane. Now here in this example that you're seeing, this data point and this data point are called as support vectors because these are the data points which are nearest from my hyperplane that I've just drawn. If I am trying to make use of this SVM model, it is going to draw this kind of hyperplane to make sure that it is separating two classes. The two classes that we have over here in this example is red and green. It's going to separate these two classes as much as possible, and it will be equidistant from my support vectors, and the support vectors are nothing but the nearest point to my hyperplane. And that is how I'm going to separate between two classes when it comes to support vector machines. Now here in this example that you're currently seeing, the hyperplane that I've just drawn, so this is a simple linear hyperplane. This is like a straight line that I'm trying to draw if I want to separate two classes of data points. Now, apart from drawing this straight line, we also have other kind of lines as well, which we can draw. So let's see how we can do that. So the types of line that we can draw, or the hyperplane that we can draw, is called as SVM kernels, that is support vector machine kernels. The example that we have seen, it's an example for linear SVM kernels. So let's see what are the other types of kernels that we have. So when it comes to SVM kernels, we have linear kernels, radial basis function kernel, and along with that, we also have polynomial kernel. Now, in case of linear kernel, I'm going to draw a hyperplane which is like a straight line. In case of polynomial kernel, I can draw my hyperplane on the basis of polynomial function that I have created, on the basis of number of variables that I have, and the degree that I have over there in case of polynomial. And in case of radial basis function, so I'll make use of radial basis to separate my data points. Okay, so these three are the important kernels that we have in SVM, and this is one of the commonly asked interview question when it comes to the topic of support vector machines. Now, let's look at some of the use cases or the way we can use this SVM to work, or let's look at some of the use cases where we can use this SVM. Okay, so we can use this SVM on many of the use cases. So to name a few, we can use it in face detection. We can use it in text and hypertext categorization. We can use the SVM if I'm trying to classify any images. I can make use in bioinformatics. And if I'm trying to detect something, so I can, in an example here, remote homology detection, handwriting detection, or in general, we can make use of this generalized predictive control. So wherever we are dealing with the task of classification, we can use this SVM model. Okay, now that we have a theoretical understanding as what is SVM and how it is actually going to look like and how it will be, let's have a quick walkthrough as how we can implement this SVM. Now, to implement this SVM, these are the common steps that we are going to follow. We are going to load the data, we'll explore the data, and once we have explored the data, we are going to split the data into two parts. The reason is simple. When I have training, so I'll be making use of my training data, and once my training is complete, I'll check how my model has been trained with the help of my test data. So I'm going to split the data. Now once that is complete, we are going to train this SVM model, and finally we can evaluate the model and observe as how model is working. So this is the overview of the implementation of support vector machines. So let's do one thing. Let's work it out and let's create the notebook in Google Colab and let's see it in action as how we can implement this SVM. I'll come back to my Google Colab. So this is the notebook that I have already prepared, and I'll give you a walkthrough as we proceed along. Now here in my first cell, I'm importing my NumPy library, pandas library, and along with that, for creation of plots, I'm importing my matplotlib library. Now if you are comfortable with Seaborn, you can use the Seaborn library as well. So in my example, I'm just making use of matplotlib because we are not interested in creation of visualization, but we want to understand as how a model is being working. Okay, and I'm going to execute this cell. So this is going to take care of necessary imports. I'm importing my necessary libraries. And once that is done, here I'm importing this SVM. So this SVM model is available inside my sklearn library. So I've mentioned as sklearn.svm, and from sklearn.svm, I'm importing my SVC. Okay, so I'm importing my SVC. So I'll show you what is this SVC. SVM SVC. So it's C means support vector classification. Okay, now here when I'm instantiating this SVC, I can mention what is the kernel that I want to use, and if I'm working with any polynomial kernel, then I can also mention what is the degree of polynomial that I want to use while performing the fit for my data set. So I'm importing my SVC, and along with that, I'm also importing the data sets. So in the sklearn library itself, we have a data set. So sklearn host already, like it actually, sklearn has many toy data set which will actually help us in our learning journey. So we are going to use one of the data set, the famous iris data set. We use that for multi-class classification. So I'm going to load that iris data set, and I'm just going to extract only two features. So the two features that I'm extracting is petal length and petal width, because I don't want to complicate it. I just want to visualize the data. So in order to help in visualization, a data set which is in multi-class classification, I'm just going to convert it into a binary classification task. You'll get a better understanding once I execute this next cell. So this is going to prepare my data set, and once the data set is prepared, if I create a scatter plot, so I'm just creating the scatter plot to show us what and how my data set looks like. So this is how my data set looks like. On my x-axis, I think I'm having petal length. On my y-axis, I'm having petal width. And here, the blue points refers to the class 0, and the orange points refers to the class of 1. Okay, so this is how my data set looks like. You can clearly see that I have one set of points in one region and I have another set of points in another region. Now this is a classic example to understand about the SVM. How does it draw a hyperplane? So we have the data set ready, and as I mentioned already, in order to fit this model, so when I say support vector machine, I'm going to draw a line. This line that I have drawn, it will be equidistant from my support vectors. Now here in this example, the support vector is this because this is the only point which is nearest to my line. And here I think this is the data point which is nearest to my SVM line, that is this fisted line, hyperplane line. So I'll be placing this hyperplane such that it is equidistant from the support vectors. That is how I'll be drawing this support vector line. So we now have an intuition. Let's see whether we get the same outcome as we are expecting. So here I'm initializing my model. So for initialization, I'm saying it as SVC. Use the kernel as linear because I'm able to draw a line effectively. We just seen, and I'm using the C as infinity. That means it should be a hard classifier. So hard classifier means I want the 100% result. I mean, I don't want any loose ends. I want to draw a line which clearly separates two classes. So I'm saying it as C as infinity to mention this as a hard classifier. And once I initialize any model, here in this scenario SVM model, I am performing the fit on my data set. Now this is the common flow that we follow whenever we are performing the fit. So we'll initialize the model and then we perform the fit on a data set. Now since this SVM being a supervised machine learning model, I have to specify both my input X as well as my output Y. Hence SVM classifier.fit X, Y. So this is going to perform the fit for my data set. I'll just execute this. So this has performed the fit, and here it is giving me the confirmation as this is the parameter that are being used to perform the fit. Okay, now once I have drawn and once I have found this fit, next if I want to display the weight terms, so I can say it as SVM classifier dot coefficients. So these are the weight terms. And if I want to display my bias term or the intercept, it is minus 3.78. Now this means the line that I have just drawn, so that line has the C term as, or the W0 term as minus 3.78, and W1, W2 are 1.29 and 0.82 respectively. So that's how the data is distributed for us. That's how the values has been found for our scenario. Next, in order to get the better visualization, here I have created a function that is called as plot SVC decision boundary, and this takes my SVM model, the Xmin and the Xmax. Now W and B I'm extracting from the coefficient and the intercept parameter that we have over here. So we are extracting from this attributes that we have from this model. And now if I want to draw a decision boundary, so I need the set of points. So in order to get the points, I'm saying it as x0 is equal to nb dot linspace xmax comma xmin comma xmax comma 200, and I'm specifying as how does my decision boundary should look like. My decision boundary is given by w0 into x0 plus w1 into x1 plus b is equal to 0. So this is what my decision boundary would look like. So I know what is x0, I know w0, I also have w1, and I also have b. So the only term that I do not have is my x1. Okay, so the only term that I do not have over here in this example is x1, and the x1 if I want it, so I just have to substitute it. So x1 is equal to minus w0 divided by w1 into x0 minus b divided by w1. Now I'm specifying the same equation over here for my x2. So my x0 and the decision boundary will give me the pair of input and output. Okay, now along with this, there is a property in SVM Okay, so the property is given by whenever I have a margin, so that margin is given by 1 over W1. Okay, so the margin is nothing but the distance between my hyperplane and the support vector. So that is given by 1 by W1. Hence, I have mentioned as gutter up and down. Gutter up means one line or the one line where the support vector lies. So that is given by decision boundary plus margin, and one line below my below my hyperplane, that is where another support vector would lie. So I have mentioned as decision boundary minus margin. Okay, then I'm defining where exactly my support vectors are present. My support vectors, I can access the support vector coordinates by saying it as by accessing the attribute of my train model support underscore vectors underscore. Now I'm specifying where exactly those support vectors are present with the help of a simple scatter plot by highlighting my support vectors, and I'm specifying where exactly my decision boundary is present, and I'm also mentioning where is my line that is gutter up and gutter down. So let's do one thing. I'll just execute this. This is going to create me a function. I'm going to call my function support vector machine classification, and I will specify my range of x and y as here, yeah, x min and x max as 0, 5.5. I'll just execute this. So what we have done just now is we have created this hyperplane. So the middle one, the solid line that you're seeing over here, so this solid line is called as your hyperplane. And these points that you're seeing over here, so these 2 points which are highlighted, these 2 points are actually called as support vectors. Okay, so this dotted line that you're seeing, so this dotted line refers to my gutter up and gutter down, which I've found right here. Let's do one thing. I'll add some labels so that you'll get some more visualization in the plot itself. I'll say label, and I'll mention it as hyperplane. Okay, and there is one more, yeah. These are support vectors, and I'll say pld.legend. So this clearly says which are all my hyperplane and which are all my support vectors. So this is the intuition behind support vector machines. So we'll be drawing a hyperplane which separates the points that we have. Okay, and whichever the point which is nearest to my hyperplane, we call that point as a support vector. Now to access that support vector, we make use of the attribute. So let's do one thing. Let's explore the attributes svm dot support underscore vectors underscore. So this is going to tell me where exactly my support vectors are present. So one point is given by 1.9.0.4. I think this is the point that I'm talking about. And the another support vector that we have is at the location 3, 1.1. So 3 and 1.1. This is where we have another support vector. So using all these attributes, we have been able to create this visualization. Okay. Now, whenever we are working with the support vector machines, it's very important that we scale the data first. If I do not scale the data, I'll not be able to get a better fit of my SVM model. So here I've given one more example where I have my X is given as 1, 50, 5, 20, 3, 80. As you can clearly see, it's not scaled. Okay. So I'm going to execute this cell. So this is going to tell me and give me a visualization as how the fit will be in case of scaled and unscaled. See, if it is unscaled, if it is not scaled, okay, that means if it is unscaled, we can clearly see that the hyperplane that I'm drawing and the distance from my hyperplane, it's very close to each other. And whenever I'm working, it will be difficult for me to separate those two data points. But if I scale them correctly, now here for scaling, I have made use of a scalar and standard scalar. Now, if I scale it correctly, then in that scenario, it will be easier for me and it would actually work better when I have scaled data. Okay, so this is about using the linear SVM model to perform the fit on my given data set. Now, if I go below, we have some more examples about nonlinear classifiers as well. Now, in order to test out the same, here I'm creating an example dataset, and that dataset that I'm generating is called as make moons dataset, and this has been generated with the help of a sklearn dataset generator. Now, as you can clearly see, I cannot make use of linear classifier. So linear classifier is nothing but a classifier, okay, which is an SVM model where I'm drawing or where I'm using a straight line to split my data points. I can clearly see that wherever I join or wherever I try to draw a line over here, I cannot split the data in an effective manner. Now this brings us the challenge. Now if I have a data set in this way where I cannot linearly separate it, how can we go about and perform the fit on our SVM model? So in order to save us, we have a model that is called as SVM model, and from that SVM model, we can actually create a polynomial kernel. So we can make use of polynomial kernel, and using that polynomial kernel, I can actually create it like this. I mean, using polynomial kernel, I can perform polynomial regression, or I can draw a line like this. Now to show you how it works, I'm getting some data like this. So this is some random data, and I'm making use of pipeline. So this pipeline is going to take care of my standard scalar as well as kernel. I'll do one thing, I'll just come below. So this is what we are currently interested in. So here I'm importing the polynomial features and I'm generating the polynomial features for my data. I'm performing the fit and transform my polynomial data. That means I'm just modifying my existing data and I am sending it for my x. Okay, so this is how my pair of input x and y looks like. Now I'll use my x. I'm going to transform it with the help of my polynomial features, and then I'm going to scale it with the help of my standard scalar, and I'm going to send it inside my classifier, that is SVM classifier. Okay, so I'm going to combine it together like this. Now observe what would happen. Now once that is complete, see, with the help of my uh, polynomial features that have applied on my given linear data, so I have increased the degrees by which my model can learn. Now instead of straight line, my model is also having the ability to learn this complex representation as well, because I have increased the model complexity by adding my polynomial features. And while doing it, to make sure that we follow a clear path, so I have defined this sklearn pipeline. So if you're new to data science machine learning, I highly recommend you to learn this concept of sklearn pipeline. Now this sklearn pipeline helps us to combine multiple operations in a single call. So here we have created a pipeline. This pipeline is going to add some polynomial features for my input data, and on top of it, this is going to perform scaling, and then I'm going to perform this binomial classification using this SVM. And finally, I'm performing the fit on my data set. See, when I perform the fit, it takes my input X and it's going to do all these activities. It is going to chain all these activities together, and then it is going to perform the fit for my data Y. Once the fit has been complete, so we can validate how my model is performing.
So what is a clustering technique? Clustering technique is something that we will use it for grouping purpose. So especially there is a very easy way to understand what is clustering technique. You would have seen such while we are going through an COVID-19 situation, the government has came up with creating some containment zones, as all of you must be knowing. So how, on what criteria government has taken that, okay, which area is supposed to be a containment zone, or which area is supposed to be applied with some restrictions, or which areas can be considered as normal, on what criteria that they have created. So that's what using clustering technique, which means the governments, or when I say government, means that the people who will be taking the final decision in such criteria, either prime minister, either the chief ministers of that particular state will be taking decisions whether to go for a lockdown, whether to not to go for lockdown, or which areas has to be considered as containment zones or non-containment zones. So those high-level decisions are something which will be taken based on the clustering technique output which is generated by these algorithms, based on a number of inputs. Okay, what is the population in a particular area? How many number of people are affected? How many number of hospitals which are present? How many number of people who are been recovered? So likewise, based on these multiple criteria, people will do some clustering technique on top of the data, and according to that, people will be segregated, or the areas will be segregated. So that saying that, okay, these are the observations which belong to one cluster, these are the observations which belong to one cluster, like that, so that people can cluster them, which can make organizations to take decisions on a very high level. Okay, that's what is our clustering technique, which clustering technique output will contain the different groups. It itself will group the different components based on whatever the number of clusters that you want to generate. That may not give the direct output. On top of the generated output, people will be taking business related decisions. That's what is all about clustering techniques. Okay, so now what we will do, let's take an example of within clustering techniques, what are the different types of clustering techniques we have. So what are the different types of clustering that we have? So there are multiple types of ways based on the type of output that we want to produce. There are multiple different types of clustering techniques we have, but out of which let's try to understand about what are the very famous and most widely used clustering technique algorithm, out of which we have something called K-means clustering algorithm is one of the very famous and most widely used. More than 90% of the people will end up with using K-means clustering algorithm, which is very famous in clustering techniques, right? Which is very famous in clustering techniques. So what are these clustering techniques? As I said, how this clustering technique will work. So K-means clustering is nothing but, always remember one thing, if any one of you are going to work in machine learning or anywhere, wherever you see a notation called K, by default K is nothing but you are supposed to, as a user, you are supposed to provide what is the input of K, which means wherever you see, there are multiple techniques that we have in machine learning, like K-means clustering technique, K nearest neighbor is one of the algorithm, K-fold cross validation. Likewise, wherever you see a notation called K, what does a K means? It's an input that you are supposed to provide. Always remember this. It's an input that you are supposed to provide to your algorithm. Your algorithm cannot identify that K value. Of course, everything else will be taken care by your algorithm. But whenever you see K, which means in K-means clustering, what is the meaning of K-means clustering? How many number of clusters that you want to provide? That is something that you have to input it to your algorithm. That is something that you have to input to your algorithm, right? Here, the meaning of K is how many clusters that you want to generate. So how many clusters that you want to generate? Okay, when you have 1,000 observations which are present, when you have 1,000 input records which are present in your historical data, how many number of clusters that you want to produce? Do you want to go for one cluster? Obviously, one cluster means that the entire data set will be considered as is. Do you want to create 2 clusters out of the data? Do you want to create 3 clusters out of the data, 4 clusters, 5 clusters, or 10 clusters? So how this can be done? There are multiple steps that are involved in generating K-means clustering algorithm. So you can see, choose the number of clusters. This is what is nothing but your first step. It means you need to decide what is your K is nothing but number of clusters that you want to produce. And then there is an initialization of centroids will happen as a one-time activity. right? So there is an initialization of centroids which will be declared, that will be used as your initial step for your machine, and then assign the clusters, move the centroids, and optimization, and then converge all the clusters into one component. Yes, I know it will be very difficult to understand by looking at this thing. So let me show you a very simple example how exactly it will be done. Maybe let me take a simple diagram for you to show how exactly that's going to work. Okay, so let's say, for example, I'm going to take some historical data just to explain you on how exactly the k-means clustering algorithm will work. So what is that it is written in the first step? What is that it is written in the first step? So the choose number of clusters. Choose number of clusters. Now, which means, say for example, we need to take some historical data. I'm considering some historical data here. Let's assume this is the historical data. Let's assume this is the historical data that we have. So as you can see, there are multiple historical data points. So as you can see, the first step, choose number of clusters, which means, let's assume, to make this thing simple, I'm going to choose that we want to have 2 clusters generated. Okay, so this is, which means we want to have 2 clusters created. So because my number of clusters that I want to generate is 2, I'm going to consider that there are 2 centroids which are present. This is my first step. How this algorithm will do? How algorithm will come with the number of clusters? So this is how it will happen. So first step is to choose the number of centroid and then initialize your centroid. That's the second step. So now what is the third step? Let's assume this is observation number 1. This is our data point 1. So now what is the next step? We will take the distance from every observation to every centroid and every observation to every centroid, which means, now tell me which observation, for this observation number 1, which centroid is more closer? Is the green color centroid is more closer, or the red color centroid is more closer for this? Centroid means that data points, the one which I have highlighted, that's what we call a centroid, data points. We have chosen 2 centroids only because that is as a user you are supposed to input what's supposed to be your k. What's supposed to be your k value, that's what I said. You need to know what is your k, is nothing but how many number of clusters that you want to provide. Usually your business users are going to provide that. In case if you are going to work in this kind of algorithms, they will provide that. Or else there are some methods available like elbow method or other things. We will talk about that. Now this observation is more closer to red color. So now what happens? What is the next step? The algorithm will assign this particular observation 1 as a red color for now, as considering that this belongs to red color. Likewise for the second observation, when the second observation appears, what is the distance from the second observation to both the centroids? Now which one is more closer? I see green color is more closer. So now I'll mark this as green color. If the distance is same equal, so then the algorithm will force any of the observation to get into any of the centroid. So number of clusters, number of centroids that you will choose based on the k value, as I said. Now you're going to likewise you will repeat the same process, and whatever the observation which is more closer to whatever the centroid it is, you will mark them as with their so-called mark like this. Now you are going to initially mark them as observations into either into green color, either into red color. So now these observations are now considered as green color observations, and these observations are now considered as red color observations. This is step number 1. What is the step number 2? Step number 2 is segregate all these red color observations and take the average value of x and y coordinates, and repeat the same process for calculating average coordinates of x and y coordinates for the green color observations. Take the average of all these observations, calculate average, and take all these observations, take the average. You'll end up with getting a new centroid positions called xy, which means now you ended up with getting a new centroids. In the initial step that we have taken random centroid, now you got the centroids that you can use based on the previous iteration. Now you ended up with getting a new centroids. You repeat the same process again you repeat the same process. Take the distance from every observation to every centroid and assign the observation based on the nearest distance, and continue to mark every observation either into red color or either green color or whatever it is, and you repeat the process until you will be able to see there will be no change applicable for your clusters. You repeat the process, which means in every step you might end up with changing your centroid. Every step will continue to change your centroid. Now the centroid might become like this, then later your centroid will become like this. Likewise your centroids will be keep on moving. Initially you are taken it like this, but it might continue to move like this. Somewhere it will be fixed, and after that there will be no change that you will notice if you are repeating the same process. At this particular stage, whatever the observations which are marked into, which are grouped into green color, you will say like these are the green color observations. whatever the observations which are marked into red color, you will mark them as, okay, these are the observations which belong to red color. These are the observations which belong to red color. Likewise, you will segregate all these observations either into red color or green color, right? So that's how we can generate these clustering technique. That's how the K-means clustering algorithm will generate these algorithms, output of using this algorithm. Okay, so that's how K-means clustering algorithm will work. Okay. So now, likewise, there are multiple algorithms that we have. So, like when we talk about machine learning, so there are multiple types of algorithms that we have. So, like how we have the how does the k value will occur, as you can see on the PPTs, which are also mentioned. So, you're going to choose some randomly generated k value, and you will be choosing the number of k's over here, and you can see that it will assign them based on the number of this easy most nearest distances, and according to that, you will change your centroids. Once you change your centroids, you will repeat the same process until you are able to change that your centroids don't move further, and then once it has been finalized, you will say like this is the final centroid and final cluster output that we can generate out of this, right? So likewise, we also have different types of clustering technique, and the second type of clustering technique that we have is fuzzy or C-means clustering. So what is fuzzy or C-means clustering? The output will remain same. So C-means clustering means that there are places that one or two observations can belong to one or two different clusters, right? One or two different clusters, which means usually the primary difference between your C-means and K-means clustering technique is, in case if there are any observations which are having equal amount of distance, usually in K-means clustering, what we will do, we will force this observation to be part of any of the cluster. But in C-means clustering, based on the distance that we see, there are chances that an observation can go to or can belong to one or two clusters. So it purely depends on the business use case, who is going to decide to either to go for K-means clustering or C-means clustering based on the business use case, based on our business outcome. So if people are going to decide whether to go for C-means clustering or K-means clustering. So there are a number of observations which might, it's not mandatory, which might can belong to one or more clusters that can happen. So the third is agglomerated clustering. So which is the third type of clustering technique that we have. Okay, so which is also one of the clustering technique that we have. Okay, so now which can also be used here. Okay, so now what is this agglomerative clustering? So this is what we also call it as hierarchical clustering. So in times you'll also call them as hierarchical clustering. These clustering techniques are built using H clustering. In short, we call it as H clustering, and also people will also call it as hierarchical clustering technique. So what are this? So based on the type of algorithm, they will try to, there is a mathematical expressions which are involved in it, but considering that the limited time that we have, I'm not going to take you through all the in detailed depth of it. So considering the way how the data points have been segregated, it will build a kind of dendrogram. So on top of this dendrogram, your observations can be classified here like this, as you could see on the screen. Is K-means clustering sensitive to outlier? You need to understand one thing. When we are talking about unsupervised learning algorithms, as I said, you may or may not have clarity on the data, which means your assumption is that at the least level, you don't have clarity on the data. Then if you don't, when you don't have clarity on the data, how can you say this is an outlier or this is not an outlier? When you have clarity on the data, especially when you're working on supervised learning algorithms, you can, but you don't have output column also. How you will be able to evaluate how the so called output column can be evaluated, because this is not been classified properly, this is not been clustered properly based on the historical data, because there is no output column. So those type of concepts are something which you don't need to worry about when you are working on unsupervised learning. They will be constrained when you are working on supervised learning algorithms. And of course, in case if you see that there are outliers which are present, obviously it will be considered as one of the clustering any of the cluster it belongs to the data. But anyhow, that's the characteristic of the data. You don't need to, you don't be taking care, because you might be killing the actual original values which are present in the data, but you cannot expect that outlier can be recognized for all the cases that you have in unsupervised learning. So the next type of clustering technique that we have is division clustering. So what is this division clustering? As the division clustering is also creates the data in a form of dendrogram, but the difference is you can see that it starts with all data points in one cluster, splits the root into child recursively based on the dendrogram, and stops when there is a singleton clusters which are created, which means that for every cluster there will be one observation which belongs to. So likewise, the clustering technique will work. Now there is one more technique that we have in terms of building a clustering technique. That's what we call the mean shift clustering. So what we will do, we'll take an average of every cluster that we have. What we will do, we'll end up with reducing their means into into a single density of items, and then we'll continue to repeat the process to see to that which observations mean will belong to the same cluster, and according to that we'll continue to identify which observation will belong to a cluster, a particular cluster. So likewise, we can apply different types of clustering technique that can help us to cluster the data which is part of unsupervised learning, right? So now let's jump into something called a small hands-on. Okay, let's take a small Python example, and we will see how do we build that particular clustering technique on top of the data using one of the simple data that we have. Jupyter Notebook. Let me open how we can use scikit-learn using one of the example. So meanwhile, let me show you some of the data set also. Let me show you a data set that I'm going to use as well. So what I'm going to do is I'm going to take this movie metadata information. Let me open this data set. I'm going to take this example of movie metadata information where this data set has got a number of observations which are present. Okay, let me open this. Okay, you can see that there are a number of movies related information. As you can see, the movie names. So Avatar, Pirates of the Caribbean, Spectre, The Dark Knight, Star Wars, etc., etc., John Carter, Spider-Man 3, Tangled, or etc., etc. We have a lot of movies. And about every movie, we got a lot of information which is present, like who is the director, who is the actor, what are the director Facebook likes, what are the actor Facebook likes. Likewise, we got a lot of information which is present as part of these particular every observation. So now what we will do, we will try to cluster these data points. You can see a lot of observations which are given. What is the gross of the movie? What is the number of reviewers? What is the IMDb rating? What is the so and so called IMDb score? What is the movie span? What is the gross? What is the budget and everything? So now what I'll be doing, I'll be reading this data set using one of the pandas library that we have. Okay, so I'll be reading this data set. Let me open the Jupyter Notebook. I'll be using something called pandas. As you can see, read.pandas.csv. I'll be reading this data set where you can see that this is the data set that I am able to read. I got a number of observations that are present. I can see that director Facebook likes and actor 3 Facebook likes. So now what is that I want to do is, instead of building this clustering technique on top of every observation, so what I will do is I will take these columns called number of Facebook likes on director and number of actor Facebook likes versus director Facebook likes. So where I can see that if I want to select a director Facebook likes alone, I'll be able to choose this director Facebook likes alone. You can see for every movie you got the number of director Facebook likes which are present. So if there are more number of Facebook likes, what does it mean? The director is famous person, correct? Or either if there are more number of famous Facebook likes that the actor has got, which means that the person is or the actor is very famous person. So that's what you can understand. So now we can see that I'll try to extract these independent components that we're talking about. I will extract all the records in all the director Facebook likes versus actor Facebook likes, where I'm just going to form an object called new data by applying some iLocation as a filter. iLocations, ILOC stands for index location, where I can filter out what are the records that I wanted to, what are the columns that I wanted to, using this iLocation function. Now I got all the so and so called number of director Facebook likes versus actor Facebook likes which are present as part of this. Okay, so this is being loaded into an object called new data. So now what is that I'll be doing? After that, I'm importing something called sklearn k-means cluster. So this algorithm is available as part of this scikit-learn algorithm. Whatever the number of steps that we have discussed, you're not supposed to execute all these steps manually. And of course, if you want, you can also write such a program as well. But what is that we'll be doing? In scikit-learn library, there is a Python library called scikit-learn which has got most of the algorithms present, and we will be importing this k-means clustering algorithm. And for this k-means clustering, I'm providing the c is equal to number of clusters is equal to 5. So here, if you are aware of object-oriented programming using Python, you'll be able to correlate. I'm importing this k-means clustering, which is implemented as a class here, where I'm creating an object called k-means clustering by providing an input called n number of clusters is equal to 5, which means that what is the meaning of 5? I want to build 5 clusters out of this. So where once you create an object using k-means, I'm calling this method called fit method by providing new data as my independent variables. I'm calling this fit method, which means fit is a method that's going to invoke what's supposed to be the process that needs to be executed. That's going to build my clustering technique algorithm by taking number of clusters is equal to 5. So now I'm able to generate my algorithm where by looking at my model, I'll be able to extract what are the centroids that I got, final centroids, because initially you'll be taking some random centroids, but at the end you'll end up with getting a final centroid position somewhere fixed to it. That is nothing but a center point for every cluster that we got. These are the final centroid that we got. Even if I want to print what is the labels which are generated, labels is nothing but it will extract the outcome. You can see that these are the label numbers which are added here. Out of 5,000 movies, we got the labels which are added as an array. But we won't be able to see it like that. What is it I'm trying to do? I'm trying to get all the unique values present in these labels with respect to the counts. Now you can see that my data is now clustered into 5 different, all the movies are clustered into 5 different clusters. As you see, cluster number 0 has got 4,700. Most of the observations are moved into cluster number 0. 104 movies went into observation number 1. 11 movies are moved into cluster number 2. And 87 movies are moved into cluster number 3 and 67 into cluster number 4. So the data properties are being distributed, and that's how the clustering technique has divided the data into 5 clusters. Now you can see what is that I'm trying to do. I'm trying to put this into a new data of cluster, which means whatever the labels that are generated here. This is my output column. I'm going to create this into as a new column in my new data, where I'm using this LM plot that will print whatever the column that I have called director Facebook likes versus actor Facebook likes. And I'm choosing this data is equal to new data that will help me to identify what column can be considered as hue, so that I'll be printing it in a cool warm type chart. You can see that palette type is equal to cool warm type, which will help me to identify based on the cluster that you have created. Now if I print this, you can see that pretty much every observation is now categorized into individual cluster. You can see these are the movies which are now graphical representation. This is the graphical representation that we are using to see how these movies are being segregated. I can see these movies are nothing but cluster number 0. You can see there are a few more movies which are extracted over here. This is nothing but based on the color indication. This is cluster number 3. And these movies are created as a cluster number 1, cluster number 2. These movies are something which are created as cluster number 1. And these movies are created as cluster number 4. 0, 1, this is nothing but 2, cluster number 3, cluster number 3, and cluster number 4, like this. Now you can clearly see that how the K-means clustering has came up. The movies which are made by new people with new directors, new actors are making films with new directors, or new directors are making film with new actors. These are all, you will see more number of movies will fall into this category, because you will end up with getting new people into the film industry most of the cases. A lot of movies are being made with new directors with new actors. And you can see that these movies are the clusters which are being segregated very clearly. The famous actors are making films with new directors. Very famous actors are making films with new directors. And these movies are something where very famous directors are average fame directors are making films with some new actors. You can see these movies are nothing but very famous directors are making films with very new actors. You can see very famous directors are making films with very famous actors. Like Spielberg might be making a film with Tom Cruise or something like that. So likewise, you can clearly see that where instead of, if you do this activity manually, it might take a little longer time for you to segregate each and every component. But within 5 minutes, we're able to cluster this activity, right? So that's what the beauty with algorithms. You don't need to manually do this activity, where you can provide your data automatically based on the properties of the data. Your algorithm itself will build this clustering output out of the data. All right. So that's how we will be able to build a clustering technique on top of the given data. So that's what we have as part of one of the hands-on example.
What is hierarchical clustering? So hierarchical clustering, it is also known as HCA, or hierarchical cluster analysis. And this is a method of cluster analysis, as we have seen. So what happens here is that this clustering allows us to build the tree structure from data similarities, like we have built X and Y, and we have created trees, and these trees are actually known as dendrograms. So the way you represent a hierarchical cluster or hierarchical clustering is through dendrograms. So we actually drew a dendrogram. Okay. So this is how the clustering is being formed, and this is how the clusters are being made, and this is how the relationship among the clusters is being shown by a dendrogram. So based on these things, now we will go on further to understanding what is agglomerative clustering. So when this hierarchical clustering follows a bottom-up approach, this is called agglomerative clustering. And when this is following up a top-down approach, this is used in divisive clustering. So now let us understand what is agglomerative clustering. So the types of hierarchical clustering are two, that is agglomerative and divisive. So now moving on further, what is agglomerative clustering? So agglomerative hierarchical clustering, this is also known as AGNES, which means agglomerative nesting hierarchical clustering, and it follows a bottom-up approach, which means that clustering or clusters, they are formed from the bottom and are again clustered till a complete single cluster is formed. And what happens then is that the clustering continues until we obtain a single cluster, and we will see how we obtain a single cluster, and we also represent it. So individual data points are clustered based on similarity, and we go on clustering until there's only one single cluster left. So let us just plot this agglomerative clustering and make things really simple for us. Now suppose I have got these data points scattered here, A to G, and these data points have to be clustered. So another important thing is that now we will form clusters. So how clusters are formed? So we can see that based on some similarity, like because of the distance, nearby distance, A and B can be grouped together in a single cluster. So I am just doing that. C and D, I form another cluster because they are near. So I just club them. And again, I would just club E and F based on their distance. And G is separate, so I will just form a separate cluster. Now what happens in agglomerative clustering is that I have to plot all these data points like A, B, C, right, D, E, F, and G. So these are separate clusters. The clustering starts from the bottom, and each data point is treated as a single cluster, which we will also understand with the help of an example further. But now for simplicity, let's take A, B, C, D. So then what happens is that since A and B are grouped as one cluster, so this is how I just group them, all right? And C and D is grouped as one cluster. This is how I group them. E and F are grouped in one single cluster. This is how I group them. Now remains G, which is not being grouped into any of the cluster. So now clustering, I said that it continues until a single cluster is left. So now I would have to have another level of clustering. That means that E, F, G, since G is very close to E, F, I will cluster it in one single cluster. Okay. And since I can see that both these A, B, and C, D pairs, these clusters are again together, so I will just cross this line and I will make one single cluster of these 4 points, right? So what I do is, since these two are connected, I connect them with the help of this line figure, that is tree structure dendrogram, and this G, E, and F, they are connected somehow. I connect them. All right. Now what happens is that I have got two big clusters, and clustering continues until a single cluster is obtained. So in the end, I will have to cluster everything into a single cluster. And this is how I do that. And to join it, I will again join this entire graph. So this is when it follows a bottom to up approach. This is called as agglomerative hierarchical clustering. Okay. So now we will go and see an example of this hierarchical agglomerative clustering, right? Okay. So let us understand what is agglomerative clustering with this example. Now we see that here the clustering takes place from bottom to up. And we have taken an example of population wherein we go on clustering until we get population. So here from the bottom, the individual professions are being plotted. And we see that let's take for a convenience the left hand side. And on the left hand side, the red dots, as you see, this is individual profession in public sector. And on the another side, which we see in the brown circles, is the private sector employment. So somehow there's similarity between private sector. So they are being clustered as one single cluster and the private sector as another cluster. These again are being clustered into one single cluster, and that is employment cluster. Whereas on the another side, we can see another cluster which is different, and that is unemployed section of cluster of people. Now, they again share one similarity, and that is that they all belong to a single gender, that is male. So everything is being clustered into one single cluster, that is male. And then again, male and female clusters are being clustered together to form one single cluster, that is population. Similarly, we also divide on the right hand side the individual professions of women clubbed into private and public sector. And then again, we have separate clusters of employed and unemployed women, and they had been grouped into one single cluster, and that is women. Again, we merge the two big clusters into one single cluster, that is population. So this is how the clustering is taking place. The levels are being increasing from bottom to up. So when we are using this bottom up approach, this is agglomerative clustering.
Now, many of us have visited retail shops such as Walmart or Target for our household needs. Or let's say that we are planning to buy the new iPhone from Target. What we would typically do is search for the model by visiting the mobile section of the store and then select the product and head towards the billing counter. But in today's world, the goal of the organization is to increase the revenue. Can this be done by just pitching one product at a time to the customer? Now the answer to this is clearly no. Hence, organization began mining data relating to frequently bought items. So market basket analysis is one of the key techniques used by large retailers to uncover associations between items. Now, examples could be the customers who purchase bread have a 60% likelihood to also purchase jam. Customers who purchase laptops are more likely to purchase laptop bags as well. They try to find out associations between different items and products that can be sold together, which gives assisting in the right product placement. Typically, it figures out what products are being bought together and organizations can place products in a similar manner. For example, people who buy bread also tend to buy butter, right? And the marketing team at retail stores should target customers who buy bread and butter and provide an offer to them so that they buy a third item, suppose eggs. So if a customer buys bread and butter and sees a discount offer on eggs, he will be encouraged to spend more and buy the eggs. And this is what market basket analysis is all about. This is what we are going to talk about in this session, which is association rule mining and the Apriori algorithm. Now, association rule can be thought of as an if-then relationship. Just to elaborate on that, we have come up with a rule. Suppose if an item A is being bought by the customer, then the chances of item B being picked by the customer too under the same transaction ID is found out. You need to understand here that it's not a causality, rather it's a co-occurrence pattern that comes to the force. Now there are two elements to this rule. First is the if and second is the then. Now if is also known as antecedent. This is an item or a group of items that are typically found in the item set. And the later one is called the consequent. This comes along as an item with an antecedent group or the group of antecedents are purchased. Now, if we look at the image here, A arrow B, it means that if a person buys an item A, then he will also buy an item B, or he will most probably buy an item B. Now, the simple example that I gave you about the bread and butter and the eggs is just a small example. But what if you have thousands and thousands of items? If you go to any professional data scientist with that data, you can just imagine how much of profit you can make if the data scientist provides you with the right examples and the right placement of the items which you can do. And you can get a lot of insights. That is why association rule mining is a very good algorithm which helps the business make profit. So let's see how this algorithm works. So association rule mining is all about building the rules. And we have just seen one rule that if you buy A, then there's a slight possibility or there's a chance that you might buy B also. This type of a relationship in which we can find the relationship between these two items is known as single cardinality. But what if the customer who bought A and B also wants to buy C? Or if a customer who bought A, B, and C also wants to buy D? Then in these cases, the cardinality usually increases and we can have a lot of combination around these data. And if you have around 10,000 or more than 10,000 data or items, just imagine how many rules you're going to create for each product. That is why association rule mining has such measures so that we do not end up creating tens of thousands of rules. Now, that is where the Apriori algorithm comes in. But before we get into the Apriori algorithm, let's understand what's the maths behind it. Now, there are three types of matrices which help to measure the association. We have support, confidence, and lift. So support is the frequency of item A or the combination of item A or B. It's basically the frequency of the items which we have bought and what are the combination of the frequency of the item we have bought. So with this, what we can do is filter out the items which have been bought less frequently. This is one of the measures, which is support. Now what confidence tells us? So confidence gives us how often the items A and B occur together, given the number of times A occur. Now, this also helps us solve a lot of other problems, because if somebody is buying A and B together and not buying C, we can just rule out C at that point of time. So this solves another problem, is that we obviously do not need to analyze the products which people just buy barely. So what we can do is, according to the sales, we can define our minimum support and confidence. And when you have set these values, we can put these values in the algorithm and we can filter out the data and we can create different rules. And suppose even after filtering, you have like 5,000 rules. And for every item, we create these 5,000 rules. So that's practically impossible. So for that, we need the third calculation, which is the lift. So lift is basically the strength of any rule. Now let's have a look at the denominator of the formula given here. And if you see here, we have the independent support values of A and B. So this gives us the independent occurrence probability of A and B. And obviously, there's a lot of difference between the random occurrence and association. And if the denominator of the lift is more, what it means is that the occurrence of randomness is more rather than the occurrence because of any association. So lift is the final verdict where we know whether we have to spend time on this particular rule, what we have got here or not. Now let's have a look at a simple example of association rule mining. So suppose we have a set of items A, B, C, D, and E, and a set of transactions T1, T2, T3, T4, and T5. And as you can see here, we have the transactions T1 in which we have ABC, T2 ACD, T3 BCD, T4 ADE, and T5 BCE. Now what we generally do is create some rules or association rules, such as A gives T or C gives A gives C, B and C gives A. What this basically means is that if a person buys A, then he's most likely to buy D, and if a person buys C, then he's most likely to buy A. And if you have a look at the last one, if a person buys B and C, he's most likely to buy the item A as well. Now, if we calculate the support, confidence, and lift using these rules, as you can see here in the table, we have the rule and the support, confidence, and the lift values. Now let's discuss about Apriori. So Apriori algorithm uses the frequent item sets to generate the association rule. And it is based on the concept that a subset of a frequent item set must also be a frequent item set itself. Now this raises the question, what exactly is a frequent item set? So a frequent item set is an item set whose support value is greater than the threshold value. Now just now we discussed that the marketing team, according to the sales, have a minimum threshold value for the confidence as well as the support. So frequent item set is that item set whose support value is greater than the threshold value already specified. Now example, if A and B is a frequent item set, then A and B should also be frequent item sets individually. Now let's consider the following transaction to make the things a little easier. So suppose we have transactions 1, 2, 3, 4, 5, and these items are there. So T1 has 1, 3, and 4. T2 has 2, 3, and 5. T3 has 1, 2, 3, 5. T4, 2, 5, and T5, 1, 3, and 5. Now the first step is to build a list of item sets of size 1 by using this transactional data. And one thing to note here is that the minimum support count which is given here is 2. Let's suppose it's 2. So the first step is to create item sets of size 1 and calculate their support values. So as you can see here, we have the table C1 in which we have the item sets 1, 2, 3, 4, 5 and the support values. If you remember the formula of support, it was frequency divided by the total number of occurrence. So as you can see here, for the item set 1, the support is 3. As you can see here, that item set 1 appears in T1, T3, and T5. So as you can see, its frequency is 1, 2, and 3. Now, as you can see here, the item set 4 has a support of 1 as it occurs only once in transaction 1. But the minimum support value is 2. That's why it's going to be eliminated. So we have the final table, which is the table F1, in which we have the item sets 1, 2, 3, and 5, and we have the support values 3, 3, 4, and 4. Now the next step is to create item sets of size 2 and calculate their support values. Now all the combination of the item sets in the F1, which is the final table in which we discarded the 4, are going to be used for this iteration. So we get the table C2. So as you can see here, we have 1, 2, 1, 3, 1, 5, 2, 3, 2, 5, and 3, 5. Now, if you calculate this support here again, we can see that the item set 1, 2 has a support of 1, which is again less than the specified threshold. So we're going to discard that. So if we have a look at the table F2, we have 1, 3, 1, 5, 2, 3, 2, 5, and 3, 5. Again, we're going to move forward and create the item set of size 3 and calculate their support values. Now all the combinations are going to be used from the item set F2 for this particular iterations. Now before calculating support values, let's perform pruning on the dataset. Now what is pruning? Now after the combinations are being made, we divide C3 item sets to check if there is another subset whose support is less than the minimum support value. That is what frequent item set means. So if you have a look here, the item sets we have is 1, 2, 3, 1, 2, 1, 3, 2, 3 for the first one. Because as you can see here, if we have a look at the subsets of 1, 2, 3, we have 1, 2 as well. So we are going to discard this whole item set. Same goes for the second one. We have 1, 2, 5. We have 1, 2 in that, which was discarded in the previous set or the previous step. That's why we're going to discard that also, which leaves us with only two factors, which is 1, 3, 5 item set and the 2, 3, 5. And the support for this is 2 and 2 as well. Now, if we create the table C4 using 4 elements, we're going to have only one item set, which is 1, 2, 3, and 5. And if we have a look at the table here, the transaction table, 1, 2, 3, and 5 appears only 1. So the support is 1. And since C4, the support of the whole table C4 is less than 2, so we're going to stop here and return to the previous item set, that is C3. So the frequent item sets are 1, 3, 5 and 2, 3, 5. Now let's assume our minimum confidence value is 60%. For that, we're going to generate all the non-empty subsets for each frequent item sets. Now for I equals 1, 3, 5, which is the item set, we get the subset 1, 3, 1, 5, 3, 5, 1, 3, and 5. Similarly for 2, 3, 5, we get 2, 3, 2, 5, 3, 5, 2, 3, and 5. Now this rule states that for every subset S of I, the output of the rule gives something like S gives I to S. That implies S recommends I of S. And this is only possible if the support of I divided by the support of S is greater than equal to the minimum confidence value. Now applying these rules to the item set of F3, we get rule 1, which is 1, 3 gives 1, 3, 5 and 1, 3. It means 1 and 3 gives 5. So the confidence is equal to the support of 1, 3, 5 divided by the support of 1, 3. That equals 2 by 3, which is 66% and which is greater than the 60%. So the rule 1 is selected. Now if we come to rule 2, which is 1, 5, it gives 1, 3, 5 and 1, 5. It means if we have 1 and 5, it implies we're also going to have 3. Now if we calculate the confidence of this one, we're going to have support 135 divided by support 15, which gives us 100%, which means rule 2 is selected as well. But again, if we have a look at rule 5 and rule 6 over here, similarly, if we select 3 gives 135 and 3, it means if we have 3, we also get 1 and 5. So the confidence for this comes at 50%, which is less than the given 60% target. So we're going to reject this rule. And same goes for the rule number 6. Now, one thing to keep in mind here is that although the rule 1 and rule 5 look a lot similar, they are not. So it really depends what's on the left hand side of the arrow and what's on the right hand side of the arrow. It's the if then possibility. I'm sure you guys can understand what exactly these rules are and how to proceed with these rules. So let's see how we can implement the same in Python, right? So for that, what I'm going to do is create a new Python file and libraries imported and read the file. So as you can see here, we are using the online retail.xlss format file. And from ML Extend, we're going to import Apriori and association rules. It all comes under ML Extend. So as you can see here, we have the invoice, the stock code, the description, the quantity, the invoice data, unit price, customer ID, and the country. Now next in this step, what we're going to do is do data cleanup, which includes removing the spaces from some of the descriptions and drop the rows that do not have invoice numbers and remove the credit card transactions, because that is of no use to us. So as you can see here, the output in which we have like 532,000 rows with 8 columns. So after the cleanup, we need to consolidate the items into one transaction per row with each product. For the sake of keeping the dataset small, we are only looking at the sales for France. So as you can see here, we have excluded all the other sales. We are just looking at the sales for France. Now there are a lot of zeros in the data, but we also need to make sure any positive values are converted to 1 and anything less than 0 is set to 0. So as you can see here, we have still 392 rows. We're going to encode it and see. Check again. Now that you have structured the data properly, in this step what we're going to do is generate frequent item sets that have support at least 7%. Now this number is chosen so that you can get close enough and generate the rules with the corresponding support, confidence, and lift. So guys, as you can see here, the minimum support is 0.7. Now what if we add another constraint on the rules, such as the lift is greater than 6 and the confidence is greater than 0.8. So as you can see here, we have the left-hand side and the right-hand side of the association rule, which is the antecedent and the consequence. We have the support, we have the confidence, the lift, the leverage, and the conviction. So guys, that's it for this session. That is how you create association rules using the Apriori algorithm, which helps a lot in the marketing business. It runs on the principle of market basket analysis, which is exactly what big companies like Walmart, you have Reliance and Target do. Even IKEA does it.
But the first thing that we need to focus on is why artificial intelligence? Why do we need artificial intelligence? Now let us understand this with an example. So nowadays, if you have noticed, if your car exceeds the speed limit, so you'll get a letter or basically a challan at your home. How do you think that happens? Do you think that there's a person who is sitting in a chair and actually noting down all the number plates that crosses the speed limit? Well, that is not possible because there might be millions of cars that pass through that road. And at once, there might be many cars that will be passing through that road. So for a human being to actually do this task is next to impossible. Now let us see another approach to this particular problem. So what we can do, we can actually make use of cameras that will click the picture of the car that exceeds the speed limit, and then we can convert that picture into a text. For example, we have UKPLATE. So in this way, the human error, the risk of human error has been reduced, and at the same time, machines, they never get tired. So because of that, you can capture all the images of cars that actually crosses the speed limit. Similarly, you can think of many other examples as well. It is used in order to recognize a sign, that is in banks if you want to authenticate whether that person is the bank customer or not. Apart from that, it is even used for self-driving cars as well. So in US, around 30,000 people die every year because of road accidents. So that can be completely removed if we use the self-driving cars, which is based on the concept of artificial intelligence. And let me tell you guys, you might find it very fascinating that people in MIT are using artificial intelligence in order to predict the future. So you can imagine why we need artificial intelligence. If you have any questions, any doubts, you can ask me. It is even used in places where humans can't reach. For example, deep oceans or navigation in Mars. So in those places, we need machines which are smart enough to carry our tasks. So this is why we need artificial intelligence. Let us move forward and understand what exactly is artificial intelligence. Now, artificial intelligence, I know the word sounds pretty complex and there are a lot of Hollywood movies that are based on artificial intelligence. If you have seen Terminator or Matrix, so all these movies are based on artificial intelligence, but you don't need to worry about it because till now we haven't reached that level as they have shown in movies like Terminator. But yeah, the concept is pretty similar. So basically, we want systems and softwares in such a way that they can imitate the human behavior. Now, what happens in artificial intelligence? Artificial intelligence is accomplished by studying how human brain thinks and how human brain learns, decide and work while trying to solve a problem. And then we use the outcome of this study as the basis of development of intelligent software and systems. So our major goal is to have systems or softwares that can imitate the human behavior. the way they think, the way they decide, the way they solve a problem. So in that similar fashion, we want our machines to do that. So this is basically artificial intelligence in a nutshell. Let us move forward and look at various applications of artificial intelligence. So this slide basically talks about the application of artificial intelligence. Now I've listed only 3 of them, but there are millions of applications. For example, it is used in speech recognition. So whenever you search something on Google, so you can just tell Google and it'll search it for you. Similarly, it is used for understanding natural language as well as for image recognition as well. And there are many other applications in which artificial intelligence finds its use. For example, it can be used in self-driving cars, it can be used in Siri for recommending some products, and even when you go to websites like YouTube or Pandora, YouTube knows which video you want to next. Pandora knows which song you want to listen to. How do you think this happens? It happens all because of artificial intelligence. So all of these are a few examples of artificial intelligence, but nowadays it is used almost everywhere, guys. Trust me on that. Now let us move forward and understand how to achieve artificial intelligence. Now, in order to achieve artificial intelligence, there were a few technologies that came. First came machine learning. Now, there were certain limitations of machine learning. In order to overcome those limitations came deep learning. Now, let me tell you guys, the concept of artificial intelligence is not new. It was first coined in 1956, but it was just a theoretical concept. Then in 80s and 90s, we were talking about neural networks. But since we didn't have enough computational power, so we couldn't utilize it properly. But in late 90s and 2000s, we started using neural networks for machine learning. Then in 2006, the term deep learning was coined for the first time that overcame the limitations of machine learning. And from 2010, deep learning was used commercially as well. So this was just a small history about artificial intelligence, machine learning, and deep learning. Now, in order to understand this deep learning, we need to first look at machine learning and what were the various limitations of machine learning that led to the evolution of deep learning. So we'll move forward and understand what exactly is machine learning. Now, what is machine learning? So machine learning is nothing but a type of artificial intelligence, or you can say a subset of artificial intelligence. And it provides computers with the ability to learn without being explicitly programmed. So you don't need to hard code your machine for that. Let us understand this with an example. So we have a problem statement in which whenever you give a certain input, we need to determine the species of the flower. And what is that input? That input will be sepal length, sepal width, petal length, and petal width. So whenever we get these 4 parameters or these 4 variables, our machine should be able to predict what sort of a flower it is. Now, how do you think that will happen? First, what we need to do, we need to train our machine on the basis of the data that we have. So in this data, we have sepal length, sepal width, petal length, and petal width, and we have species. So our machine will learn from this data. It will determine what should be the length and width of the sepal and petal in order to classify it as setosa or versicolor or other species of flowers as well. Now what happens next? So you have trained your data. So you have trained your machine from the data set. Then what happens whenever you give a new input to this particular machine, it will predict the species of the flower. So this is how machine learning works. It is nothing but machine learning in a nutshell. So basically, I'll just revise it once more. So you have a data set. So you split that data into training and testing data. So what happens with the help of training data, you train your particular machine. And after that, you test it in order to determine the accuracy. And once it is done, whenever you give the new input, it'll predict the outcome or the desired outcome. So this is how machine learning works, guys. Let us move forward and understand various types of machine learning. So the first type is called supervised learning. Now in supervised learning, what happens, you have input variables X and an output variable Y. And you can use an algorithm to learn mapping function from the input to the output. Now let me simplify it for you. So what happens in supervised learning, the data that you have already contain the classification. Now let me talk about the previous example itself. So from our data set, we knew that if we have this width, this length of our sepal and petal, so that will be the species of flower. So the classifications are already defined. So that will be under supervised learning. Now let me tell you how it actually works. So you have data, you divide that data into training data as well as test data. So on the basis of this training data, you train your machine, and after that you create a model. So as you can see that this phase is called training phase, and after that you create a model. Now in order to check this model to get the accuracy, you have test data. So you'll pass that test data and you'll see the accuracy. That is nothing but the actual output minus the output that is present in the test data. So with that, you can get the accuracy. So this is nothing but supervised learning, and if you have any questions, you can ask me right now. So we'll move forward and understand unsupervised learning. Now in unsupervised learning, unlike supervised learning, you don't have any predefined classes. So what happens, you have data. So on the basis of that data, you try to create your own class. You try to make sure that whatever class you create has high intra-class similarities and have low inter-class similarities. That means if I've created two classes like this, class 1 and class 2, so the elements of this particular class should have high similarity, but at the same time, it should have low similarity with the elements of class 2. So you can think of examples as well of unsupervised learning. For example, if I have a data about my customers, so if I have a website and there are millions of visitors on my website, and I want to make sure that I group people on various criteria. For example, I can group people on the basis of willingness to purchase a product that is there on my website, or where they are coming from, what is the source, all those things. So I want to group my customers, and I want to make sure that I have certain high priority customers, and I have low priority customers, and I have medium priority customers. So with the help of unsupervised learning, I can actually do that. I can make certain classes of people on whom I should focus more on as compared to the other class. So this was just an example, guys. You can use it in various other fields as well. So in marketing, this is how you can use unsupervised learning. So this brings us to our next type of machine learning, which is called a reinforcement learning. Now this is reinforcement learning, guys. Now what happens in reinforcement learning? The machine learns by interacting with space or an environment. So it learns with its experience, with its past experience, and also by new choice exploration. Now I'll take the analogy of dogs. So if you have any dog or a pet at your home, so if you have trained your dog in order to get the newspaper, and if it gets it, then you reward it with some chocolate or things that the dog likes, right? So the dog will know whatever he has done, he's actually rewarded for that. So it'll continue doing that. But apart from that, if he does something else, if instead of the newspaper, he brings something else. So what you'll do, you might even punish it. So because of that, the dog will come to know that it has to get a newspaper every morning. Now, the same example is there in front of your screen. So you have this machine. So it has two choices, either to touch the fire or touch the water. Now, first, what it does, it goes on and touch the fire. So because of that, it gets some burning sensation. Now it has only other option, that is to touch the water. So when it touches the water, it gets some reward. So because of that, it'll understand that it does not have to touch fire ever again. Now there's a diagram that is there in front of your screen. So what happens is you have an agent, all right, that agent performs some action. And on the basis of that action, it'll be exposed to some sort of an environment. Now, if that action is correct, then it'll be rewarded with that. But if it is not, then it'll change its choice and it'll again perform some action. So this process will keep on repeating. So this is how reinforcement learning works. So let us move forward and understand, when we have machine learning, why do we need deep learning? That is, we'll look at various limitations of machine learning. Now the first limitation is high dimensionality of the data. Now the data that is now generated is huge in size. So we have a very large number of inputs and outputs. So due to that, machine learning algorithms fail. So they cannot deal with high dimensionality of data, or you can say data with large number of inputs and outputs. Now there's another problem as well, in which it is unable to solve the crucial AI problems, which can be natural language processing, image recognition, and things like that. Now one of the biggest challenges with machine learning models is feature extraction. Now let me tell you what are features. So in statistics, we consider features as variables, but when we talk about artificial intelligence, these variables are nothing but the features. Now, what happens because of that? The complex problems such as object recognition or handwriting recognition becomes a huge challenge for machine learning algorithms to solve. Now, let me give you an example of this feature extraction. Suppose if you want to predict that whether there will be a match today or not. So it depends on various features. It depends on whether the weather is sunny, whether it is windy, all those things. So we have provided all those features in our data set, but we have forgot one particular feature, that is humidity. And now our machine learning models are not that efficient that they will automatically generate that particular feature. So this is one huge problem, or you can say limitation with machine learning. Now, obviously we have limitation, and it won't be fair that if I don't give you the solution to this particular problem. So we'll move forward and understand how deep learning solves these kind of problems. Now, as you can see that the first line on your slide, which says that deep learning models are capable to focus on the right features by themselves, requiring little guidance from the programmer. So with the help of little guidance, what these deep learning models can do, they can generate their features on which the outcome will depend on. And at the same time, it also solves the dimensionality problem as well. if you have very large number of inputs and outputs, you can make use of a deep learning algorithm. Now, what exactly is deep learning? Again, since we know that it has been evolved by machine learning, and machine learning is nothing but a subset of artificial intelligence, and the idea behind artificial intelligence is to imitate the human behavior. The same idea is for the deep learning as well, is to build learning algorithms that can mimic brain. Now, let us move forward and understand deep learning, what exactly it is. Now, the deep learning is implemented with the help of neural networks, and the idea or the motivation behind neural networks are nothing but neurons. What are neurons? These are nothing but your brain cells. Now, here is a diagram of neuron. So we have dendrites here, which are used to provide input to our neuron. As you can see, we have multiple dendrites here, so these many inputs will be provided to our neuron. Now, this is called cell body, and inside the cell body, we have a nucleus, which performs some function. After that, that output will travel through axon, and it will go towards the axon terminals, and then this neuron will fire this output towards the next neuron. Now, the studies tell us that the next neuron, now, or you can say the two neurons are never connected to each other. There's a gap between them. So that is called a synapse. So this is how basically a neuron works like. And on the right hand side of your slide, you can see an artificial neuron. Now, let me explain you that. So over here, similar to neurons, we have multiple inputs. Now, these inputs will be provided to a processing element like our cell body. And over here in the processing element, what will happen? Summation of your inputs and weights. Now, when it moves on, then what will happen? This input will be multiplied with our weights. So in the beginning, what happens? These weights are randomly assigned. So what will happen if I take the example of x1? So x1 multiplied by w1 will go towards the processing element. Similarly, x2 and w2 will go towards the processing element. And similarly, the other inputs as well. And then summation will happen, which will generate a function of s, that is f of s. After that comes the concept of activation function. Now, what is activation function? It is nothing but in order to provide a threshold. So if your output is above the threshold, then only this neuron will fire, otherwise it won't fire. So you can use a step function as an activation function, or you can even use a sigmoid function as your activation function. So this is how an artificial neuron looks like. So a network will be multiple neurons which are connected to each other will form an artificial neural network. And this activation function can be a sigmoid function or a step function. That totally depends on your requirement. Now, once it exceeds the threshold, it will fire. After that, what will happen? It will check the output. Now, if this output is not equal to the desired output, so these are the actual outputs, and we know the real outputs. So we'll compare both of that, and we'll find the difference between the actual output and the desired output. On the basis of that difference, we are again going to update our weights. And this process will keep on repeating until we get the desired output as our actual output. Now, this process of updating weight is nothing but your back propagation method. So this is neural networks in a nutshell. So we'll move forward and understand what are deep networks. So basically, deep learning is implemented by the help of deep networks, and deep networks are nothing but neural networks with multiple hidden layers. Now, what are hidden layers? Let me explain you that. So you have inputs that comes here. This will be your input layer. After that, some process happens and it'll go to the next node, or you can say to the hidden layer nodes. So this is nothing but your hidden layer 1. So every node is interconnected, if you can notice. After that, you have one more hidden layer where some function will happen. And as you can see that again, these nodes are interconnected to each other. After this hidden layer 2 comes the output layer. And this output layer, again, we are going to check the output, whether it is equal to the desired output or not. If it is not, we are again going to update the weights. So this is how a deep network looks like. Now, there can be multiple hidden layers. There can be hundreds of hidden layers as well. But when we talk about machine learning, that was not the case. We were not able to process multiple hidden layers when we talk about machine learning. So because of deep learning, we have multiple hidden layers at once. Now let us understand this with an example. So we'll take an image which has 4 pixels. So if you can notice, we have 4 pixels here, among which the top 2 pixels are bright, that is, they're black in color, whereas the bottom 2 pixels are white. Now what happens? We'll divide these pixels and we'll send these pixels to each and every node. So for that, we need 4 nodes. So this particular pixel will go to this node, it will go to this node, this pixel will go to this node, and finally this pixel will go to this particular node that I'm highlighting with my cursor. Now what happens? We provide them random weights. So these white lines actually represent the positive weights, and these black lines represents the negative weights. Now this particular brightness, when we display high brightness, we'll consider it as negative. Now what happens? When you see the next output or the next hidden layer, it will be provided with the input with this particular layer. So this will provide an input with positive weight to this particular node, and the second input will come from this particular node. Since both of them are positive, so we'll get this kind of a node. Similarly, this node as well. Now, when I talk about these two nodes, the first node over here, so this is getting input from this node as well as from this node. Now, over here, we have a negative weight. So because of that, the value will be negative, and we have represented that with black color. Similarly, over here as well, we are getting one input from here which has a negative weight, and the another input from here which again has a negative weight. So accordingly, we get again a negative value here. So these two becomes black in color. Now, if you notice what will happen next, we'll provide one input here, which will be negative and a positive weight, which will be again negative. And this will be also negative and a positive weight. So that will again come out to be negative. So that is why we have got this kind of a structure. If you notice this is nothing but the inverse of this particular image. When I talk about this node over here, we are getting the negative value with a positive weight, which is negative, and a negative value with a negative weight, which is positive. So we are getting something which is positive here. Now, obviously, I want this particular image to get inverse. I want these black strips to come up. So what I'll do, I'll actually calculate the inverse by providing a negative weight like this. So over here, I've provided a negative weight, it will come up. So when I provide a positive weight, so it'll stay wherever it is. After that, it'll detect, and the output you can see will be a horizontal image, not a solid, not a vertical, not a diagonal, but a horizontal. And after that, we are going to calculate the difference between the actual output and the desired output, and we are going to update the weights accordingly. Now, this is just an example, guys. So guys, this is one example of deep learning where what happens, we have images here. We provide these raw data to the first layer, to the input layer. Then what happens, these input layers will determine the patterns of local contrast, or it will fixate those patterns of local contrast, which means that it will differentiate on the basis of colors and luminosity and all those things. So it will differentiate those things. And after that, in the following layer, what will happen, it will determine the face features. It will fixate those face features. So it will form nose, eyes, ears, all those things. Then what will happen, it will accumulate those correct features for the correct face, or you can say that it will fixate those features on the correct face template. So it will actually determine the faces here, as you can see it over here. And then it will be sent to the output layer. Now, basically, you can add more hidden layers to solve more complex problems. For example, if I want to find out a particular kind of face, for example, a face which has large eyes or which has light complexion, so I can do that by adding more hidden layers. And I can increase the complexity also at the same time if I want to find which image contains a dog. So for that also I can have one more hidden layer. So as and when hidden layer increases, we are able to solve more and more complex problems. So this is just a general overview of how a deep network looks like. So we have first patterns of local contrast in the first layer. Then what happens, we fixate these patterns of local contrast in order to form the face features such as eyes, nose, ears, etc. And then we accumulate these features for the correct face, and then we determine the image. So this is how a deep learning network, or you can say deep network, looks like. So we'll move forward and I'll give you some applications of deep learning. So here are a few applications of deep learning. It can be used in self-driving cars. So you must have heard about self-driving cars. So what happens, it'll capture the images around it, it'll process that huge amount of data, and then it'll decide what action should it take. Should it take left, right, should it stop? So accordingly, it'll decide what action should it take. And that will reduce the amount of accidents that happens every year. Then when we talk about voice control assistants, I'm pretty sure you must have heard about Siri. All the iPhone users know about Siri, right? So you can tell Siri whatever you want to do, it'll search it for you and display for you. Then when we talk about automatic image caption generation, so what happens in this, whatever image that you upload, the algorithm is in such a way that it'll generate the caption accordingly. So for example, if you have say blue colored eyes, so it'll display a blue colored eye caption at the bottom of the image. Now when I talk about automatic machine translation, so we can convert English language into Spanish, similarly Spanish to French. So basically automatic machine translation, you can convert one language to another language with the help of deep learning. And these are just few examples, guys. There are many other examples of deep learning. It can be used in game playing. It can be used in many other things. And let me tell you one very fascinating thing that I've told you in the beginning as well. With the help of deep learning, MIT is trying to predict future. So yeah, I know it is growing exponentially right now, guys. So this is the problem statement, guys. We need to figure out if the banknotes are real or fake. And for that, we'll be using artificial neural networks. And obviously, we need some sort of data in order to train our network. So let us see how the data set looks like. So over here, I've taken a screenshot of the data set with few of the rows. In it, data were extracted from images that were taken from genuine and forged banknote-like specimens. After that, wavelet transform tools were used to extract features from those images. And these are few features that I'm highlighting with my cursor. And the final column or the last column actually represents the label. So basically label tells us to which class that pattern represents, whether that pattern represents a fake node or it represents a real node. Let us discuss these features and labels one by one. So the first feature or the first column is nothing but variance of a wavelet transformed image. The second column is about skewness. The third is curtices of wavelet transformed image, and finally fourth one is entropy of the image. After that, when I talk about label, which is nothing but my last column, over here if the value is 1, that means the pattern represents a real node, whereas when value is 0, that means it represents a fake node. So guys, let's move forward and we'll see what are the various steps involved in order to implement this use case. So over here we'll first begin by reading the data set that we have. We'll define features and labels. After that, we are going to encode the dependent variable. And what is a dependent variable? It is nothing but your label. Then we are going to divide the data set into two parts, one for training, another for testing. After that, we'll use TensorFlow data structures for holding features, labels, etc. And TensorFlow is nothing but a Python library that is used in order to implement deep learning models, or you can say neural networks. Then we'll write the code in order to implement the model. And once this is done, we will train our model on the training data. We'll calculate the error. Error is nothing but your difference between the model output and the actual output. And we'll try to reduce this error. And once this error becomes minimum, we'll make prediction on the test data and we'll calculate the final accuracy. So guys, let me quickly open my PyCharm and I'll show you how the output looks like. So this is my PyCharm guys. Over here I've already written the code in order to execute the use case. I'll go ahead and run this and I'll show you the output. So over here, as you can see, with every iteration the accuracy is increasing. So let me just stop it right here. Alright, till now any questions, any doubts with respect to what is our use case, what is the data set about? Any questions guys, you can go ahead and ask me. Okay, there's a question from Arpan. He's asking, can you explain the code? Definitely Arpan, I'll be doing that at the end of this class. When you are done with all the fundamentals of neural networks, I'll explain you the entire code, how I've written that and how I've used TensorFlow in order to implement neural networks. I hope you are satisfied with the answer. Okay, he's fine with it. Any other questions, any other doubts guys, just go ahead and ask me. Over here you don't need to worry about code right now guys, because I'll explain this later in the session. So what I'll do, I'll open my slides once more and we'll discuss the fundamentals of neural networks that are required in order to implement this use case. So in order to understand why we need neural networks, we are going to compare the approach before and after neural networks. And we'll see what were the various problems that were there before neural networks. So earlier conventional computers use an algorithmic approach. That is, the computer follows a set of instructions in order to solve a problem. And unless the specific steps that the computer needs to follow are known, the computer cannot solve the problem. So obviously we need a person who actually knows how to solve that problem, and he or she can provide the instructions to the computer as to how to solve that particular problem, right? So we first should know the answer to that problem, or we should know how to overcome that challenge or problem which is there in front of us. Then only we can provide instructions to the computer. So this restricts the problem solving capability of conventional computers to problems that we already understand and know how to solve. But what about those problems whose answer we have no clue of? So that's where our traditional approach was a failure. So that's why neural networks were introduced. Now let us see what was the scenario after neural networks. So neural networks basically process information in a similar way the human brain does. And these networks, they actually learn from examples. You cannot program them to perform a specific task. They will learn from their examples, from their experience. So you don't need to provide all the instructions to perform a specific task. And your network will learn on its own with its own experience. All right, so this is what basically neural network does. So even if you don't know how to solve a problem, you can train your network in such a way that with experience, it can actually learn how to solve the problem. So that was a major reason why neural networks came into existence. We'll move forward and we'll understand what is the motivation behind neural networks. So these neural networks are basically inspired by neurons, which are nothing but your brain cells. And the exact working of the human brain is still a mystery though. So as I've told you earlier as well, that neural networks work like human brain, and so the name. And similar to a newborn human baby, as he or she learns from his or her experience, we want a network to do that as well. But we want it to do very quickly. So here's a diagram of a neuron. Basically, a biological neuron receives input from other sources, combines them in some way, perform a generally non-linear operation on the result, and then outputs the final result. So here if you notice these dendrites will receive signals from the other neurons. Then what will happen, it will transfer it to the cell body. The cell body will perform some function. It can be summation, it can be multiplication. So after performing that summation on the set of inputs, via axon it is transferred to the next neuron. Now let's understand what exactly are artificial neural networks. It is basically a computing system that is designed to simulate the way the human brain analyzes and processes the information. Artificial neural networks has self-learning capabilities that enable it to produce better results as more data becomes available. So if you train your network on more data, it will be more accurate. So these neural networks, they actually learn by example. And you can configure your neural network for specific applications. It can be pattern recognition or it can be data classification, anything like that, all right? So because of neural networks, we see a lot of new technology has evolved. From translating web pages to other languages, to having a virtual assistant to order groceries online, to conversing with chatbots. All of these things are possible because of neural networks. So in a nutshell, if I need to tell you, artificial neural network is nothing but a network of various artificial neurons. Alright, so let me show you the importance of neural network with two scenarios, before and after neural network. So over here we have a machine and we have trained this machine on 4 types of dogs, as you can see where I'm highlighting with my cursor. And once the training is done, we provide a random image to this particular machine which has a dog. But this dog is not like the other dogs on which we have trained our system on. So without neural networks, our machine cannot identify that dog in the picture, as you can see it over here. Basically, our machine will be confused. It cannot figure out where the dog is. Now, when I talk about neural networks, even if we have not trained our machine on this specific dog, but still it can identify certain features of the dogs that we have trained on, and it can match those features with the dog that is there in this particular image, and it can identify that dog. So this happens all because of neural networks. So this is just an example to show you how important are neural networks. Now I know you all must be thinking how neural networks work. So for that, we'll move forward and understand how it actually works. So over here, I'll begin by first explaining a single artificial neuron that is called as perceptron. So this is an example of a perceptron. Over here, we have multiple inputs, x1, x2, dash, 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 till xn. And we have corresponding weights as well, w1 for x1, w2 for x2, similarly wn for xn. Then what happens, we calculated the weighted sum of these inputs. And after doing that, we pass it through an activation function. This activation function is nothing but it provides a threshold value. So above that value, my neuron will fire, else it won't fire. So this is basically an artificial neuron. So when I talk about a neural network, it involves a lot of these artificial neurons with their own activation function and their processing element. Now we'll move forward and we'll actually understand various modes of this perceptron or single artificial neuron. So there are 2 modes in a perceptron, one is training, another is using mode. In training mode, the neuron can be trained to fire for particular input patterns, which means that we'll actually train our neuron to fire on certain set of inputs and to not fire on the other set of inputs. That's what basically training mode is. When I talk about using mode, it means that when a taught input pattern is detected at the input, its associated output becomes the current output, which means that once the training is done and we provide an input on which the neuron has been trained on, so it will detect the input and will provide the associated output. So that's what basically using mode is. So first you need to train it, then only you can use your perceptron or your network. So these were the 2 modes, guys. Next up, we'll understand what are the various activation functions available. So these are the 3 activation functions, although there are many more, but I've listed down 3. Step function. So over here, the moment your input is greater than this particular value, your neuron will fire, else it won't. Similarly for sigmoid and sine function as well. So these are 3 activation functions. There are many more that I've told you earlier as well. So yeah, these are the 3 majorly used activation functions. Next up, what we are going to do, we are going to understand how a neuron learns from its experience. So I'll give you a very good analogy in order to understand that. And later on, when we talk about neural networks, or you can say multiple neurons in a network, I'll explain you the math behind it. I'll explain you the math behind learning, how it actually happens. So right now I'll explain you with an analogy. And guys, trust me, that analogy is pretty interesting. So I know all of you must have guessed it. So these are 2 beer mugs, and all of you who love beer can actually relate to this analogy a lot. And I know most of you actually love beers, so that's why I've chosen this particular analogy, so that all of you can relate to it. All right, jokes apart. So fine, guys. So there's a beer festival happening near your house and you want to badly go there. But your decision actually depends on 3 factors. First is how is the weather, whether it is good or bad. Second is your wife or husband is going with you or not. And the third one is any public transport is available. So on these 3 factors, your decision will depend whether you will go or not. So we'll consider these three factors as inputs to our perceptron, and we'll consider our decision of going or not going to the beer festival as our output. So let us move forward with that. So the first input is how is the weather. We'll consider it as x1. So when weather is good, it'll be 1, and when it is bad, it'll be 0. Similarly, your wife is going with you or not, so that'll be your x2. If she is going, then it's 1. If she's not going, then it's 0. Similarly, for public transport, if it is available, then it is 1, else it is 0. So these are the three inputs that I'm talking about. Let's see the output. So output will be 1 when you're going to the beer festival, and output will be 0 when you want to relax at home. You want to have beer at home only. You don't want to go outside. So these are the two outputs, whether you're going or you're not going. Now what a human brain does. Over here, okay, fine. I need to go to the beer festival. But there are three things that I need to consider. But will I give importance to all these factors equally? Definitely not. There'll be certain factors which will be of higher priority for me. I'll focus on those factors more. Whereas few factors won't affect that much to me. Alright, so let's prioritize our inputs or factors. So here our most important factor is weather. So if weather is good, I love beer so much that I don't care even if my wife is going with me or not, or if there is a public transport available. So I love beer that much that if weather is good, then definitely I'm going there. That means when x1 is high, output will be definitely high. So how we do that, how we actually prioritize our factors, or how we actually give importance more to a particular input and less to another input in a perceptron or in a neuron. So we do that by using weights. So we assign high weights to the more important factors or more important inputs, and we assign low weights to those particular inputs which are not that important for us. So let's assign weights, guys. So weight W1 is associated with input X1, W2 with X2, and similarly W3 with X3. Now, as I've told you earlier as well, that weather is a very important factor, so I'll assign a pretty high weight to weather and I'll keep it as 6. Similarly, W2 and W3 are not that important, so I'll keep it as 2, 2. After that, I've defined a threshold value as 5, which means that when the weighted sum of my input is greater than 5, then only my neuron will fire, or you can say then only I'll be going to the beer festival. Alright, so I'll use my pen and we'll see what happens when weather is good. So when weather is good, our x1 is 1, our weight is 6, we'll multiply it with 6. Then, if my wife decides that she is going to stay at home and she will probably be busy with cooking and she doesn't want to drink beer with me, so she's not coming. So that input becomes 0. 0 into 2 will actually make no difference because it will be 0 only. Then again, there is no public transport available also. Then also this will be 0 into 2. So what output I get here? I get here as 6. And notice the threshold value, it is 5. So definitely 6 is greater than 5. That means my output will be 1. Or you can say my neuron will fire, or I'll actually go to the beer festival. So even if these two inputs are 0 for me, that means my wife is not willing to go with me and there is no public transport available, but weather is good, which has very high weight value and it actually matters a lot to me. So if that is high, it doesn't really matter whether the two inputs are high or not. I will definitely go to the beer festival. Alright, now I'll explain you a different scenario. So over here our threshold was 5, but what if I change this threshold to 3? So in that scenario, even if my weather is not good, I'll give it a 0. So 0 into 6. But my wife and public transport both are available. Alright, so 1 into 2 plus 1 into 2, which is equal to 4. And it is definitely greater than 3. Then also my output will be 1. That means I will definitely go to the beer festival even if weather is bad. And my neuron will fire. So these are the two scenarios that I have discussed with you. Alright, so there can be many other ways in which you can actually assign weight to your problem or to your learning algorithm. So these are the two ways in which you can assign weights and prioritize your inputs or factors on which your output will depend. So obviously in real life, all the inputs or all the factors are not as important for you. So you actually prioritize them. And how you do that in perceptron, you provide high weight to it. This is just an analogy so that you can relate to a perceptron to a real life. We'll actually discuss the math behind it later in the session as to how a network or a neuron learns. Alright, so how the weights are actually updated and how the output is changing, that all those things we'll be discussing later in the session. But my aim is to make you understand that you can actually relate to a real life problem with that of a perceptron. All right. And in real life, problems are not that easy. They are very, very complex problems that we actually face. So in order to solve those problems, a single neuron is definitely not enough. So we need networks of neurons. And that's where artificial neural network, or you can say multi-layer perceptron, comes into the picture. Now let us discuss that. Multi-layer perceptron or artificial neural network. So this is how an artificial neural network actually looks like. So over here we have multiple neurons present in different layers. The first layer is always your input layer. This is where you actually feed in all of your inputs. Then we have the first hidden layer. Then we have second hidden layer, and then we have the output layer. Although the number of hidden layers depend on your application, on what are you working, what is your problem. So that actually determines how many hidden layers you'll have. So let me explain you what is actually happening here. So you provide in some input to the first layer, which is nothing but your input layer. You provide inputs to these neurons. All right. And after some function, the output of these neurons will become the input to the next layer, which is nothing but your hidden layer 1. Then these hidden layers also have various neurons. These neurons will have different activation functions. So they'll perform their own function on the inputs that it receives from the previous layer. And then the output of this layer will be the input to the next hidden layer, which is hidden layer 2. Similarly, the output of this hidden layer will be the input to the output layer. And finally, we get the output. So this is how basically an artificial neural network looks like. Now let me explain you this with an example. So over here, I'll take an example of image recognition using neural networks. So over here, what happens, we feed in a lot of images to our input layer. Now this input layer will actually detect the patterns of local contrast and then will feed that to the next layer, which is hidden layer 1. So in this hidden layer 1, the face features will be recognized. We'll recognize eyes, nose, ears, things like that. And then that will be again fed as input to the next hidden layer. And in this hidden layer, we'll assemble those features and we'll try to make a face. And then we'll get the output, that is the face will be recognized properly. So if you notice here, with every layer, we are trying to get a more abstract version or the generalized version of the input. So this is how basically an artificial neural network, how it works. All right. And there's a lot of training and learning which is involved that I'll show you now. Training a neural network. So how we actually train a neural network. So basically the most common algorithm for training a network is called backpropagation. So what happens in backpropagation, after the weighted sum of inputs and passing through an activation function and getting the output, we compare that output with the actual output that we already know. We figure out how much is the difference. We calculate the error. And based on that error, what we do, we propagate backwards. And we'll see what happens when we change the weight. Will the error decrease or will it increase? And if it increases, when it increases by increasing the value of the variables or by decreasing the value of variables. So we kind of calculate all those things and we update our variables in such a way that our error becomes minimum. And it takes a lot of iterations. Trust me guys, it takes a lot of iterations. We get output a lot of times and then we compare it with the model, with the actual output. Then again we propagate backwards, we change the variables, then again we calculate the output, we compare it again with the desired output of the actual output. Then again we propagate backwards. So this process keeps on repeating until we get the minimum value. All right. So there's an example that is there in front of your screen. Don't be scared of the terms that I used. I'll actually explain you with an example. So this is the example over here. We have 0, 1 and 2 as inputs and our desired output or the output that we already know is 0, 1 and 4. All right. So over here we can actually figure out that desired output is nothing but twice of your input. But I'm training a computer to do that, right? The computer is not a human. So what happens, I actually initialize my weight, I keep the value as 3. So the model output will be 3 into 0 is 0, 3 into 1 is 3, 3 into 2 is 6. Now obviously it is not equal to your desired output, so we check the error. Now the error that we have got here is 0, 1 and 2, which is nothing but your difference. So 0 minus 0 is 0, 3 minus 2 is 1, 6 minus 4 is 2. Now this is called an absolute error. After squaring this error, we get square error, which is nothing but 0, 1 and 4. All right. So now what we need to do, we need to update the variables. We have seen that the output that we got is actually different from the desired output. So we need to update the value of the weight. So instead of 3, our computer makes it as 4. After making the value as 4, we get the model output as 0, 4 and 8. And then we saw that the error has actually increased. Instead of decreasing, the error has increased. So after updating the variable, the error has increased. So you can see that square error is now 0, 4 and 16. And earlier it was 0, 1 and 4. That means we cannot increase the weight value right now. But if we decrease that, make it as 2, we get the output which is actually equal to desired output. But is it always the case that we need to only decrease the weight? Definitely not. So in this particular scenario, whenever I'm increasing the weight, error is increasing, and when I'm decreasing the weight, error is decreasing. But as I've told you earlier as well, this is not the case every time. Sometimes you need to increase the weight as well. So how we determine that? Alright, fine guys, this is how basically a computer decides whether it has to increase the weight or decrease the weight. So what happens here, this is a graph of square error versus weight. So over here what happens, suppose your square error is somewhere here, and your computer, it starts increasing the weight in order to reduce the square error. And it notices that whenever it increases the weight, square error is actually decreasing. So it'll keep on increasing until the square error reaches a minimum value. And after that, when it tries to still increase the weight, the square error will increase. So at that time, our network will recognize that whenever it is increasing the weight after this point, error is increasing. So therefore it will stop right there, and that will be our weight value. Similarly, there can be one more scenario. Suppose if we increase the weight, but then also the square error is increasing. So at that time, we cannot increase the weight. At that time, computer will realize, okay, fine, whenever I'm increasing the weight, the square error is increasing. So it'll go in the opposite direction. So it'll start decreasing the weight, and it'll keep on doing that until the square error becomes minimum. And the moment it decreases more, the square error again increases. So our network will know that whenever it decreases the weight value, the square error is increasing. So that point will be our final weight value. So guys, this is what basically backpropagation in a nutshell is. Fine, so we'll move forward, and now is the correct time to understand how to implement the use case that I was talking about at the beginning. That is how to determine whether a node is fake or real. So for that, I'll open my PyCharm. This is my PyCharm again, guys. Let me just close this. All right. So this is the code that I've written in order to implement the use case. So over here, what we do, we import the first important libraries which are required. Matplotlib is used for visualization. TensorFlow we know in order to implement the neural networks. NumPy for arrays, Pandas for reading the data set. Similarly, sklearn for label encoding as well as for shuffling, and also to split the data set into training and testing parts. All right, fine guys. So we'll begin by first reading the data set, as I've told you earlier as well when I was explaining the steps. So what I'll do, I'll use Pandas in order to read the CSV file which has the data set. After that, I'll define features and labels. So X will be my feature and Y will contain my label. So basically X includes all the columns apart from the last column, which is the fifth one. And because the indexing starts from 0, that's why we have written 0 till 4th. So it won't include the 4th column. All right. And so our last column will actually be our label. Then what we need to do, we need to encode the dependent variable. So the dependent variable, as I've told you earlier as well, is nothing but your label. So I've discussed encoding in TensorFlow tutorial. You can go through it and you can actually get to know why and how we do that. Then what we have done, we have read the data set. Then what we need to do is to split our data set into training and testing. And these are all optional steps. You can print the shape of your training and test data. If you don't want to do it, it's still fine. Then we have defined learning rate. So learning rate is actually the steps in which the weights will be updated. All right. So that is what basically learning rate is. Then when we talk about epochs, means iterations. Then we have defined course history. That will be an empty NumPy array, and its shape will be 1, and it will include the float type objects. Then we have defined ndim, which is nothing but your x shape of axis 1, which means your column. Then we'll print that. After that, we have defined the number of classes. So there can be only 2 classes, whether the node can be fake or it can be real. And this model path I've given in order to save my model. So I've just given a path where I need to save it. So I'll just save it here only in the current working directory. Now is the time to actually define our neural network. So we'll first make sure that we have defined the important parameters like hidden layers, number of neurons in hidden layers. So I'll take 10 neurons in every hidden layer, and I'm taking 4 layers like that. Then X will be my placeholder, and the shape of this particular placeholder is none, comma n underscore dim. N underscore dim value, I'll get it from here, and none can be any value. I'll define one variable W, and I'll initialize it with zeros, and this will be the shape of my weight. Similarly for bias as well, this will be the particular shape, and there will be one more placeholder Y dash, which will actually be used in order to provide us with the actual output of the model. There'll be one model output and there'll be one actual output, which we use in order to calculate the difference, right? So we'll feed in the actual values of the labels in this particular placeholder Y dash. And now we'll define the model. So over here we have named the function as multi-layer perceptron, and in it we'll first define the first layer. So the first hidden layer, and we are going to name it as layer underscore 1, which will be nothing but the matrix multiplication of X and weights of H1, that is the hidden layer 1. And that will be added to your biases B1. After that, we'll pass it through a sigmoid activation function. Similarly, in layer 2 as well,
matrix multiplication of layer 1 and weights of H2. So if you can notice, layer 1 was the network layer just before the layer 2, right? So the output of this layer 1 will become input to the layer 2. And that's why we have written layer underscore 1. It'll be multiplied by weights H2 and then we'll add it with the bias. Similarly for this particular hidden layer as well and this particular layer as well. But over here we are going to use the ReLU activation function instead of sigmoid. Then we are going to define the weights and biases. So this is how we basically define weights. This is how we basically define weights. So weights H1 will be a variable which will be a truncated normal with the shape of n underscore dim and n underscore hidden underscore 1. So these are nothing but your shapes. All right. And after that, what we have done, we have defined biases as well. Then we need to initialize all the variables. So all these things actually I've discussed in brief when I was talking about TensorFlow. Since in TensorFlow, we need to initialize the variables before we use it. So that's how we do it. We first initialize it and then we need to run it. That's when your variables will be initialized. After that, we are going to create a saver object. And then finally, I'm going to call my model. And then comes the part where the training happens. Cost function. Cost function is nothing but you can say an error that will be calculated between the actual output and the model output. All right, so y is nothing but our model output and y dash is nothing but the actual output or the output that we already know. All right, and then we are going to use a gradient descent optimizer to reduce the error. Then we are going to create a session object as well. And finally, what we are going to do, we are going to run the session. So this is how we basically do that. For every epoch, we will be calculating the change in the error as well as the accuracy that comes after every epoch on the training data. After we have calculated the accuracy on the training data, we are going to plot it for every epoch how the accuracy is. And after plotting that, we are going to print the final accuracy which will be on our test data. So using the same model, we'll make prediction on the test data. And after that, we are going to print the final accuracy and the mean squared error. So let's go ahead and execute this, guys. All right, so training is done. And this is the graph we have got for accuracy versus epoch. This is accuracy, y-axis represents accuracy, whereas this is epochs. We have taken 100 epochs and our accuracy has reached somewhere around 99%. So with every epoch, it is actually increasing. Apart from a couple of instances, it is actually keep on increasing. So the more data you train your model on, it will be more accurate. Let me just close it. So now the model has also been saved where I wanted it to be. This is my final test accuracy and this is the mean squared error. All right, so these are the files that will appear once you save your model. These are the 4 files that I've highlighted. Now what we need to do is restore this particular model. And I've explained this in detail how to restore a model that you have already saved. So over here, what I'll do, I'll take some random range. I've taken it actually from 754 to 768. So all the values in the row of 754 and 768 will be fed to our model and our model will make prediction on that. So let us go ahead and run this. So when I'm restoring my model, it seems that my model is 100% accurate for the values that I've fed in. So whatever values that I have actually given as input to my model, it has correctly identified its class, whether it's a fake node or a real node. Because 0 stands for fake node and 1 stands for real node, okay? So original class is nothing but which is there in my data set, so it is 0 already. And what prediction my model has made is 0. That means it is fake. So accuracy becomes 100%. Similarly for other values as well. Fine guys, so this is how we basically implement the use case that we saw in the beginning. So in the slide you can notice that I've listed down only 2 applications, although there are many more. So neural networks in medicine. Artificial neural networks are currently a very hot research area in medicine, and it is believed that they will receive extensive application to biomedical systems in the next few years. And currently the research is mostly on modeling parts of human body and recognizing diseases from various scans. For example, it can be cardiograms, CAT scans, ultrasonic scans, etc. And currently the research is going mostly on 2 major areas. First is modeling and diagnosing the cardiovascular system. So neural networks are used experimentally to model the human cardiovascular system. Diagnosis can be achieved by building a model of the cardiovascular system of an individual and comparing it with the real-time physiological measurements taken from the patient. And trust me guys, if this routine is carried out regularly, potential harmful medical conditions can be detected at an early stage and thus make the process of combating disease much easier. Apart from that, it is currently being used in electronic noses as well. Electronic noses have several potential applications in telemedicine. Now let me just give you an introduction to telemedicine. Telemedicine is a practice of medicine over long distance via a communication link. So what the electronic noses will do, they would identify odors in the remote surgical environment. These identified odors would then be electronically transmitted to another site where an door generation system would recreate them. Because the sense of the smell can be an important sense to the surgeon, telesmell would enhance telepresent surgery. So these are the two ways in which you can use it in medicine. You can use it in business as well, guys. So business is basically a diverted field with several general areas of specialization such as accounting or financial analysis. Almost any neural network application would fit into one business area or financial analysis. Now there is some potential for using neural networks for business purposes, including resource allocation and scheduling. I've listed down two major areas where it can be used. One is marketing. So there is a marketing application which has been integrated with a neural network system. The airline marketing tactician is a computer system made of various intelligent technologies, including expert systems. A feed-forward neural network is integrated with the AMT, which is nothing but airline marketing tactician, and was trained using backpropagation to assist the marketing control of airline seat allocation. So it has wide applications in marketing as well. Now the second area is credit evaluation. Now I'll give you an example here. The HNC company has developed several neural network applications, and one of them is a credit scoring system which increases the profitability of existing model up to 27%. So these are few applications that I'm telling you guys. Neural network is actually the future. People are talking about neural networks everywhere, and especially after the introduction of GPUs and the amount of data that we have now, neural network is actually spreading like plague right now. So this is an image of New York skyline. I personally love this picture. So when a human will see this image, he'll first notice there are a lot of buildings in different colors and stuff like that. But how a computer will read this image? So basically there will be three channels. One will be red, another will be green, and finally we have blue channel, which is popularly known as RGB. So each of these channels will have their own respective pixel values, as you can see it over here. So when I say that image size is B cross A cross 3, it means that there are B rows, A columns, and 3 channels. All right. So if somebody tells you that the size of an image is 28 cross 3 pixels, it means that it has 28 rows, 28 columns, and 3 channels. So this is how a computer sees an image. And this is for colored images. For black and white images, we have only 2 channels. So let's move forward and we'll see why can't we use fully connected networks for image classification. So consider an image which has 28 cross 3 pixels. So when I feed in this image to a fully connected network like this, then the total number of weights required in the first hidden layer will be 2352. You can just go ahead and multiply it yourself. All right. But in real life, the images are not that small. All right. So whatever images that we have, they are definitely above 200 cross 3 pixels. So if I take an image which has 200 cross 3 pixels and I feed it to a fully connected network, so at that time, the number of weights required at the first hidden layer itself will be 120,000 guys. So we need to deal with such huge amount of parameters, and obviously we require more number of neurons. So that can eventually lead to overfitting. So that's why we cannot use fully connected network for image classification. Now let's see why we need convolutional neural networks. So basically, in convolutional neural network, a neuron in the layer will only be connected to a small region of the layer before it. So if you consider this particular neuron which I'm highlighting right now is only connected to 3 other neurons. Unlike the fully connected network where this particular neuron will be connected to all these 5 neurons. Because of this, we need to handle less amount of weights, and in turn, we need less number of neurons as well. So let us understand what exactly is convolutional neural network. So convolutional neural networks are special type of feed-forward artificial neural networks, which is inspired from visual cortex. So visual cortex is nothing but a small region in our brain which is present somewhere here where you can see the bulb. And basically what happened, there was an experiment conducted and people got to know that visual cortex is small regions of cells that are sensitive to specific regions of visual field. So what I mean by that is, for example, some neurons in the visual cortex fires when exposed to vertical edges. Some will fire when exposed to horizontal edges. Some will fire when exposed to diagonal edges. And that is nothing but the motivation behind convolutional neural network. So now let us understand how exactly a convolutional neural network works. So generally a convolutional neural network has 3 layers: convolution layer, ReLU layer, pooling layer, and fully connected layer. We'll understand each of these layers one by one. We'll take an example of a classifier that can classify an image of an X as well as an O. So with this example, we'll be understanding all these 4 layers. So let's begin, guys. Now there are certain trickier cases. So what I mean by that is X can be represented in these 4 forms as well, right? So these are nothing but the deformed images of X. Similarly for O as well.
So these are deformed images. So even I want to classify these images either X or O. All right, because even this is X, this is X, this is X, this is X. But all these are deformed images, but they are in turn X, right? So I want my classifier to classify them as X. So basically that's what I want. So if you can notice here, this is a proper image of an X, and which is actually equal to this particular X, which is a deformed image. Same goes for this O as well. So now what we are going to do is, we know that a computer understands an image using numbers at each pixels. So what we'll do, whatever the white pixels that we have, we are going to assign a value -1 to it, and whatever black pixels we have, we are going to assign a value 1 to it. When we use normal techniques to compare these two images, one is a proper image of X and another is a deformed image of X, we got to know that a computer is not able to classify the deformed image of X correctly. Why? Because it is comparing it with the proper image of X, right? So when you go ahead and add the pixel values of both of these images, you get something like this. So basically our computer is not able to recognize whether it is an X or not. Now what we do with the help of CNN, we take small patches of our image. So these patches or these pieces are known as nothing but features or filters. So what we do, by finding rough feature matches in roughly the same positions in two images, CNN gets a lot better at seeing the similarity between the whole image matching schemes. What I mean by that is, we have these filters, right? We have these filters that you can see. So consider this first filter. This is exactly equal to the feature or the part of the image in the deformed image as well. So this is our proper image and this is our deformed image, all right? So this particular feature or this particular part of the image is actually equal to this particular part of the image. Same goes for this particular feature or filter as well. And similarly, we have this filter as well, which is actually equal to this particular part of the deformed image, all right? So let's move forward and we'll see what all features that we'll be taking in our example. So we'll be considering these three features or filters. This is a diagonal filter, this is again a diagonal filter, and this is nothing but a small x. So we'll take these three filters and we'll move forward. So what we are going to do is we are going to compare these features, the small pieces of the bigger image. We are going to put it on the input image, and if it matches, then the image will be classified correctly. Now we'll begin, guys. The first layer is convolution layer. So these are the beginning two steps of this particular layer. First, we need to line up the feature in the image and then multiply image by the corresponding feature pixel. Now let me explain you with an example. So this is our first diagonal feature that we'll take. We are going to put this particular feature on our image of X, all right? And we are going to multiply the corresponding pixel value. So 1 will be multiplied with 1, we'll get 1 and we'll put it in another matrix. Similarly, we are going to move forward and we're going to multiply -1 with -1. We're going to multiply -1 with -1, as you can see. Similarly, we multiply this as well, -1 into -1, then again -1 into -1. So we are going to complete this whole process when we are going to finish up this matrix. All right. And once we are done finishing up the multiplication of all the corresponding pixels in the feature as well as in the image, we need to follow two more steps. We need to add them up and divide by the total number of the pixels in the feature. So what I mean by that is, after the multiplication of the corresponding pixel values, what we do, we add all these values, we divide it by the total number of pixels, and we get some value, right? And then now our next step is to create a map and put the value of the filter at that particular place. We saw that after multiplying the pixel value of a feature with the corresponding pixel value of with that of our image, we get the output, which is 1. So we place 1 here. Similarly, we are going to move this filter throughout the image. Next up, we are going to move this filter here. After that, we are going to move it here, 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 everywhere on the image. We are going to move it and we are going to follow the same process. All right, so yeah, this is one more example where I've moved my filter in between, and after doing that, I've got the output something like this, 1, 1, -1 and all. So over here, if you notice, I've got a couple of times -1 as well, due to which my output that comes is 0.55, right? So I'm going to place 0.55 here. Similarly, after moving the pixel, after moving the filter throughout the image, I got this particular matrix. All right, and this is for one particular feature. After performing the same process for the other two filters as well, I've got these two values. So we have these three values after passing through the convolution layer. Let me give you a quick recap of what happens in convolution layer. So basically we have taken three features, all right, and one by one we'll take one feature, move it through the entire image, and when we are moving it, at that time we are multiplying the pixel value of the image with that of the corresponding pixel value of the filter, adding them up, dividing by the total number of pixels to get the output. So when we do that for all the filters, we got these three outputs, all right? So let's move forward and we'll see what happens in ReLU layer. So this is ReLU layer, guys, and people who have gone through the previous tutorial actually know what it is. So let me just give you a quick introduction of ReLU layer. So ReLU is nothing but an activation function, all right? So what I mean by that is, it will only activate a node if the input is above a certain quantity. While the input is below 0, the output is also 0, all right? And when the input rises above the certain threshold, it has a linear relationship with the dependent variable. Now I'll explain you with an example. We have a graph of ReLU function here. So my function says that when f of x is equal to 0 if x is less than 0, and it is equal to x when x is greater than 0. All right. So whatever values that I have which are below 0 will actually in turn become 0, and whatever values that are above 0, our function value will also be equal to that particular value. So f of x will be equal to x if it is greater than or equal to 0, and it will be 0 if it is less than 0. So if I have x value as minus 3, so definitely it is less than 0, so f of x becomes 0. Similarly, if I have minus 5x value, then again it is less than 0, so my f of x value becomes 0. But when I consider 3 as my x value, then my f of x becomes equal to x, which is nothing but 3. So over here I'll have 3. Again, if I take my x value as 5, then obviously it is greater than or equal to 0. Then my f of x becomes equal to x, so my f of x value becomes 5. So this is how a ReLU function works. So why are we using ReLU function here is we want to remove all the negative values from our output that we got through the convolution layer. So we'll only take the first output that we got by moving one feature throughout the image. So this is the output that we have got for only one filter. All right. So over here, I'm going to remove all negative values. So over here, you can see that it was minus 0.11 before, and I've converted that to 0. Similarly, I'm going to repeat the whole process for the entire matrix. And once I'm done with that, I get this particular value. Now remember, this is only for the output that we got through one feature. All right. So when we were doing convolution at that time, we were using 3 features, right? So this is the output only for one filter. After doing it for the output of the other 2 filters as well, we have got these 2 values more. So totally we have these 3 values after passing through ReLU activation function. Next up, we'll see what exactly is pooling layer. So in pooling layer, what we do, we take a window size of 2 and we move it across the entire matrix that we have got after passing through ReLU layer. And we take only the maximum value from there so that we can shrink the image. So what we are actually doing is we are reducing the size of our image. So let me explain you with an example. So this is basically one output that we have got after passing through ReLU layer. And over here we have taken a window size of 2 cross 2. So when we keep this window at this particular position, we see that 1 is the highest value. So we are going to keep 1 here. And we are going to repeat the same process for this particular window as well. So over here the maximum value is 0.33, so 0.33 will come. So if you notice here, earlier we had 7 cross 7 matrix, and now we have reduced that to 4 cross 4 matrix. So after doing that for the entire image, we have got this as our output. This output we have got after moving our window throughout the image that we have got after passing through ReLU layer, right? And when we repeat this process for all the 3 outputs that we have got after the ReLU layer, then we get this particular output after pooling layer, right? So basically we have shrinked our image to a 4 cross 4 matrix. Now comes the tricky part. So where we are going to do now is stack up all these layers. So we have discussed convolution layer, ReLU layer, and pooling layer. So I'll just give you a brief recap of what all things we have discussed. In convolution layer, what we did, we took 3 features, and then after that, one by one, we moved each filter throughout the image. And when we were moving it, we were continuously multiplying the image pixel value with that of the corresponding filter pixel value. And then we were dividing it by the total number of pixels. All right. With that, we got 3 output after passing through the convolution layer. Then those 3 output we passed through a ReLU layer where we have removed the negative value. All right. And after removing negative value, again, we have got the 3 outputs. Then those 3 outputs we passed through pooling layer. So basically we're trying to shrink our image. And what we did, we took a window size of 2 cross 2, moved it through all the 3 outputs that we have got through ReLU layer. And after doing that, we were only taking the maximum value, pixel value in that particular window. And then we were putting it in a different matrix so that we get a shrinked image. And after passing it through pooling layer, we have got a 4 cross 4 matrix. And since we took 3 features in the beginning, so therefore we have got 3 outputs after passing through pooling layer. All right. Next up, we are going to stack up all the layers. All right. So let's do that. So after passing through convolution, ReLU, and pooling, we have got this 4 cross 4 matrix. This was our input image. Now when we add one more layer of convolution, ReLU, and pooling, we have shrinked our image from 4 cross 4 to 2 cross 2, as you can notice here. Now we are going to use fully connected layer. Now what happens in fully connected layer? The actual classification happens here, guys. Okay. So what we are doing here is we are going to take the shrinked images and put it into a single list. So basically this is what we have got after passing through 2 layers of convolution, ReLU, and pooling. And this is what we have got. So basically we are converting into a single list or a vector. How we do that? We take the first value 1, then we take 0.55, then we take 0.55, then we take 1 again. Then we take 1, then we take 0.55, 0.55, 0.55. Then we again take 0.55, 1, 1, and 0.55. So this is nothing but a vector, or you can say a list. If you notice here that there are certain values in my list which is high for x,
And similarly, if I repeat the entire process that we have discussed for O, there'll be certain different values which will be high. So for X, we have first, fourth, fifth, 10th and 11th element vector values are high. For O, we have second, third, ninth and 12th element vector which are high. So basically we know now if we have an input image which has first, fourth, fifth, 10th and 11th element vector values high, we know that we can classify it as X. Similarly, if our input image has a list which has the second, third, ninth and 12th element vector values high, then we can classify it as 0. Now let me explain you with an example. So after the training is done, after doing the entire process for both X and O, you know that our model is trained now. Okay, so we have given a new input image, and that input image passes through all the layers. And once it has passed through all the layers, we have got this 12 element vector. Now it has 0.9, 0.65, all these values, right? Now, how do we classify it, whether it is an X or O? So what we do, we'll compare this with a list of X and O, right? So we have got the list in the previous slide. If you notice, we have got two different lists for X and O. We are going to compare this new input image list that we have got with that of X and O, right? So first, let us compare that with X. Now, as I've told you earlier as well, for X, there are certain values which will be high, which is nothing but first, fourth, fifth, 10th and 11th value, right? So I'm going to sum first, fourth, fifth, 10th and 11th value, and I've got 5. So 1 plus 1 plus 1 plus 1 and plus 1. So 5 times 1, I've got 5. And now I'm going to sum the corresponding values of my input image vector as well. So the first value is 0.9. Then the fourth value is 0.87, fifth value is 0.96, 10th value is 0.89, and the 11th value is 0.94. So after this, doing the sum of these values, I've got 4.56. When I divide this by 5, I got 0.91, right? Now this is for X. Now when I do the same process for O, so in O, if you notice, I have second, third, ninth, and 12th element vector values as high. So when I sum these values, I get 4. And when I do the sum of the corresponding values in my input image, I've got 2.07. When I divide that by 4, I got 4.51. So now we notice that 0.91 is a higher value compared to 0.51. So when we have compared our input image with the values of X, we got a higher value than the value that we have got after comparing the input image with the values of O. So the input image is classified as X. All right, so now let us move towards our use case. So this is our use case, guys. So over here, what we are going to do is we are going to train our model on different types of dogs and cat images. And once the training is done, we are going to provide it an input, and it will classify whether the input is of a dog or a cat. Now, let me tell you the steps involved in it. So what we are going to do in the beginning is obviously first we need to download the data set. After that, we are going to write a function to encode the labels. Labels are nothing but the dependent variable that we are trying to predict. So in our training data and testing data, obviously we know the labels, right? So on that basis only we can train our model. So we are going to encode those labels. After that, we'll resize the image to 50 cross 50 pixel, and we are going to read it as a grayscale image. Then we are going to split the data, 24,000 images for training and 50 for testing. Once this is done, we are going to reshape the data appropriately for TensorFlow. Now TensorFlow, I think everyone knows about TensorFlow. TensorFlow is nothing but a Python library for implementing deep learning models. Then we are going to build the model, calculate the loss. It is nothing but categorical cross entropy. Then we are going to reduce the loss by using Adam optimizer with a learning rate set to 0.001. Then we are going to train the deep neural network for 10 epochs, and finally we are going to make predictions. All right, so I'll just quickly open my PyCharm and I'll show you the code, how it looks like. So this is the code that I've written in order to implement the use case. In the beginning, I need to import the libraries that I require. And once it is done, what I'm doing, I'm defining my training data and the testing data. So train and test one contains both my training data as well as testing data respectively. Then I've taken my image size as 50 and learning rate I've defined here. And I've given a name to my model. You can give whatever name you want. All right, so first thing that we saw, we need to encode the dependent variable. That's what we are doing here. We are encoding our dependent variable. So whenever the label is cat, then it will be converted to an array of 1, 0, and when it is dog, it will be converted to an array of 0, 1. So why we are actually encoding the label? Because our code cannot understand the categorical variable. So we need to encode it, right? Next, what I'm doing is I'm resizing my image to 50 cross 50, and I am converting it to a grayscale image, right? And once this is done, I'm going to split my data set into training and testing parts. So yeah, we are basically splitting the data set into two parts for training and testing. And here we are defining a model. So I can just go ahead and throw in a comment here. Building the model. Yeah.
So this is where we are building the model. So basically what we have done here is we have resized our image to 50 cross 50 cross 1 matrix, and that is the size of the input that we are using, right? This input that I'm talking about. Then what we have done, a convolution layer we have defined with 32 filters and a stride of 5 with an activation function, a ReLU. And after that we have added a pooling layer, max pool layer. Okay. Again, what we have done, we have repeated the same process, but over here we are taking 64 filters and 5 stride, passing it through a ReLU activation function, and after that we have a pooling layer, max pool layer. Then we have repeated the same process for 128 filters. After that we have repeated for 64 filters, then for 32 filters. And after that we are using a fully connected layer with 1024 neurons. And finally we are using the dropout layer with key probability of 0.8 to finish our model. So this is where our model is actually finished. And then what we are doing is we are using the Adam optimizer to optimize our model. So basically whatever the loss that we have, we are trying to reduce it. And this is basically for your TensorBoard. So we are creating some log files, and then with that log file, TensorBoard will create pretty fancy graphs for us that helps us to visualize the entire model. And then what we are doing is we are trying to fit the model. And we have defined epochs as 10, that is the number of iterations that will happen will be 10. And yeah, so this is pretty much it. Model name we have given, then input is x_test to check the accuracy. Similarly, the target will be y_test. The labels associated with that test data will be a y_test, and which we have encoded basically. So this is how we are going to actually calculate the accuracy, and we'll try to reduce the loss as much as possible in 10 epochs. So till now our model is complete. We are done with it. Next, what I'm doing is I'm feeding in some random input from the test data, and I'm validating whether my model is predicting it correct or not. All right. So I've already trained the model because it takes a lot of time, and yeah, I cannot do it here. So I've already trained the model, and you can see that the loss that came after the 10th epoch is 0.2973, and the accuracy is somewhere around 88%, which is pretty good, guys. And yeah, and I've done the prediction on the test data as well. So let me just show it to you that. So this is the prediction that it has done on few of the images in the test data. So yeah, it is a cat predicted as cat, cat predicted as cat, 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 and dogs as well. There are certain dogs as well. Why can't we use feed-forward networks? Now let us take an example of a feed-forward network that is used for image classification. So we have trained this particular network for classifying various images of animals. Now if you feed in an image of a dog, it will identify that image and will provide a relevant label to that particular image. Similarly, if we feed in an image of an elephant, it will provide a relevant label to that particular image as well. Now if you notice, the new output that we have got, that is classifying an elephant, has no relation with the previous output, that is of a dog. Or you can say that the output at time t is independent of output at time t minus 1. As we can see that there is no relation between the new output and the previous output. So we can say that in feed-forward networks, outputs are independent to each other. Now there are a few scenarios where we actually need the previous output to get the new output. Let us discuss one such scenario. Now what happens when you read a book? You'll understand that book only on the understanding of your previous words. Alright, so if I use a feed-forward network and try to predict the next word in a sentence, I can't do that. Why can't I do that? Because my output will actually depend on the previous outputs. But in the feed-forward network, my new output is independent of the previous outputs. That is, output at t plus 1 has no relation with output at t minus 2, t minus 1, and at t. So basically, we cannot use feed-forward networks for predicting the next word in a sentence. Similarly, you can think of many other examples where we need the previous output, some information from the previous output, so as to infer the new output. This is just one small example. There are many other examples that you can think of. So we'll move forward and understand how we can solve this particular problem. So over here, what we have done, we have input at t minus 1. We'll feed it to our network. Then we'll get the output at t minus 1. Then at the next timestamp, that is at time t, we have input at time t that will be given to our network along with the information from the previous timestamp, that is t minus 1, and that will help us to get the output at t. Similarly, at output for t plus 1, we have two inputs. One is a new input that we give. Another is the information coming from the previous timestamp, that is t, in order to get the output at time t plus 1. Similarly, it can go on. So over here, I have just written a generalized way to represent it. There's a loop where the information from the previous timestamp is flowing. And this is how we can solve this particular challenge. Now let us understand what exactly are recurrent neural networks.
So for understanding recurrent neural network, I'll take an analogy. Suppose your gym trainer has made a schedule for you. The exercises are repeated after every third day. Now this is the order of your exercises. First day you'll be doing shoulders, second day you'll be doing biceps, third day you'll be doing cardio. And all these exercises are repeated in a proper order. Now what happens when we use a feed-forward network for predicting the exercise today? So we'll provide in the inputs such as day of the week, month of the year, and health status. All right, and we need to train our model or our network on the exercises that we have done in the past. After that, there'll be a complex voting procedure involved that will predict the exercise for us. And that procedure won't be that accurate. So whatever output we'll get won't be as accurate as we want it to be. Now what if I change my inputs and I make my inputs as what exercise I've done yesterday? So if I've done shoulder, then definitely today I'll be doing biceps. Similarly, if I've done biceps yesterday, today I'll be doing cardio. Similarly, if I've done cardio yesterday, today I'll be doing shoulder. Now there can be one scenario where you are unable to go to gym for one day. Due to some personal reasons, you could not go to the gym. Now what will happen at that time? We'll go one timestamp back and we'll feed in what exercise that happened day before yesterday. So if the exercise that happened day before yesterday was shoulder, then yesterday there were biceps exercises. Alright, similarly biceps happened day before yesterday, then yesterday would have been cardio exercises. Similarly, if cardio would have happened day before yesterday, yesterday would have been shoulder exercises. Alright, and this prediction, the prediction for the exercise that happened yesterday will be fed back to our network, and these predictions will be used as inputs in order to predict what exercise will happen today. Similarly, if you have missed your gym say for 2 days, 3 days or 1 week, so you need to roll back. You need to go to the last day when you went to the gym. You need to figure out what exercise you did on that day, feed that as an input, and then only you'll be getting the relevant output as to what exercise will happen today. Now what I'll do, I'll convert these things into a vector. Now what is a vector? Vector is nothing but a list of numbers. Alright, so this is the new information guys along with the information from the prediction at the previous timestamp. So we need both of these in order to get the prediction at time t. Imagine if I have done shoulder exercises yesterday. So this will be 1, this will be 0, and this will be 0. Now the prediction that will happen will be biceps exercise because if I have done shoulder yesterday, today it will be biceps. So my output will be 0, 1 and 0. And this is how vectors work guys. So I hope you have understood this guys. Now this is how a neural network looks like guys. We have new information along with the information from the previous timestamp. The output that we have got in the previous timestamp will use certain information from that. Will feed into our network as inputs and then that will help us to get the new output. Similarly, this new output that we have got will take some information from that, feed in as an input to our network along with the new information to get the new prediction, and this process keeps on repeating. Now let me show you the math behind the recurrent neural networks. So this is the structure of a recurrent neural network guys. Let me explain you what happens here. Now consider at time t equals to 0, we have input x naught and we need to figure out what is h naught. So according to this equation, h of 0 is equal to wi weight matrix multiplied by our input x of 0 plus wr into h of 0 minus 1, which is h of minus 1, and time can never be negative, so this particular equation cannot be applied here, plus a bias. So wi into x of 0 plus bh passes through a function g of h to get h of 0 over here. After that I want to calculate y naught. So for y naught I'll multiply h of 0 with the weight matrix wi and I'll add a bias to it and pass it through a function g of y to get y naught. Now in the next timestamp, that is at time t equals to 1, things become a bit tricky. Now let me explain you what happens here. So at time t equals to 1 I have input x1. I need to figure out what is h1. So for that I'll use this equation. So I'll multiply wi, that is the weight matrix, by the input x1 plus wr into h of 1 minus 1, which is 0. H of 0 we know what we got from here. So wr into h of 0 plus the bias, pass it through a function g of h to get the output as h1. Now this h1 we'll use to get y1. We'll multiply h1 with wi plus a bias and we'll pass it through a function g of y to get y1. Similarly, the next timestamp, that is at time t equals to 2, we have input x2. We need to figure out what will be h2. So we'll multiply the weight matrix wi with x of 2 plus wr into h of 1 that we have got here plus b of h and pass it through a function g of h to get h of 2. From h of 2 we'll calculate y of 2, wi into h of 2 plus by, that is the bias, pass it through a function g of y to get y2. And this is how recurrent neural network works guys. Now you must be thinking how to train a recurrent neural network. So a recurrent neural network uses backpropagation algorithm for training. But backpropagation happens for every timestamp. That is why it is commonly called as backpropagation through time. Over here, I won't be discussing backpropagation in detail. I'll just give you a brief introduction of what it is. Now with backpropagation, there are certain issues, namely vanishing and exploding gradients. Let us see those one by one. So in vanishing gradient, what happens? When you use backpropagation, you tend to calculate the error, which is nothing but the actual output that you already know minus the model output, the output that you got through your model, and the square of that. So you figure out the error. With that error, what do? You tend to find out the change in error with respect to change in weight or any variable. So we'll call it weight here. So change of error with respect to weight multiplied by learning rate will give you the change in weight. Then you need to add that change in weight to the old weight to get the new weight. All right. So obviously what we are trying to do, we are trying to reduce the error. So for that, we need to figure out what will be the change in error if my variables are changed, right? So that way we can get the change in the variable and add it to our old variable to get the new variable. Now over here, what can happen if the value dE by dW, that is a gradient, or you can say the rate of change of error with respect to our variable weight, becomes very small than 1, like it is 0.00 something. So if you multiply that with the learning rate, which is definitely smaller than 1, then you get the change of weight which is negligible. All right. So there might be certain examples where you are trying to predict, say, a next word in a sentence, and that sentence is pretty long. For example, if I say I went to France dash dash dash, I went to France, then there are certain words, then I say few of them speak dash. Now I need to predict speak, what will come after speak. So for that I need to go back in time and check what was the context, which will be very complex, and due to that there will be a lot of iterations, and because of that this error, this change in weight will become very small, very small. So the new weight that we'll get will be actually almost equal to your old weight. So there won't be any updation of weight that will be happening. And that is nothing but your vanishing gradient. All right, I'll repeat it once more. So what happens in backpropagation, you first calculate the error. This error is nothing but the difference between the actual output and the model output and the square of that. With that error, we figure out what will be the change in error when we change a particular variable, say weight. So dE by dW, multiply it with learning rate to get the change in the variable or change in the weight. Now we'll add that change in the weight to our old weight to get the new weight. This is what backpropagation is, guys. All right, I'm just giving you a small introduction to backpropagation. Now consider a scenario where you need to predict the next word in a sentence. And your sentence is something like this. I have been to France. Then there are a lot of words. After that, few people speak. And then you need to predict what comes after speak. Now, if I need to do that, I need to go back and understand the context. What is it talking about? And that is nothing but your long-term dependencies. So what happens during long-term dependencies, if this dE by dW becomes very small, then when you multiply it with n, which is again smaller than 1, you get delta W, which will be very, very small. That will be negligible. So the new weight that you'll get here will be almost equal to your old weight. So I hope you're getting my point. So this new weight, so there will be no updation of weights, guys. This new weight will always be almost equal to our old weight. So there won't be any learning here. So that is nothing but your vanishing gradient problem. Similarly, when I talk about exploding gradient, it is just the opposite of vanishing gradient. So what happens when your gradient or dE by dW becomes very large, becomes greater than 1, all right? And you have some long-term dependencies. So at that time, your dE by dW will keep on increasing, delta W will become large, and because of that, your weights, the new weight that will come will be very different from your old weight. So these two are the problems with backpropagation. Now let us see how to solve these problems. Now exploding gradients can be solved with the help of truncated BTD, backpropagation through time. So instead of starting backpropagation at the last timestamp, we can choose a smaller timestamp like 10. Or we can clip the gradients at a threshold. So there can be a threshold value where we can, clip the gradients. And we can adjust the learning rate as well. Now for vanishing gradient, we can use a ReLU activation function. We have discussed ReLU activation function in artificial neural network tutorial, guys. Similarly, we can also use LSTM and GRUs. In this tutorial, we'll be discussing LSTMs, that are long short-term memory units. Now let us understand what exactly are LSTMs. So guys, we saw what are the two limitations with the recurrent neural networks. Now we'll understand how we can solve that with the help of LSTMs. Now what are LSTMs? Long short-term memory networks, usually called as LSTMs, are nothing but a special kind of recurrent neural network. And these recurrent neural networks are capable of learning long-term dependencies. Now, what are long-term dependencies? I've discussed that in the previous slide, but I'll just explain it to you here as well. Now, what happens sometimes we only need to look at the recent information to perform the present task. Now, let me give you an example. Consider a language model trying to predict the next word based on the previous ones. If we are trying to predict the last word in the sentence, say, the clouds are in the sky. So we don't need any further context. It's pretty obvious that the next word is going to be sky. Now, in such cases where the gap between the relevant information and the place that it's needed is small, RNNs can learn to use the past information. And at that time, there won't be such problems like vanishing and exploring gradient. But there are few cases where we need more context. Consider trying to predict the last word in the text, I grew up in France. Then there are some words. After that comes, I speak fluent French. Now, recent information suggests that the next word is probably the name of a language. But if we want to narrow down which language, we need the context of France from further back. And it's entirely possible for the gap between the relevant information and the point where it is needed to become very large. And this is nothing but long-term dependencies. And the LSTMs are capable of handling such long-term dependencies. Now, LSTMs also have a chain-like structure like recurrent neural networks. Now, all the recurrent neural networks have the form of a chain of repeating modules of neural networks. Now, in standard RNNs, the repeating module will have a very simple structure such as a single TANH layer that you can see. Now, this TANH layer is nothing but a squashing function. Now, what I mean by squashing function is to convert my values between -1 and 1. All right, that's why we use TANH. And this is an example of an RNN. Now we'll understand what exactly are LSTMs. Now, this is a structure of an LSTM. Or if you notice, LSTM also have a chain-like structure, but the repeating module has different structures. Instead of having a single neural network layer, there are 4 interacting in a very special way. Now, the key to LSTM is the cell state. Now, this particular line that I'm highlighting, this is what is called the cell state. The horizontal line running through the top of the diagram. So this is nothing but your cell state. Now, you can consider the cell state as a kind of a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. Now, what I'll do, I'll give you a walkthrough of LSTM step by step, all right? So we'll start with the first step. All right, guys. So the first step in our LSTM is to decide what information we are going to throw away from the cell state. And you know what is the cell state, right? I've discussed in the previous slide. Now, this decision is made by the sigmoid layer. So the layer that I'm highlighting with my cursor, it is the sigmoid layer called the forget gate layer. It looks at ht-1, that is the information from the previous timestamp, and xt, which is the new input, and outputs a number between 0 and 1 for each number in the cell state ct-1, which is coming from the previous timestamp. A 1 represents completely keep this, while a 0 represents completely get rid of this. Now, if we go back to our example of a language model trying to predict the next word based on all the previous ones, in such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject, right? We want to use the gender of the new subject. So we'll forget the gender of the previous subject here. This is just an example to explain you what is happening here. Now let me explain you the equations which I've written here. So ft will be combining with the cell state later on, that I'll tell you. So currently ft will be nothing but the weight matrix multiplied by ht-1 and xt and plus the bias, and this equation is passed through a sigmoid layer. All right, and we get an output that is 0 and 1. 0 means completely get rid of this, and 1 means completely keep this. All right, so this is what basically is happening in the first step. Now let us see what happens in the next step. So the next step is to decide what information we are going to store. In the previous step, we decided what information we are going to keep, but here we are going to decide what information we are going to store here. All right, what new information we are going to store in the cell state. Now this has 2 parts. First, a sigmoid layer, this is called a sigmoid layer, and which is also known as an input gate layer, decide which values we'll update. All right, so what values we need to update. Then there's also a TANH layer that creates a vector of the candidate values C bar of t-1 that will be added to the state later on. All right, so let me explain it to you in a simpler terms. So whatever input that we are getting from the previous timestamp and the new input, it will be passed through a sigmoid function, which will give us I of t. All right, and this I of t will be multiplied by ct, which is nothing but the input coming from the previous timestamp and the new input, with that is passed through a TANH, that will result in ct. And this will be later added on to our cell state. And the next step will combine these two to update the states. Now let me explain the equations. So I of t will be what? Weight matrix, and then we have ht minus 1 comma xt multiplied by the weight matrix plus the bias, pass it through a sigmoid function, we get I of t. C bar of t will get by passing a weight matrix ht minus 1 xt plus bias through a tanh squashing function, and we'll get C bar of t. Alright, so as I've told you earlier as well, in the next step we'll combine these two to update the state. Let us see how we do that. So now is the time to update the old cell state ct minus 1 with the new cell state ct. Alright, and the previous steps we have already decided what to do. We just need to actually do it. So what we'll do, we'll multiply the old cell state ct minus 1 with ft that we got in the first step, forgetting the things that we decided to forget earlier in the first step, if you can recall. Then what we do, we add it to it and ct, then we add it by the term that will come after multiplication of it and c bar t, and this new candidate value scaled by how much we decided to update each state value. Alright, so in the case of the language model that we were discussing, this is where we would actually drop the information about the old subject gender and add the new information as we decided in the previous steps. So I hope you are able to follow me, guys. Alright, so let us move forward and we'll see what is the next step. Now our last step is to decide what we are going to output, and this output will depend on a cell state, but it will be a filtered version. Now finally what we need to do is we need to decide what we are going to output, and this output will be based on our cell state. First we need to pass ht minus 1 and xt through a sigmoid activation function so that we get an output that is OT. Alright, and this OT will be in turn multiplied by the cell state after passing it through a tanh squashing function or an activation function. And why we do that? Just to push the values between -1 and 1. So after multiplying OT, that is this value, and a tanh CT, we'll get the output H2, which will be our new output, and that will only output the part that we decided to. Whatever we have decided in the previous steps, it will only output that value. Alright, now I'll take the example of that language model again. Since it just saw a subject, it might want to output information relevant to a verb, and in case that's what is coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into. All right, and you can see from the the equations as well. Again, we have a sigmoid function. Then that whatever output we get from there, we multiply it with tanh ct to get the new output. All right, guys. So this is basically LSTMs in a nutshell. So in the first step, we decided what we need to forget. In the next step, we decided what are we going to add to our cell state, what new information we are going to add to our cell state, and we were taking an example of the gender throughout this whole process. All right, and in the third step, what we do, we actually combined it to get the new cell state. Now in the fourth step, what we did, we finally got the output that we want. And how we did that? Just by passing ht minus 1 and xt through a sigmoid function, multiplying it with the tanh ct, the tanh new cell state, and we get the new output. Fine, guys. So this is what basically LSTM is, guys. Now we'll look at a use case where we'll be using LSTM to predict the next word in a sentence. All right, let me show you how we are going to do that. So this is what we are trying to do in our use case, guys. We'll feed our LSTM with correct sequences from the text of 3 symbols. For example, had a general and a label that is council in this particular example. Eventually, our network will learn to predict the next symbol correctly. So obviously, we need to train it on something. Let us see what we are going to train it on. So we'll be training our LSTM to predict the next word using a sample short story that you can see over here. Alright, so it has basically 112 unique symbols. So even comma and full stop are considered as symbols. Alright, so this is what we are going to train it on. So technically, we know that LSTMs can only understand real numbers. Alright, so what we need to do is we need to convert these unique symbols into a unique integer value based on the frequency of occurrence, and like that we'll create a dictionary. For example, we have had here that will have value 20, A will have value 6, general will have value 33. All right, and then what happens, our LSTM will create a 112 element vector that will contain the probability of each of these words or each of these unique integer values. All right, so since 0.6 has the highest probability in this particular vector, it will pick the index value of 0.6, then it will see what symbol is attached to that particular integer value. So 37 is attached to council. So this will be our prediction, which is absolutely correct, as a label is also council according to our training data. All right, so this is what we are going to do in our use case. So guys, this is what we'll be doing in our today's use case. Now I'll quickly open my PyCharm and I'll show you how you can implement it using Python. we'll be using TensorFlow, which is a popular Python library for implementing deep neural networks or neural networks in general. All right, so I'll quickly open my PyCharm now. So guys, this is my PyCharm, and over here I've already written the code in order to execute the use case that we have. So first we need to do is import the libraries. NumPy for arrays, TensorFlow, we know TensorFlow.contrib. From that we need to import RNN, then random collections and time. All right, so this particular block of code is used to evaluate the time taken for the training. After that we have log underscore path, and this log underscore path is basically telling us the path where the graph will be stored. All right, so there will be a graph that will be created, and then that graph will be launched. Then only our RNN model will be executed. Then that's how TensorFlow works, guys. So that graph will be created in this particular path. All right, and we are using summary writer. So that will actually create the log file that will be used in order to display the graph using TensorBoard. All right, so then we have defined a training underscore file, which will have our story on which we'll train our model on. Then what we need to do is read this file. So how are we going to do that? First is read line by line whatever content that we have in our file. Then we are going to strip it. That means we are going to remove the first and the last white space. Then again we are splitting it just to remove all the white spaces that are there. After that we're creating an array, and then we are reshaping it. Now during the reshape, if you notice, this -1 value tells us the compatibility. All right, so when you're reshaping it, you need to make sure that we are providing in the correct parameters to reshape it. So you can convert a 3x2 matrix to a 2x3 matrix, right? So just to make sure that it is compatible enough, we add this -1 and it will be done automatically. All right, then return content. After that, what we are doing, we are feeding in the training data that we have, training underscore file. We are feeding in our story and calling the function read underscore data. Then what we are doing, we are creating a dictionary. What is a dictionary? We all know key value pairs based on the frequency of occurrences of each symbol. All right, so from here collections.counter words.most common. So most common words with their frequency of occurrence, there will be a dictionary created. And after that, we'll call this dict function, and this dict function will feed in word, and which is equal to length of dictionary. That means whatever the length of that particular dictionary is, how many times it is repeated. So we'll have the frequency as well as a symbol. That will be our key value pair, and we are reversing it as well. Then what we are doing, we are calling it build underscore data set, and we're feeding in our training data there. This is our vocabulary size, which is nothing but the length of your dictionary. And then we have defined various parameters such as learning rate, iterations or epochs. Then we have display step and underscore input. Now learning rate, we all know what it is. The steps in which our variables are updated. Training underscore iterations is nothing but your epochs, the total number of iterations. So we have given 50,000 iterations here. Then we have display underscore step, that is 1,000, which is basically your batch size. So batch size is what? After every 1,000 epochs, you'll see the output. All right, so it'll be processing it in batches of 1,000 iterations. Then we have n underscore input as 3. Now the number of units in the RNN cell will keep it as 512. Then we need to define X and Y. So X will be our placeholder that will have the input values, and Y will have all the labels, all right, vocab size. So X is a placeholder where we'll be feeding in our input dictionary. Similarly, Y is also one more placeholder, and it'll have a shape of none, comma, vocab size. Vocab size we have defined earlier, as you can see, which is nothing but the length of your dictionary. Then we are defining weights as well as biases. After that, we have defined our model. All right, so this is how we are going to define it. We'll create a function RNN when we'll have X weights and biases. And after that, we are calling in RNN.multi-RNN cell function. And this is basically to create a 2-layer LSTM, and each layer has n underscore hidden units. After that, what we are doing, we are generating the predictions. But once we have generated the prediction, there are n underscore input outputs, but we only want the last output. All right, so for that, we have written this particular line. And then finally, we are making a prediction. We are calling this RNN function, feeding in X weights and biases. After that, we are calculating the loss and then we are optimizing it. For calculating the loss, we are using reduce underscore mean, softmax cross entropy. And this will give us basically the probability of each symbol, and then we are optimizing it using RMS prop optimizer. All right, and this gives actually a better accuracy than Adam optimizer, and that's the reason why we are using it. Then we are going to calculate the accuracy, and after that we are going to initialize the variables that we have used. As we have seen in TensorFlow that we need to initialize all the variables, unlike constants and placeholders in TensorFlow. All right, and once we are done with that, we are feeding in our values, then calculating the accuracy, how accurate it is, and then when optimization is done, we are calculating the elapsed time as well. So that will give us how much time it took in order to train our model. Then this is just to run the tensor board on local host 6006. And this particular block of code is used in order to handle the exceptions. So exceptions can be like whatever word that we are putting in might not be there in our dictionary or might not be there in our training data. So those exceptions will be handled here, and if it is not there in our dictionary, then it will print word not in a dictionary. All right, so fine guys, let's input some values and we'll have some fun with this model. All right, so the first thing that I'm gonna feed in is had a general. So whenever I feed in these three values, had a general, there'll be a story that will be generated by feeding back the predicted output as the next symbol in the inputs. All right, so when I feed in had a general, so it will predict the correct output as council, and this council will be fed back as a part of the new input, and our new input will be a general council. So it will be a general council. All right, so these three words will become our new input to predict the new output, which is 2. All right, and so on. So surprisingly, LSTM actually creates a story that somehow makes sense. So let's just read it. Had a general council to consider what measures they could take to outwit their common enemy, the cat. By this means, we should always know when she was about and could easily. All right, so somehow it actually makes sense when you feed in that. So what will happen when you feed in these three inputs? It will predict the next word, that is council. After that, it will take council and it will feed back as an input along with a general. So a general council will be your next input to predict 2. Similarly, in the next iteration, it will take general council 2 and predict consider for us. And this will keep on repeating.
Alright, now to start off, let us now understand what is natural language processing and why do we even need it. You see, natural language refers to the speech analysis in both audible data as well as a text document. NLP system can capture meaning from an input such as sentences, paragraph, pages, and give out a desired output based on our application. So why do we need NLP? You see, natural language processing helps computer communicate with humans in their own language and scale other language related tasks. For example, NLP makes it possible for computers to read text, hear speeches, interpret it, measure the sentiment, and then determine which part of it are important. Today's machines can analyze more language-based data than humans, that too with consistency, accuracy, and in an unbiased manner. More or less, we all know that there is a staggering amount of unstructured data that is generated every day, be it from a medical record or to a social media. Automating NLP tasks will critically be helpful in future for analyzing text and speech data efficiently. So moving ahead, let us now see the ways we can process our textual data. We can process our textual data in one of two ways. One is a machine learning way and other one is a deep learning method. In machine learning, we can make use of algorithms such as bag of words, TF-IDF to classify and predict the desired output. But the drawback of this is that these machine learning algorithms do not consider the context of the word or a sequence. Here, the way it works is based on number of times the word is repeating, a probability is derived out of it, and then performs a classification task. This is the reason why we have deep learning model for NLP tasks. Speaking about deep learning model, we have something like recurrent neural network, LSTM, transformer network, Google's BERT algorithm, and many more. This deep learning model learns the pattern of a word or a sequence and then tries to predict the desired outcome of the task. We can perform NLP using deep learning in one of two ways. One by pre-trained models such as Google's Word2Vec or global vector models. And the other way is to train our own model. If we are trying to train our own model, it would require a very huge amount of data and also compute power to support it. In most of the cases, we will be using pre-trained models. Moving ahead, let us now discuss recurrent neural networks. As I mentioned earlier, the bag of word or TF-IDF model for processing our text is very inefficient. As I mentioned earlier, the bag of word or TF-IDF model that was used in machine learning to process our textual data is very inefficient, as it takes one word at a time and also the context of the word in which it is being spoken about is totally ignored. Although this would give us some prediction, but we can expect a lot of loss. This is why we use RNN model or recurrent neural network. Here, it requires a sequential data. Now you might be wondering, what does this sequential data mean, right? In simple words, sequential data is dependent on the past values. What I'm trying to say here is that we can read our document, right? We can read our document or English documents only from left to right side. Or take example of stock price prediction. We cannot randomly place the dates, right? If you have to make a prediction for next 2-3 months, we'll obviously refer to the data that was previously recorded. So this is what a sequential data means. So what makes RNN capable of handling sequential data? Well, you see, RNN model makes use of something called a state. This is nothing but a temporary memory that stores the previous data. As you can see here in an image, this is the general architecture of a recurrent neural network. So let me now move to my canvas and show you how a recurrent neural network works and what are its internal workings. All right. So as we have seen in an image, right, back in our slide, you saw that, recurrent neural network have something called as states, and then we also had some boxes, right? So what does those boxes represents? So let me quickly draw over here and show you what does this box represents. So if you remember, right, it goes something like we have a box here, okay, and then we also had another box, and then let's consider like 2 more boxes, that would be sufficient, okay. And then the way we provide input for our recurrent neural network is over here, okay. Now based on our application, we can demand our recurrent neural network to provide output in either one of 3 ways. It can either be like we can have multiple inputs, as you can see here, or we can have single input and multiple outputs, or the other way around is we can have single input and single output. So here what we'll consider is we are using multiple inputs and also we have multiple outputs. Okay, so now let us see, as this is a supervised learning model, right? Obviously it will have some kind of input and then it will also have labels to clarify the data. So let's take something like if this is our X data, right? So if this is the X data, so let's take this as a list, and then over here we'll have data which would represent something like X1, then we'll have X2, then we'll have X3, and then so on, and we'll have something like Xn. Okay, so what does this X over here represents? See, here let's take an example that Uri, which was a movie, is a good movie. We can have a couple more X's and we'll just put here as good movie. Okay, so this is nothing but the inputs, each of these words. Now what our model over here does, let's take an example that we are trying to find name entity prediction, which stands for NER, right? So what this name entity prediction does is, it trains the model in such a manner that it finds a pattern. So as you can see here, this is Uri, right? Uri, it's something like a name, right? So this goes as 1, and is not a name, so this would be 0. Good, this is also not a name, and movie is also not a name. So the output over here would be something like 1000. All right. So now let's see what are the inputs and how it would look like. So first off, we have inputs. So if this is our X data, so we'll have input something like Xi. This would be in lowercase. Okay, so this would be X1. Then we'll have X2. We'll have X3, and then we'll have X4. Similarly, the Y, the output over here would be something like, we'll give it Y hat of 1, Y hat of 2, Y hat of 3. At the same time, we'll also have Y hat of 4. Now, if you're wondering what does this Y hat represents, Y hat over here is nothing but predicted values. And Y is nothing but, the labeled value or trained values. And now, as we all know that the main thing or the main feature behind recurrent neural network is nothing but the states. And the way the states are represented is by using the state vector, or it can also be called as context vector. So the state vector over here starts with A. Let me give it as a different color here. Let me give it as blue. So here we'll have A, and this would be 0. Okay. And now this A would be passed down to this. Okay. So this would be A of 1, and over here we'll have A of 2, A of 3, and then finally A of 4. I'm pretty sure you might be wondering what does this A contains, right? So over here, as I have mentioned, let me take this very example. So here Uri is good movie. Okay. And so what this A1 will contain? A1 will contain Uri. See, if we take the normal algorithm, what's going to happen is it will just consider only this one particular block. Okay. If this was just a normal algorithm or something which is used in the olden days, it will just consider this particular block and it won't be considering the previous values. So this previous value is being stored over here in the form of a memory. So now A1 will contain Uri, and what A2 will contain over here. So A2 will be having something like Uri is. And similarly, as it goes through here, it will collect each and every word. And finally, A4 will be complete context vector. So it will have the entire sentence, Uri is a good movie. Okay, I hope you understood what does this A signifies over here. Let me quickly erase all of these. Okay, So the another important part which goes over here in any machine learning or deep learning model is nothing but the weights. So let's consider that we have weights, which is nothing but W, or let's take it as U. Let me give another color here, U, V, and W. In this RNN model, right, what we're going to do is we're going to have a single, or we'll have just only one weights, right? So the U weight is same for all of these inputs here. V weight over here is same for all the outputs. The weight W is same for all our state metrics. Okay, so this is how the weights are determined. So now to get a better understanding of what's happening over here and to derive a mathematical equation for feed-forward network, let's take a single block over here. And let's see how this internal working of this is working, okay? So over here we'll have a box, okay? And this will be our input. So let's give our input as x of t, because this is a generalized model, right? And now what we're going to do over here is this would be a of t minus 1. That's because a of t will be present over here. And now if we have an output which is present over here, and this would be nothing but y hat of t. All right. So as I mentioned earlier that we will be having weights. So the weights over here is nothing but u, v, and w. So what's happening over here? Okay. So first off, there will be a matrix multiplication between these two values. Okay. Another, there will be a matrix multiplication between these two values. And once they are done, we'll add these two values and then give a activation function to it. Okay. And the activation function that would be used over here is tan h. So if I have to put it in an equation form over here, so the product of these two, x of t times, or it would be a dot product of u, okay, and the sum of these two, so it will be t minus 1 times w. And now what we're going to do is we're going to pass an activation function, which is nothing but tan h over here. So let's just give a small dotted notation over here. So whatever the output which comes, it will be performing an addition of these two and also give an activation function, which will represent here by f. All right. So this is how we get an activation function over here. So what does this value signifies this? This is nothing but this output over here, a of t. So I hope you understand what is a of t. A of t is this value. Okay, let me quickly highlight that for you. So a of t is this value. Okay, so a of t is represented over here. And the way we get this is by this particular equation. Now, what about the value for y hat of t, or the prediction of y of t? So for y of t, it's going to be something like this. So y hat of t, this would be nothing but we have to multiply this particular a of t with this matrix over here. Okay, or the weights I can say. So it's going to be nothing but a of t times the weight matrix, that is v. And then we have to pass activation function. Usually the activation function that is going to be used over here is softmax or sigmoid. It totally depends upon what kind of output you're expecting. All right. And this is how it works. And now an important thing that I would like to mention over here is that we also have to add something called as bias. So it will be B over here. I'll just represent this by a different color. So this is an equation for our recurrent neural network in a mathematical form. So now what's going to happen is, in order to find a loss, right, we have to subtract whatever value we have predicted with the given value. So the predicted value over here, let's say this is as capital Y. Okay. And we also have been given the trained value. So this would be looking something like this. So we'll obviously have the trained values. Let's just give a random output, but there will be 4. So it'll be 0, 1, 0, 1. Okay. So this is nothing but the trained values. And now we'll have the other, this is nothing but the given label data. So this would be correct values. So 1, 0, 0, 1. As this is a supervised learning, so we obviously will be given this label data over here. So now what this will do is this will subtract each of these values and calculate a loss. So how do you calculate a loss, right? Okay. So as you can see here, if I give this L, like let me change the color here. So if I say L is loss, so this would be nothing but y hat of first value minus the actual value. Okay, so this is nothing but the predicted value, and this is nothing but the given value. So if I try to find out the loss of this, then what this would look like is, this is just for the one value, right? So if I have to do it for all the values, then it would be the summation. So it would be nothing but loss is equal to summation I, which ranges from 1 to n, right? And then we'll have loss and then theta I. Okay, so this Li over here represents these values. Okay, so this is just for one. So if you want me to explain you this in detail, so over here we have y1, y2, y3, and y4. How this would look like is something, so this would be for 1 plus y hat of 2 minus actual value of y of 2, then summation predicted value of y3 minus the actual value of y3, and then it will be predicted value of y4 minus the actual value of y4. And when I perform addition over here, or when I perform summation, I can generalize this equation into this form. But we are not yet done over here. As you can see, we have something called as theta values. So what does this theta values represents? You see, the main agenda behind finding a loss is to increase our accuracy, right? So if I say this is my gradient descent and this is the lowest global minima, right? So my agenda over here is to reach this global minima. So now, in order for me to do this, in order to increase my accuracy, I have to obviously change my values. So how do I do that? How do I increase an accuracy? It's obviously by these weights. Okay, it's by this W, U, and V. So W, U, and V are nothing but the weights. So what this theta over here represents, let me quickly erase this. Okay, so what this theta over here represents is nothing but the values of W, U, and V. So now what we're going to do is we are going to have a partial derivative of the loss with respect to U, and then we'll have a partial derivative of loss with respect to V, and then we'll also have partial derivative of loss with respect to W. These are nothing but weights, and we are trying to train the weights. This is done in order to increase our accuracy. Okay, and the way these models get trained is with the help of backpropagation, and the way the backpropagation works over here is by partial derivative. So what I'm trying to say here is, as if I get my weights over here, so let me just take another color. So this V, we know that it is totally dependent upon this value over here. This won't be V, this would be W. Okay, so this W value will be totally dependent on the previous one, and this value will be dependent on this one, and this value will be dependent on this one, and this one would be finally dependent on this. So this is in order to move from here to here to here and then to here, we'll use something called as partial derivatives, right? So that's how we update our old weights. All right. And another important concept that make neural network or recurrent neural network very important is nothing but embedding layer. So let me quickly draw a boundary over here. Okay, so embedding layer. All right, so what does this embedding layer signifies? Okay, so if I take a convention way, right? So like, let's say that, our X, or, our input over here, this is nothing but X over here, right? So what is the dimension or the shape of this X? The shape of this X is nothing but 1, 4, right? 1, 4. Similarly, it's 1, 4 here, 1, 4, and 1, 4. But this is not usually the case when you're working with real world examples. When you're working with real world examples, we won't be having 4 different words, right? We'll obviously have lakhs of values. So for example, let's say we have X, and the shape of this X is something like we have 10,000 values. Okay, so now if I try to feed this 10,000 values into my network over here, obviously I would be using batch propagation. So it would take a lot of time, right? Because it's 10,000 values after all. So in order to overcome this, what we're going to do is we're going to reduce the size of this. Okay, so basically what word embedding layer does is think that we have a matrix. This is our input layer, right? Or input word. So we call this as sparse matrix. This is nothing but, an individual value, that's xi or x1, x2, x3. Let's, for generalization, we'll give here as xi. And the shape of this is nothing but 1, v. V here represents the n number of dimensions. And 1 is because it's just going to be one word, right? So it's going to be 1. So if I consider with respect to this is 1 and this is v. Okay. So now what will happen is, if v is 10,000 or pretty great, it obviously we won't have much, we are going to lose a lot of time on computation and also take huge compute power. So what we'll do is I'll multiply this with an embedding layer. And what this embedding matrix does is it is basically a set of features. So this is something, this is a black box model. And all this would do is this would attract a couple of features. If you want me to give you a better analogy of what this is, and if you want me to compare this with respect to a CNN, which is nothing but another great algorithm for image processing using deep learning, right? Over there, we are going to use something called as filters or kernels. So each of those filters or kernels is responsible for extracting one specific feature, right? So this is what embedding layer does. And what this would do, for example, now let's say that the size of embedding layer is v, k. K is something that we provide an input over here. So now what this would happen is this would give us a new matrix or embedded matrix whose size would be 1, k. I'm pretty sure you didn't understand this because over here I'm using, these letters. So in order to make you better understand this, what I'm going to do is let me take a matrix over here. Okay, let me take something like, because this would be in an embedded form, right? This would be a sparse matrix. So it will be like 0, 0, 0, 0, 0, 1, then we'll have 0, 0, and so on. Okay, so now what this would do is we'll also create a matrix over here. The size of this would be something similar to that of V. This is nothing but 1 comma V, and over here it would be K. So the matrix shape over here would be V comma K, right? To give you a better analogy, let me also draw a couple of boxes here. So this is the matrix, and this is the matrix over here again. So now what will happen over here is, when I try to perform this matrix multiplication, right, what this would do, as everything is 0 and only one value is true. So let's say this is the one value, right? And this would be going across, from left to right, and this would be from top to bottom. Only one part over here would be marked, and rest everything would be 0. Therefore, reducing the dimension, let me give some random values like 0.5, 1.8, 0.5, just some random values. So now this would obviously reduce the size of 1 comma K. So what I'm trying to say here is, now for example, say that I have a size over here as 1 comma 10,000, okay, which is a very huge matrix. And the shape of this, let's say that it's 10,000 comma 200. When I perform this embedding, right, word embedding, the shape of the new matrix would be nothing but 1 comma 200. If I compare this part over here to the embedding, whatever we have received over here. So let me just give a quick brief. So this is our embedded layer. So this is really 1 comma 200. So you will see that we have decreased the dimensions by a drastic amount. Okay, so this is 10,000 and this is only 200. And this would be very efficient when we are trying to feed this to our recurrent neural network. And let me quickly show you how this would go. So first let me draw our architecture. Let's take this blocks like this. And then we'll have an output over here. Okay, so this would be our inputs, right? So let me give something like this. So initially we used to provide X values over here, right? Now we won't be doing that. We won't be providing any X values directly. Instead of that, what I'm going to do is I'll have an embedding layer over here. And this will have the X values. So let me give here as X of 1, so X of 2, X of 3, and then we'll have X of 4. And then similarly, let's take this model to be multiple input and single output. So here we'll have y hat of t, and then we'll have weights obviously. So this would be u, v, and w. And this is nothing but our matrix over here. So this would be a of 0, a of 1, a of 2, a of 3, and finally a of 4. Okay, so this is our context matrix. And obviously we'll be performing an activation function here. So I'll just give it f. You can put f, you can put g, it's totally up to you. So this is how a recurrent neural network would actually work. All right. So now that we know how RNN works, let us now understand what is LSTM, or we can also say it as long short-term memory. You see, traditional RNNs are not good at capturing long-range dependencies. What I mean to say here is that when we tend to work with a very huge data set and multiple RNN layer, we are at the risk of vanishing gradient problem. Now you might be wondering, what is this vanishing gradient, right? Well, you see, when training a very deep neural network, gradient or the derivatives decrease exponentially as it propagates down the layer. This is known as vanishing gradient problem. These gradients are actually used to update the weights of a neural network. But when the gradients vanish, these weights will not get updated. In the worst case scenario, it will completely stop the neural network from training. This vanishing gradient problem is a common issue in very deep neural networks. So to overcome this vanishing gradient problem in RNNs, long short-term memory was introduced. You see, LSTM or long short memory is a modification to RNN's hidden layer. LSTM is capable of remembering RNN's weights and their inputs over a very long period of time. In LSTM, in addition to the hidden state, cell state is passed down to the next block. The way LSTM works is that it can capture long-range dependencies, that is all weights. It can have memory of previous inputs for a very extended time duration. The way LSTM cell does this is by using three main gates. First one is a forget gate. Forget gate removes the information that is no longer useful in the cell state. Then we have input gate. Additional information to the cell state is added by input gate. And finally, we have something called as output gate. Additional useful information to the cell state is also added by an output gate. This gating mechanism of LSTM has allowed network to learn the conditions for when to forget, ignore, or keep information in the memory cell. So let me now quickly move to my Jupyter notebook and show you how I can implement LSTM on name entity prediction. Alright, so let me quickly move there. Alright, so over here, first off, I'll be opening my Google Colab. Okay, so let us give a name for our Google Colab over here. Let's give a short term, right? Name entity prediction. And let's connect our Google Colab to our server. Okay, meanwhile that's connecting. So now you might be wondering, from where am I going to use my data set? So for me to use my data set, I'll just go for Kaggle, Kaggle, baby names. So let me just quickly show you how this data set would look like. So this is a CSV file over here. All right, so as you can see here, we have over 93,889 unique values. Okay, so this is a very huge data set. And let's try downloading this. To download this is pretty simple. All you need to do is click this and it will get downloaded. As I've already downloaded this file, let me quickly upload this on my Jupyter notebook. So let me go here and upload it from here. Okay, so let me go to this upload file. And yeah, so I have my CSV file here and let me open this. As this is a pretty huge data set, it would take some time. Meanwhile, that's loading. Let's see what we can do. So first off, let's import a couple of libraries. So we'll have import pandas as PD, and then we are going to import numpy as np, and then we also need to have matplotlib. So from sklearn. All right, and we also need something like label encoder, but I'll show you a shortcut way to bypass label encoding. Okay, so let's try to load our cell here. And in order for us to read this data, so it's pretty simple. All we are going to do is let's give this as a data. This would be nothing but pandas.read CSV, and then we are going to pass our file name. Let me change this to our root directory. We're putting a dot over here. Okay, so I won't be executing this as of now because it's trying to load our file. All right, so now that we have successfully loaded our data, so let's try running this cell over here. Okay, so let me close this and let me zoom in over here. So now what we are going to do is let's see the shape of our data. So let's see what's the data shape, data.shape, and now let's see what it would be like. Okay, so as you can see here, we have 5 columns, but the number of rows that we have is 1.8 million. That is approximately 18 lakhs, right? So this is a pretty huge value. So now what we're going to do is we'll just see how our data is looking like. So we'll see data.head, and let's see what we need. So as you can see here, we have ID, which is of no use for us. Then we have name. Okay, then this year, I don't think it's of any use for us. Then we have gender and count. Count here represents, how many people have the name Mary, how many people have the name Anna, how many people have the name Emma, Elizabeth, and Minnie. This is over here. Out of this, if you see, right, there are a couple of things that we don't need. We can drop them out. All we need is a name. Okay, and then we also need the gender, because this is going to be our prediction. We are going to predict, we'll give our own custom name, and then we'll see whether the name that we are giving is a male or a female. Okay, so now what we're going to do is let's see how many unique values we have. So let me quickly erase this first. Okay, so what I'm going to do is data.names. So this should give us here name, and then we'll type here as unique. Okay, so this would give me unique values. Okay, so over here I have 93,889 unique names. Okay, so now what we are going to do is we want to label encode this, right? So we want our female, which is nothing but F, we want female to be 0 and then male to be 1, or vice versa. So in order to do that, either we can use label encoder, or there's a shortcut method to this. Let me quickly show you how that works. So first off, we'll take our data frame. So it's data, and which column we want to do this for? We want to do this for our gender column, right? So let me pass this and give gender. And now what we're going to do is, okay, we'll take this as type. Okay, this would be obviously in the form of category. And now what we'll do is this is cat dot codes. Okay, so this is nothing but panda shortcut, do label encoding. Let's try to execute this and see what it would look like. So as you can see here, we have a couple of zeros and ones. This is nothing but it's representing females with 1 and males with zeros. Okay, so now what we'll do is we have to update this column. So we'll paste this and this should be something like this over here. And let me execute this. Okay, so if you want to see how our data would look like now, let me just quickly run this once again. So you'll see here now the values has been label encoded. Okay, so now what we're going to do is we obviously need to take the unique names, right? And then we'll obviously group it by, right? So what we'll do for this is we'll take something like data. We'll group this by the names. So group by names. All right. And now what we'll do is we'll calculate the mean of the genders. We'll reset the index. The reason why we want to reset the index is because, if we don't give the index, then our name over here will become the index, right? So we'll give reset underscore index. All right. So let's give this to a new data frame and we'll call this as df. Okay, let me execute this now. And let's see how this df would look like. Okay, let me execute this right after this. So as you can see here, it has grouped by names, everything in an ascending order. So this is all in an alphabetical manner. And yeah. And now only thing that I want to work on is this gender. Okay. The reason is because over here I'm getting a floating point value. I don't want this floating point value. I want to change this to integer value, right? So what I'll do is df gender. This would be nothing but df gender. Then all I'm going to do is as type. I'll just put here as int. So let's now see what this value would look like. Fantastic. We over here have now, ones and zeros, which is nothing but an integer value. Okay. So if you want to see this, so either I can write df or I can also put as head. Okay. So these are the first 5 values. Okay. So now the way our neural network is going to work, or the recurrent neural network is going to work, is that, I hope you remember these boxes, right? So when I was talking or when I was explaining this RNN, I was saying that I would be passing around the words. But here in this project or in this program, we won't be passing words over here. We won't be passing like Abha or Abida or Adam. We won't be passing these words. Instead of that, we'll be passing letters. So over here, it's going to be like alphabets. So A, B, it can be any alphabet, it can be Z here. So basically it depends upon whatever the value is coming here. So in order to do that, we have to find number of unique alphabets. So we know how many unique alphabets we have, right? So it's 26. So in order to get these alphabets, what we'll do is, let me first quickly erase this. Erase all drawing. So now we have 26 alphabets. We have to create our own vocabulary. So what I'm going to do is I'm going to import string. So now I need letters, right? So letters, this would be nothing but list of string.ascii. Okay. And if you want to see what this would give me, this would be nothing but the list of alphabets, which are in lower cases. Okay. And now what we'll do is we'll try to create a label encoding, or we have to create a vocabulary, right? So we'll have something like vocab. This would be nothing but I'll be using dictionary. And now what I want is zip. The way I want over here is, for every individual values of this A, B, C, D, I want to label encode this to 0, 1, and whatever the value it is, right? So it would be from 1 to 27, unique numbers, right? So this would be nothing but letters. And then we need something like range 1, 27. So this would give me the matrix from 1 to 26, right? And let's now see what this would look like. So we have vocab, and let me execute this. This should give me a dictionary. Okay. So here we'll convert A to 1. Okay. And then B would be 2, C would be 3, and so on. Z would be 26. And now what we are going to do is we'll just try to create the reverse vocabulary. And the reason is we obviously won't be needing this, but just in case if you want to use, it should be something very similar to this. Let me just copy the exact same thing and paste it over here. So we'll just give it as reverse, right? So it will be R underscore, and here instead of numbers being second, we'll just cut this letters and we'll pass letters over here. And now you'll see if you're trying to decode whatever we have predicted, we can just pass it down like this. Okay, so now what will happen is we need to do something like, all our data, whatever is there, we have to convert them into a lowercase. So, and then once we convert them into a lowercase, we have to encode them into numbers. So whatever I'm saying is this AABAN, right? ABAN. So this AA, obviously first off, we have to convert all of this into a lowercase, this value. and then whatever the equivalent value of A, like numerical value of A, so it's obviously going to be 1. We'll substitute that with this, and it's going to be a list, right? So how do I do that? So for that, I'll write a function. So we'll have def word to number, right? Word to. So now what I'm going to do is I'm going to have for loop for I in range. So this would be nothing but we have to go through the entire shape, right? So df dot shape. This would give me a list, and I just need the first index. Okay, so now what I'm going to do is I'll create one new list sequence. This would be nothing but for letters in df. Obviously we want the names part, and in this we are going to pass the index value. It's going to be I. Let me just give some space here just so that you better understand this. And now what I'm going to do is, I'll have this vocab. See, every time I pass a letter, it will convert it into, this individual letter, it will convert it into a list or the equivalent, numerical representation. It will be letters, and obviously it has to be in lower, so it will be lower. And then we'll just close this bracket here. So now what we are going to do is, before we execute this function, we'll have to append this. So it will be df, and this is going to be names dot I. We'll replace the name in that index with this particular sequence. Okay, so now all we need to do is run this function over here, and yeah, this will take some time. The reason is because we have almost around 18 lakh values. So yeah, this will take some time. Meanwhile, let me just comment this. Okay, so in the next stage, what we are going to do is, let's see how this value over here would look like. So let us now first execute this. All right, so let us now see how our data frame will look like. So let me execute this block now. So as you can see here, our names have been completely changed or converted into a list of numbers. But now only issue that we are trying to have is the imbalance in the size of the list. Because when we are trying to have the number of boxes, right, we won't be having variable number of boxes. Okay, so what we're going to do is either we set a value like something like take an average number like 10, 20, or you can take something like, something like you either depend on maximum number or the minimum number of list. But the thing is, if you take the maximum number, then we have to pad a lot of zeros, and this would lead to a loss. So if I reduce the size, this would also decrease the accuracy, right? So what we're going to do is we'll plot this name and gender in the form of a histogram. So let's take here X. This would be df names, and we'll give here as dot values. And then same thing, we'll do it for Y, df gender, and this would be dot values. So what we'll do is we also need a list. Okay, so now as we are going to plot this on a histogram, and what we are going to see in the histogram is just to analyze, this is a graph. We want to analyze, where does the highest number of sequence, or if suppose this is a size, if this is size 8 and this is like 8,000 words or 8,000 names have the size 8, then we can keep our average somewhere near, and then we can also decide, if the number after 10, if not many names have a longer number or the longer length of that name, so we can keep our average somewhere around 9 or 10. Okay, so let's now quickly see how we can do that to get the length of our names. So length X or name length, this would be like list comprehension for I in range 0, df dot shape of 0. And now what we're going to do is we need to find the length. So this would be length X of I. Over here you can either give df or you can also give this X, right? So it would be length of X. Okay, so let me quickly execute this. Okay, so here we're getting an error. Oh yeah, it's not O, it's going to be 0, right? So let me execute this now. Okay, so let me show you how this would look like. Name length, and let me print this off. So as you can see, this is giving me a list of names. So there are a huge amount of names. So as you can see, first we had 5, 5, and then 9. So let's now plot this and see how it would look like. Import matplotlib splt. All right, this is perfect. So now what I'm going to do is I have to plot this, right? So all I'm going to do is plt.hist. All right, and now I'm just going to give name length and number of bins. This would be like, let's give 20, okay? And then plt.show. Okay, so what do we find from this graph over here? You see, this is nothing but the length of the names. So 2, 4, 6, 8, 12. All these are the length of the names. And this is nothing but 0, 5,000, 10,000. This is nothing but number of names that have a length 4 or number of names that have the length 6. So as you can see, right, there are around almost 25,000 names whose length is 6. And then as I cross like 10 or as I cross 12, not many names are there whose length is greater than, 12. So what I'm going to do here now is, now we have to pad, right? Now we have to pad the number of zeros. So in order to pad zeros, we have something called as built-in function from Keras. So from Keras, or you can also set as Keras dot preprocessing dot sequence import pad sequence. So let me quickly execute this now. And now what I'm going to do is I'm going to create a new list. So let this be X. This is in lowercase. So pad sequence. And the things that this is going to take is obviously the sequence. We have to give a list of sequence. Okay. And then we'll give something like df.names. And then this is going to be values. And now we want to define the max length. So this is going to be 10. We also have an option of providing where do you want to do the padding. So you can also do it as pre or post. We'll obviously be doing pre. So let's see, how do we do that? This would be nothing but, if you can see this sequence over here. So we have padding is equal to pre. It's by default, right? So pre. So let me execute this now. And let's see how this X would look like. Okay, so as you can see here, X is a matrix whose length is 10. Okay, so each of these, like this is nothing but 19 million cross 10. So there are 10 columns throughout all. So now what we're going to do is we're going to create our own model. So for that we'll do from keras.layers import input layer, and then we have to have embedding layer, because if you don't have embedding layer, then it would be like each input would be something like 1.9 million, that is 18 lakhs. So it's a pretty huge value to compute. So we don't want that. So that's why we'll use embedding layer. Then we have dense layer, and then we have LSTM. We also, rather than taking this as a sequential model, we'll take it as, feed forward. So what we'll do is from keras.models import model. So now what we are going to do is we'll have to create our input layer. So this will be input is equal to input. And now the shape that we are going to pass over here. So for this shape, so how many columns do we have? We obviously have 10 columns, right? So it's going to be 10. So now what we're going to do is next we are going to have embedding layer. So let's say this is EMB and this would be embedding. So input over here, or the input dimension over here, is nothing but vocab size. We haven't defined this vocab size, so let's quickly do that. So vocab size, this would be nothing but length of vocabularies plus 1. The reason why I'm doing plus 1 is because we also have zeros over here, right? And this would be like vocab size if you want to see. And let me execute this. So we have 27, right? So 26 are the number of alphabets, and 1 is because we have number of zeros. So we'll pass this as vocab size. Okay, and now we are also going to pass output dimension. So output dimension, this is nothing but how many dimensions we want. So now this is going to be 5. All right, and the input for this embedded layer is going to be from INT. Okay, and now we are going to have our first LSTM layer. So it's going to be LSTM1. So this would be LSTM layer. Number of units we have to define here. So units, this is going to be like 32. The units over here does not represent the number of boxes. The units over here represent the A values, right? So now we have to do return sequence, and this is going to be true. And the input for this is going to be from embedded layer. Then we have LSTM second layer, and this is be LSTM units we're going to pass. So number of units that we're going to pass now is 64. And now the input for this is going to be LSTM1. Finally, we have an output layer. So at the end, right, we're going to have a dense layer, right? So dense. So number of units or number of neurons at the end, we are going to have 1. And kind of activation function that I'm going to have here is going to be sigmoid, because we have to predict either it's a male or a female. Okay, so sigmoid, and the input for this is going to be LSTM2. So finally, we have to add this to our model. So I'll give it as my model. This would be model. So now I have to define the inputs. So INPUTs, this is going to be inputs, INP, and outputs, this is going to be out. Okay, so let me quickly execute this now. Okay, so we have this error. Please provide either a shape. Okay, so let's see what's, oh yeah, oh here I've given it as sparse, right? So it's not going to be sparse, it's going to be shape. So let me quickly execute this once again. Okay, as you can see, we have successfully executed this. And now let's see the model.summary. So as you can see here, first off, we have input layer. Okay, so we can have a number of values, but there will be only 10 features. Okay, that's 10 columns. And then we are going to have, once you go through this embedding layer, then, instead of having 10, instead of having that 1 million or whatever it is, 1.8 million, we'll have just 135 parameters. Okay, similarly over here, and finally at the dense, we have 65 parameters, and then we have 1. The reason why we have 65 here, just for, if you don't know, is because 64 plus 1 bias, and this would give us 65. Okay, so now finally we are going to train our model, but before that we have to compile it. It's going to be my model dot compile. Okay, so we have to find an optimizer. So optimizer, best one that I feel is Adam. Then we have to find the loss. So as we are going to use just 2 predictions, right? It's either it's male or female. We'll use binary cross entropy. And then finally the matrix that we want to use here is, this will be accuracy. So let me execute this now. And finally, we are going to compile this. So we'll have history. So this will be model.fit. Okay. And now we are going to pass our values. We're going to give X. We're going to give Y. As you know, X is nothing but the matrix, which has a padding. And Y is nothing but, the other classes. They're telling us either it's ones or zeros. And number of epochs, this is going to be 10. Batch size, as this is a pretty huge data set, we are going to keep a pretty high batch size. So I'll give a batch size here as 256. And then finally, we need validation split. Okay, it's not going to be my model, it's going to be my model, right? So my underscore model. So finally, we're going to have validation split here. So let's give it as 20%. So it's going to be 0.2. All right, so finally, it's the moment of truth. Let us now execute our code. This should take some time to execute. So let's see how this would look like. Okay, so if you can analyze this data over here, so as you can see, right, this validation accuracy has to increase. And we cannot see every time, if our model is overfitting, the accuracy over here will keep on increasing. All right. So the more reliable source over here to see is nothing but validation accuracy. So if validation accuracy is increasing, that means our model is neither overfitting nor underfitting. And you can also see that we have our validation loss, which is kind of decreasing. And over here as well, we can see the validation loss. Over here, we can see the loss of a model is decreasing from 60, then 40, then 39, 39, and 80, 38. So let's now wait for a few more epochs. So we have 4 more to go. Okay, so as you can see here, our validation accuracy has been increasing. So this is a very healthy growth. And even over here, our accuracy of a model is also increasing. Fine. And the loss is decreasing. It's decreased from 60% to 37%. And over here, our validation loss decreased from 42% to 36%. So let us now map this, like whatever values we have received. So in order to map this, we have H. This model over here retrieves us the history function, right? So we'll give hist.history, and let me execute this. Okay, so now what we're going to do is, this is nothing but key value pairs. So if I put H, if I give something like accuracy, okay, well, let's plot this. So model.plot, right? So plt.plot. Okay, we'll have accuracy. We'll compare this with respect to accuracy, and then plt.plot. Then we'll have validation accuracy, and we want to show this, right? So plt.show. So as you can see here, okay, so just to give a better analogy, let's execute one of these first. Okay, so the blue line over here represents the accuracy of a model, and then this is nothing but the accuracy of our training data, right, or testing data. So as you can see, our model accuracy isn't decreasing, so it's a very good model and it has trained very well. So now coming down to the moment of truth. So let's now take a random name and see whether it can predict whether the name is true or false. Okay, so we'll give here as test_name. So let's give something like, this would be like name, right? So we'll give name.lower. And now we are going to pass the name over here. So this would be, let's say, Tom. Okay, so we have to convert this into letters, right? So it will be vocab of I for I in test name. And now we'll give the name here as xtest. So this would be nothing but we have to pad the sequence, pad sequence. We'll pass this in a form of a tuple. Then this would be seq. And then we know that we have to pad 10, right? And anyways, we don't have to say whether it's pre or post, because by default it's going to be pre. Fine. So let us now see how our text data would look like. So X test string attribute has, okay. Oh yeah, so I have done a typo over here. It's going to be LOWER. So let me execute this once again. So as you can see here, we have a matrix which has a size of 10. And let's now see what this would predict. So it's the moment of truth. So y.predict, this would be model.predict. And I'm going to pass here as X test. And let's see what does this predict. So we'll give here as ypred. And yeah, let us execute this. Okay, so we are getting this in a form of an array. So what this tells us, this tells us that, this is like 70% chances that this name is Tom. In order to make this, layman stuff, so what we are going to do is we'll have if ypred. Let me execute this first. So let me go down to another block. So this would be something like if ypred is less than 0.5, then we'll say the name is female, okay? Else print name is masculine or name is, or let it be male, okay? So same thing over here, we'll just keep it as male. So let's now see what this thing predicts. Okay, so this thing predicts male. So let's take another common name. Let's take something like, let's go to Google and see what name can we take. Yeah, we can take up something like Brad Pitt. Okay, so let's execute this and let's execute this again and then this. So as you can see here, this is giving me a male name. And let's give a female name over here. Let's give as Mary. And let's see whether this would predict it as male or female. So as you can see here, it's female. Now, as if you have seen the data set, right, it says this is the name from the US kids, right? What will happen if I give an Indian based name? So let me give an Indian based name like Priyanka. And let me execute this. It's giving me a female name, right? So this is something pretty astonishing, right? So why do you think it gave me a female name? Well, the reason is because when we are training this model, like RNN, using RNN, right? It's not looking at the name. It doesn't know whether the name is female or not. But as a matter of fact, it is looking at the pattern, okay? So it might be looking at, if the name ends with so-and-so, it is a female. If the name starts with this, or if a name have something like this, it means, it's a female or a male. So to give you a better analogy, let's give something like Julia. So let me execute this. This will give me a female, right? So what if I give something like Junaid? This would give it as male. So all it's trying to do is it's trying to see, recognize a pattern. That's why it's taking individual words at the same time. So this is what makes NLP using LSTM very effective. All right, so moving ahead, let's see some of the LSTM's use cases. You see, LSTM is a very popular deep learning algorithm for sequential models. Apple Siri and Google's voice search are some of the real-world examples that have used LSTM. And you won't believe it, LSTM is a success story for those algorithms. So let us now have a look and see how LSTM changed that technology. Okay, so starting off with Apple. In 2003, Apple was the first major tech company to integrate a smart assistant, that is Siri, into an operating system. And the Siri was actually a byproduct of some other company. So Siri was a company's adoption of a standalone app that has been purchased along with the creators who made it. It was somewhere in 2010. The initial reviews about Siri was that it was intense. But over the next few months and years, the users became more impatient with the shortcomings. And all too often, it wrongly interpreted commands. And then, no matter what you do, there was no fix for it. So this is when Apple moved Siri's voice recognition to a neural-based system. Some of the previous techniques remain operational, something like, applying hidden Markov models. But most of the time, DNN or deep neural network using LSTM was used. Although people did not find any changes on the outside, but from within it was a supercharged deep learning model. Speaking about Google's implementation, Google implemented Google Voice Search somewhere in 2009. Google Voice Transcription had initially used something called as Gaussian matrix model. This was nothing but an acoustic model, and this was something considered to be a state-of-the-art speech recognition for almost 30 plus years. But it was in 2012 there was a boom in deep neural network. And when Google implemented deep neural network, that too using multiple layer networks, there was a huge performance gap. But things really improved when the recurrent neural network, especially with LSTM RNN, first launched on an Android speech recognition in May 2012. Compared to deep neural network, LSTM RNNs have additional recurrent connections and memory cell that allows them to remember the previous data. Alright, so moving ahead to our last topic of our session, let us now see some of the real-world applications of LSTM RNN networks. First off, we can perform name entity recognition. This is something which we did in our previous demo, right? So what is this name entity recognition? You see, name entity recognition is a subtask of information extraction that seeks to locate and classifies name entity mentioned in an unstructured data. Okay. Next, we have something called as sentiment analysis. Sentiment analysis is a predictive modeling task where a model is trained to predict the polarity of a textual data or sentiments like positive, neutral, or negative. Sentiment analysis is performed by various businesses to understand their consumers' behavior towards the product. Then we have machine translation. The task of machine translation consists of reading text in one language and generating text in another language. When neural networks are used for this task, we talk about neural machine translation. Within neural machine translation, an encoder-decoder structure is quite a popular LSTM RNN architecture. Why should we choose deep learning for various tasks? So the big advantage of using deep learning is that we can extract more number of features. And when we have more number of features and when we can work at the same time with huge amount of data, we can perceive an object like a human being does. What I'm trying to say over here is, like, if you want to perform a classification task between pen and a pencil, you'll obviously know, as a human being, you'll know the difference because you have looked at a pen and a pencil continuous number of times. And now when you're trying to actually classify it, you can do it with ease. Okay, and the reason for this is because you know the features of a pen and you know the features of a pencil. Okay, similarly, this is how deep learning works. More the data you feed, more the dimensions it can analyze, more the dimensions it can learn. All right, so as I've already mentioned, one of the most popular application of deep learning is image classification. And when it comes to image classification, it can be something as simple as classifying between two different animals to something as complicated as hiding data or trying to run automated cars using classification tasks. Okay, all right, so next type of application using deep learning is using on sequential data. Sequential data basically refers to something like time series data or having to understand natural language. So the reason why we call it sequential data is because here the previous word or the previous feature is dependent upon the next feature. Okay, so as you can see over here, we have what time is it, right? So if I just say it is, like over here, what time is and it are basically features, right? And in order for you to make an analogy or to understand, obviously you have to know what has happened in the past. So in order to do this, we use something called as RNNs. Okay, and there are various versions of RNN that go around in order to overcome the disadvantages, which we'll look in some time. All right, so moving on to the next application, that is GANs. GANs, which stands for Generative Adversarial Network, is an unsupervised part of a deep learning application. Some of the common applications which you can see in recent days is nothing but deep fakes and many more. Finally, coming down to performing classification and regression tasks using multi-layer perceptron. If you remember, or if you're well versed with machine learning, in order to perform classification in machine learning, we had algorithms like decision tree, random forest, or something very simple as linear regression or logistic regression. But let me tell you what, when we try to perform classification using MLP or multi-layer perceptron, we get a very high accuracy even compared to SVM and decision trees. Alright, so now that we know what exactly is deep learning and why we use it, let's now stream down to understand how can we process natural language data using RNNs. So what are RNNs, right? Well, RNN basically stands for Recurrent Neural Network. And we usually use this in order to deal with a sequential data. Sequential data can be something like a time series data or a textual data of any format. So why should one use RNN, right? Well, this is because there's a concept of internal memory here. RNN can remember important things about the input it has received, which allows them to be very precise in predicting what can be the next outcome. So this is the reason why they are performed or preferred on a sequential data algorithm. Okay, and some of the examples of sequential data can be something like time series, speech, text, financial data, audio, video, weather, and many more. Although RNN were the state-of-the-art algorithm for dealing with sequential data, they come up with their own drawbacks. And some of the popular drawbacks over here can be like, due to the complication or the complexity of the algorithm, the neural network is pretty slow to train. And as there are a huge amount of dimensions here, the training is very long and difficult to do. Okay. Apart from that, the most decisive feature for RNN or for the improvement in RNN is that of a vanishing gradient. What this vanishing gradient is that, when we go deeper and deeper into our neural network, the previous data is lost. This is because of a concept called as vanishing gradient. And due to this, we cannot work on a large or a longer sequence of data. Okay. To overcome this, we came up with some new or upgrades to the current recurrent neural networks, or RNNs. Starting off with bidirectional recurrent neural network. You see, bidirectional recurrent neural network connect two hidden layers of opposite direction into the same output. With this form of generative deep learning, the output layer can get information from past, future states simultaneously. So as you can see here, we have two layers over here. And as they are bidirectional, what happens is when the algorithm feels that it is kind of losing its gradients or the previous data, it can go back and get the data from the past. So why do we need bidirectional recurrent neural network? Well, bidirectional recurrent neural network duplicates RNN processing chain so that the input process both forward and reverse time order, thus allowing bidirectional recurrent neural network to look into future context as well. The next one is long short-term memory. Long short-term memory, or also sometimes referred to as LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. Unlike standard feed-forward neural network, LSTM has a feedback connections. It can not only process single data point, but also the entire sequence of data. So as you can see here, from what I'm trying to say is, with LSTM or long short-term memory, it has something like, we can feed a longer sequence compared to what it was with bidirectional RNN or RNNs. So why is LSTM better than RNN? We can say that when we move from RNN to LSTM, we are introducing more and more control over the sequence of the data that we can provide. Thus, LSTM gives us more control ability and thus better results. Alright, so the next type of recurrent neural network is the gated recurrent neural network, or also referred to as GRUs. You see, GRU is a type of recurrent neural network that is, in certain cases, is advantageous over long short-term memory. GRU makes use of less memory and also is faster than LSTM. But thing is, LSTMs are more accurate while using longer data sets. I'm sure by now you might have got a hint about the trend that has led to the improvement, right? So the trend over here is, the model should be capable of remembering and taking in on a longer input sequence. The game changer part for the sequential data was developed when we came up with something called as transformers. And this paper was something which is based on a concept called as attention is everything. All right, so let's take a look at this. The paper, Attention is All You Need, introduces a novel architecture called as transformers. Like LSTM, transformers is an architecture for transforming one sequence into another while helping other two parts, that is encoders and decoders. But it differs from previously described sequence to sequence model because it does not work like GRUs. Okay, so it does not implement recurrent neural networks. Recurrent neural network until now were one of the best ways to capture the timely dependence on a sequence. However, the team presenting this paper, that is Attention is All You Need, proved that an architecture with only attention mechanism does not use RNN can improve its result in translation tasks and other NLP tasks. One of the best examples for transformers is Google's BERT. So what exactly is this transformer, right? You see here we have encoder on the top and decoder on the bottom. Both encoder and decoder are comprised of modules that can stick onto the top of each other multiple times. So what happens here is the inputs and outputs are first embedded into n-dimension space since we cannot use this directly. So we obviously have to encode our inputs, whatever we are providing here. One slight but important part of this model is the positional encoding of different words. Since we have no recurrent neural network that can remember how sequences are fed into the model, we need to somehow give every word or part of our sequence a relative position since the sequence depends on the order of the elements. Okay. These positions are added to the embedded representation of each words. Alright, so this was the brief about transformers. So let us now move ahead and see some of the popular language models that are available in the market. Alright, so let us now start off by understanding OpenAI's GPT-3. The successor to GPT and GPT-2 is the GPT-3 and is one of the most controversial pre-trained models by OpenAI. The large-scale transformer-based language model has been trained on 175 billion parameters, which is 10 times more than any previous non-sparse language model. The model has been trained to achieve strong performance on many NLP datasets, including tasks like translation, answering questions, as well as several other tasks. Then we have Google's BERT. BERT stands for Bidirectional Encoder Representations from Transformers. It is a pre-trained NLP model which is developed by Google in 2018. With this, anyone in the world can train either their own question answering module with up to 30 minutes on a single cloud TPU, or few hours using single GPU. The company then released this showcasing the performance of 11 NLP tasks, including very competitive Stanford dataset questions. Unlike other language model, BERT has only been pre-trained on 250 million words of Wikipedia and 800 million words of book corpus, and has been successfully used as a pre-trained model in deep neural network. According to researchers, BERT has achieved 93% accuracy, which has surpassed any previous language models. Next, we have ELMO. ELMO, also known as Embedding for Language Model, is a deep contextualized word representation that models syntax and semantic words as well as their logistic context. The model developed by Allen NLP has been pre-trained on a huge text corpus and learned functions from bidirectional models, that is BiLM. ELMO can easily be added to their existing models, which drastically improves the features of functions across vast NLP problems, including answering questions, textual intent, and sentiment analysis.
What are GANs? So we are going to start with generative models. So generative models are nothing but those models that use an unsupervised learning approach. In a generative model, there are samples in the data, that is input variables x, but it lacks the output variable y. And we use the only input variables to train the generative model, and it recognizes patterns from the input variables to generate an output that is unknown and based on the training data only. In supervised learning, we are more aligned towards creating predictive models from the input variables. And this type of modeling is also known as discriminative modeling. And in a classification problem, the model has to discriminate as to which class the example belongs to. And on the other hand, unsupervised models are used to create or generate new examples in the input distribution. To define a generative model in layman terms, we can say generative models are able to generate new examples from the sample that are not only similar to the examples but are indistinguishable as well. And the most common example of a generative model is a naive Bayes classifier, which is more often used as a discriminative model. Other examples of generative models include Gaussian mixture model and a rather modern example, that is generative adversarial networks. So let us try to understand what exactly are GANs, or generative adversarial networks. Generative adversarial networks, or GANs, are a deep learning based generative model that is used for unsupervised learning. It is basically a system where two competing neural networks compete with each other to create or generate variations in the data. It was first described in a paper in 2014 by Ian Goodfellow, and a standardized and much stable model theory was proposed by Alec Radford in 2016, which is also known as DGCAN, also known as DCGAN, or we can call it as Deep Convolutional General Adversarial Networks. And most of the GANs today use Deep Convolutional General Adversarial Networks. The GANs architecture consists of two submodels known as the generator model and the discriminator model. So a generator network takes a sample and generates a sample of data. A discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the form or the range 0 and 1. So let us go ahead and take a look at how GANs actually work. To understand how GANs work, let's break it down. So generative means that the model follows the unsupervised learning approach and is a generative model. When we talk about adversarial, the model is trained in an adversarial setting. And network simply means for the training of the model, we use the neural networks as artificial intelligence algorithms. In GANs, there is a generator network that takes a sample and generates a sample of data. And after this, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 to 1. The generative model analyzes the distribution of the data in such a way that after the training phase, the probability of the discriminator making a mistake maximizes. And the discriminator, on the other hand, is based on a model that will estimate the probability
that the sample is coming from the real data or not the generator. The whole process can be formalized in a mathematical formula. So G over here is generator, D is equal to discriminator, P data X is the distribution of real data, P data Z is the distributor of generator, X is the sample from the real data, and Z is the sample from generator, where DX is the discriminator network and GZ is a generator network. So let's take a look at the flowchart once again, guys. So we have the training data, which is going to give the real sample, and the generator network is going to generate the sample from the random noise or the examples. And then it will go to the discriminator network, where it's going to check if the sample that is coming is real or fake. So that is how a GAN actually works. Now let's take a look at the training phase, like how a generative adversarial network is actually trained. So it happens in two phases, guys. So the first phase is where we train the discriminator and we actually freeze the generator, which means that the training set for the generator is turned false and the network will only do the forward pass and there will not be any back propagation. Basically, the discriminator is trained with real data and checks if it can predict them correctly. And the same with the fake data to identify them as fake. After this, there's the second part where we train the generator and freeze the discriminator. So we get the result from the first phase and we use them to make better from the previous state to try and fool the discriminator better. So to understand this in the layman's term, I'm gonna tell you a few steps for training, like how you should start. So the first step is you have to define the problem. You have got to define the problem and collect the data. After this, the second step is you have to choose the architecture of GAN. So in this step, depending on your problem, you have to choose how your GAN should look like. The third step is training the discriminator on real data. So we train the discriminator with real data to predict them as real for n number of times, or we call it epochs as well. And then we generate the fake inputs from the generator. So in this step, we are going to generate the fake samples from the generator. And the next step is we train the discriminator on fake data. So whatever samples are generated from the generator network, you're going to train the discriminator to predict the generated data as fake. So that's how we know that discriminator is actually predicting the values as correctly. And the last step is we train the generated with the output of discriminator. So after getting the discriminator predictions, we train the generator to fool the discriminator. So that's how we train the GAN to actually get our solution from the problem, which is like defining the problem. So you'll understand this when I'm talking about the applications, guys. So no worry. Now let's go ahead and take a look at a few challenges of generative adversarial networks. So the concept of GANs is rather fascinating, but there are a lot of setbacks that can cause a lot of hindrance in its path. Some of the major challenges faced by GANs are, the first one is the stability. So there has to be a stability that is required between discriminator and the generator network. Otherwise, the whole network would just fall. For example, in case, let's say, if the discriminator is too powerful, the generator will fail to train altogether. Won't be able to push fake samples to the discriminator and it will always identify them as fake. And let's say if the network is too lenient, the discriminator network is too lenient, so any image that would be generated by the generator network would make the network useless. The next challenge that is faced by GANs is GANs fail miserably in determining the positioning of the objects in terms of how many times the object should occur at that location. Suppose we have a image in which we have, let's say, 3 dogs with 2 eyes, and sometimes a GAN will fail to determine the positioning of the objects in terms of it will generate an image with like 1 dog and 6 eyes. So that's kind of a problem that we face while working on GANs. And the next challenge is 3D perspective troubles GANs, as it is not able to understand the perspective also. So it will often give a flat image for a 3D object. So that's one challenge that we face with GANs as well. And GANs have a problem of understanding the global objects, and it cannot differentiate or understand a holistic structure. Like if you're talking about trees or if you're talking about flowers, that's a problem that GANs will follow. And last but not least, newer types of GANs are more advanced that I've talked about, that is deep convolutional generative adversarial networks, and are expected to overcome these shortcomings altogether. So we don't have to worry about these. These are the shortcomings that we face with normal GANs. the initial generative adversarial networks. Now that they have become more advanced, they actually overcome these shortcomings, so you don't have to worry, guys. So last but not the least, I want to talk about a few applications of generative adversarial networks. So the first one is prediction of next frame in a video. So let's say the prediction of future events in a video frame is made possible with the help of GANs, and DVD GAN, or we can call it as dual video discriminator GAN, can generate a 256 by 256 videos of notable fidelity up to 48 frames in length. And this can be used for various purposes, including surveillance, in which we can determine the activities in a frame that gets distorted due to other factors like rain, dust, smoke, etc. So the possibilities are immense with this. If you are able to predict the next frame in a video, that actually helps in a lot of things like surveillance, security, and we can predict outcomes based on these frames that we generate from a video. After this comes the text to image generation. So basically object driven attentive GAN, which is also known as object GAN, performs the text to image synthesis in 2 steps. So the first step is generating the semantic layout, and then generating the image by synthesizing the image by using a deconvolutional image generator is the final step. So this could be used intensively to generate images by understanding the captions, the layouts, and refine details by synthesizing the words. And there is another study about the story GANs that can synthesize the whole storyboards from mere paragraphs. So that's actually a very good idea if you're talking about GANs. So you can just give a few layouts and captions. Based on that, it will generate an image for us. Talking about the next application, we have image to image translation. So Pix2Pix is a model which is designed for general purpose image to image translation. So let's say we have 3 images. We have a real image, then we'll be having a generated image, which is basically a fake, and then it will be reconstructed to the previous image, which was real. So this is how image to image translation work, guys. And after this, we have enhancing the resolution of an image. So super resolution generative adversarial network, or also known as SR-GAN, is a GAN which can generate the super resolution images from low resolution images with finer details and better quality. So this is actually a very good application of GANs, guys. The applications can be immense. So you imagine a higher quality image with finer details generated from a low resolution image. The amount of help it would produce to identify details in low resolution images can be used for wider purposes, including surveillance. We can use it for documentation, security. We can use it for detecting patterns, etc. And last but not least, we have interactive image generation. So GANs can be used to generate interactive images as well. And Computer Science and Artificial Intelligence Library, also known as CSAIL, has developed a GAN that can generate 3D models with realistic lighting and reflections enabled by the shape and texture editing. And more recently, researchers have come up with a model that can synthesize a reenacted face animated by a person's movement while preserving the appearance of the face at the same time. There are a lot more applications we can work on. Evolution of AI. So AI as we know today is entirely different from where it started. Back in the 18th century, it was entirely based on myths, speculations, and fiction. But it did start taking shape, and the real initiation in its truest essence took place in 1956. The AI surge began with 6 major design goals. The first one was teach the machines to reason in accordance to perform sophisticated mental tasks like playing chess, providing mathematical theorems, and others. The second one is knowledge representation for machines to interact with the real world as humans do. Like machines needed to be able to identify objects, people, and languages. Programming language Lisp was developed for this very purpose. The third one is teach the machines to plan and navigate around the world we live in. With this, machines could autonomously move around by navigating themselves. The fourth one is enable the machines to process natural language so that they can understand the language, conversations, and the context of speech. The fifth one is train the machines to perceive the way humans do, like touch, feel, sight, hearing, and taste. And general intelligence that included emotional intelligence, intuition, and creativity was the sixth point. Talking about machine learning as we know can be remotely explained with the evolution of robots in the past years. Although Machine learning isn't just a machine that is going to learn stuff. It has a lot more to it. Basically, we have data at our bay. We train and test the model, which in this case can be a robot, and then make it to do tasks relevant to the learning. And then again, learning can be of different types, which is supervised, unsupervised, reinforcement, etc. To know more about machine learning in detail, refer to our machine learning full course tutorial to get on speed. Now, let us go ahead and take a look at what exactly is AI and machine learning. So, what exactly is AI? According to the Merriam-Webster dictionary, artificial intelligence is a branch of computer science dealing with the simulation of intelligent behavior in computers. AI is a technique that enables machines to mimic human behavior. Artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. If you ask me, AI is the simulation of human intelligence done by machines programmed by us. The machines need to learn how to reason and do some self correction as needed along the way. And artificial intelligence is accomplished by studying how human brain thinks, learns, and decide to work while trying to solve a problem, and then using the outcomes of this study as a basis of developing intelligent software and systems. Now let us go ahead and take a look at what exactly is machine learning. So machine learning is a concept which allows the machines to learn from examples and experiences, and that too without being explicitly programmed. So instead of you writing the code, what you do is you feed the data to the generic algorithm, and the algorithm or the machine builds the logic based on the given data. Machine learning algorithms are an evolution of normal algorithms, and they make your program smarter by allowing them to automatically learn from the data that you provide. Now that we know what AI and ML actually is, let us go ahead and take a look at a few applications of AI ML today. So AI ML can be widely used in so many applications, and I have listed down a few applications to give you a wider perspective. So first of all, I'm going to talk about the usage of AI and ML in healthcare. AI and ML in healthcare is an angel in disguise. To understand this, imagine you have the past data of millions of patients with diseases in the past. Now, all this data can be put to an effective use in a sense that we would be able to detect a disease in early stages with the help of machine learning and artificial intelligence algorithms. And since the numbers never lie, we can be pretty sure about the accuracy of the results. Even so, if we have any doubts, we can always check the accuracy in almost all the cases. Now let's talk about the usage of AI ML in finance. So artificial intelligence in finance is transforming the way we interact with money. AI is helping the financial industry to streamline and optimize processes ranging from credit decisions to quantitative trading and financial risk management. And if we have that figured out, it saves us from a lot of bad and risky decisions. Now let us go ahead and take a look at object detection, in which we use AI and ML. So object detection today is playing an important part in the IT industry. For example, surveillance has never looked more tech savvy. Google Lens is one example that uses image recognition to identify the images on the camera in real time. Now let us go ahead and take a look at AI ML in risk detection and predictive analysis. So predictive analysis has proven its mettle in the industry already, with almost every organization using it to derive conclusions based on previous data. So one example is how sports franchisees such as a cricket team would take account of the performance of a player, let's say a batsman, facing the deliveries of bouncer and short ball deliveries. So they will be able to figure out the best possible outcomes based on the shot selection and strategies using the artificial intelligence and machine learning algorithms. So this is one way we can use predictive analysis, and it's just one example. We can use it for many purposes. Like we can use it to predict stock prices that we can do in finance, and we can use it to predict the weather based on the hundreds and hundreds of years of data that we already have. Now let's talk about AI and ML in marketing and advertising. So marketing and advertising industry is the most benefited with the evolution of AI and ML. They are able to recognize the browsing patterns of users through data and target users with specific content on the internet. For example, to reach out in a subtle way, you only see those ads which interests you. And you must have felt sometimes like you keep getting ads or the content on the internet that you talk about or you were talking about or you were thinking about. It's basically nothing but AI and machine learning that is learning a pattern through the data and your browsing history or your browsing pattern and reaches out to you in the form of targeted marketing. And now that we have talked about the current applications, let us talk about how AI and ML will shape up in the future and how it would look like 10 years, maybe 20 years from now. So we cannot be sure about if AI and ML would shape in the future like we have seen in the movies, but For now, we will stick to the realistic possibilities. Although when I say realistic possibilities, we are not really sure how it would look like, but we can take a guess. So when we talk about future of healthcare would seem pretty reachable and advanced. Even now, researchers are working on detecting diseases in the early stages based on the lifestyle and other relevant data. And in the future, we can expect more advancements in the psychological part as well, where we will be able to identify traits and warnings in the early stages and work on it before it gets the better of us. Now imagine being able to cure a disease before even getting the hint of it. That is what researchers are aiming for. And it looks pretty promising, guys, let me tell you. Now let's talk about the future of self-driving cars. So self-driving cars looks like a dream come true today. But in the coming decades, we are going to see a lot of developments in the self-driving cars. We would have overcome all the challenges that we face today. And I'm not saying we will have levitating cars driving you to your destinations, but it won't be less than a fascinating experience that may look like a dream today or you might have seen in the movies. Now, let's talk about the AI/ML in manufacturing that would take the future. So, robots in manufacturing is one thing that is going to change the future for us. Manufacturing industries will have the best ever workforce, and I'm not talking about the human aspect of it. The manufacturing would be so much easier with the robots, and since they don't get tired and they won't even ask for leaves, or they might, we never know. And AI in robotics is a risky slope, although, but that is not entirely true. Researchers and experts are working day and night to make it as safe as possible. And then again, let me talk about future of finance with AI and ML. So managing finance and risk detection would become a piece of cake. And to understand this in layman terms, you will be able to do your taxes without even lifting a pen. And the fraud detection and trading would become a lot easier and accessible. Financial advisory would take a much advanced shape as we are already seeing it with a lot of trading applications in the market. Then again, we have computer vision, which is going to change the future for us. And I'm sure most of you are aware of the concept of God's eye that we have already seen in the movies, although it is fictional, but not sure for the wrong reasons, but for the greater good. This might be the possibility in the coming years as computer vision has started to overcome a lot of challenges in the real time image recognition. And then we have the future of NLP, natural language processing, and it's going to, it would open a lot of linguistic barriers in the conversational AI. The conversational AI that we see today is limited to certain tasks, but in coming years, it could be like a personal assistant or even a life guide as well. And with the recent advancements, we are aiming for a very flexible interface that is going to work for everyone with any linguistic experience or any linguistic expectations. And then we have a rather fictional concept that I'm going to talk about, which is immortality through AI. So there are scientists and researchers who are trying to figure out a way to map the brain simulation on a computer. So immortality isn't just living until the very eternity. It is, in my opinion, leaving a legacy. And but in hindsight, this task is pretty impossible. But we never know in the future. This might be a possibility, and we will be able to live through a computer where people would have figured out a way to shift all our brain simulations onto a computer and it'll be able to think on its own like our own very image. So that is one possibility with the future in AI and ML that many researchers are actually aiming for, and we might as well get through with it. So hang in there, guys. And now let me just talk about a key skills of AI and ML specialists. There was a lot of applications that I just told you about. Now let's take a look at what are the skill sets that are required to become a AI ML specialist in today's world. So first of all, you have to be familiar with programming in Python, and you must be very well aware of maths and statistics as well because it needs a lot of logic to build algorithms and understand them, and there's a lot of applied mathematics behind it as well. So you have to be familiar with maths and statistics and programming language, which is Python, and the versioning tools like TensorFlow, Keras, PyTorch, etc. And then you must have an expertise in one of the following machine learning domains, which is image processing, computer vision, language processing, speech signal processing, etc. And then you must have an advanced knowledge in deep learning algorithms as well, because it is a very important aspect of AI ML. And there has to be an effective communication skills, and you have to be a problem solver, because in hindsight, if you get a problem, the only thing that an employer seeks from you is the solution of the problem. So anyways, you have to be a problem solver in that skill set, and you must be experienced in data visualization tools and methods like Tableau, Matplotlib, Power BI, etc. And there has to be a knowledge in Ensemble and online learning. And you must have an experience with SQL and other database related languages. And you have to be familiar with parallel computing using GPUs and unique bake systems. So these are the key skills that are required to become an AI/ML specialist, guys. Now let me just walk you through the market trends that looks pretty promising for now. So first of all, I'm going to talk about the market trends, and it looks pretty solid, guys, with the amount of data flowing in each year. That it is pretty obvious that it will be opening a lot of doors for skilled professionals, and the correct approach is to get skilled since it is still in the evolution phase, and we have to scale a lot more possibilities in these domains. So if you have the skill set for it, it's going to be a very bright future for you guys. And to be specific, there are a lot of opportunities in healthcare, finance, conversational AI, or we can call it chatbots, and object detection, etc. Almost every industry would move to automating their processes. And what else than machine learning and AI to do your job? So it is the best time to learn AI and ML if you're looking for a bright career right now. And let us go ahead and take a look at the salary trends as well, so you get the perspective of how much you're gonna get paid. So I have categorized the salary trends in a few job profiles in AI and ML. For a machine learning engineer, the takeaway fruits of your labor would look around $114,000 a year. And for a machine learning scientist, the average salary looks around $120,000 a year and can go as high as $150,000 a year. And for an AI engineer, the average salary is around $90,000, but it can go as high as $140,000 a year as well. And for an AI researcher, it goes from a $125,000 average to as high as $150,000 a year. And now let us go ahead and take a look at a few companies that are hiring right now for AI and ML specialists. And although there are a lot more companies that are hiring for AI ML specialists right now, I've just listed down a few over here. So we have Ford Motors, we have Capgemini, Accenture, Dell, Deloitte, Google, Amazon, and there are a lot of startups as well, which are actually artificial intelligence and machine learning based. So there's a lot of opportunity for you guys. And let me just tell you the best approach to actually get a job in AI ML industry. So the best approach to find a job as an AI ML specialist, even if you are a beginner or an experienced professional, this works for everyone. So first of all, you have to start with the programming language, preferably Python, because it works best with AI and ML algorithms. And after you're done mastering these basics, start with machine learning and artificial intelligence algorithms. And before that, make sure you are sophisticated enough to work with data. I mean, you can analyze the data, clean it, prepare it for model building, and etc. And try to learn all of them with the implementations on unique data instead of the generic data that you find on the internet. The next step would be to learn the advanced concepts in AI ML like TensorFlow for object detection, speech recognition, image processing, etc. And after you have mastered the versioning tools, you must make sure that you have a credibility in order to get a job. Because as an employer, anyone would look for a credible person proficient enough to do the job. And where will you get that? If you have a relevant master's degree, it is well and good. But if you don't have a degree, you can always go for a certification, which will give you the credibility and it is going to be the best option to prove your mettle. And then there's one way to look at it. I mean, you can take up the Edureka's postgraduate program in artificial intelligence and machine learning, which is going to be a very good deal for you because it is an affiliation with a top college. And then you are good to go. You can apply for jobs and you'll get the job easily if you have all the skill sets and you have the experience in making relevant, you are working on real-time projects as well. So these are going to be very useful for you.
Let's get started with our basic level questions. So first we have, what is the difference between AI, machine learning and deep learning? I'm sure all of you have this question at the top of your mind because there's a huge confusion between AI, machine learning and deep learning. So let's try to understand how they are different. Now, first of all, AI came into existence at around 1950s. All right, this was followed by machine learning and then deep learning was introduced. Now, AI basically represents simulated intelligence in machines, which means that it represents any robot or any machine that can mimic the behavior of a human being. Machine learning, on the other hand, is a practice of getting machines to make decisions without being explicitly programmed to do so. Now, if you don't program a machine, how are you going to let it make decisions? Now, the way machines learn is through data. So the most important thing in machine learning is the data. All right, you're going to train machines using data so that they can make their own decisions. Next, we have deep learning. Now, deep learning is basically the process of using artificial neural networks to solve complex problems. So basically, you can think of deep learning as a field that tries to mimic our brain. Okay, so how we have neural networks in our brain, that's exactly how deep learning uses the concepts of artificial neural networks in order to solve problems. Now, AI is a subset of data science. So guys, first of all, data science is the process of deriving useful insights from data. Right? It's a process of extracting information from data that will help you solve problems. So AI is a subset of data science. Now, on the other hand, machine learning is a subset of AI and data science because machine learning comes after AI. So basically in AI, you're going to make use of techniques and concepts of machine learning in order to solve problems. Then we have deep learning. So it's sort of a hierarchy. First we have data science, then we have AI, then we have machine learning, and then we have deep learning. Deep learning is a subset of machine learning, AI, and data science. Okay, I hope this is clear. Now, the main aim of artificial intelligence is to build machines in such a way that they are capable of thinking like human beings. All right, so basically, they must be able to mimic the behavior of a human being. Now, the aim of machine learning, on the other hand, is to make machines learn by providing them a lot of data. Okay, once you make a machine learn through data, it's going to be able to solve complex problems and find solutions. Now, the aim of deep learning is to build neural networks that are able to solve more advanced and complex problems. Okay, now, like I mentioned, deep learning is like an artificial brain. All right, you're basically building an artificial brain that is able to think exactly like how we do. Okay, that's what deep learning is. It's a little more advanced than machine learning. Now, guys, in short, AI, machine learning, and deep learning are used to solve problems through data. So basically, AI makes use of techniques and methods of machine learning and deep learning to solve problems or to draw useful insights from data. So this is the difference between AI, machine learning, and deep learning. I hope all of you are clear with this. Now let's look at our question number 2. The question is, what is artificial intelligence? Give an example of where AI is used on a daily basis. So there are a lot of definitions of AI on the internet. A few of them are: artificial intelligence is an area of computer science that emphasizes on the creation of intelligent machines that work and react like humans. So like I said, basically a machine that is able to mimic the behavior of a human being is known as artificial intelligence. Another such definition is the capability of a machine to imitate the intelligent human behavior. All right. So artificial intelligence, in short, is basically a machine that we created who can act and think like a human being. Now, where do you think AI is used on a daily basis? There are tons of applications that make use of AI, but one of the most popular applications of AI is the Google search engine. Now, if you just open up Google search and you start typing anything, immediately you get recommendations. These recommendations you derive by using machine learning algorithms, by using deep neural networks, and so on. So on the top of my head, the most general example of AI is the Google search engine. All of us use Google search engine and we know how quick it is with its results and how relevant searches it gives us. All this is because of AI. All right. Now let's look at our next question, which states, what are the different types of AI? Now, a lot of people might not be aware of this because there are a couple of types of AI or a couple of types of machines which are hypothetical. Okay, we haven't actually implemented these machines in the real world. We just have a theoretical definition of these. Okay, let's look at what I'm talking about. So first of all, we have reactive machines AI. Now, these machines are all based on the present actions. Okay, they have no memory or they have no concept of storing memory so that they can learn from their experience. They just react at the moment. Okay, so they're based on present actions and they cannot use previous experiences to form current decisions and update their memory. Then we have limited memory AI. Now, this type of AI has some temporary storage of memory in it. Now, if we have some memory stored in a machine, we know that it can look back into the memory and it can try to make decisions based on previous or past experiences. So limited memory AI makes use of that concept. We have temporary memory here. We do not have permanent memory. But one of the top applications of limited memory AI is the self-driving cars. I'm sure all of you have heard of self-driving cars. They make use of limited memory AI in order to run. Then we have theory of mind AI. Now, like I mentioned earlier, there are a couple of types of artificial intelligent machines which are not actually implemented in the real world. An example of that is theory of mind AI. Okay, this is basically an advanced machine which will have the ability to understand emotions, people, and other things in the real world. We might have come close to this type of AI, but we haven't actually developed something that can understand emotions. Next, we have self-aware AI. Now, this is another such example of a machine that is not built in the real world. This basically includes any machine that has consciousness or that can react just like a human being. Okay, so basically a machine that can take own decisions, that can form own conclusions, and these are machines that have the capability of making their own decisions without any human intervention. Now, this kind of AI is not developed, like I mentioned, because it's going to take up a lot of resources and we still haven't reached that peak of evolution yet. Then we have artificial narrow intelligence. Now, these are the general purpose AI that we see on a daily basis. I'm sure all of you have used Google Assistants, you've used Siri. All of that comes under artificial narrow intelligence. After that, we have artificial general intelligence. Now, these are a little more advanced than the artificial narrow intelligence. Then we have artificial superhuman intelligence. Now, these are one of the most advanced type of AIs that are there. Now, like I mentioned earlier, there are a couple of types of artificial intelligent machines which are not actually implemented in the real world. An example of that is artificial superhuman intelligence. So guys, these were the different types of AI. Now let's look at the next question, which says explain the different domains of artificial intelligence. Now AI covers a lot of different domains, starting with machine learning. Okay, so machine learning, like I mentioned earlier, is the science of getting computers to act by feeding them data and by letting them learn a few tricks on their own without being programmed to do so. Okay, so you're not explicitly programming the machine. Instead, you're feeding it a lot of data so that it understands the data and it makes its own decisions. Then we have neural networks. Now, neural networks are basically a set of algorithms, or you can say a set of techniques, which are modeled in accordance with the human brain. Okay, like I mentioned earlier, deep learning or neural networks is almost the same thing. Deep learning makes use of neural networks in order to solve complex problems. Now we have robotics. Now, robotics is a subset of AI, which includes different branches and applications of robots. These robots are basically artificial agents which act in a real world environment. Okay, so an AI robot works by manipulating the objects in its surrounding, by perceiving, moving, and taking relevant actions. Then we have expert systems. Now, an expert system is basically a computer system that mimics the decision-making ability of a human being. Now, I know all of these domains sound very similar, but they have a very different approach with which they solve a problem. All right, that's the main difference between these domains. Next, we have fuzzy logic systems. Now, traditional systems usually give out output in the form of binary. So usually if you feed something to a machine, it's always in the binary form. The output is also usually in the form of yes, no, true, false, and so on. But when it comes to fuzzy logic, it tries to give an output in the form of degrees of truth. Okay, so it's very different when compared to the traditional computer systems or the traditional programs. Next, we have natural language processing. Now, this is a field of AI that analyzes natural human language to derive useful insights so that it can solve problems. Now, NLP is used majorly in social media platforms. So, Twitter sentimental analysis is done via NLP. Even Facebook uses NLP in a lot of things. Alright, so NLP, fuzzy logic, expert systems, machine learning, neural networks, and robotics are the different domains of AI. I hope all of you are clear with the domains. Now let's look at our next question. Okay, so how is machine learning related to artificial intelligence? There is a huge confusion between machine learning and AI. A lot of people tend to believe that AI and machine learning is one and the same thing. All right, I would say that you cannot compare AI and machine learning because machine learning is a subset of AI. So basically, AI makes use of machine learning algorithms and machine learning concepts to solve problems. That's the basic difference, or that is where the confusion ends. Machine learning is a technique which is implemented in artificial intelligence in order to solve problems. I hope this is clear. Now let's look at what are the different types of machine learning. So there are three types of machine learning. We have supervised, unsupervised, and reinforcement learning. Now, supervised learning is the type of learning in which the machine learns by using labeled data. Now, to make you understand, let's look at an example. Okay, let's say that you've input images of apples and oranges to your machine and you've labeled them. You've told the machine, like, listen, this is the apple, this is an orange, and the output should also look like this. Okay, so you're labeling the input as apple and an orange, and then you're asking the machine to output an apple and an orange. But when it comes to unsupervised learning, you're not going to label them. You're just going to give them images of apple and oranges, and it has to figure out on its own. It has to try and understand the difference between apple and oranges, try and understand how they look different or how they have a different color. So basically in unsupervised learning, you don't have a labeled data set. Okay, you're going to give it an unlabeled data set and you're going to ask it to find out and classify which is an apple and which is an orange. Okay, that's the difference between supervised and unsupervised. Now, reinforcement learning is comparatively different. Let's imagine that you were put off in an island. Okay, let's say that you were left in an isolated island. What would you do? Now, initially, we'll all panic and we won't know what to do. But after a point, you'll start exploring the island. You start adapting to the change in the climate conditions. You start looking for food, and then you'll try and understand which food is right for you and which food is wrong for you. You learn from your experience. So in reinforcement learning, basically an agent interacts with its environment by producing actions and discovers errors or rewards. Now, the type of problems that supervised learning is used to solve is regression and classification. When it comes to unsupervised, it is association and clustering. And in reinforcement learning, it solves reward-based problems. The type of data for supervised learning is labeled data. For unsupervised, it is unlabeled. And for reinforcement, it is no predefined data. Now, when I say no predefined data, I mean that the reinforcement learning agent has to start collecting the data. So basically, in reinforcement learning, from data collection to model evaluation, it does everything. In terms of training, supervised learning provides external supervision in the form of labeled data set. In unsupervised learning, there's no supervision. That's why it's called unsupervised learning. Again, in reinforcement learning, there's no supervision at all. The agent has to figure everything out. Now, how supervised learning works is you map the labeled input to the known output. So basically, you teach the machine, like you tell it that this is the input and this has to be the output. When it comes to unsupervised learning, you just provide data to the machine and it has to understand patterns and it has to discover the output. Now, in reinforcement learning, it has to follow the trial and error method. Okay, there's no particular way in which the agent learns. It just has to explore the environment, try out a few things and learn from that experience. Popular supervised learning algorithms include linear regression, logistic regression. For unsupervised, we have k-means, and for reinforcement learning, we have q-learning. So guys, these were the different types of machine learning, and I also discussed the difference between the three. Now let's move on and look at our next question, which is what is q-learning? In the previous slide itself, I told you that a type of reinforcement learning algorithm is q-learning. So basically here what happens is an agent tries to learn the optimal policy from its past experience with the environment. The past experience of an agent are a sequence of action, state, and rewards. So what happens is, first of all, you take an agent and you put it in state 0. Okay, let's say there's some state known as state 0. Now this agent is going to perform some action A0. On performing this action, it is going to get a reward R1. And if it gets a reward R1, then it's going to move to state S1. But in case the action is wrong, then it's going to get a negative reward, as in some points are going to be reduced. So guys, think of q-learning as a game. You're in state 0 and then you do some action and either you get a reward and go to the next state, or else you lose and you go back to the same state. So until you learn, you're going to be in the same state. But if you keep learning and if you keep receiving positive rewards, then you're going to move on to state 1, and similarly you'll move on to state 2, 3 and so on. This is what q-learning is about. Now the next question is, what is deep learning? Now deep learning, like I mentioned earlier, basically mimics the way our brain works. Okay, it learns from experience. Now the main concept behind deep learning is neural networks. In our brain also we have neural networks. So what deep learning tries to do is it tries to use the concept of neural networks in order to solve complex problems. So basically we're trying to mimic our brain. Any deep neural network will have 3 types of layers. The first is the input layer. Now this layer will basically receive all the input and it will forward them to the hidden layer. Now in the hidden layer, all the analysis and the computation takes place. Alright, once the computation is done, the result is transferred to the output layer. Now there can be n number of hidden layers depending on the type of problem you're trying to solve. Then we have the output layer. So basically this layer is responsible for transferring the information from the neural network to the outside world. So it's as simple as that. It's pretty obvious. Input layer will take in the input, hidden layer will perform the computations, and the output layer will give out the output. This is a small explanation of what deep learning is. Now, of course, this is much more complex than this, but in short, this is exactly what deep learning is. Now let's look at our next question, which is explain how deep learning works. So basically, deep learning is a concept based on something known as neuron. Okay, neuron is a basic unit of the brain. Inspired from this neuron, they came up with something known as perceptrons or artificial neurons. Now, in this image on the left-hand side, you can see that there is something known as dendrite. These are modules which receive the input. It basically receives all the signals that we send to our brain. Okay, similar to the dendrites are the input layer in our artificial neural networks. Now, in the previous slide, we discussed that the input layer takes in all the input from the outside. That's exactly what a dendrite does. So basically, a perceptron receives multiple inputs, it applies various transformations and functions, and then it provides an output. So basically, guys, just like how our brain contains multiple connected neurons called neural networks, we also have a network of artificial neurons called perceptrons to form a deep neural network. So basically, an artificial neuron or a perceptron, it models a neuron which has a set of inputs, each of which is assigned some specific weight. Okay, all of these inputs will have a specific weight, and the neuron will compute some function on these weighted inputs and give you the output. So the neuron will basically perform analysis and all of that on these weighted inputs to give you some output. This is the basic concept of deep learning. So there are inputs which have some weight on it, and these inputs are then formulated and analyzed in order to give you an output. Now let's look at our next question, which is explain the commonly used artificial neural networks. Now this is a very theoretical question because in order to make you understand how each of them work will take a lot of time. Okay, so I'm just going to briefly tell you what each of these networks are and what they do. Now, feed-forward neural network is the most basic kind of artificial neural network. So basically, the feed-forward neural network is unidirectional. The data passes through the input nodes and leaves through the output nodes. In feed-forward neural network, usually the number of hidden layers depends on the complexity of the problem. Coming to convolutional neural networks, here basically the input features are taken in small sets, okay, or they're taken in batches. This will help the network remember better because you're feeding batches of images or you're feeding batches of input to the neural network. Now, this type of neural network is mainly used for signal and image processing. Next, we have recurrent neural networks. These are also known as long short-term memory networks. So this basically works on the principle of feeding the output of a layer back into the input layer in order to predict the outcomes. Okay, this way it's more precise and it is a little more complex when compared to convolutional networks. Now, one main important point of recurrent neural networks is that they have something known as memory. So basically each neuron will have some information or some memory stored in them so that they can use this memory in order to take actions in the future. So they have some experiences stored in the form of memory so that they can make their decisions based on previous actions. Now, finally, we have autoencoders. Now, autoencoders are mainly used in dimensionality reduction for learning generative models. Okay, and one more important thing about autoencoders is that the number of units in the output layer and the input layer is the same. This is because the output layer has to reconstruct its own inputs. So these were the different types of artificial neural networks. Now let's look at our next question, which is what are Bayesian networks? Okay, so a Bayesian network is a statistical model that represents a set of variables and their conditional dependencies in the form of a directed acyclic graph. Now, basically, on the occurrence of any event, a Bayesian network can be used to predict the likelihood that any one of several possible known causes was a contributing factor. An example of this is a Bayesian network could be used to study the relationship between diseases and symptoms. So given a set of symptoms, the Bayesian network can be used to find out the probability of the presence of any diseases. Alright, so the next question is explain the assessment that is used to test the intelligence of a machine. Now guys, this is a very common question and it is sort of a general knowledge based question. Alright, I'm hoping that most of you know the answer to this. So let's look at what the answer is. I'm not sure how many of you have heard of Alan Turing. So Alan Turing was the one who came up with the Turing test. Now, this test is basically to determine whether or not a computer is capable of thinking like a human being. So if a machine or if a computer passes this exam, it means that that machine is capable of thinking like a human being. It means that it is successfully an artificial intelligent machine, meaning that it can make its own decisions and interpret data and form their own formulations or form their own conclusions about the data.
Now, sadly, I don't think there are a lot of machines that have passed the Turing test. In fact, I'm not sure if there is any machine that's passed the Turing test as of now. But in the near future, I'm sure that we'll see machines who are more smarter than human beings and who have passed this test. Now, for a machine, it might be very easy to do computations, but it might be very hard for a machine to just get up and walk around. All right, the simple things that us humans can do is very complicated for a machine. They can do computations which we can do in probably a year. They can do those computations in maybe a week or less than a week. But doing simple things such as walking up to the fridge or walking up to the kitchen is very hard for the machines. So to achieve that level of intelligence, we're going to take a while. But in the near future, I'm sure we'll see machines which are way more capable than human beings. Now let's move on to our next level. Now here I'll basically be discussing intermediate level artificial intelligence questions. So let's look at the first question. All right, the first question is, how does reinforcement learning work? Explain with an example. Okay, so first of all, reinforcement learning is a type of machine learning. We discussed about reinforcement learning earlier. Reinforcement learning is a type of machine learning wherein there's an agent and you put this agent in an unknown environment. All right, now the agent has to figure out actions, what sort of actions it must take, and how it's going to get rewards so that it can move from state 0 to state 1. It's sort of like a video game. If you're in a video game, let's say if you're playing Counter-Strike, you're in level 0 or state 0. Now, if you perform some action and if you get some rewards, you're going to move to state 1. That's exactly how reinforcement learning works. If you perform the relevant actions and the correct actions, you're going to get a reward and you'll move on to the next state. But in case you perform a wrong action, you'll get negative rewards and you'll stay in the same state unless and until you don't learn. All right, so if you learn and achieve, then you'll move to the next state. So basically, a reinforcement learning system will have two main components. It'll have an agent and an environment. Now, the agent, I've been repetitively saying an agent. An agent is basically the reinforcement learning algorithm. It is the model. The model has to learn everything on its own. It has to collect data on its own. It has to draw useful insights on its own. Okay, you're not going to feed any predefined data to this reinforcement learning agent. All right, he has to figure out everything on its own. So let's look at an example of Counter-Strike. Okay, I'm not sure how many of you play the game, but yeah. What happens here is the reinforcement learning agent or the player one collects a state S0 from the environment. Okay, so let's suppose that you're playing Counter-Strike and you're in state 0. Now you'll perform some action A0. Right, initially it's going to be a random action. So obviously if you're put in an unknown environment, your first action is going to be random, correct? Because you don't know what's right, you don't know what's wrong. So in your state 0, you'll take an action A0. This will result in a new state S1. And on achieving state S1, the agent will get a reward R1, okay, from the environment. Now, in the case of Counter-Strike games, if you've observed, whenever you win a state or you pass a level, you're going to get some rewards. Maybe you'll get more weapons or you'll get more points. Okay, just like that, in reinforcement learning problem, you'll get some reward R1. Okay, it's basically a plus point. You might get a negative reward or a positive reward based on the action that you take. Now, this loop will go on until the agent is dead or it reaches the destination. So in Counter-Strike, until you have failed the level, you will keep playing the game, right? You'll keep moving from state 1, state 2, state 3, and so on. Or if you've reached the destination, then it's the end game. That's exactly how it works in reinforcement learning. If the agent has explored the entire environment and reached the end state, that's when the loop will end. All right, that's exactly how reinforcement learning, very similar to the games that we play. All right, it's very understandable. Now let's move on and discuss the next question. So the next question is, explain Markov's decision process with an example. Now the solution for a reinforcement learning problem is achieved through the Markov's. This is basically a mathematical approach that maps the solution in reinforcement learning. Okay, so now to understand this, there are a couple of parameters in a Markov's decision process. A set of actions called A, okay, you can name them A. A set of states, there's going to be reward, and there's going to be value. To sum it up, what exactly happens in a Markov's decision that the agent takes an action A to transition from the start state. Now, while doing so, the agent receives some reward R for each
that the series of actions taken by the agent will define a policy or an the rewards collected will define the value. So the main goal in process is to maximize the rewards by choosing the most optimum policy, meaning that you're going to choose the best solution in order to get the most number of rewards. Now, in order to make you all let's solve the shortest path problem by using Markov's decision process. I've heard of shortest path problem. This was, I think, taught to us when we were in, I'm not sure. Look at the diagram that is over here. This is basically a representation of, given this representation, our goal here is to find the shortest path between and node D. All right, you can see nodes A, B, C, and D. We have to find the short path and node D. Now, the link between these two nodes has a number on it. Okay, for example, between A and C, you can see there's a number 15. Okay, this basically denotes the cost at edge. So if you want to go from A to C, you'll spend around 15 points. So to travel between node A and node D with minimal possible cost. We should travel between A to D in such a way that our cost is minimal. Now, in this problem, if you notice that we have a set of states. Okay, these are denoted by the nodes A, B, C, D. Now, like I mentioned earlier, Markov has a set of states. Similarly, in this problem, the set of states are the action is to traverse from one node to the other. So going from A to B is basically, and from A to C is another action, going from A to D is another action, and so on. Is represented by the cost on each of these links. And the policy is the path which is taken to the destination. So our aim here is to choose a policy that gets us to the minimum cost possible. So this problem, all right, you can start off and you can take baby steps to your destination. Now, initially, only the next possible node is visible to you. Like I mentioned earlier, the initial action taken in a reinforcement learning problem is always random. So at random, you'll choose any node. Let's say you take A to B. Now, if you go from A to B, you can go B to D and you'll reach the destination. So policy is the path which is taken to reach the destination. All right, so it can go from A to B to D, or you can go from A to C to D, or you can go A, C, B, D. All right, now it's up to you to figure out which is the shortest path. All right, you have to choose a path in such a way that the cost between A to D is minimized. So guys, this was a simple problem of how Markov's decision process is used to solve the shortest path problem. Now let's move on and look at our next question. All right, now the next question is explain reward maximization in reinforcement learning. So basically, learning agent works based on the theory of reward maximization. Okay, in the previous question itself, I told you that the main aim of reinforcement learning is to maximize the reward. So that's why a reinforcement learning agent must be trained in such a way that he takes the best action so that the reward is maximum. Okay, this is exactly what reward maximization means. He has to choose the best policy in such a way that the reward is maximum. Now let me explain this with a small game. So in the figure, you can see a fox, you can see some meat, and you can see a tiger. Now, our reinforcement learning agent is the fox. His end goal is to eat the maximum amount of meat before being eaten by the tiger. Okay, so he has to explore around, eat the maximum number of meat that he can eat before the tiger kills him. Since the fox is a clever fellow, he eats the meat that is closer to him. Okay, so rather than eating the meat which is close to the tiger, he eats the meat which is only close to him. This is because the closer he gets to the tiger, the higher are his chances of getting killed. So as a result of this, the rewards near the tiger, even if they are bigger meat chunks, will be discounted. So because the fox is not going closer to the tiger and eating the meat chunks closer to the tiger, this reward will get discounted. Now I know you all are wondering what discounted is. Now this is done because of the uncertainty factor that the tiger might kill the fox. So what is discounting of reward? Okay, how does it work? To understand this, we define a discount rate called gamma. Okay, this is a parameter and the value of gamma always ranges between 0 and 1. So the smaller the gamma, the larger the discount and so on. So guys, this was reward maximization. So here basically the fox will try to get as much as meat chunks as he can And he'll also try to avoid getting killed because that will end the reinforcement learning loop. We also discussed the discounted factor. Right now, that is not needed to understand reward maximization, but I just thought I'll add on some extra info. Now let's look at the next question, which is what is exploitation and exploration trade-off? So basically, exploration is, like the name suggests, it is about exploring and capturing more information about an environment. Now, on the other hand, exploitation is about using the already known exploited information to heighten the rewards. So consider the same example that we discussed in the previous question. Here, the fox only eats the meat chunks which are close to him. Okay, he does not eat the bigger chunks because even though the bigger chunks would give him more rewards, it would get him killed. Okay, he does not go towards the tiger itself. Now, if the fox only focuses on the closest reward, he will never reach the big chunks of meat. Okay, this is what exploitation is. He's sticking only to the information that he knows and he's trying to get from it. But if the fox decides to explore a bit, it can find the bigger rewards. Okay, the bigger rewards are basically the big chunks of meat which are near the tiger. And this is exactly what exploration is. Okay, exploitation is about using the already known information to heighten your rewards. Exploration, on the other hand, is about exploring and capturing more information about an environment. All right, so that was about exploitation and exploration. Now let's move on to our next question. So this is a difference question which asks the difference between parametric and non-parametric models. So a parametric models basically uses a fixed number of parameters to build the model. Now, first of all, guys, what are parameters? Now, parameters are basically predictor variables that are used to build a machine learning model or build any predictive analytics model. Now that we know what parameters are, let's try to understand the difference between a parametric and a non-parametric model. Now, parametric model basically uses a fixed number of parameters to build the model. A non-parametric model uses flexible number of parameters to build the model. When it comes to a parametric model, the assumptions about the data are very strong. In a non-parametric model, there are fewer assumptions about the data. A parametric model has the fixed number of parameters. Everything is defined over here. So the computation is very fast. Okay, you know what sort of variables you'll need to predict the outcome. Okay, you have a defined set of variables or a defined set of predictor variables that will compute your outcome. So that's why the computation is a bit faster. When you compare to non-parametric models, there are a lot of parameters taken into account. Now, when it comes to a non-parametric model, you do not have a fixed number of parameters. Right? You do not have a fixed number of predictor variables that will help you get to the outcome. So the computation is a bit slower. Now, parametric models require lesser data and non-parametric require more data. Example of parametric models include logistic regression and naive Bayes. And for non-parametric models, we have KNN and decision tree models. Now, logistic and naive Bayes models are very stern models because they have a fixed number of parameters or a fixed number of predictor variables, and they will give you an immediate output. Okay, when it comes to non-parametric models like decision tree models and KNN, you might even observe a little bit of overfitting. Okay, this happens because you have a fewer number of assumptions about the data and also because your parameters are not fixed. Now, that's not the reason for overfitting, but it's seen that in some of the non-parametric models, overfitting occurs more often. Now, let's discuss the next question, which is what is the difference between hyperparameters and model parameters? Now, model parameters are the predictor variables that I was speaking about earlier. Hyperparameters, let's discuss what they are. Okay, model parameters are the features of training data that will learn on its own during training, whereas model hyperparameters are the parameters that determine the training process. Now, let's say that you want to determine the height of an individual depending on his weight. The height and weight will become your model parameters. But your hyperparameter is basically the learning rate. It's the rate at which your model is going to learn this correlation between the height and the weight. So this is the difference between model parameters and hyperparameters. Model parameters are the ones that you find in your data. These are all the variables that you use to predict your outcomes. Hyperparameters will define your training process. There is a huge difference between model and hyperparameters. Another difference is that they are internal to the model and their value can be estimated from the data. Hyperparameters are external to the model and their value cannot be estimated from data. Now, like I said, model parameters are derived from your data itself. Okay, these are the parameters that are there in your data. Hyperparameters are the ones that you define in order to train your entire data. So that is the difference between hyperparameters and model parameters. So the next question is, what are hyperparameters in deep neural networks? So guys, like I mentioned in the previous example, hyperparameters are variables such as the learning rate. This will define how your entire data training process goes. For those of you who don't know, in order to build a model, you first need to train the model and then you need to test it. Okay, now while training the model, you're going to make the model learn a lot of things. You're going to give it a lot of data. It has to figure out relations between various variables and how these variables are affecting the output. All of this training will depend on a few variables such as the learning rate. Okay, these are basically called hyperparameters in deep neural networks. So these parameters will define the number of hidden layers that are present in the network. Okay, and more the number of hidden layers, the more accurate your network is going to be. Whereas if you have lesser number of units, you may cause underfitting in your data. Underfitting will also result in inaccurate predictions. So that's why you need to make sure that the number of hidden units in your hidden layers are perfect, are ideal. Okay, and this is determined by your learning rate or by your hyperparameters. Not by your learning rate specifically, but by the number of hyperparameters you have. These number of hidden layers are determined by the hyperparameters. Okay, that's why hyperparameters are very important in deep neural networks. I hope you all are clear with this. Now let's look at our next question, which is explain the different algorithms used for hyperparameter optimization. We'll discuss the three methods, which are grid search, random search, and Bayesian optimization. Okay, now grid search basically will train the network only on the two sets of hyperparameters, which are learning rate and the number of layers. Okay, so it's going to use every combination of these two sets in order to train the network. Okay, after that, it will evaluate the efficiency of the model by using the cross-validation techniques. Cross-validation is the best improvement method. Okay, it's the best way to check if your model is optimal or not. Then we have random search. Now, this will randomly select samples and it will evaluate sets for a particular probability distribution. Now, in random search, there is no fixed number of hyperparameters that it's going to evaluate. So, it'll randomly select a set of hyperparameters. Okay, for example, now instead of checking your entire sample or your entire, let's say that you have 10,000 samples. Instead of checking all of these samples, it'll randomly select 100 parameters that can be checked. Okay, and then it'll use this to build the model. After that, we have Bayesian optimization. Okay, now Bayesian optimization basically uses something known as the Gaussian process. Basically, the Gaussian process will help in model tuning. Okay, model tuning, or you can also say parameter tuning. So parameter tuning will help you tweak the parameters a little bit in order to improve the efficiency of the model. Okay, so Bayesian optimization basically makes use of the Gaussian process, which will provide model tuning to your algorithm and thus improve the efficiency. Now guys, one of the most important ways to improve the efficiency of a model is by hyperparameter optimization. Okay, if you're tuning your hyperparameters and if you're trying to check in which way these hyperparameters will give you the most accurate outcome, that's when your result will be very good. Okay, so that's the best way to improve the efficiency of the model. All right, now let's look at our next question. The next question is, how does data overfitting occur and how can it be fixed? Now guys, this is a very common question in a machine learning or in an artificial intelligence interview. Okay, people expect you to understand what data overfitting is and how you can fix these problems. Okay, because data overfitting occurs pretty often, especially if you're using decision trees or if you're using random forest. Okay, random forest actually reduces overfitting, but sometimes with these complex models, you can get data overfitting. Now, to answer this question, first of all, let's understand what overfitting really is. So, overfitting occurs when a machine learning algorithm captures the noise of the data. Okay, this causes an algorithm to show low bias but high variance in the outcome. Now, what overfitting really means is you have trained your model way too many times on the training data. Okay, so basically the model has memorized the training data. It has memorized the noise in the training data. Okay, so if you feed new data to the model during the testing stage, it will not be able to recognize the noise, or it will not be able to recognize any sort of correlation in that data. Okay, that's why it won't be able to get a proper outcome. Okay, that's when overfitting happens. You have trained the model way too much with the training data, and this has resulted in inaccurate outcome during the testing phase. Okay, that's what overfitting is about. Now, how do you avoid overfitting? First of all is cross-validation. Now, before this also I mentioned that cross-validation is the best way to obtain a more optimal solution. Now, the general idea behind cross-validation is to split the training data in order to generate multiple mini train test splits. Okay, these splits can be used to tune your model. Okay, so you're basically splitting the training data in such a way that, the model does not just use the entire training data and memorize it. Instead, it's going to check the different sets in the training data and the different sets in the testing data and learn from it. Okay, so cross-validation is one of the best ways to prevent overfitting. Another method to prevent overfitting is by training the model with more data. So feeding more data to the machine learning model will help in better analysis and classification. However, this method is not always going to work, but yeah, this is also one of the ways to prevent overfitting. Okay, next we have removing features. Now, many times the dataset contains irrelevant features or predictor variables which are not needed for analysis. Such features will only increase the complexity of the model. Therefore, it will lead to possibilities of data overfitting. Okay, so if you have irrelevant data, like for example, if you're trying to understand the weight of a person depending on its height, and you have another variable, let's say you have a variable like the name of the person. Okay, now the name of the person is not relevant in understanding the height of an individual. So if you have irrelevant predictor variables, then it will just increase the complexity of the model because you have an extra irrelevant variable. All right, this will only increase the complexity of the model. It will not help the model in any way. So make sure you remove irrelevant features or you remove redundant features. Okay, the next method is early stopping. Now, a machine learning model is trained iteratively. This will allow us to check how well each iteration of the model performs. But after a certain number of iterations, the model's performance starts to saturate. Further training will only result in overfitting. Okay, so like I mentioned, if you train the model with the same data and you make the model memorize the data, then it'll just saturate. It won't be able to predict any outcomes after a point. What you have to do is you have to understand where you need to stop training the model. So this can be achieved by using a mechanism known as early stopping. So at this point, you know that you have to stop training the model because this might result in overfitting. Now, regularization is one of the most common ways to prevent overfitting. Regularization can be done in n number of ways. Okay, the method will always depend on the type of learner you're implementing. For example, pruning is performed on decision trees. Now, pruning is a type of regularization. Similarly, the dropout technique can be used on neural networks. And also there are other methods like parameter tuning, which can help to solve overfitting. The next way to prevent overfitting is by using ensemble models. Now, ensemble learning is a technique that is used to create multiple machine learning models, which are then combined to produce more accurate results. So basically, if you have one problem statement in machine learning, you're going to use like 5 to 10 different models, and then you're going to calculate the accuracy depending on the average of the result from each of these models. By this way, you will reduce overfitting. Now, ensemble models is one of the best ways to prevent overfitting. An example is the random forest. Random forest uses ensemble of decision trees to make more accurate predictions and to avoid overfitting. So basically, random forest is a set of decision trees. So here you're going to train the model by using a set of decision trees, and this way you'll have different data sets, and on each of these data sets you'll have a different decision tree model. Okay, this will reduce overfitting to a very large extent. That's why in most of the cases when you see a decision tree having overfitting issues, you'll be asked to use random forest. So guys, those were the different ways to prevent overfitting. Now the next question is mention a technique that helps to avoid overfitting in a neural network. Now the most famous method to prevent overfitting in neural networks is dropout technique. Okay, now dropout is a type of regularization technique which is used to avoid overfitting in a neural network. So here what you do is you randomly select neurons and you drop them during the training phase. right? So the dropout value also has to be chosen very carefully, because a higher dropout value will result in underlearning by the network. So if you're dropping out too many predictor variables, or if you're dropping out too many neurons in a neural network, then the model will not learn enough, okay, because there's not enough predictor variables and not enough neurons. But if you have too much of a low rate for a dropout value, then this might have a very minimal effect. So make sure your dropout value is very optimal depending on the problem you're trying to solve. Okay, so dropout is the technique which is used to avoid overfitting in a neural network. Next question is, what is the purpose of deep learning framework such as Keras, TensorFlow, and PyTorch? So Keras is basically an open source neural network library which is written in Python. So basically it is designed to enable fast experimentation with deep neural networks. Now TensorFlow is another open source software library for data flow programming. TensorFlow is mainly used in machine learning applications. Similarly, PyTorch is again an open source machine learning library for Python. Its applications are mainly in the field of natural language processing. Now, I'd say that these three deep learning frameworks are the most important when it comes to machine learning and deep learning, because they have a varied set of functions in them which help in building a better machine learning model or a better deep learning network. Now let's look at question number 24, which is differentiate between NLP and text mining. So guys, NLP stands for natural language processing, for those of you who don't know. Now, first of all, let me clear out a confusion between text mining and natural language processing. A lot of people tend to think that text mining and NLP are the same thing, but text mining is the broader field and NLP is basically an application of text mining, or it's basically a technique used in text mining. So the aim of text mining is to extract useful insights from structured and unstructured text, whereas the aim of NLP is to understand what is conveyed in these texts. Now, text mining can be done using text processing languages like Perl, and NLP can be achieved using advanced machine learning models such as deep neural networks. Now, the outcome for text mining is you'll calculate the frequency of words, you'll understand the patterns between different words, you'll understand the correlations between two different words, and you'll see how these two words occur together more frequently and why they occur together more frequently. So text mining basically will give you a more understanding about the words that are used in a document. Whereas in NLP, you will understand the grammar behind the text. You will understand in more depth about the language that is used in the document or in whatever you're trying to analyze. So that is the difference between NLP and text mining. NLP is a little more advanced field because you use deep neural networks to perform this. Text mining, on the other hand, makes use of NLP. Next question is, what are the different components of NLP? Now, there are two components of natural language processing, which is natural language understanding and natural language generation. In natural language understanding, you'll basically map your input to some useful representation. This means that you'll try to understand the correlations in your language, and it'll also include analyzing different aspects of the language. All right, so this is majorly about understanding your text. When it comes to natural language generation, here you'll understand how to generate text by having a brief plan about the text. You'll have sentence planning and you'll have text realization. Now, natural language generation will basically break down sentences or will break down text in order to understand it better. Okay, that's what natural language generation is. Natural language understanding is more about analyzing your language or analyzing the text that you have at hand and predicting some useful outcome out of it. Generation is more focused on the planning aspect of your text. So these are the different components of natural language processing. Now let's look at what is stemming and lemmatization in natural language processing. Now, what is stemming? It is an algorithm which works by cutting off the end or the beginning of the word and only taking into account a list of common prefixes and suffixes that can be found in inflected words. Now, for example, on the screen you can see that there is detections, detected, detection, and detecting. Now, if you apply stemming on these four words, it will lead to detect. Okay, because at the end of the day, detections, detected, detection, and detecting is the same thing as detect. So stemming will help you remove all of these unwanted prefixes and suffixes. This way you can analyze the importance of the word. Alright, you don't have to have extra suffix or prefix before the word. Now, sometimes during stemming, cutting off the ends of the words will form an inaccurate result. Okay, that's why we have lemmatization. In lemmatization, the most important thing is the morphological analysis of the word.
Okay, so here in order to perform lemmatization, you have to have a detailed dictionaries which the algorithm can look through and it can form back to its lemma. So the main difference between stemming and lemmatization is that stemming will just crop the prefix and the suffix, whereas lemmatization will try to understand the word in a grammatical way and give you an actual word as the output. Next is to explain the fuzzy logic architecture. Alright, so the fuzzy logic architecture looks like what is shown on the screen. Okay, so basically the input is fed into something known as the fuzzifier. Okay, the fuzzifier or the fuzzification module will transform the system's input into a number of fuzzy sets. Okay, after that it's fed to the controller. Now the controller will have knowledge base and the inference engine. Knowledge base is basically a set of rules, or you can say it's an algorithm which is provided by experts. Inference engine, like the name suggests, will basically infer meaning out of these rules. Okay, so once you've applied the rules to your input, you'll have to draw some useful insights or you'll have to infer these inputs. Okay, for that you use the inference engine. After that, whatever inferences and analysis you've formed from your inference engine is passed on to the defuzzification model. Now the defuzzification will just give you a crisp output. All right, it will give you a clear and cut output. That is the whole fuzzy logic architecture. Now let's understand the components of an expert system. Now there are three important components in an expert system, which is knowledge base, inference engine, and user interface. Now, like I mentioned in fuzzy logic, the knowledge base and inference engine will play the same part. The user interface is basically to provide interaction between the users of the expert system and the expert system. Okay, the expert system is basically a program that helps in decision making process. Okay, so here the knowledge base will contain some high quality knowledge or will contain rules and algorithms. The inference engine will acquire all the knowledge that is needed to solve the problem, and the user interface is just for the users to interact with the expert system. Okay, this is the whole expert system component. Now, obviously, this is a little more complex than this, but let's stick to how this works. All right, I'm just going to tell you the working of expert systems and fuzzy logic. If I start to explain each and everything, it's going to take a lot of time. All right, so let's move on to our next question, which is how is computer vision and AI related? Now, computer vision is a field of artificial intelligence that is used to obtain information from images or multidimensional data. Now, computer vision is basically the concept behind the self-driving cars that you see these days, right? Computer vision involves a lot of image processing. So machine learning algorithms like k-means can be used in image segmentation. Support vector machines can be used for image classification. Okay, that's how computer vision and AI are related. Because most of the things that happen in computer vision like image processing and segmentation make use of machine learning algorithms like k-means and support vector machines. So to sum it up, computer vision makes use of artificial intelligence technologies to solve complex problems such as object detection, image processing, and so on. That is the relationship between computer vision and AI. Now, question number 30 is which is better for image classification? Is it supervised or unsupervised classification? So guys, earlier in the session, we discussed what supervised learning is and what unsupervised learning is. In supervised learning, the images are interpreted manually by the machine learning expert to create feature classes. Now, what this means is you're manually going to feed a label set of data to the supervised learning model. All right, that's how supervised learning works. You're manually going to feed a set of images which are labeled to the classifier. In unsupervised learning, the machine learning software creates feature classes based on image pixel values. So basically in unsupervised classification, the model itself has to figure out what to do and what not to do. Okay, so it'll create a own feature class based on some values such as image pixels, or it can also use the image color, or it can use intensity factors in order to classify. So if you ask me, it is better to opt for supervised classification because you're manually inputting images with a lot more information. Okay, whereas in unsupervised learning, you're totally letting the model perform everything. Okay, so in image classification, I think it's better to go for supervised learning. Now let's look at question number 31. The next question is finite difference filters in image processing are very susceptible to noise. To cope up with this, which method can you use so that there would be minimal distortions by noise? Now, the noise in an image can be due to high intensity or high contrast. Okay, so if you increase the contrast and increase the intensity of an image, you won't be able to understand each pixel. Okay, so each pixel will have a value associated to it. And if the intensity and the contrast of that pixel is a little too much, it'll be hard for us to understand the image properly. It'll be hard to perform image analysis because we don't have a clear image. Contrast and intensity will just cause noise in an image. So the best method to remove this is image smoothing. Okay, it is used for reducing noise by forcing pixels to be more like their neighbors. Okay, this way you'll have a faded image or you'll have a more equalized image. Now the next question is, how is game theory and AI related? So guys, AI is actually applied in a vast number of fields. Okay, so a lot of fields from computer vision to game theory to machine learning. AI is always a concept behind these fields. Most of the game examples that we see make use of reinforcement learning or deep neural networks. Now, deep neural networks and reinforcement learning are very closely related to AI because they are branches of machine learning. So machine learning is majorly involved in game theory. An example of this is in Dota 2 also they make use of machine learning. So game theory is just a very logical approach to solving a problem. And machine learning is the best way to implement game theory. Now, question number 3 is, what is the min-max algorithm? Explain the terminologies involved in the problem. Now guys, min-max is one of the main algorithms which is used in game theory. Alright, it is used to choose an optimal move for a player, assuming that the other player is also playing optimally, meaning that both of these players are playing in order to win, and you're going to use the min-max algorithm on one of these players so that they choose the optimal move. In order to understand the min-max algorithm, you need to know what are the components in a game. Okay, there's something known as game tree. It is basically a tree structure which contains all the possible moves in a game. If it's up, down, right, left, any strategy, everything is mentioned in the game tree. Now, initial state is obviously the initial position of the player on the board. Alright, the successor function, it defines all the possible moves that a player can make. We'll understand this in the next question itself, so don't worry if you haven't understood this properly. Terminal state is obviously the end of the game. It's basically the state which will lead to the end game or it will lead to your destination. Utility function is a numerical value for the output of the game. So guys, these were the terminologies and this is what the min-max algorithm is. It is basically a game theory algorithm which helps a player choose the best optimal policy in order to win a game. Now I'll explain this in more depth in the upcoming slides. So let's move on. Now the next couple of questions are going to be scenario-based questions. Now such questions are very important in an interview because this is where the interviewer will understand how well you know the concepts. So the first question is, show the working of the min-max algorithm using the tic-tac-toe game. Now one of the major applications of the min-max algorithm is the tic-tac-toe game. Okay, you can understand and analyze all the possible outcomes of the tic-tac-toe game by using the min-max algorithm. Let's see how this happens. Now, first of all, in a min-max algorithm or in a game, there are two players involved. Okay, the max is the player that tries to get the highest possible score, and min is the player that tries to get the lowest possible score. So this algorithm is designed in such a way that, assuming that there are going to be two players, and obviously one player is going to win the game and that is the max player, and min is the player which loses the game and has the lowest possible score. Now the first step in the min-max algorithm is to generate the entire game tree. Okay, the game tree is all the possible outcomes that can happen in tic-tac-toe. Okay, in the figure you can see that first X is aligned in the first box, then in the second box, third box, and so on. All the possible actions that you can take in a tic-tac-toe game are put in this game tree. And then step number 2 is to apply the utility function to get the utility values from all the terminal states. Getting utility value is important because this is how you'll understand your outcome. Okay, you'll understand if you're going to win or lose. Now, in the terminal states, whatever numbers you see over here, these are the utility values. Now, step 3 is determine the utilities of the higher nodes with the help of utilities of the terminal nodes. Now, in this diagram, you can see that in the terminal nodes, we have the utility values. The step 3 is to get utility values in the higher stages, which is the min stage. All right, these two circles, you need to fill in the utility values by using the utility values which are in the terminal state. Now, how do you calculate the utility value? Let's start by calculating the utility value of the left node. Okay, this red color node, we'll start by calculating this. Now you calculate that by finding the minimum of the 3 nodes that it's leading to. Now this red node is leading to 3, 5 and 10, and the minimum out of 3, 5, 10 is 3. So the utility value for this red node is going to be 3. Okay, similarly for this green node it's going to be 2, because the minimum value between 2 and 2 is still 2. Now step 4 is to fill in these utility values that you've calculated. So now we have a min-max algorithm which has all the utility values filled in. Now the only utility value which isn't filled is the one with max. Okay, the one on the root node. Here we haven't filled the utility value. Again, to fill this value, you're going to check the nodes which are directly connected to it, which is 3 and 2. You'll find the maximum between these two because this is the max function. Alright, so here you'll get a value of 3. So that's why the best opening move for max is the left node. Okay, you can make use of the left node in order to win the game. This is the first step that the max player has to take in order to get to the path of winning the game. So guys, by doing this for each and every step, you can win the game. Okay, so you'll have to calculate the utility value at the terminal nodes. You'll have to move up to the other hierarchical nodes above it, calculate the utility values there until you reach the root node. Okay, once you reach the root node, you'll get a utility value, and that utility value will be connected to some move or some node. You'll have to take that node or you'll have to take that move in the game in order to win the game. So this way you'll have to calculate the utility value for each and every move that the player makes so that the player will win the game. So guys, min-max algorithm is quite easy and it's very understandable. All you need to know is a little bit of math in order to solve this problem. Question number 35 is, which method is used for optimizing a min-max based game? Now this is not a scenario based question, but this question is usually asked if an interviewer asks you about a min-max game. Now the best way to optimize a min-max game is by using something known as alpha-beta pruning. Now the main thing about alpha-beta pruning is that it will remove all the nodes that are not affecting the final decision. It's just a faster way to reach your outcome. That's what alpha-beta pruning is all about. So let's look at an example to understand this. Okay, let's say there was another node over here. Okay, here you can see that this is going down to a terminal state with utility value 2. Okay, now you don't know the value of the other two nodes, but if you use min-max to calculate the utility of the other two nodes, you'll get a value of 3. So in this example, again, we'll start at the terminal nodes. So 3, 5, 10 are the utility values here. So this will give us a value of 3 because we're calculating the minimum over here. Now here you have 2 and you have 2 unknown values. You have A or B. Okay, I've named them as A and B. Okay, let's leave this for now. Let's go to the next node. Okay, here the possibilities are 2, 7 and 3. So the minimum between 2, 7, 3 is 2. Okay, so here there's going to be 3. There's going to be a value, let's say C, and here there's going to be a value, let's say 2. Now we know that the maximum between 3, C and something else will be 3. Okay, that's because 2 is the minimum value over here and the maximum will obviously be 3. So the hint here is in the 2AB node, we know that the value or the utility value will obviously be equal to 2 or it will be less than 2 because you're calculating the minimum in this step. Now if you calculate the max out of these 3 values, we'll obviously get the answer as 3. So this way this entire node itself is removed because you don't need it to get to the final answer. Okay, that's what alpha beta pruning is all about. It'll identify the nodes which are not going to affect the final decisions and it'll just remove those nodes. So guys, this is how the optimization for a min-max game is done. It's done using the alpha beta pruning. The next question is, which algorithm does Facebook use for face verification? Now guys, even though this might seem like a general knowledge question, this is actually a very important sort of question in artificial intelligence. Okay, even if you don't know the answer to this, you should have an idea of how the algorithm might work. Okay, that's exactly what the interviewer wants to know. He wants to know whether you know how the algorithm goes step by step. You might not know the final answer or you might not know the exact algorithm which Facebook uses because obviously Facebook uses more than one algorithm to achieve this. But you must know the steps in which the face verification works. Okay, that's the main goal behind this question. Now, anyway, the algorithm used by Facebook is the deep face. Okay, deep face makes use of a lot of neural networks and a lot of algorithms. Okay, so it works on artificial intelligence techniques, like I mentioned earlier. Now, how would a face verification work? How do you think it works? Now, it starts by an input. So the idea here is you have to scan a huge number of photos and you'll have to feed it to the algorithm. Okay, now these photos can have a lot of disturbance, a lot of distortions, and it can have different angles or anything like that. Okay, you have to feed any sort of photos that are possible. Okay, even if they are complex to understand, but you have to still feed the model with all the possible photos that you can get. Now, the next step is the main process. Here, there are a few important things, which is detect, align, represent, and classify. Detect is basically you detect facial features. All right, you try to understand the distance between the eyes and the nose of a person, the way the lips is aligned, or anything like that. That's what aligning is about. You'll align and compare the various features in the face. In order to understand the facial features, you'll represent the key patterns by using some 3D graphs or 3D models. Okay, it's very important to visualize whatever you get, because visualization will help you understand the correlation. Okay, it'll help you understand that, okay, the eyes are at this distance, the nose is at this distance, and so on. Finally, you'll classify the images based on the similarity. All right, that's how the output comes out. And basically, the output is you need to detect whether two images represent the same person or not. Okay, so by studying the facial features and by using image processing and by using computer vision, Facebook achieves face verification. You need to know the basic concept behind face verification. You need to know that it starts with image collection or data acquisition. After that, you're going to perform image processing or pre-processing. All right, this might involve performing conversions from RGB to any other state like YCBCR. Okay, I'm not going to go in depth of this because the video will get to about 2-3 hours. So there are a lot of ways in which you can convert an image, and you can understand the image more properly. Also, an important thing in image processing is it's not done just based on the image. All right, you're going to take the image, you're going to form a matrix, and you're going to have pixel values in these matrix. So it is a very in-depth approach. All right, it's not a very simple approach. When I'm speaking about it, it might seem simple, but image analysis is very in-depth. After image analysis, you can perform image segmentation. All right, image segmentation is basically dividing the image into different segments and studying each image segment separately. Then after that, you can do feature extraction. Here you will try to understand the features and how they are related to each other. Finally, you'll classify the images and see whether two images represent the same person or not. So the main idea behind the Facebook algorithm is image processing, neural networks, machine learning, and computer vision. All right, and all of this comes down to artificial intelligence. Next, we have explained the logic behind targeted marketing and how can machine learning help with this. Now, target marketing is something that we see very often. All right, let's say that you were looking for some shoe on Amazon. In a day or two, you just open up YouTube and Facebook. You'll see that you'll get ads of shoes from Amazon. Okay, this is targeted marketing. So basically, Amazon knows that you've been looking for a particular type of shoe, so it's going to target you with that particular ad. Okay, this is what targeted marketing is in short. Targeted marketing can be done in different ways. For example, it can be done depending on your geography, or it can be done depending on your social economic profile. Okay, let's say that Amazon has details about your age, it has details about what sport you like to play. Let's say that you've been browsing through a lot of sports. Okay, you've been browsing through a lot of sport equipments or something like that. Amazon will know that you're interested in this by using machine learning, of course, and it will send you ads based on what you're interested in. Okay, this is what target marketing really is. Now, how does machine learning come into target marketing? Okay, so there's something known as text analytics systems. Now, the applications for text analytics ranges from search applications, text classification, name entity recognition, or pattern search. Okay, so it's basically a way to understand what you're looking for. Okay, they'll try to understand your search history and they'll try to target you by using your interests. Clustering is another way of targeted marketing. All right, you'll cluster customers who have similar interests and you'll send them similar ads or you'll send them similar offers. Classification is another method used for targeted marketing. Now, here you'll make use of algorithms like decision trees and neural networks. Now, recommender systems is what I spoke about earlier. When it comes to Amazon, they recommend items to you based on your interests or based on people who have similar interests like you. Market basket analysis is another method that machine learning uses for marketing. Okay, here basically you'll understand a combination of products that are frequently bought. Okay, by understanding what two products are frequently bought, you can give some offers or you can give some discounts on those products so that people buy more and more. Okay, that's how market basket analysis also works. So guys, this is what targeted marketing is. Now, next is how can AI be used to detect fraud? AI is used in a lot of ways in credit card fraud detection. It's used in detecting anomalies and all of that. It basically makes use of machine learning algorithms to do this. Now, let's try to understand how this process works. Okay, first it begins with data extraction or data collection. So at this stage, data is either collected through a survey or through web scraping. Okay, if you're trying to detect credit card fraud, then information about the customer is collected. All right, this includes any transactional or any shopping and personal details. Next is data cleaning. So at this stage, the redundant data must be removed. Any inconsistencies or any missing values that you have in your data, it has to be removed because they lead to wrongful prediction. Okay, so therefore you have to get rid of any inconsistencies in this stage. Next, we have data exploration and analysis. Now, this is the most important step in AI. Okay, here you study the relationship between various predictor variables. For example, let's say that a person has spent an unusual sum of money on a particular day. Now, the chances for a fraudulent occurrence is very high because usually the person is not used to spending this much money. So, such patterns have to be detected and understood in data exploration and analysis. This is followed by building a machine learning model. Now, here there are many machine learning algorithms that can be used for fraud detection or anomaly detection. One such example is logistic regression, okay, which is a classification algorithm, and it can be used to classify events into two classes. Okay, you can use them to classify a person or classify an event as either fraudulent and non-fraudulent. Then comes model evaluation. Here you'll basically test the efficiency of the machine learning model. Okay, so if there's any room for improvement, then you can perform parameter tuning and you can improve the model. This will just improve the accuracy of the model. So guys, all of these complex problems like fraud detection or object detection, all of this is done through a process. Okay, and in general, the process is data collection, data cleaning, exploration analysis, building a model, and model evaluation. Most of these complex problems can be solved by using this approach. Now let's look at our next question. Okay, a bank manager is given a data set containing records of thousands of applicants who have applied for loan. How can AI help the manager understand which loans he can approve? To be more specific, this problem statement can easily be solved by using the KNN algorithm. Okay, KNN is basically stands for K nearest neighbor. All right, this is a classification and a regression algorithm. So if you use a KNN algorithm, it will form two classes. One is the loan is approved and the other is applicants whose loan is not being approved. So like I said, K-nearest neighbor is a supervised learning algorithm that classifies a new data point into the target class depending on the features of its neighboring data points. Alright, so KNN basically focuses on the neighbors and it understands that if a new data point is similar to one of its neighbors, then it has to classify that new data point into that neighbor's class. Now again, the methodology for solving this problem is same. You start by data collection, data cleaning, exploration and analysis, building a model, and model evaluation. All right, so while data collection, you can collect data like account balance, credit amount, age, occupation, loan records, and all of that. So by using this data, you can predict whether or not to approve the loan of an applicant. Data cleaning, again, you have to remove any variables which will not help the model. Okay, any variables which will just increase the complexity of the model. Okay, so you'll remove such variables at this stage. In data exploration and analysis, you will understand the patterns in your data. Okay, let's say that a person has a history of unpaid loans. Okay, if any person or any applicant has a history of unpaid loans, then the chances are that he might not get approval on his loan application. Okay, this is obvious because the manager is going to see that his previous loans are still due. So that's why he won't be able to approve the application. So these are the kind of patterns that are detected in exploration and analysis. Now, building a machine learning model, you can use n number of models when it comes to predicting whether an applicant loan request is approved or not. Now, like I mentioned, one of the easy algorithms that you can implement is the K-nearest algorithm. Okay, it can be used for both classification and regression. It will classify the applicant's loan request into approved or disapproved based on the socio-economic profile of the applicant. Okay, based on variables like loan, based on variables like the salary, the occupation of the applicant. Now, model evaluation again is the same thing. You'll basically evaluate the efficiency of the model. You'll try to improve the accuracy of the model by using parameter tuning or cross validation. So guys, this is how a bank manager can understand whether a loan can be approved or not. Again, in this question, they are just trying to test if you know how the flow of the problem will go. If you know how this problem can be solved. You don't have to know the exact details, but you have to know how you can approach the problem.
Okay, now let's move on and look at question number 40. Now the question here is place an agent in any one of the rooms and the goal is to reach outside the building. Can this be achieved through AI? If yes, explain how it can be done. Now in this question, there is a diagram along with a small explanation. Okay, so basically there are 4 rooms in this diagram. Basically 0, 1, 2, 3 and 4 represent rooms and this 5 represents outside the building. Okay, now the goal is to place an agent in any one of these rooms in such a way that he has to reach room number 5 or he has to reach outside the building. Now they've also mentioned that room number 1 and room number 4 directly lead outside the building. That's correct because room number 1 is directly connected to 5 and 4 is also directly connected to 5, right? 4 leads outside the building. Now, if you look at room number 0, if you want to go from 0 to 5, first from 0 you'll have to go to 4 and then only you can go to 5. Similarly, if you look at room number 3, if you want to go from 3 to 5, you'll have to take 3, then you'll have to go to 1 and then only you'll have to go to 5. These are not directly connected to outside the building, whereas room number 1 and 4 are directly connected to outside the building. All right, I hope the question is clear. Now, as soon as you read the question, you must know that this is a reinforcement learning question. All right, it's pretty clear because they have mentioned that there is an agent which is going to be placed in any one of the rooms and he has to basically explore the environment and reach 5, which is basically outside the building. So as soon as you read the question, the first thing that should come into your head is that this is a reinforcement learning problem. Now, this problem can be solved by using the Q-learning algorithm. Now, if you remember earlier in the session, I discussed what exactly Q-learning is and how it works. So Q-learning is basically a reinforcement learning algorithm which is used to solve reward-based problems. So now let's look at how we'll solve the problem. First step would be to represent the rooms on a graph. All right, so each room over here, you'll represent it as a node and each door will represent a link. So if you look at this figure over here, this is our original figure that was given in the question. And now this is the graph that we draw from this figure. So we have node 1. Let's look at how node 1 is connected to node 3. So basically you can go from node 1 to node 3 and you can go from node 3 to node 1. If you look at the diagram, there is a direct connection from 1 to 3 and 3 to 1. Okay, let's look at 1 and 2. Now there's no link between 1 and 2 because if you look over here, if you want to go from room number 1 to room number 2, you cannot directly go. You'll have to go from room number 1 to room number 3 and only then you'll reach room number 2. Alright, that's why there's no link between room number 1 and node number 2. Similarly, if you look at node 1 and 4, they are directly connected to 5. This is because room number 1 and 4 directly lead to this goal. Our goal is to reach room number 5. So 1 and 4 are directly connected to 5, whereas the others are connected just like how they're shown in this figure. Okay, it's pretty understandable, guys. This is just logic. Now let's look at the next step. Now the next step is to associate a reward value to each door. What we're going to do here is we're going to build a reward matrix. Now I'll tell you what that exactly means. So for the doors that lead directly to the end goal, which is room number 5, you'll assign a reward of 100 to those doors. So if you're traversing from node number 1 to node number 5, you'll get a reward of 100. Similarly, if you're traversing from 4 to 5, you'll get a reward of 100. 5 to 5 also you'll get a reward of 100 because your end goal is 5, right? So basically any link that leads directly to our end goal, for that link we're going to assign a reward of 100. Now doors that are not directly connected to the target room will have a reward 0. This is because if you take room number 2 or if you take room number 3, you won't reach room number 5 directly. And our goal here is to reach room number 5. That's why for the other doors we've given a reward of 0. For door number 1 and door number 4, however, we have rewards of 100. Similarly, for door number 5 or room number 5 also we have a reward of 100. So basically each action or each link will represent a reward. So let's say that you're traversing from room number 1 to room number 4. If you go from room number 1 to room number 3 and then 3 to 4, your reward is going to remain 0 because you're not reaching the end goal here. Only if you traverse from 1 to 5, or if you traverse from 4 to 5 or 5 to 5, you'll get a reward of 100. All right, it's as simple as that. Now let's see how the Q-learning algorithm works in this particular problem statement. Now there are two main components in this algorithm. All right, there is state and there is action. Now basically all these rooms will represent the state, and the agent's movement from one room to the other will represent an action. So basically 0, 1, 2, 3, 4 and 5 represent the state, and let's say you're traversing from 2 to 3. This 2 to 3 will basically represent an action. In order to make you understand how this works, let's say that you're traversing from room number 2 to room number 5. Your initial state is going to be room number 2. Your next state is going to be room number 3. All right, so you're moving from 2 to 3 and you're getting a reward of 0. Remember that. Now from state 3, you'll either be going to state 2, or you can go to state 1 or state 4. All right, if you choose 4, you can directly go to 5, and here you'll get a reward of 100. If you choose 1, again you'll go directly to 5, you'll get a reward of 100. But if you go back to 2, you'll get a reward 0. So guys, let me tell you that the agent is going to explore over here. Okay, he has no idea about the environment, so he's not going to go from 2, 3, 1, 5 directly. All right, he's not going to know that this will lead to the output. He has to explore, he has to make mistakes, he has to learn, and he has to find out the best path to reach room number 5. Now next is our reward matrix. So guys, there are two main matrices in Q-learning algorithm. One is the reward matrix and the other is going to be the Q matrix or the memory matrix. All right, I'll be discussing the memory matrix in a while, but for now let's look at the reward matrix. So what I'm doing here is I'm basically putting all the reward values for traversing from one node to the other node in a matrix known as reward matrix. Now the -1 will basically represent the null values. What I'm trying to say is there is no connection from 0 to 0. All right, that's why I'm giving a value of -1. But you might say that why is the reward from 5 to 500? Now this is because if you go from room number 5 to room number 5, you're still reaching the end goal. All right, that's why there's a reward of 100 over here. Let's look at 0, 4. All right, there is a link from 0 to 4, but the reward is going to be 0 because 4 is not the end goal. All right, 4 is not your goal room or anything. That's why your reward is going to be 0. Now the reward is 100 only for 1, 5. That is if you traverse from 1 to 5. For 4, 5, which is if you traverse from 4 to 5, and 5, 5. Now this is because through all these three actions, you're going back to room number 5, all right, which is your end goal. That's why we have a reward of 100 for these three actions, all right. So like I mentioned earlier, we're going to have another matrix known as a Q matrix, which will basically represent the memory of what the agent has learned through experience.
Okay, that's the only way the agent will actually learn further. If the agent forgets everything that he's learned, then there's no point because he'll have to redo everything from scratch and again he'll forget everything. That's why we have a matrix known as a Q matrix, which represents the memory of the agent. Okay, so if an agent has traveled from room number 2 to 3, he's going to remember the reward. Okay, that reward is going to be stored in the Q matrix. The rows of the Q matrix will represent the current state and the columns will represent the possible actions which lead to the next state. Now the formula to calculate the Q matrix is the following. You have Q state comma action is equals to R state comma action. Okay, let's say the state is you're at state number 1 and you're moving to state number 2. Okay, so Q1 comma 2 is going to be so on. R state comma action will represent the reward of 1 comma 2. Okay, let's try to understand the reward. So the reward of 1 comma 2 is -1. Okay, so here you'll get a value of -1. And then you'll have plus the gamma parameter into the maximum of the next state and the next possible action that you can take. Okay, now what is a gamma parameter? So the gamma parameter has a range of 0 to 1. Okay, so it can be between the value of 0 and 1. Now, if gamma is closer to 0, then the agent will tend to consider only immediate rewards. But if the gamma parameter is close to 1, the agent will consider future rewards with greater weight. Now, I don't know if this reminds you of something, but earlier in the session, I discussed two important concepts of reinforcement learning, which was exploration and exploitation trade-off. Now, if you're exploring, then the gamma parameter is going to be closer to 1. But if you're exploiting, then the gamma parameter is going to be closer to 0. It's better if the gamma parameter is closer to 1 because it means that you're exploring the entire environment and you're trying to get future rewards. You're going to get greater weightage and more rewards. So guys, to sum up the entire thing, let's look at how the Q-learning algorithm will solve the problem. So you begin by setting the gamma parameter and the environment rewards in reward matrix R. We already did that. After that, you'll set the matrix Q to 0 because initially the agent will start with no knowledge of the environment. As the agent explores the environment, the Q matrix will start filling up. After that, the next step will be select a random initial state. Like I mentioned earlier, initially you'll randomly select any state because the agent has no idea about the environment. So you'll randomly select a stage at step number 3. Then step number 4 is you'll set the initial state as current state. Step number 5, select one among all possible actions for the current state. Okay, so if you've chosen the current state as 1, let's say that all the possible states that you can traverse to from 1 is 2, 3, and so on. So these are all the possible actions for the current state. Now use the possible actions and consider going to the next state. Once you know what are the possible actions from the current state, you're going to go to one of those possible actions and then you'll move to the next state. After that, get maximum Q value for this next state based on all possible actions. If you get the maximum Q value, it means that you've chosen an optimal policy in order to reach your end state. Finally, you'll compute the Q value by using the formula that we discussed earlier. And the last step is you have to repeat all of these states until your current state is equal to your goal state. And our goal state is room number 5. Now guys, this is a very logical solution because you can easily understand what is happening over here. You have an agent, he has to explore through all the states in such a way that he reaches the end goal using the optimum policy. Okay, that's the end goal of Q-learning algorithm, and that's exactly how you're going to solve this problem.
And with this, we have come to an end to this full course on AI and ML. If you enjoyed listening to this full course, please be kind enough to like it, and you can comment on any of your doubts and queries. We will reply to them at the earliest. And do look up for more videos and playlists and subscribe to Edureka's YouTube channel to learn more. Thank you for watching and happy learning.